Hello everyone, thanks for joining this course. In this course, basically we are going to focus on enterprise routing services, implementation and troubleshooting. In 1.1, we have to understand about troubleshooting the administrative distance related to routing protocols. First of all, we'll go and understand about the administrative distance, what's the use of administrative distance, how it is working. And then in the upcoming section, we'll go and understand the troubleshooting strategy related to AD values. Now, while we are talking about routing protocol, we know this term that first of all, these protocols, they will go and form the neighbor relationship. That means they will exchange their hello packets, find their neighbors, discover the neighbors, they will form the neighbor relationship. After that, they are building the topology table. They have to build the complete database, means complete roadmap, you can say, across the network or throughout the network, that is termed as a topology table. That means everything they have in the database. Now, on top of topology table, if they are running OSPF, they are running SPF algorithm. If you have EIGRP, it will use dual algorithm or dual algorithm to compute the best path out of this topology table. So out of everything, you are selecting the best path. That's the routing table. And then that routing table, the traffic is being used from source to destination. Okay. Now, what's the use of administrative distance? We know that all the protocols, they are associated with AD value. And this is one of the factor inside that how the devices, they are selecting the best path, correct? So the point being here is this, that administrative distance is nothing but it's termed as a trustworthiness or the believability of that particular route. So what does it mean? It's actually the comparative thing. So it means that if we have two different protocols and suppose I am a router, I am getting the same route from two different protocols. As per the lower AD value, I will trust the lower AD value route. So suppose if I am learning a route with respect to ISIS, whose AD value is 115, and with respect to RIP, whose AD value is 120. So I will prefer obviously ISIS because its trustworthiness is believability is high because its AD value is less. Suppose if I'm getting one route, the same route from ISIS, same route I'm getting via the static route. So obviously, I will go and trust the static route because its believability is more than ISIS. Its AD value is less. Okay. So now, do we have any mechanism that we can go and tune the AD value? Because the um, the AD distances, AD values, they have a local significance. So how I am learning, can I go and change it? Yes, we have the option that we can go and use the distance command to tune the AD value. But use it with caution, because if we are not using it with uh, proper degree of administration, or if we're not using it in a proper manner, there are chance that it will create routing loops, black hole in a network. So if you are using the distance value, use it properly. You should know as a network engineer that where we are doing this path manipulation, how we are doing this path manipulation. Now, before showing this distance command, you can see one example here. So I am at router R1, I am getting one route. So you can see with the EIGRP, whose AD value is 100. So two routes are coming. One is coming with EIGRP, mark as a I, and one route is coming, same route is coming with a RIP as well. So 10.0.0.0 and 10.0.0.0 is coming via RIP, is coming via EIGRP. Since EIGRP having AD value 100 and RIP having AD value 120, so EIGRP is winning. So that's why you can see here in the routing table, the EIGRP routes getting installed either in R1 and R2. Both places you can see that EIGRP routes, they're winning. Now, if I go to R1, So you can see I'm in R1. If I go inside the RIP and if I change the distance, so RIP distance, now I am doing the manipulation. I'm making it 90 instead of 120. So that means that R1, now when R1 will learn the route, you can see that AD value is 90. And now you can see that it is, this R1 is learning the same route via the RIP protocol. Although if you go and check the R2, still R2 is learning via EIGRP. Correct. So it is using, if you go and change the trustworthiness, that means that you are manually changing how the routers, they are getting learning the routes. That's the one use case while we are doing some sort of traffic engineering, some sort of path manipulation or AD manipulation. The other important use case we have with AD value is the failover scenarios. Sometimes we are using it as a fallback link. So what does it mean? It means that we can go and utilize this with a static route. So in a static route, you can see that I have one primary path, but suppose if that primary path will go down, I have put one entry here in my routing table, the static route whose AD value is 250. So that means that my primary link or maybe Ethernet link, if it will go down, then it will go and use this dialer interface. It is not being used in first place because you can see it's a 250. It's way higher than whatever protocol we have. Now, if you go and use this, that means if my primary link will go down, this dialer interface will come into the picture because now this dialer interface is being used as a fallback interface. All right, so let's stop here and we'll continue the troubleshooting section in the upcoming video. In this section, we are going to understand troubleshooting related to route redistribution, and I'm going to add administrative distance troubleshooting as well in that redistribution topic. So overall, we are going to cover 1.1 and 1.4 in this particular section. Now, before doing the troubleshooting, before checking that what actual troubleshooting we have, means I have prepared the lab here. So before going to the lab related to troubleshooting route redistribution, I just wanted to cover up first of all what is route redistribution and why we need it. Okay, we need route redistribution. Why? Because suppose if you are in multi-protocol environment, so there are chances that in the organization you may have different protocols running, Ospf, EIGRP, and some others as well. Now, if you want to learn or exchange the routes in between different routing protocols, then we have to go and enable we have to do the route redistribution. So suppose EIGRP, if you want to send to Ospf, Ospf you want to send to EIGRP, we need to do the redistribution. Now, there are some very important points that we should understand while doing the redistribution. So while you're doing the redistribution, the first thing is that one of your router that may work as a border router should have both the protocol running. So you can see router B has running EIGRP plus OSPF. That's the first thing, that one router understanding multiple protocol. Second important thing, we know that EIGRP metric value is different. OSPF metric value is different. Now, if you send EIGRP routes to OSPF, obviously EIGRP will lose its metric value, because once it is in OSPF domain, then that particular route will be known with their OSPF metric values, not the EIGRP metric values. Because here in this area, you have to do some sort of route manipulation, and that will be occur with respect to OSPF attribute. Vice versa is also true if you are sending the OSPF within the EIGRP domain. So now the OSPF route, whatever metric it has, it will be known by the EIGRP metric. Correct. So these are two very important points. Apart from that, rest of the points we'll go and discuss. Now, so when we are doing the redistribution, the step for redistribution is easy. Suppose if you want to send EIGRP to RIP, go to the RIP process and call EIGRP. While you're calling the EIGRP, give the route metric that will be RIP metric, correct? The RIP understand hop count or distance. Hop count basically number of routers in between. So you have to go and give the metric that RIP can understand. Vice versa. Suppose if you want to send RIP inside IGRP, so go inside IGRP and then, so you can see that we are inside IGRP and then we are redistributing with IGRP metric like reliability, load, MTU, bandwidth delay, etc. Okay, so these are the basic three fundamentals that one router should have both the protocols running. They will lose their metrics. So while doing the redistribution, you have to take care about the metric value. Now, suppose if you want to make the metric constant throughout the protocols, throughout different routes that you have, then we have the option of manual metric as well. So we can go and use the default metric. So here you can see that you can go to the EIGRP call OSPF and then you can put the default metric bandwidth, delay, reliability, load, and MTU. Now some of the protocols, if you're not putting the default metric, they will mark this as a zero metric and it will not advertise. Not the case in OSPF. OSPF having default metric as a 20. So that means still it will work. Okay, but some of the protocols, they have default metric 0 that we can go and list those protocols. Great. Finally, when we are doing the OSPF redistribution, you can see that by default they are type 2, and if you want to change it, you can go and use the OSPF type as a type 1. First thing. Second thing, the OSPF, they are taking EIGRP as a class full routing protocol unless classless or otherwise classless. So suppose if that is the case, that means you are redistributing EIGRP into OSPF, you are redistributing RIP inside OSPF. So you have to use one key called subnets. That means it is supporting a variable length mask or classless type of routing domains or the subnets. Great. So very good important points we have discussed, 4 or 5 very important points that we can list down all these very important points. Lastly, in this section, if you want to redistribute the static and connected routes, so that option is also there. Only one caution is there. If you go and use the keyword redistribute connected, that means whatever interfaces we have with the router, all these interfaces will get redistributed. So what we can do, we can go and create one route map. Route map I will cover later on. So we'll go and create one route map where we can match the interfaces, and then inside the protocol we can call the route map with this. Obviously, when you call this route map, it will go and match only these interfaces. Right. So idea being here, select those interfaces, match inside the route map, and then redistribute this route map inside the protocol. Great. So now we have the lab section where I'm going to show you the lab scenario that we are going to discuss now. I have this lab topology here. What we'll do, that we have 6 router. You can see 1, 2, 3, 4, 5, and 6. And these two router number 3 or router C and router D, or 3 or 4. So router C and router D, they are working as a area router, means they are running both the protocols OSPF and RIP. So what I will do, I will go and give the IP address. You can see the IP schema is very straightforward. To 192.168.1.x belonging to, or 0.0x belonging to OSPF, 10.1.0.0/24 or XX belongs to RIP. So anything belonging to 10 belongs to RIP, anything belonging to 192 in this lab belonging to OSPF. I have created certain loopbacks because when we manipulate routes, we need some extra network. So here you'll find the loopbacks. So this network, this network, this network, this network, they are the loopback. Rest of the connected interfaces are there. I'll do one thing. I'll go and log into the lab devices. I will show you the IP address and the OSPF configuration. Plus, once we will go and do the two-way redistribution, you'll find that there are issues related to routing loop. Okay, so first of all, what I will do, I will show you the configuration, and next section we'll go and discuss about the issue that we have. So here I am in the router number 1. You can see that IP address schema, it's easy and straightforward. And because this is router 1, so it is running only Ospf. So you can see that I'm advertising the Ospf. I just wanted to highlight. So here you can see that Ospf is running here. Okay. And let me quickly go and run the same command in all the routers. So I can go to router number 2, and here also I just wanted to show you the IP first. So IP is over the interface and the loopback. Then you can see the router configuration means Ospf configuration. Although we have network only 3, 4, and 5 here, we don't have 1.0 and 2.0. So leave these two lines, first two lines. The rest is okay. Then I can go to router number 3. Oops. And show IP int brief. You can see here router number 3 is working bridge between Ospf and RIP, and you can see the protocols that are running here. So you can see that inside Ospf I am calling RIP with the metric with the subnets keyword, and inside Ospf I am calling. So inside RIP, I am calling actually Ospf, and inside Ospf, I am redistributing or calling RIP. So two-way redistribution is happening here, easy and straightforward. Finally, we can go to router number 4, the bottom router in the diagram, and you can always refer the diagram. So you can see we have checked router 1, router 2, router 3, we are checking. That also running both the protocol, and here also you can see RIP and should see RIP and Ospf. So Ospf we are calling RIP, and RIP we are calling Ospf. I can see some distance command is there that I don't need. We need this distance command later on. So let me quickly go and remove this. I don't need this distance command. We will check later on the usability of this distance command. All right, and then let me quickly verify. Show run section router. Let's see, show run is a little bit slow here. All right, so RIP calling Ospf, Ospf calling RIP. That's okay. And then you have two other routers. They are purely inside the RIP domain. Correct? So here you can see show run section router. And likewise, the last device, router number 6. Here also you can check that the configuration, the interface configuration, and the router configuration. Okay, now since we have done two-way redistribution, so if you go and check the route over R3, so if I go here and check show IP route, you can see that router number 3, they are learning some network related to RIP via Ospf, and that is not good. Likewise, if you go and check show IP route for router number 4, we'll see that it is learning more routes via Ospf. That is not good. So in next section, we'll go and discuss about that, why this loop is happening. And next we'll go and remove certain problems from the network. We will see that what options we have to correct from such loops. In this section, I'm going to show you that what problem we have if we are doing the redistribution, and in the redistribution, if different protocols having different AD values, we know that lower will be selected. Now here you can see in the diagram that one side we have 192 network running Ospf, other side we have 10 network running RIP. Now, when we'll do the two-way redistribution, a RIP network will come inside Ospf. Now, since we have done the redistribution, obviously we want to send Ospf to RIP as well, but that's the thing. Now what will happen, and if you go and focus to this particular router, so what will happen that any of the routes, so for example 10.13.0, that is coming here 10.13.0. Now when Ospf will send this particular route to a RIP, first of all it will go to this particular router. Now this router, he is getting 10.13.0 with Ospf AD value 110, and he is getting the same route here, you can see, with 10.130 with the AD value of 120. So to whom he will learn? Obviously, he will go and install the Ospf route, and that's the loop. So same route that he should get from RIP, because maybe he is originator or near to originators. He's learning inside the RIP domain. The same route that he is advertising, he is getting. Okay, and that's a loop you will find here in this case, and that's the explanation we have. So this is termed as a routing loop. That means that we should go to router 1. So once there is loop, so once we'll go and detect the loop, there are methods that we can go and improve it. Correct. So I'm going to show you in the lab that once we will go and detect the loop, so I don't want to learn Ospf route in this interface. So I'll go inside router number 3, and I will use one distribute list applying in this direction, that in this direction I don't want to learn these routes. That is the RIP routes. That is one way. The second way that we can improve this, that we can go and lower the RIP AD. So lower the RIP AD means we'll go and make the RIP administrative distance as less than Ospf 70 or 50 or 40, etc. So that means that when this router have to learn the network, he will see Ospf coming with 110, RIP route that is coming with maybe AD 50. So that means it will go and install the RIP route, because we are changing the AD distance here, or maybe we can go and increase the Ospf external AD value to more than 120. Okay, so these are the methodologies we have. I'm going to show you this this particular section, that how we can go and use the distribute list feature inside router number C, even router number D as well, or router number 2, router number 3, and router number 4. So R3 and R4, we are going to apply this particular rule. So let's go here. Let me quickly show you the problem first. If we are inside the router number 4 or 3, and if you go and check show IP route, you should learn 10 network. You can see 10 network is coming via the Ospf. It should not be the case. It should be a learning with the RIP process. So I'll do one thing. I'll go here, and first of all I'll go and create the access list. So access list 40, and then I want to deny certain routes. So I want to deny 10, 2, 3, 4, 0. So we can go and give this network 0, 0, 0, 255. Let's create the ACL first, and then 3, and then 4 and 5, because these are the network belonging to RIP. Once we deny this, apart from these routes, what we want to allow everything. So I'll create one more statement that will permit everything except these routes. So permit any. Now, once we have the access list like this, then what we can do, we can go to the Ospf process, and inside Ospf process, we can go and use the distribute list. I want to apply in this particular interface. Oops. This particular interface, that is Gigi 0/1, because this interface we don't want to learn. Even here you can see that all the routes, all the RIP routes, my router he is learning from this interface in terms of Ospf. So now we'll go and create the distribute list. Distribute list for 0. Let's see the options that we have in the inbound direction. And then the gig interface 0/1. Let's check the route. Do show IP route. And now you'll see that it is learning these routes via the RIP. Okay, so this is the routing loop you can see, and with the distribute list, what we have done that we have corrected that particular loop. Now let's do this thing. Section access list. The same ACL call 40 that we have created, correct? Same ACL I will go and create inside router number 3 as well. And then we'll go to router OSPF1, distribute list for 0. And then we can go and apply this in the inbound direction to the gigabit Ethernet 0/1, correct? 0/1, and then we can go and check show IP route. Great. So you will see once the protocol will get converged, we are blocking OSPF on this interface. I should have RIP route coming here. I should have RIP first of all forming. Show run section RIP. Do I have RIP which is getting learned here, or if some issue with any of the interface? But yeah, overall you can understood that the process that is working here. So if I go to router number 3 and let's see that what interfaces we have. So 0/2 part of this interface, 0/2 should have correct routing and all those configure. It should be pairing with router number 5, 0/1. So let's see. So if I ping here 10.1.1.5 should be the IP. Let's see here. Router number 5. So 10 dot, that's correct. 0/1 and show run section rep. Okay, and in router number 3, RIP version 2, network show IP route. So you can see that it took some time to converge because RIP hello packets, they have some delay in that. But you can see that 23-second back, we have this routing update. Great. So this way we can go and troubleshoot our network. We can go and correct the loop, means we can prevent from the loop. All right, so we are good here. We can now go and stop this particular section. In this section, I'm going to cover 1.2, that is troubleshooting route map for any routing protocol. First of all, we'll go and discuss the theory related to route map. And then in the next section, we'll go and perform the lab related to troubleshooting. So that's about 1.2. About 1.3, in the specific protocol, suppose if you go and study EIGRP, and after this section, we have EIGRP after a few videos. So in that EIGRP video, I will go and cover different type of mechanism related to loop prevention. So when I go and give you detail about specific protocol like EIGRP, OSPF BGP as per our syllabus. Then I will go and cover section 1.3 because it seems like only one bullet point, but we should understand the routing protocol, the mechanism, and then we can go and apply different type of rules to protect from the routing loops. For example, in the previous section, you have seen that with help of filtering, so we have used something called distribute list, and then we have protected from the loop. And in upcoming section, in upcoming lab section, I'm going to tag a route map with the tagging. So route map will understand in this recording, and we are going to use some sort of tag. Tag is nice way to protect from the loop, and we'll perform the lab task. So slowly we'll build the concept and we'll perform the troubleshooting lab as well. All right, so let's understand route map. Before understanding route map, I have few small concepts such as prefix list and distribute list to discuss. And then I will go and check that route map and how it is building, how we can go and apply the route map, etc. Prefix list. We know at this point of time that how access list, ACLs, they are working. Likewise, we have prefix list as well. Either you can use ACL, access control list, or you can go and use prefix list. There is no much difference. Although the use of ACL, so ACL is working as a placeholder, and ACL, once you create access control list, you can use inside route map policy, distribute list, NAT policy. There are so many places that we can go and use ACLs. But prefix list you'll find mostly we are using inside the route map, and we are playing around with BGP attributes. Mostly we are using there, although we can use with distribute list as well. So what's the use? When we are talking about prefix list, so it is adding the network. So two parts are there. So it will go and add the network, and plus it will go match. So match the network first and then match the subnet mask. So two matching criterias actually are there for prefix list, and it's a nicer way to match the IP and the subnet, network and the subnet, correct? So here you can see the example, two examples are there. Suppose if you are matching, let's just start with a smaller one. So suppose if I have to go and match 10.1.10/20 for exact match, so I can go and use this. Although if you want to match the variable length, suppose if you want to match 24 till 30, you can go and use /24 less than equal to 30. And suppose if you want to match 24 greater than 26 and less than 30, so you can go and use this statement. So it depends that what type of matching criteria we have. According to that, we can go and match. Some explanations are here. You can have a look. Great. Now, if you want to match everything, then you can start with 0 up to 32. That means you are matching everything. Match all prefixes. All right, so this is about the prefix list. Then what about distribute list? We have performed the lab task in previous section related to distribute list. So either I have access list or prefix list. I can go and match that entry inside my distribute list. So distribute list, I want to match this access list or prefix list, and then we can go and apply this over the routing process in and out, or in or out. So either inbound or outbound we can use. Now different protocol behave differently, at least OSPF and ISIS, because they have their own LSA type of databases. So when you are applying the distribute list to OSPF and ISIS, you have to be cautious because they have to. So whenever we are applying their distribute list, they have to go and match that distribute list with their link state database. Okay. Great. So let's talk about route map, our main area in this particular section, that we have to understood route map, how it is used, and then how we can do the troubleshooting related to route map. Route map, clearly you can see in here in the slide that they are going to control the redistribution between routing protocol, one big use of route map. Other big use, playing around the attribute with respect to BGP, and it's a huge, because BGP itself is a big protocol. It is something we are telling that BGP is a protocol for internet. It's a huge, it's too many attributes BGP having. Now we can go and match and set the attributes related to BGP with respect to route map. So if you want to tune the BGP attributes, route map is the best tool. And then finally, we can go and use the policy-based routing as well. We have separate section for policy-based routing, PBR. So we'll go and discuss more in that particular section. Okay, great. So how the route map is working now? It's actually easy. It's like programming type of a structure. So you can go and create, say, a route map and then a statement, say permit or deny 10. Now inside 10, you can go and match. So you have condition match, you have condition set. Okay. So likewise, you can go to line number 20, line number 30, line number 40, etc. By end of all the lines, what you have implicit deny. So that means if you are not matching by the end of the line, it will go and drop everything. Like that, we can think about the logic. Okay, so let me quickly highlight that line here. So you can see, however, ACLs can merely permit or deny, while route map can additionally modify perform. It's telling that, okay, I am matching one condition, related to ACL. Now, if you are doing some permit deny inside the ACL, again, you can go and modify that thing inside the route map. So the statement that we have inside the ACLs, that also we can go and change here. Okay. So route map is actually easy. Let me show you with respect to the examples. So how you can go and create, first of all, you can go and create either ACL or prefix list. Then you can go and create the route map, match the address, and then set the next hop. This is actually policy based routing example, PBR. So you're matching certain IPs, and then you're setting those IP next hop somewhere. So these IPs, they will think that their next hop. So suppose if you have multiple next hop, you can go and apply this policy on this interface. So for some subnets, the next hop will be this, some subnet next hop will be this. So next line, again, you can go and create the access list too with IP addresses like 2111, etc. and next hop 2.1. Okay, so you can go and change the next hop attribute as well with related to route map. That's one example. Apart from that, I'm going to show you all three examples I have in this video. Now before reaching there, let's discuss a little bit more about route map. So route map, we can write our points. So first of all, we are creating the policies with respect to sequence. So sequence 10, 20, 30, etc. We are matching. You can go and use the match and the set commands, correct? Now, if you go and match the ACLs like 1, 2, 3, suppose you have ACL1, ACL2, ACL3, or ACL ABC, whatever name of ACL, if you go and give like this, that means it will go and match the OR condition. This means it is matching the OR condition. Now, if you go and give that match statement line by line, so line 1, line 2, line 3, like that. So this will go and match the AND condition. We know that what is the use of OR and AND. OR means either this or this or this. AND means everything has to match. That's the AND condition. Okay. So how we are writing the policy, it is also very important. Then what we can do, we can go and set. So you can see that we can go and match the address. We can set the weight. We can set the preference. This is related to BGP configuration. So let me show you one by one all these examples. So here you can see that one of the example related to route map, we are creating the route map called my map, matching the address, match the interface. Then we are matching the prefix list. Then for that prefix list, next hop, match the metric, match the route type, match the tag, match the community. See how deep we can go inside the policy, inside the route map policy, correct? Likewise, we can go and build the BGP related policy as well. So here you can see BGP related policy, create the route map. If you have any interface, set it, then go and match the metric, tag, community, local preference, weight, IP preference. Each and everything inside the BGP attribute, the route maps they are supporting. Okay, here you can see that once we have the policy, so here you can see that we can go and set the metric, and then over the BGP process, so router BGP, we are applying this route map to the neighbor, okay, in the outward direction. So you can create the policy like this. So route map policy you have created, and then with respect to neighbor, you can go BGP neighbor, you can go and apply it. Okay, redistribution, how we are applying route map with respect to redistribution, you can go and create the ACL or prefix list, create the route map policy. So route map policy, my map, match the address 1, set the tag 150, and then you can go to the routing process, router EIGRP. So see, in Ospf, we are redistributing EIGRP. Correct. So go to Ospf, redistribute EIGRP 10, metric subnets, these things we have discussed earlier, that if you are redistributing RIP or IGRP or EIGRP, you have to go and use subnets and then route map my map. That means this program will call this program, and this program will call these ACLs. Like it's like different objects you are creating in terms of programming. So this is one of your object which is called here. So it will go and check his own name, and then it will go and call this ACL. Great. One last example I have related to PBR, policy based routing. Again, it's easy. Now you can create the route map policy. First of all, create the ACL, create the route map policy, permit 10, match the address, set the next hop, and then this policy you have to apply over the interface. So here you can see, build the policy and then apply the policy. In case of PBR, policy-based routing, we are applying the policy to the interface. In case of route redistribution, we are applying with the redistribute keyword over the routing process. And with respect to BGP, we are applying to the neighbor, either inbound or outbound. Okay, great. So this is the usability use case with the route map. We can stop here, and in the next section we have to work on one troubleshooting ticket. In this section we have to work related to route map troubleshooting. So I'm going to show you how we can go and check the steps when we have issue in a network with respect to route map. Maybe redistribution is not working with respect to route map properly. How we can go and tag, how we can go and check different type of attributes related to route map, and even if we want, we can go and do the filtering as well. So all these steps related to troubleshooting, I'm going to show you in the lab. Now, before starting that lab, I just wanted to give you the hint here that what we are going to do perform in the lab. So you can see that we have the lab set up, and previously we have done a few of the lab tasks here. Now, in this particular lab, you can see that we have two different routing domain, OSPF and RIP. And in previous section, we have done some sort of redistribution in between them. But while doing the redistribution, we found that a routing loop start occurring, or maybe chances that for router number 2 to reach router number 1 loop back, he may go via RIP, and then he will reach to router number 2 loop back. This is termed as a suboptimal routing or suboptimal path, because he is not believing or trusting to its direct peer, although he is finding better way, is less metric or some loop or some suboptimal path to reach to that particular destination. So how we can go and remove the loop with respect to tagging? Tagging is one nice feature we have inside route map. We can tag the routes, and while sending or receiving, we can use that tag. So what I can do here, I can go in this lab setup. I will tag OSPF domain as a 44. So OSPF route, whenever they will go to other domain, those routes, they will get tagged with tag 44. And RIP protocol, we are going to tag a RIP with tag 33. That means when the RIP route will go to other domain, they will come with tag 33. Now, what will happen with this, and what good thing will happen with this particular feature? So once we have tagging, so we have tagged the route. Now, what will happen? Suppose if we do redistribution and RIP will go and get the routes with tag 33, he will drop it. Correct. Likewise, if we do the redistribution and suppose if OSPF will go and get the route with tag 44, he will drop it. Why? Because this is my route. I have the trust within my network. I don't want to get the same route from others. And that's the whole concept that we can use to break this suboptimal routing. Now, when we have the loop or suboptimal routing, sometimes it is termed as a route feedback as well. You are getting same route from other domain. That is not good. So we are going to use this technique of tagging, not only tagging, but we can go and set certain attributes as well. Not only the tag attribute, but we can go and set the metric values as well. We can go and put some sort of ACL, access control list as well. And that's the whole idea behind this particular section 1.2. So what I will do here, let's go and log in to the lab where we have the break scenario. Means I'm going to show you one lab where we have some issues. We have to dig deeper inside the lab. We have to correct each and everything and make it proper and working. So while doing that, obviously we will learn that how we can correct the route map. At this point of time, we are well aware about our lab setup. So if you go to R1, let's go to R1 where we have OSPF routing domain, or OSPF is configured in between R1, R2, R3, R4, first portion of R3 and R4. So if we go here and if you go and verify the OSPF configuration, you can see flat OSPF configuration, no distribution. Means obviously here we don't have distribution. We have distribution on the border routers like R3 and R4, but in R1 and R2 you do not have redistribution. But if you go and check show IP route, do I am getting routes from a RIP domain? Let's see. So it seems that a redistribution is working and we are getting the route, and you can see the AD values 20 is type E2. That's good. And if we go and check R6, let's see in R6, do R6 getting the routes from OSPF? And let's see. So here you can see that R6, it is not getting the routes from OSPF. And now if I go here and check any of the routes, show IP route 10.1.1.0, let's see if we have any tagging. So tag is not there in this route. Okay, that means we have to go and check our R3 where we have done the redistribution. So over R3, if we go and check the configuration, although I can see some route map configure, OSPF to RIP, OSPF to RIP, the RIP to OSPF, but it is somewhere it is configured, somewhere it is not configured. So what I'll do here, let's do the troubleshooting. Let's first of all check the route map. And to make this little bit easier, what I will do that we will go and do the one-way redistribution. So we'll correct the routes in this direction first. RIP to OSPF. Okay, that means we have to go inside OSPF and call the RIP. And then we will go and correct in this direction. So first in this direction, second in this direction. So let's check router 3 and router 4 and this direction that is coming from RIP to OSPF. Great, let's go back to the lab. So here we are in R3. Let's check show run section route map. Just wanted to correct the route map that is coming RIP to OSPF. So I'm focused on RIP to OSPF. Do we have RIP to OSPF? Yeah, here you have. So I can see here clearly that we have the route map called RIP to OSPF, how it is configured. You can see that some deny statement is there, some IP match statements are there. Okay, so what is the idea? Idea here is this, that it is going from RIP to OSPF. That means, let me write here. So route map, and this route map that is RIP to OSPF. Oops. Route map RIP to OSPF, it should deny, and what it should deny? It should deny tag 44. See, OSPF don't want tag 44 route. So that means that this statement is correct. OSPF do not want, because OSPF having tag 44. You don't need this. So first statement is 100% correct inside the route map. What about second statement? So I will go and second statement, I'll start with permit 10. Now second statement, you can see here that we are not setting any tag. So see, this route is coming from where? OSPF. Sorry, this route is coming from where? RIP to OSPF, RIP. So RIP should having tag 33. Correct. And then you have match IP address permit any. Now we have to go and check what is this ACL. Is it permit everything, or is it permit only RIP domain like 10.110, 10.120, etc., etc. But permit any will also work. But if you want tight filtering, you can go and check the specific routing, specific ACL. Correct. So let's see here, do show, and then let me show you the route map, and the route map related to RIP coming to OSPF. So let's focus on RIP coming to OSPF. Deny 44, that is 100% correct. Then permit 20, the match address, I will show you this as well. Sure, and section permit any, what is that? And let me use 2. So you can see that permit any is permitting everything. So this is also correct. If you have any misinformation in ACL, that will also not work perfectly. So this is also okay. And setting the tag with 33, that is also okay. So that means if you go here to R1, and now if you go and check the show IP route 10.110, this 10.110, since we have set the tag as 33, it should have that. So we'll wait. Now I can see here that metric is 20. That means that we have to go and check the redistribute statement as well. So we'll go and check the redistribute statement as well here. So we'll see here, so run section router. And here redistribute. So we are going inside router OSPF 1, and then we need to redistribute. See, we have 2 options here. Either we can redistribute RIP and set the metric value here, correct? So I can go here, redistribute to RIP metric, and because RIP is coming to OSPF, so I have to give OSPF type of metric value here. I can go and give, correct? And you can see here the statement to redistribute RIP subnets. Remember, in the theoretical section, I told you that OSPF by default, if you do not use any metric, it will give a metric as 20. And that's the reason here you can see that this metric value is 20. Okay. So the metric value is 20 by default because we are not giving any specific thing. Either I can go and change this statement here, OSPF. Even I can see that when we are going to OSPF, we are not giving our route map as well. So everything is redistributing here default, correct? So first of all, I should go here to OSPF and I should remove this statement. First remove this. Once it get removed, let's go here. No redistribution, that means it should not get any route, and it may get because there is other peer also, router number D, who can send. So I think there also it is not coming. So you can see we have removed the redistribution, things blocked. Now redistribute rip the route map. What's the name? The name is rip is going inside OSPF, correct? So rip to OSPF, enter. Now again, I'm not giving the metric value here. Metric value, if we do not give, it will take default as a 20. Enter. Now we'll go back here. You can verify. And let's see, the route should come. See, you can see the routes are coming here. And now if you go and check this specific route, so you should have the tag. See, tag is also coming. So these checks are correct, but the metric is 20. And if you want to check the metric, again, you can go and change the attribute. So I can go inside the route map. The name is rip to OSPF. The statement is permit 20. And here I can set the metric. And metric, I can say I'll give 11. And then I can set the other attribute as well. Suppose if you want type 1, oops, type 1, because by default here you can see it was taking type 2, OSPF OE2. And if you do here, oops, if you go and check the IP route, you will see that OE1, and you can see there's 11 plus some 1 for gig interface. The cost value for gig interface is 1. So 11 plus 112. So now it is working perfectly in this direction. From where to where? It is working perfectly from RIP to OSPF, correct? Now, if you go and check the OSPF to RIP redistribution, so let's see that. So now we have to go inside RIP. We can go and use the OSPF to RIP. So route map configuration application to interface is correct. Now we can go and check the OSPF to RIP route map, and here you'll see. So now what we are doing, RIP should not match the tag 33 is 100% correct as per the logic. In permit 20 statement, you can see that match the tag. This is not correct. And set the metric is correct. So only one correction I need to do, that we can go here. Oops. We can go here to a statement number 20. And once we are inside a statement number 20, then I should remove the match statement because, oops, because we want to set this. OSPF is going to set this. So I should go and do no match tag 44 because we want to set the tag 44, and done. Now if you go to R4, you can go and check this, show IP route. Now same configuration as mirror configuration you have to do for router number 3 or router number D as well. Now here you can see that when we are getting this 192, we can see it's getting metric as a 3. That means 2. We have set here 2. Okay, if you go and check, set the metric as say 13. And now if you go to here, if you check, so you should see change because RIP updates, they are taking some time. See, it's become 14 now. So now our two-way redistribution, troubleshooting, route map, their filters, their tag attributes, I have covered each and everything in this particular section. Let us see that what we have covered so far and what are the topics I'm going to cover in this section. So we have covered 1.1 troubleshooting AD value. Then in the previous section, we have done the troubleshooting related to a route map. And even we have done troubleshooting related to loop prevention as well. Now, loop prevention with respect to route map tagging, with respect to distribute list, and with respect to if you want to change the AD distance values. Okay, so all these things we have covered earlier. Then in 1.4 we have redistribution, troubleshoot redistribution between routing protocol, and this also very much covered in the previous section, because in previous sections we have done the troubleshooting with respect to RIP and OSPF and RIP, and then we have checked the attributes related to route map. We have done the troubleshooting as well. Then we have 1.5. 1.5, I'm going to put a small lab related to 1.5 inside EIGRP section. And in the EIGRP troubleshooting section, again, we will go and we will check more on the troubleshooting related to manual auto-summarization. So 1.5 you will get later on in the specific protocol section. Now, once we complete up to section number 1.1 up to 1.5, then we have section 1.6 where we have to configure and verify the policy-based routing, PBR, correct? Now, we have learned this thing in route map, that in route map, we have one specific use case that with respect to route map policy, we can go and create PBR policies as well. That I'm going to show you here in this particular section. So this thing we have discussed earlier in the in the route map theory, that you can go and create the ACL. So you have the ACL, then you can go and create the route map, and inside route map you can go and match and set the attribute. Correct. So match the ACL and set the next hop, whatever gateway you have, and then you can go and apply this policy over the interface. This is one of the simplest form of PBR. We are going to use this logic here in our lab. So what we are going to do in our lab, you can see the topology. I have one router where one portion is belonging to LAN, local area network, and other portion it has ISP1, and other portion it has ISP2. In ISP also, while going via the ISP, I have given one destination 10.1.1.3. That's the router number 6 in the lab topology. So that means when you have host 1, so these routers you can assume as a host 1 and host 2. So host 1 and host 2, then when they will go and reach to their destination, so host 1 can go like this. So before applying the PBR, I'm going to apply policy based routing in this particular router. And if you do not apply the PBR, that means host to reach this particular destination, host 1 can go via this path or can go via this path as well. But if we go and apply the specific route PBR, policy-based routing or routing-based policy, whatever we can tell it. So PBR, policy-based routing. So what will happen that few of the subnets, so for example, host 1 and other subnets, we can prefer in one direction, correct? So what will happen that few of the destination will go in this direction via this gateway, via this ISP gateway, and few of the destinations can be reachable via this path along with this gateway. And that's the whole idea. So you can segregate the traffic over one path versus two paths. So if we have two exit gateways, some of the traffic you can force as a next hop. So what I can do, I can go and hard code that next hop for certain IPs will be this. And for certain IPs, say host 2 related IPs, the next hop will be this router. So the destination will be reachable in this direction. Okay, so I'm going to show you the lab. Here you can see in the lab IP schema, you can see it's straightforward. I will do and do basic static routing configurations here. Important configuration I will do, like policy based routing configuration I will do. And host 1 and host 2, these IP addresses are 192.168.1.10 and he has 1.20. I'm going to create the ACL related to host 1 and host 2 as well. So let me quickly go and show you this. So here, if I go to router 1, which is working as a host 1, and let me show you the destination IP as well. So destination IP is, let's see, it is 10 113, and if I go to the host one, if I ping to this IP, you can see it is pingable. And if I go and do the trace route to this particular IP, so trace route is in progress. Likewise, I can go to host number 2, and let's ping first. So pingable, and if I go and do the trace route, let's see, before applying any policy, how these hosts, they are reaching to their destination. So it is going to first gateway, and once it is there in the first gateway, then let's see that which path. So it is going via ISP1. Remember, 200 is for ISP1, and let's see that how he is going. So let's see, it is also, so both the host, they are going via 200, correct? Now what I will do, I'll make the change that host 1 should go via 200, or maybe I can make this as a 201. So let's do crisscross. Host 1 will go via 202. Actually 202 is the IP. Let me quickly show the IP as well. So the ISP IPs. If I go and enable show IP int brief, you can see that you have two IP, 200.111 and 200, 200.2.111. So one ISP versus other ISP, the top ISP versus the bottom ISP. Okay. And now crisscross means that host 1 should go via 202, correct? So let me show you how we can go and create. I can go here, and first of all, I can create the IP access list, host 1 via ISP2, or make it simple, host 1 ISP2, that's the name. Then I should go and give a standard here. You can go and give the keyword called a standard, and then you can go and you can do permit host 192.168.1.10, correct? Likewise, I'll create one more. So this time I'll create host 2 via ISP1. This is just the name, and this time I will give the IP. Host 2 IP is 20. Okay, so now I have the ACL that will be consumed inside the route map. So we'll go and create one route map policy, name ISP prefer, okay, and then permit 10, match the IP address. What IP address? So host 1 via ISP2, correct? And then set the next hop, set the IP next hop will be, we know that host 1 ISP2 means 202.1.1.2. So host 1 IP, that is nothing but 192.168.1.1 is preferred by ISP2. Then I'll go and create the other statement, that is statement number 20. And this time what we'll do, we'll match the IP address that will be host 2 via ISP1, and IP next hop, and set the IP. Next hop will be 200.1.1.2. Okay, now once we create this policy, we have to go and apply this policy to the interface, to the LAN interface. But before applying that interface, let's run this test one more time, because we should be clear that how the path is before the policy and after the policy. So meanwhile this trace is going on, I will go quickly. I will show you that where you can go and apply this. You should go to the LAN interface, that is gigi 0/1. And here you can go and apply the IP, let's see, policy, route map, and the policy is ISP prefer. I will not press enter here. I'll come back and press enter later on. Let's see the path. So here you can see that host 1 is going via ISP1 as per this trace before applying the policy. Both they are going via the ISP1. I'll go here and press enter. So policy is applicable now. I will restart this trace route from R1 and from R2. And meanwhile the trace is going on, I can show you the hit count. So now if you want to see the hit count, show route map and your ISP, your route map name, and press enter. So here you can see that you have packets. So for host 1 ISP2 packets, for host 2 ISP1 you have the packets, and you can see the packet 11.7. Now if I go press enter, it should increase. So this time 18 packet, 17 packet. That means that traffic is going, hitting these rules at least. And clearly you can see that now host 2 is going via the next set hop, that is 202 as ISP2. And here you can see that it is going via the ISP1. So see that with respect to policy map, how we can play around with the next hop and we can load balance the traffic. So not only that we are changing the next hop, but we are playing around with the traffic as well to load balance the traffic as well. All right, let's just stop here. Virtual routing and forwarding. What is the use of VRF? When you're creating virtual routing and forwarding instance, so at that time you can segregate or segment the routing table. So for example, you have one global routing table, and then you may have a routing table for segmented, or for example, you can think like for customer A, you have one, customer B, you have one, customer C, you have one, like that. So it's like segmentation in routing. And what's the use case for that? So you may have business VPN services, network segmentation, data center access, etc. Now, this term that VRF that we are seeing here is actually layer 3 virtualization in terms of routing. But if you see and verify that, do you have any layer 2 virtualization technique? Yes, we have VLAN, virtual LAN, as a layer 2 virtualization technique where you have, say for example, every VLAN having their own spanning tree instance. Every VLAN has its own MAC forwarding table. Likewise, if you go and check VRF, you'll find that all the VRFs, they have their own CIF, they have their own routing processes. Means most of the routing protocols, they are supporting VRF. And in the diagram, you can see that you have one global table, and then you can have VRF. So what we are doing that we are creating a VRF, and then we are associating that VRF to one of the L3 interface. So that means that one L3 interface, or one interface specifically, can have only one VRF. And later in the lab section, you'll come to know about this. Now we have various techniques related to VRF to provide fast switching or fast pathing. VRF Lite and then MPLS. MPLS is quite a bit popular. So what's the idea behind this is that you may have end-to-end segmentation. So suppose if I have diagram, so here you can see that maybe you have one end where you have VRF A and VRF B, and then you want this segregation, or you want this virtual routing forwarding instance to propagate throughout the network, means end-to-end routing instance or end-to-end segmentation. Now, if you go and use VRF Lite, so in that case, whatever devices you have in between, here you can see, although you have only one switch in between, but it is showing green and red, means you have two VRF, two routing forwarding instance, two inside process, or two virtualization inside one box. We can think like that. So the idea here is that if you are using VRF Lite, then you have to go and enable VRF Lite to all the devices. And that's the problem, that VRF Lite, although they are very easy to use, but they are not scalable. So that's the reason we are using MPLS, multi-protocol label switching, where again you are using LDP as a protocol to create the labels and then to exchange the label. Okay, so this is one of the use of the VRF. Although we are going to have, so we are going to perform one lab, and in that lab you will see use Let us perform the lab task related to VRF Lite. Now in the diagram, you can see that we have two sides. One side where we are going to configure the VRF. Other side, we have the global routing table. One side, I'm going to put the address space. So you can see the same address spaces that we are going to use in router 1 and router 2. You can see loopback 1 having IP 1111, but loopback 2 having IP 1111. One is inside VRF, but other one is inside the global routing. And you will see the configuration. I'm going to show you the configuration snippet, and I'm going to share all this configuration as well. Although we are going to run EIGRP, either it's a global routing table or it's an instance inside VRF. Everywhere we are going to use the EIGRP as a routing. All right, so let me go and log into all the devices, and I will show you the configuration for all these devices, what configurations we have related to these devices. You can refer the topology. Topology is straightforward, that router 1 is connected with router 2 again is connected with router 3 and router 4. Now one side of the topology you can see, so let me quickly show you that topology one more time. One side of the topology you can see that we have VRF Lite configuration, that is from R1, R2, R4, correct? So here we have the VRF Lite. So here we are going to do the testing, ping testing with respect to VRF. And one side R1, R2, R3, it is configured as a normal global routing table. Okay, great. So let's go and let me show you first of all the IP addresses, and then I will show you all the rest of the configuration. You can see here that we have loopback 1, loopback 2, and if you go and check show and int loopback 1, loopback 1 we have created put inside the VRF. That means that it is going to connect from R1, R2 to R4. And if you go and check show VRF, let me show you the VRF. So we have VRF, and see this inside this VRF, we have interface loopback 1, and we have interface gig 0/1. Same address space, see 10.1 and 10.1 for both the interfaces. One interface, so CDP neighbor, one interface that is going actually 01 and 02, both are going from R1 to R2. We have two link going from R1 to R2. And if I go inside R2, let me show you the IP schema. So R2 is a bridge between R1, R3, and R4. And here you can see the connection with R1 and then connection with R3 and R4. 03 connected with R3 and 04 connected with R4. Let me show you the show CDP neighbor. So you can see here R3 is connected with 03, R1 connected with 01 and 02 interfaces. R4 is connected with 0/4. Okay, so straightforward. And again here also you can go and check the VRF show VRF. You can see the interfaces loopback 0, gig 01 that's going towards router number 1, and gig 04 that is going towards router number 4. Rest these devices, they don't need VRF Lite configuration. And here you have very easy, straightforward configuration. So here you can see that you have two interfaces. One is loopback, just to add one extra interface for testing purpose. And even in R4 as well, if you go and see, the configuration is very simple and straightforward. Now here, if you go and check the EIGRP, you'll find that EIGRP configuration is also very straightforward. We are starting the EIGRP process and advertising the network. Likewise, inside R3 also, you'll find the EIGRP configuration is easy and straightforward. But we have interesting configuration related to EIGRP here in R1. So let me show you here. We are using EIGRP name is VRF underscore Lite. And then we are using the address family. First of all, you can see that we have the global type of address family. That's the unicast, this address family. Autonomous system, we are using one. And inside the topology base, you can see I'm advertising loopback one, whose IP is 11111. And then we have the other interface that is going from R1 to R2, correct? That is inside the global routing table. So let me quickly confirm here that which interface is there inside the VRF. So if you go and check show VRF, actually loopback one inside VRF. So this IP is actually the first IP that you are seeing here inside loopback. This is loopback 2 address. So inside global routing table, I have loopback 2 and this IP because they are going towards R3. So R1 to R2 to R3 where we have global routing table, correct? And then this portion of configuration is belonging to actually loopback 1, and then this is belonging to R1 to R2 that is that we want to send towards R4. So gig 0/1. Okay, this particular IP. So one IP we are advertising inside where we are advertising inside the address family unicast, but it is VRF instance, correct? And one IP is global. Likewise, we can go and check the R2 EIGRP configuration. So if you go and check R2 EIGRP configuration, you'll see that one IP should be as a global and one IP should be as a part of a VRF. So very much similar configuration. Now the partition. So from R1, if you go and check show IP EIGRP neighbor, which neighbors are part of VRF here, you can see it is telling that is a part EIGRP IPv4 VRF. The name is VRF Lite. And if I can do details, so I can show you the detail about that. So I can see that neighbor is up. Let me show you show IP EIGRP neighbors, and then detail. If I can show you some more information about any of the interfaces that we have. Yep. So EIGRP is not in a requested interface because we are actually running network based configuration. So I can see here that one interface that's gig 0/2, we have EIGRP enable on that and show run section EIGRP. Let's see the configuration. All right, so 0/2, we can see that EIGRP is there. Now what I want to show you here, it's very important. So if you go and check show IP route and VRF VPN underscore A, you should learn the EIGRP specific route. See, router number 4. I'm learning. Even I'm learning on loopback that is belonging to which interface. You can see it's coming via 0/1. So one is specific uh, subnet that is belonging to router number 2 that is part of VPN A or VRF A. So here you can see that we are learning correct routes 22224444. Now if I go here and if I do show IP route EIGRP with respect to global routing table, so you should see 3 here. You can see 3. You are seeing 222 as well because we have 2 IP addresses. Remember, one is loopback 1, one is loopback 2. One is part of VRF, one is under global routing table. Not only that we are seeing the VRF Lite, but we are seeing that the usability of IP addresses as well. So let's do the testing. Now, if I want to do the testing with related to my VRF VPN A and the destination we know towards router number 4, we are going via the VRF, correct? And source is We know that our loopback one having IP address 111, and you can see here sure and interface loopback one is a part of VRF. Correct. So it's going properly. There is no problem. And if you do the trace route, you will find that yes, it should go from R1 to R2 to R4. So VPN A and the destination is 4444 and the source is loopback 1. Okay, so first hop should be router number 2 and then the second hop should be router number 4. So it should follow that particular path. Okay, so now at this point of time, we are testing the path from R1 to R2 to R4. Now next we'll go and test the path from R1 to R2 to R3. Okay, so same type of test, ping test and trace route I'm going to do. Ping because this time we are inside the global routing table and I can give the source as a loopback 2, correct? Because this is under the global routing table. Likewise, we can go and do the trace route with the source of loopback 2. All right, so this is the lab related to VRF Lite. What I will do that I will put the configuration file. So you can also go and check the router 1, 2, 3, and 4 configuration. Although router number 3 and router number 4 configuration is easier, straightforward. Router number 1 and 2, what we are doing, we're going inside the EIGRP address family and then we are configuring the global routing table and we are configuring the routing under the VRF. So here also you can see that all the test pass. That means we are good to stop this particular lab. Next important topic, we have BFT. BFT, that's bidirectional forward detection, providing fast failure detection with respect to different type of media types, encapsulation, topologies, and routing protocols. Now, how BFT is doing that, they are working in sub-seconds. So that means that if other protocol, they are using 10 seconds to send the hello packets and then the dead timers of, for example, 40 seconds to detect that the peer is not responding. With respect to that, BFT is using milliseconds to detect that. And BFT, so not only that, they detecting the failure or detecting the neighbor unreachability, etc. BFT is less CPU intensive, and that's the one very important thing. And second thing is that BFT makes network profiling and planning easier. Okay, so what are the things that BFT is providing us? BFT is providing the fast failure detection. It is less intensive to CPU. It is easier to do profiling and planning, etc. Okay, and that's why BFT is quite popular and used almost everywhere. Some of the protocol internally they are using BFT. For example, Cisco SD-WAN, Viptela. When they are forming the IPsec tunnel, BFT is there enabled by default. That means you don't have to do anything. BFT is automated or encoded there inside the data plane to detect the IPsec tunnels. Okay, we can go to the Nexus switch and we can enable the BFT in the asynchronous mode. So now what does this mean by asynchronous mode? Asynchronous mode, that means that you have to go and enable the BFT in both the neighbors, so neighbor A and B, and then BFT will come into the picture. It has three characteristics. It has TX, it has RX, TX that desired minimum transmit interval, RX that is required minimum receive interval, okay, and then is failure. Detect the multiplier in terms of failure. So suppose you're sending the hello packet after every 20 milliseconds and expecting that you will receive also after every 20 milliseconds. And if you go and give the multiplier of 3, that means after 20 milliseconds, not in seconds, so 20 milliseconds. So after 60 millisecond, you will detect that the peer is not responding, and then you can take the action that peer is unreachable, etc. Correct. Now, good thing about BFT is this, that you can go and attach the BFT with different type of network protocol like OSPF, ISIS, EIGRP, any type of networking protocol we can go and attach with them, first thing. Second thing, even we can go and link BFT with IPv6 as well. We can link a BFT with HSRP, VRRP, etc. Okay, so wide range of protocol is there that is supported by BFT. Now let's understand in this diagram that how BFT is helping OSPF to form the, first of all, BFT neighbor relationship, and then we'll check the failure scenario. Correct. So here you can see that what is happening, that OSPF neighbor is forming, and we are going to do the configuration as well. I'm going to take example with respect to ISIS. So in our lab, ISIS is running. On top of ISIS, we'll go and configure the BFT. So you have your OSPF neighbor, they are up and running. And then once we go and configure the BFT inside OSPF, then BFD will start working in between the peers. Correct? Now, what will happen if there is failure? So in case of failure, because we know that BFT, they are working in sub-seconds. Okay, and OSPF hello timer is much more higher than BFT. That thing we know. So what will happen, that once you establish the BFT session in between two neighbors, and you can see here that as per your OSPF BFT configuration, you have established the BFT relationship or BFT session in between two neighbor. Correct? Now, what will happen, suppose if you have any type of failure, you can see the failure is there, some link issue, unreachability, high CPU, device reboot, etc. There may be so many different type of failures. So in that case, the BFT, they are sending, receiving TX, RX, and then the multiplier in between. So after 3 consecutive uh, multiplier, I mean, suppose if your multiplier is 3, so after 3 consecutive transmit, you are not getting any receive, and then you detect that, okay, after maybe 100 millisecond, you find that the peer is unreachable. Correct? And we know that 100 millisecond is 1/10 of second. So once the BFT will detect as a lower protocol, then it will go and inform the upper protocol. So BFT will go inform OSPF that your neighbor is unreachable. You have two options. Either you shut down the neighbor, that means you break the relationship with the neighbor, or you reconverge your protocol and try to find some other way to reach to the neighbor. Okay, and that's why the convergence will be faster with BFT. BFT is helping protocols to do the convergence. Uh, if you have alternate path as a routing protocol, then you can go and look for the alternative path. So what is happening here? You have two devices, you are running your higher protocol OSPF. We are going to check this inside ISI. So I'm running, for example, ISIS, and then I have my BFT profiling. So that means the BFT, so first of all, your ISIS is running, ISIS, and then your BFD, I'll put inside this, not here. So I have my BFD as well. BFD, they are using, for example, 1/10 of second to send the TX, and then RX is also 1/10 of second. Now, if any failure is here or here, because it's a bidirectional, so any place if you have the failure, then after 3 of 10th, 1/10 of second, 1/10 of second, and 3/10 of second, like that. So I'll make this that 1/3 of second. Anyhow, you come to know that, okay, there is a failure, and then you'll go and inform the upper layer protocol that a protocol. Your agency, your neighbor is unreachable or having some issue. Can you check some alternate path if you have any backup path to reach to the neighbor, so you can reconverge your SPF algorithm and check alternatives. Okay, so like that, BFT is helping to reconverge faster. Now, how we can go and do the configuration? We have two modes of configuration. We can go and configure over global interface. We can go and configure over the interfaces as well. So we can go to the config, configure it, or we can go to the particular interface and configure it. If you want to disable it, you can go and use no feature BFT. So BFT feature will get disabled. We know that in the Nexus switch, we have to go first of all and enable the feature called BFT, and then you can do the rest of the configuration. Okay, so in terms of global parameter, how we can do the configuration, you can go to the global mode, say conf t, and then you can go and configure BFT interval. First of all, you have to give the TX. TX is not given here, but first option will be TX, and you can read the purpose here. So TX is 50 millisecond, and then minimum RX. Again, we are giving 50 millisecond, and then a multiplier is 3. Okay, and we have discussed about what does it mean by TX and RX. You can refer this particular slide as well. So minimum transmit interval, the interval at which the device want to send the BFT. Minimum receive interval, the minimum interval at which the device can accept BFT hellos, and then you have the multiplier. Great. So this is the configuration command here. You can see, let me highlight only the configuration here. So BFT interval 50, minimum 50, multiplier 3, and you can see what's the minimum, what's the maximum, and what's the default value here. Okay, now over the interface also we can go and configure like this, but we have some other options as well. So first of all, if we can go to the interface, we can do the configuration related to BFT like we have done in the global mode. And then if we want, we can give the key as well. So BFT authentication key, that's the first thing. And there are some other parameters as well we can go and give to the interface as well. So I will go and I'll show you that some other parameters as well we can go and provide. Okay, but so very minimum that you can go and enable the BFT. If you are in the Nexus switch, enable the feature, go to the global mode and run this command, or enable the feature, go to the particular interface and run this command. Great. So we are going to check the BFT configuration over ISIS. So I will go and run this BFT over ISIS, and what we'll do, we'll go and check over the interface. Okay, what you need to do, you have to go and check over the interface, because I want to do it over the interface. So we'll go to the interface, and then we'll run ISIS BFT. Okay, and then we'll go and even go and check the configuration related to BFT as well. So I'm going to show you this ISIS BFT in a while. Before that, let me go and complete this particular section. I have few examples related to other protocols as well to show before going to the lab. So for ISIS, you can go to the router ISIS, you can enable BFT. You can go to the address family. If you have IPv6 address family, you can go to the address family, you can enable the BFT. So here you can see BFT example feature, BFT, if you have protocol feature OSPF, and over OSPF, you can go and enable like this. Over EIGRP, you can go and enable like this. Over IPv6, where you are using OSPF version 3, you can go and enable like this. Okay, so it is supporting, it has a wide range of support, and we can go and enable over almost all the routing protocols. All right, so let me log into the lab section and let's go and configure the BFT related to ISIS. Here you can see in the diagram that in between R4 and R5, what interfaces we have. So R4, I have gig 0/2. R5 I have gig 0/1. So I want to enable BFT in between that. So let me go to R4 and let me go to R5. And what we can do here, we can go to the interface and we can enable that BFT feature. So inside R4, the interface is gig E0/2. So let's go to gig E0/2, interface gig 0/2, and then we can go and give BFT. So let's check if we have ISIS BFT here. Yeah, we can go and enable ISIS BFT. And now we have the syslog message. So BFT session created, BFT session created with the neighbor. Okay, and what we'll do, we'll go to this side. And here also, we can go to the interface gig 0/1 and we'll give ISIS BFT and 45.4, 45.5. So with this peer, the BFT session has been created. Now what I can do here, we can go here and we are already over the interface. We can shut down the interface. At the moment I shut down the interface, you'll see that BFT session destroyed, BFT session destroyed, handle high, process ISIS, handle act, and administratively down, BFT is down. So at the moment the interface is down, you can see that BFT is down and it is telling that ISISC BFT is down. You can check your neighbor or you can reconfigure the protocol. So here also you can see we are getting the message. So this is the way. It's very easy to enable it, and because this is the iOS platform, so here you have simply one small command to enable it. If we'll go and enable it in the Nexus, so we have the option to do the configuration related to TX, RX, and the multiplier. All right, so we have checked the BFT. Let's stop here. In section 1.9, we have to understand about EIGRP troubleshooting. Now, what I have done that I have created one playlist related to EIGRP technologies. That means before knowing the troubleshooting, what are the troubleshooting steps we have in EIGRP, we should understand the technology behind EIGRP. So here you can see that I have created one playlist with 13 videos where we'll understand about EIGRP basics, how they are forming their neighbors, what is EIGRP Metric, EIGRP Basic Lab as well. So this particular theories, they are backed up with the lab as well. How EIGRP, they are forming the neighbor table, topology table, and then finally routing table, how EIGRP, they are doing the convergence, and some of the labs related to load balancing, authentication, and summarization. So please go complete these videos, and after these videos I'm going to start with the EIGRP troubleshooting. Okay, so after that I'm going to add few videos related to EIGRP troubleshooting, and that will complete our section 1.9 with respect to EIGRP. Let us understand the routing fundamental. In this case, we are going to understand about EIGRP basics. Now, what is happening that all the routing protocols, they have same type of fundamental. That means that they have to establish the communication. So suppose if two routers are there, obviously they will form some sort of relationship in between them over the reliable transport, and then only they will start exchanging their routing informations. Correct. So in the same line, you'll find that they have to establish a communication, then they will start exchanging the routes. They have to perform the competition. That means suppose if you have multiple nodes in between and you're exchanging the routes, that means they have to use their algorithm to get the best route, to select the best path, and all those calculations. Correct. In EIGRP, we have something called dual algorithm. In OSPF, we have a SPF algorithm. We'll check dual algorithm in upcoming slides, more about that. But yeah, to build the relationship, to exchange the route, to perform the computation, and finally, you install the route inside the memory. So that should be consistent. That means whenever your traffic want to reach that, you can use your memory, your CPU will tell you, okay, you can go by this. So all the time you will actually not build the same thing. You will use whatever cached inside and then perform the routing. Great. So you can see the fundamentals are there, and EIGRP is no exception. EIGRP is using some sort of reliable transport RTP to build the relationship in between that. They have the reliable transport. Again, they are doing some sort of three-way handshaking. First of all, to build the relationship. So this was the point one. Then a reliable transport to route exchange. Then path competition. We have dual algorithm, diffuse and update algorithm. Then finally, they have the routing table update and peer update if it is required. Correct. But yeah, if you go and sequence, you'll find that most of the protocol having the same type of strategy. We know that EIGRP is a distance vector routing protocol. Sometimes we are referring that this is advanced distance routing protocol because it has the attribute of distance vector protocol, but it has attribute taken from the link state type of protocols as well. Now, how distance vector protocol they are working? So they know the prefix and the next hop. So suppose if D has to learn the A prefix, so obviously they will learn via B and C. So D can learn 10110 either from B or C, correct? That means that to reach here, it has to go here and it has to go here. It's just straightforward. So B and C, first of all, they will learn the 10110, and then D will learn from either from B or C. It depends that whatever matic is better, one will be preferred, other will be backup. Now, we'll see the problem here. So problem here is this, and that's a very important point. Now, when we are talking about the routing protocol, more precisely the distance vector routing protocols, so we do not have a visibility of the topology. So the devices in between, they do not have a visibility of entire database. So suppose if he's one of the router, he don't know means he don't have the visibility what is there, correct? So something is happening in between A and B, and if don't know, suppose if has to go and learn 10110, so it will be difficult for him to know him what is happening behind the scene, because topology you can see is hidden, and that's the problem, and that's the overcome. We'll see that how EIGRP is coming out of this. Now with this problem, what is happening that when A and B, suppose if this link will fail, so D will send, so D will tell, hey, see, this 10110, because some link issue is there, I'm not able to send you. Then what if will do? It will start sending query to everyone, all his neighbors. See, do you have this network? Do you have this network? Do you have network? And doing so, this will result in increase in CPU, memory, and convergence time. Correct? Now this is the problem, because we don't have full visibility in the topology, and that's actually the problem with the distance vector protocols. Later on, we will discuss about uh, terms that how we can go and overcome from these issues and how we can limit on these criterias. Still, we are in the basics of EIGRP, and we are going to learn more terms and features inside EIGRP. One of the terms we have in EIGRP is that they are part of autonomous system. So autonomous system is what? Autonomous system is that you are under same administrative control, you are under same number. So you should have a consistent routing policy, and then you're part of one system, you're part of one tag, like that you can think. So autonomous system 100 belongs to me, it's my domain, it's my area. So a part of same group, that means the autonomous system. Let me quickly summarize whatever we have studied earlier in coming 2 slides. EIGRP is using diffusion update algorithm, okay, to do the computation. So compute part is happening with respect to dual algorithm. They are part of same autonomous system. That means same administrative control, same policy segment, etc. So this and this very important point. Then EIGRP can use unicast or they can use multicast to send the hello packet, correct? They are using RTP to build the trust communication in between two nodes. Now, EIGRP to build their routing database, do not send periodic full table routing update. Update are sent when a change occurs. Okay, so that's very important. It's like RIP, they are not sending the entire databases all the time. If there is any change, then they are sending the update, and they are classless protocol. They are supporting a variable length subnet mask. So these are very important high points related to EIGRP. They are multicast, they are multi-protocol support, means they are supporting different type of routed protocol stack like IP, IPX, AppleTalk, etc. The internal AD is 90, the external AD is 170. Their metric, although this EIGRP metric value is little bit complex to understand. They depend upon 5 criterias: bandwidth, delay, reliability, load, and MTU. Some of the books they are referring that MTU is not part of metric value, but you can think that at this point of time, you can think that, okay, EIGRP metric value heavily relying upon bandwidth and the delay. Okay, reliability and load, they have less impact, but mostly they are depending upon bandwidth and the delay. They can go up to the maximum hop count of 224, and default hop count will be 100. And finally, while they are building their routing table, their best table, so first of all, they are also going into the phases like they are building the neighbor table, topology table, and then finally the routing table. Remember the topology table, a list of all the routes in same administrative controller, same administrative policy, same AS. Like this AS is not like BGP AS, but they are part of same autonomous system. Great. So these are the basic point related to EIGRP. Let's stop here. In this section, we will go and check the basic configuration related to EIGRP. That means that when we log into the router and when we are doing the day 0 type of configuration, the first configuration what we want to do related to EIGRP. Now, EIGRP, Cisco has done some enhancement. So initially EIGRP having the classical mode, that means you can go log into the router, go to the configuration mode, and you can write router EIGRP and then the AS name, AS system name, like 10, 20, 30, etc. So router EIGRP and then 10. That means you are kicking EIGRP process start. So EIGRP route process will start with this command. And then later on, we can go and add commands related to network advertisements and some other. Correct. So that is one of the mode that is called termed as a classical mode. But Cisco has done the enhancement, and now we have advanced mode. You can think as well advanced in terms of named EIGRP mode as well. Now, named EIGRP mode, that means if we are supporting or if we are running the address based or the name based EIGRP, more precisely it is termed as that. So in that case, we have multiple address family support plus some other added features as well. So here you can see side by side the differences in terms of configuration. The classical EIGRP, normally we can go router EIGRP1, we can give the network command, summary command, etc. And then we can go to the interfaces, and over the interfaces, we can go and run the summary address EIGRP command. Okay, but when we are coming to the name base, then we can go to the EIGRP, we can give the name. Right? And this name is not something that should be common in all the routers. It is something like you are starting the name based EIGRP, and then inside that you can go, still you have to go and give the autonomous system. So name is not something that we should have same in all the routers. It's not a constant thing. In router 1 I can give different name, router 2 I can give different name, router 3 I can give different name, but for the sake of uniformity, sake of simplicity, we can give same name within the autonomous system. Correct. So that's one thing. So here you can see that how it will be. You can go and give a router EIGRP and the name. Then we can go inside different type of address families like IPv4, IPv6, or certain VRFs as well. Once we are inside the address family, then we can go and run the classical EIGRP command. So here you can see that we can go to the address interface, address family interface, and give the summary address, one thing. Then the router based command or routing level command, we can go to topology base, and then we can do the summarization. We can change the k values related to metrics, and then we can go and give the network commands. Correct. So you can see that if we are using the named based EIGRP, so at that time all the address families that can be put inside same like IPv4, IPv6, VRFs, etc. Everything is supported under one name, under one hierarchy. Means obviously you have to go inside the address family and you have to write the command related to IPv4, IPv6, etc. But it is uniform now. It is clubbed in an organized way. Unlike classical EIGRP, it will work, do the same thing, but again, for different address families, you have to go and write it separately. Correct. So now when we are talking about the EIGRP, the configuration is straightforward, but when we are running with the named mode, they are going to support IPv4, IPv6, VRF instances as well, and we have a uniform type of configuration throughout the configuration or throughout the system. Correct. So you can go to the name, then you can go to the address family, VRF, even multi VRF supports are there, multiple address family supports are also there. Apart from that, there is name based EIGRP, they are supporting multiple interfaces as well. So you can see that you may have default interface, or you can go to the specific interface and you can execute the command. Like you can see here that we can go to one of the AF interface and then we can do the summary. Okay. And then finally, you can see this is the summary that we have. So you can go to IPv4, IPv6 address family. So once we are inside the named, we can go to the address family IPv4. We can give the summary command related to network. We can go to IPv4 VRF. Then we can go and use network command. We can go to the IPv6 and then we can give the IPv6 related commands. Then we can go inside IPv6 VRF and then we can go and give the commands. Correct. So you can see that in wider picture, in longer run, the usability that we have with respect to named based EIGRP. In this section, we'll learn that how EIGRP, they are going to form the neighbor relationship. Now, EIGRP, they are using multicast packet 224.0.0.10 to exchange their hello packets. They can use a unicast packets as well to do so. Now, while forming the neighbor relationship, node A and B, they are using some sort of three-way handshaking or three-way communication to form the neighbor relationship. So how it is working? First of all, suppose if B has sent the hello packet to A, then A will go and send the init packet to B, some packet with null bit inside that. And meanwhile, what it will do, it will mark the state as a pending. So pending in terms of that, the neighbor relationship is pending, it is in progress. Correct. Now, once A will send the init bit to B, then B has to send the ACK back. And this is the third step. So step number one is the hello. Step number two is the init exchange. That means A has to send the init to B. And step number three, that B has to send the ACK for A init. So that means that three-way handshake process will complete, and now A will mark that pending state to the up state. So that means now A and B, they are neighbors, and then they are ready to exchange further routing informations. Correct? To verify the neighbor is up or down, we have one CLI command, show IP EIGRP neighbors. Now with this command, we are going to get good amount of information about the neighbor. First of all, the order in which I have learned the neighbor, what are my neighbor addresses, which interfaces I am learning the neighbors, the hold down time. That means how much time I have to wait to mark that neighbor is down. Generally, this is 3 into hello time. So suppose if your hello time is 5 seconds, so this will be starting from 15, 14, 13 going to 1, 0. After 0, that means that neighbor is down. The neighbor is up from last 6 days or 2 weeks or 3 weeks, etc. Those timers, those time counters. Then we have Srtt, that is a smooth round trip timer, that is going to tell you that how long it will take for this neighbor to respond to the reliable packet. And again, here you can see that the description for Srtt, that average amount of time it take to get an ACK for a reliable packet for his peer. Means you are waiting for your peer to get the acknowledgement. That's the average, A to B, B to E. That's the round trip timer. Then we have request timeout. Request timeout means how much time you will wait for the retransmission related to acknowledgement. Queue count is there. Queue count is going to tell you that if any packets they are stuck. If queue count, if you get some numbers here, that means some issues, some problem with the line, link, etc. Finally, the sequence number. There's the last reliable packet sent. Great. So good amount of information we are getting. Still in that, if we go and use the keyword detail, so we are going to get some more information. So we are going to get the number of retransmissions and retries, the version of iOS and EIGRP. So you can see that the versions of iOS, EIGRP, retransmit, retrans, and if we have any stub configuration. So we are going to get these details inside show IP EIGRP neighbor detail. Some other informations as well. So suppose A and B, they have formed the neighbor relationship with a default hello timer of 5 seconds. But in case if you want to change the timer, so we have option. We can go to the link basis and we can change the timer. So we can go and use the command IP hello interval EIGRP. EIGRP 10. 10 is the autonomous system. And then we can go and use the 7 second. 7 second means this, now the timer for hello packet is 7 seconds instead of default 5 second. Likewise, we can go and change the hold down timer as well. So instead of 15 second, if you want to make 15 second, if you want to make 21 second, you can do it. Now suppose one device having a timer 5 and 15 second, other device has timer 10 and 30 seconds, still they will form the relationship. The way that they are transmitting their hello or dead timers, those timers will get changed. Okay. Now one very important point here is this, that while forming the neighbor relationship, these devices, they should use their primary addresses, and their primary addresses should be part of same subnet. Suppose if they are not part of same subnet, then you will get one error message that EIGRP neighbor not in the common subnet. Okay. And finally, if you want to log the changes, so we have the CLI command we can go and use. First of all, go to the routing process and use EIGRP log neighbor changes, and then you can use EIGRP log neighbor warning. Okay, let's stop here. In this section, we are going to understand about EIGRP packet types and different type of flags that EIGRP is using. Now we know that EIGRP, first of all, they are building the relationship, neighbor relationship in between the nodes. So suppose if you are in the shared media point-to-point link or NBMA network, any type of network or media we have, EIGRP will go, first of all, they will build the neighbor relationship and then they will exchange the packets. Now, that's interesting fact here about EIGRP is that they are using both type of messages. So they are using unreliable messages or the packet types, and they are using reliable messages or packet types as well. Now, while building the neighbor relationship, when they are going with three-way handshaking, means you're sending the hello, receiving the init or initialization bit, then you're sending the ACK, correct? So that three-way handshaking process that EIGRP has. After that, so during that, they are using unreliable messages like they are using hellos. So hellos and ACK, they are part of unreliable message exchange. But after that, whenever they will go and do the query, reply, update, etc., means those type of messages types, they are falling under reliable criteria. So here you can see that the reliable are hellos and acknowledgement, and then update, queries, replies, stuck in active queries and replies, they're part of a reliable packet exchange. Now, why we are talking about reliable or unreliable? Because if it is reliable, that means you are using some sort of sequence number, you are using some sort of ACK packets, acknowledgement. Correct? We know this thing from the TCP world that they are using connection-oriented, reliable communication, that TCP protocol. Like that, the EIGRP, they are using RTP, and the major packet types you can see here that hello, query, reply, request, and update. The hello and ACK, they are falling under unreliable packet exchange, but the rest of them are reliable. Means they have the sequence number and the acknowledgement. Let me quickly go one by one. So hellos and ACK, we know that hellos, when they try to form the neighbor relationship, the EIGRP, when they are discovering some new neighbors, then at that time they are using hellos and ACK. Update means that you want to update, means you learn something and you want to share that information to your neighbors. So that is the update. Then query, suppose if your neighbor or someone is looking for new messages, new network actually, or new subnets, then they can send query packet and then query. So if someone will do query, so the reply will come into the picture. Correct. Now these update, query, reply, stuck in active, query, reply, all these packages, they should have the acknowledgement because they are falling under reliable packet criterias. Then finally, you have a stuck in active. That means that suppose you don't know the network, you are doing the query, but still you are not getting the reply. So at that time, SIE query, so stuck in active query, so they will go and do the query to the non-replying peers. So that means your query is forwarded throughout the network to until unless you'll get the response. Okay. Now we have very important flags as well. So one of the flag we know from the previous section, that is the init bit. During the hello exchange, it is going to be used. Apart from that, we have CR, something known as conditionally received. We are going to discuss about CR in upcoming slide. We have RS, that is the restart flag, and this is set in case of hellos and init update, and when we are using non-stop forwarding signaling. So again, at the time of initial negotiation, this RS restart flag will come into the picture, but in case of non-stop forwarding, NSF signaling. Then we have EOT, end of table. What is usability of this? Again, I will cover this in the upcoming slide. So these 2 points I want to cover in detail in the upcoming slide, the CR and the EOT, because these are important. Great. So before reaching to CR and EOT, we have some few more slides for information purpose. Let's talk about updates and advertisement. We know that whatever network that router A has, he wants to send the update. Obviously, he wants to advertise their own network to the neighbor. Now, what will happen when A will send the update to B? B will send a poison reserve. Okay, so what does it mean? This poison reverse, that means that poison reverse route is something that, okay, I got the route from yourself. Now you will not get the same route from myself. So in other words, this poison reverse means that do not teach me what I am teaching you. Like that is root poisoning type of thing. Correct? All right. So that is one very important thing. So what is happening here, that A is sending the update to B, then B, what they are doing, they are using this poison reverse route. So B in the update, what they are doing, that they are making the matrix as an infinity. Obviously, this is something that A has learned. I learned from A. I don't want to teach you A. That's the indirect meaning. Then finally, what is happening, that the A, and this we have discussed here, means we have talked about this EOT, end of table. So now A, what the A is doing, when he is finishing sending all the update from himself to router number B, they are sending the marker, the flag EOT, end of table. That means that whatever I have explained to you. Now I don't have anything. That's the marker. So A is putting the marker. That's a flag actually. EOT, end of table. Okay. So that's the use of EOT. Correct. You're telling your neighbor, your peer, that see, finished. Everything I have told to you now. It finished. My table is finished. So that's EOT. So now we know init flag, we know about EOT, we know about RS. I'll go and cover CR as well, conditional receipt. This is also very important. Great. So we know at this point of time that apart from acknowledgement, apart from hello packets, you are getting the acknowledgement for everything. Correct? All the packet, all the message exchange we are getting. Now we have very important flag here termed as a conditional receipt. What is happening in conditional receive is that suppose A is sending update to B, C, and D. So after sending the update, obviously A is looking for acknowledgement. Now, due to some reason, if A is getting the acknowledgement from C and D, but it is not getting the acknowledgement from B, that means that A will go and start the conditional receive mode. Okay, so that means here the conditional receive mode will get enabled before the timer will get expire, and A will go and send the retransmit bit. The CR mode will be act. So CR mode is enabled. Now what the CR mode will do, let's understand about that. But meanwhile, since A hasn't got the acknowledgement, so next time when it will build its hello packet, what A will do, in that hello packet, he will mention the B's address as well. Now, when this particular packet will be multicast in a network, so C and D will receive this message and it will open that hello packet. It will see, oh, this message having some other address. This message does not include my address. So C will think this message does not have my address. D will think this message does not have my address. That means that we will also put ourselves into CR mode. Okay, so remember, whoever address is there in this built hello packet, that particular device will not go into CR mode. So for that particular device, CR bit or flag is not active. So here it is active. Suppose 1 means active. Here it is active. 1 means active. At the moment, we'll think like that. 1 is active, and here CR mode is 0. So that means now since A, C, and D, they are part of CR, conditional receive. So that means they will go and they can exchange any type of reliable packet. Okay, update, query, whatever. They will do the exchange. But since B is still the CR is not activated for B, that means still A will try to establish the neighbor relationship with the unreliable packet exchange. And once this will be completed, then only now you can think that now you can think like B will also become CR. So for B also CR will become 1. And if all the devices having CR bit flag 1, that means they are eligible to do the reliable packet exchange. So now you can understand this concept of reliability and unreliability. Up to what point EIGRP is using unreliable packet exchange, and then after up to what point EIGRP using the reliable packet exchange. All right, so let's just stop here. Let us learn about EIGRP metric. EIGRP metric formula is a little bit complex, and I'm going to show you that how it look like and how we can do the basic calculation from there. In the next section, we have EIGRP Basics Lab. There also you will find that how you can calculate the EIGRP formula, means from that formula how you can derive the metric value. Okay, so here you can see that EIGRP, inside EIGRP, we know that the metric is there. All the routing protocols, they have the metric. According to that, they are selecting or get selected for the best path. In EIGRP, we have different values such as load, reliability, MTU. You can see internal tag as well. I will show that where it will be used. Apart from that, we have the bandwidth and delay. So 5 values are there, and those values are associated with some constants, some K values as well. Okay. So delay is something, it's a cumulative delay. Next slide, I'll show that how it can get calculated. Bandwidth is used as a minimum bandwidth over the link. Then MTU, basically MTU is not used. So some places you'll find that MTU being used inside EIGRP metric calculation. Some places you'll find that it is not being used. Mainly delay bandwidth is used heavily, but if you want to tune, you can go and use other factors as well, such as reliability and load. Reliability means if the value is 255, that means it's 100% reliable. In case of load, its value is 255, that is 100% load is there, that is not good. So if load is less, that means it's good for the link, it's good for the routes to learn via that path. And then you can see one new item here, that's the internal tag. A tag assigned by the network administrator that is untouched by EIGRP, means that is assigned by network engineer. Here you can see the formula. You have router A, B, and C. And now it's easy to understand when we are talking only in terms of bandwidth and delay. Okay, so bandwidth, you can see the bandwidth here. 3 places you can see bandwidth 1156. And as for the formula, we know that the metric value is 10 to power 7 divided by bandwidth in kbps, and that will be the minimum bandwidth. So suppose 56 kbps, if it is minimum out of 3, so that will be taken, correct? And then we have delay in terms of cumulative delay, in terms of microseconds, correct? So delay, you can see that delay will get added. So here it will be 100, then in this hop the delay is 1100, this hop the delay is 3100. So delay will be 3100, and it is in 10 of minus 3. It's 10 of actually in microseconds, and then it will get multiplied by 256, and whatever value will come, that will be the metric value. Now in the lab section, you'll see the actual mathematical formula, the calculation. I will open the calculator and I'll show you that. Great. So what's the big formula? We don't need to memorize this formula. Here you can see that the metric value, and again with respect to classical metric value. Classical means when we are running the classical EIGRP, we know that we have 2 modes. We have classical, correct, and we have named mode as well. In case of named mode, you'll find that things will be different. The metric, even the metric formula is more complex there. So here, what is happening that K1, the constant K1 and constant K3 become 1. So your bandwidth value, and you'll find your delay value will become 1. But rest of the things like K2, K4, K5 related to load, reliability, MTU, those will become 0. So finally, the formula will come little bit like this: metric equal to 10 power 7 by bandwidth in kbps into plus cumulative delay in terms of microseconds 10 of minus 3 and then into 256. Again, this is a classic metric formula, but when we are using the named based EIGRP, the formula got changed. So here you can see with respect to name based EIGRP, the formula here you have one more constant K6, and that is there related to extended metric. So now here you can see this is a big formula, K into throughput, then K2 into throughput divided by 256 minus load, K3 latency, K6 into extended metrics into K5 divided by K4 plus 11. It's a big formula, correct? But here also, if you go and make the constant as a 0, so suppose if you go and make K2, K4, K5, K6 as 0, so again you are calculating the formula upon bandwidth. Bandwidth is actually the throughput. So you are calculating over throughput and you are calculating over latency. So the final formula will be depending upon the throughput, and again how the name-based EIGRP, they are calculating the throughput. There are measures, methods to check the throughput, like the max throughput or net throughput, etc. So throughput and then the latency. Depending upon that, and here you can see a little bit of description. So the latency derived from the interface delay, throughput derived from the interface bandwidth. See, in the classical, here also in the classical EIGRP also you can see that we have the delay factor, correct? And delay is latency factor here in name based EIGRP metric formula. In classical also you have bandwidth. Here in the name based metric you'll find that throughput is derived from the bandwidth, and then the load over the interface, reliability over the interface, extended metric, that is derived from the router or the configuration. All right, so these are the formula, these are the calculations related to the EIGRP metric. Next section, we are going to perform a lab task. In that lab, we are going to learn about the classical metric formula only. But if you are much more interested about the new metric calculations and formula, you can refer some of the Cisco websites. Let us do the EIGRP configuration. And after that configuration, I will go and verify, first of all, the basic things like how EIGRP having their neighbor table, then their topology table and their routing table. Plus we'll see the various type of packet types that they have. Then we'll go and check the other things that we have studied in the previous section. So let's start. And what I'm going to do, you can see here the diagram. R1 and switch 105. So in between that, you can see the interfaces. I'm going to assign the IP address to all these related interfaces, and plus I'm going to give one loopback address as well, just for verification purpose or testing purpose. So let me quickly go and assign the IP addresses to all these interfaces. So I have assigned the IP addresses to all the interfaces. Let me quickly show you that. We can go and verify once. Show IP interface brief, and I want to include the manual. We'll go and run this to all these devices, 101, 102, 103, 5 and R1, and I should press enter, send the script. So here you can see that over R1 I have this IP address, then switch number 105, I have these IP addresses. Although I haven't pinged and verified that they are reachable or not, but I have assigned the IP addresses over the interfaces and created over the loopback interface as well as per our topology. Okay, so next task I have that I should run EIGRP. So let's go and enable the router. EIGRP, we know that we have to give the autonomous system for that. So let me show you from here, from the global config mode, router EIGRP, and then we can assign the autonomous system. For example, I'm using 10. I'm going to use no auto summary, means I don't want to do the automatic summary. So that's why this no auto summary command. Then I want to advertise the network. Now we know that what type of IP we have, and if you want to check the network, connected network, you can go and then do show IP route or show IP route, so you can get the connected network list. But because I have this network here, so I can go and use, and then we have this option that we can use the wildcard bit. Then I can go and use the other network. Oops. Then I have other network as well, that is this one. And I can go and use the wildcard bit here as well. Then the third and the fourth one. So this is my third network. And then finally the fourth one. The loopback address having /32, the CIDR. So I'll go and use this 00000 as a wildcard bit. We can quickly check the EIGRP configuration. So here you can see that we have these many network. Now I should go and enable this to the other devices as well. So we have done the configuration to 101. Let me go and do to 103. So for 103 the network is, so let's go to 103 router EIGRP 10. We should have the same autonomous system, no auto summary. Then the network, we know that network is this. At the moment I enable or I run this command, you'll see that they will start forming the neighbor table, topology table, and the final is the routing table. So dual algorithm will run here. Here you can see that it is running the dual algorithm, and then we have the routing table as well. All right, so at this point of time, at least I can go and check show IP EIGRP. First of all, the neighbor table. So here you can see that this guy is the neighbor. The uptime is this many second. Rest of the things we don't have much worry. We don't need to worry about this request timeout, the queue count, sequence number, a round trip timer, etc. If you have any issue at that time, you'll see that queue count is increasing, or you have the RTO value is increasing, or uh, a round trip timer is increasing, etc. Okay. So first table will be the neighbor table. Then you can go and check the other stuffs as well. Like I can go and check show IP, EIGRP, topology table. That's the database you have. Now here you can see that you have the successor, feasible distance successors, and then you can see that you have the metric value as well. So here you can see your FT values. Now this calculation, we'll discuss this in upcoming slides, or even now also we can discuss. So I need to open the mathematical calculation and the calculator. So for that we'll go and check what's the bandwidth and how this calculation is coming into the picture. That's 409600. Okay, that's the FT. Again, you can see that P stands for passive, and then you have all the codes. So let me quickly open the calculator and let's do the calculation here. So we know roughly the formula for the metric value is, the metric value is 256 into 7 divided by bandwidth in kbps and plus delay. Roughly, this is the rough calculation. So let's try to understand first of all the bandwidth for the interface. Everywhere we are using Mbps, so my bandwidth is 100 Mbps. Now this 100 Mbps, let's calculate it in kbps. So let's try to do this. Now 10 to the power 7, so 4, 5, 6, 7 divided by 100 Mbps means 100 into 1000, means we have to convert into kbps. So number of zeros will be 0, that is 100, and then 30, so that will become the kbps. So the final value will be 100 and plus delay. So I should go and check the delay over the interface. So for example, show interface E0/0. Now if you go here and you can see the delay, this is in microsecond, this is not in this is 10 to the power minus 6, that's the microsecond we have, and that's okay. So what will be the value for this? 1000 into 10 to the minus 6, correct? Okay, and that's correct format actually. So let's see, let me open the calculator one more time. So that means we should go and add 1000 here, and then if we do 256 281600, I can see the bandwidth in kilobits, that is showing 10 to the power 4 only. And let's go and verify that what is our metric value. That is 281600, that's correct. So yep, let me open the calculator, and here you can see you have the exact 281600, 281600. Yeah, so this is the way that we can do the calculation for the metric. Okay, so what I'm going to do here now, let's just stop here, and this lab we will study some theory, and again I'm going to build, and I'm going to continuously build this lab as well in the upcoming sections as well. In this section, we are going to learn about EIGRP topology table, and in the next section, we'll discuss about the dual algorithm. Now, to understand the EIGRP topology table is a key, because mostly you'll find that EIGRP having issues, and if they have issues, we should understand that how is database construct, how the topology table built is there, because we know that there are 3 stages: neighbor table, so we can go and do the troubleshooting related to neighbor table. Then on basis of neighbor table, we have topology table. That's actually the core local database that we have inside EIGRP. And if we are able to figure out that what is the issue inside the topology table, some of the routes are missing, some of the links are missing, then we can easily figure out, we can easily do the troubleshooting related to EIGRP. Okay, so what this topology table consists of? It consists of all known paths, local learn, and the external routes. That is coming via the redistribution. And once we have the topology table, so topology table will present it for dual algorithm, and after that dual algorithm will run, and then we'll go get the best path. Dual algorithm we are going to discuss in the next section. All right, so we know the steps. We know the steps are neighbor table, then topology table, and then finally we have the best path, that's the routing table. What are the key terms we have inside topology table? How we can go and understand, memorize those key terms that I'm going to explain here. Now, This diagram seems very easy, and we can refer this diagram. For example, if you are going for your Ccnp exams, this is actually key. They may test you upon various key terms and the usability. So you may get terms such as what is reported distance, what is compute distance, what's the feasible distance, what's the successor, feasible successor, etc. There are so many interrelated terms that we should understand. Okay. So now let's understand all these terms one by one. First of all, suppose A is the source, and for A, if the destination is E, so behind E, suppose I have some destination route that want to reach to A, correct? So let's try to understand the common terminologies used inside EIGRP. So first term is the reported distance. Now reported distance, so A has their neighbors, correct? B, C, and D. B, C, and D are the neighbors of A. So that means that whatever routes you have, actually these are the metric, but this is in simplified manner. So whatever the route metric we have, so metrics such as B to E is 10, C to E is 10, and then D to E is 30. So these metric value that is coming from the upstream routers such as B, C, D, they are termed as a reported distance. So 10, 10, 30, they are the reported distance. Clear? So whatever I am learning, whatever metric I am learning from my neighbor, those are reported to me. Those are the reported distance. Okay, straightforward. Now then, what is the compute distance? Compute distance, you can see here the definition. Now these things are linked. So compute distance is reported distance plus the link cost. So you have reported distance 10, 10, and 30, and then the compute distance here, it will be 10 plus 10. Here it will be 15 plus 10. Here it will be 15 plus 30. So that means for three different link, you can see that you have three different links, so three different compute distance. These are the metric compute distance. So now once we understand the reported distance, once we understand the compute distance, understanding of feasible distance is easy. So feasible distance, there is one mathematical formula, feasible distance equal to lower of compute distance. Now you have three compute distances here, such as 20, 25, and 45, correct? Now in these three, we know that 20 is less. So 20 will become the feasible distance. That means that this is, so feasible distance equal to least of the compute distance, and that will become the successor. Correct? So successor, now successor is your primary path that will be installed inside the routing table. But the key here inside EIGRP, that EIGRP, not only they have the successor, but they have the backup path as well. That's the feasible successor as well. Now there is condition. So there is feasible condition for feasible successor. And now the feasible condition is this mathematical formula. So if the reported distance will be less than the feasible distance, remember what is feasible distance? That is equal to list of compute distance. So that means indirectly, if reported distance is less than least of the compute distance, that will become the feasible successor or backup path. Okay, so in this case, you can see that what is the reported distance and what is the feasible. We know that the feasible distance we have is 20, correct? 20 is our feasible distance because 10 plus 10, this is my primary path. Okay, so my feasible distance, my primary path metric value, or my primary path distance or compute distance is 20, correct? Now here you can see that C to E, what is that? That is 10. So that means that 10 is less than 20, and that's why this particular link is the feasible successor. This particular link is the secondary path. Now there may be chances that it will take some time to understand the reported distance, the compute distance, the feasible distance, the feasibility condition, the feasible successor, etc. So you please pause the recording here, go back, watch that 10-minute or maybe 6-7-minute video, come back here. You will understand each and everything I have explained here. And it's very important. Only with this diagram, we can understand each and everything related to topology table inside EIGRP. And this knowledge will be useful in the next section when we'll go and understand the dual algorithm. Okay, active and passive states are very easy. Passive means good. That means it is a stable state. Active means actively I'm looking for a stable routes. Like that we can think. Okay, but the key here is these terms. They should understand these terms. Now, once we understand these terms, then you can go and check inside your lab, inside your output. So you can go and check show EIGRP address family IPv4 topology or show IP EIGRP topology table like that. And then we can go and mark that, okay, so my successor having the feasible distance, then you have the compute distance, and then you have the reported distance. Remember, feasible distance equal to list of compute distance, correct, CD. So that means there is direct proportionate relationship between feasible distance and compute distance. Okay, so that's why you can see that this feasible distance and this compute distance are same, because these are the minimum. And then you have the successor criteria as well. So we know that what is the feasible successor criteria, and you can see in the bottom, the feasible successor should be less than. So here you can see that the condition. So feasible successor condition itself is that RD, reported distance, should be less than the FT, feasible distance. Okay, so now we understand that the use of the topology table. Some other terms are there because topology table is very, very important, and topology table in EIGRP is quite proactive as well. So not only they have the primary path, but they have the secondary path as well. So that means if route will get converged, it will not reconverge the entire protocol, but it will check, oh, I have my backup path with me, I can go and check it. Now, EIGRP, not only that they have the backup path with them, but they have possible successes as well, like possible backups as well. And that's the key as explained here. So you can see here in this output that you have the feasible distance, you have the successor, you have the backup path. That's the feasible successor, correct? But EIGRP having possible successes as well. So that means that in case of outage, that entire EIGRP will not reconverge, because to do the reconvergence, again, all the routers, they will use their processing to compute, to calculate, compute the best path, to calculate, compute the metrics, etc. So it will take some convergence. Not only the convergence is not like it's taking some time, but you know, your resources, they are getting utilized, your memory, process, etc. So to prevent from that, they have not only the feasible successor, the backup path, but they know that who can be their possible successors. Okay, great. And finally, we can go and we can check certain outputs are there. For example, if you are looking for the detailed information about your destination, so you have the command show IP EIGRP topology, this destination. So this destination is learned via 3 different paths, and all these 3 different paths you can see here and their detail. Apart from that, if you have any external routes, you can see if I am learning external route injected in router D, so that external route information also we are getting with the topology command and with the destination external route IP and subnet. Great. So this was the explanation related to the EIGRP topology table. It's very important. Let's stop here. And next section we'll learn about the dual algorithm. In this important section, we are going to understand about behind the scene how this diffusion update algorithm work. We have the topology table. We know this thing that we have the topology table, and on top of topology table, so topology table as an input, then the dual algorithm will work, and how the dual algorithm will give loop-free best path, and how the convergence will be faster in case of EIGRP. So we are going to discuss about all these important points. Now let's try to understand via the diagram. We are going to do quick revision that what we have studied in the previous section. You can see here you have one node, N node, and for N node, different routers they want to reach. So for example, if A want to reach, so what will be the A feasible distance? So from A, obviously this is the successor path. With FD of 1, it can reach to N. Likewise, for B, you can see 1 plus 1. So B, the feasible distance, actually the successor. So this is the successor path. So the feasible distance is 2. For C, again 1 plus 1, you can see the successor via A, and the feasible distance is 2. Now, for D, you will see the dual algorithm will come into the picture. So for D, to reach to N, what are the parameters? Means what EIGRP dual algorithm will provide. The point here with the dual algorithm is this, that it should be loop free. So either you can use path in this way. So this may be path number 1, or this may be path number 2. Either we are going 1, 2, or 2, 1, whatever a successor and feasible successor we have, it should be loop free, because EIGRP dual algorithm, they are maintaining loop free path. Okay, so for example, in this case, suppose B is my successor. So if B is my successor, that means that via C, I have my feasible successor or backup path. Now it up to router number D that from C it got the update, or from B it got the update, means from the neighbor who has sent the update first in case of equal cost, correct? So here you can see that you have the equal cost. Now in case of equal cost, it depends that what is the frequency, how sooner we get the update from my neighbors. So that will become the successor, and other path will become the feasible successor or the backup. Okay, so that's one very important thing. Now let's understand the failure scenario. So suppose this is your primary path and this is your secondary path. Now if the primary link, so a link between A and B will go down. Now since D has primary and secondary, that means D has the successor and feasible successor. So at that time, route computation will not happen. Okay, so routers, they will not do the route computation, the convergence will not happen, the CPU processor of devices will not get utilized. Now it will get utilized, so route computation will occur with respect to dual algorithm and with respect to C. Now think with respect to C. Now if the link between A and C will go down, for D there is no problem, because I have my primary path and I have my successor, I have my primary path, there is no problem. But with respect to C, what happened? For C to reach to N, he loses his primary path and he don't have any feasible successor or backup. So in that case, he will go and send the query to D. He will tell D, I want to form, I want my successor, I want my new path. So the new competition, so dual algorithm will come into the picture. So as per the neighbor exchange, as per the topology exchange, C will figure out how to reach to the N, and this time the route competition will happen. Okay. So clearly you understand which case you have route competition, which case you don't have route competition. Okay, great. Now these terms we have discussed earlier. So with respect to A, who will be the RD? We know that RD, that is coming from your neighbor. So from your neighbor cost B, C, and D, these costs will become your RDs, correct? And in the previous section, I told you that the formula for feasible distance is least of the compute distance. This thing we have discussed earlier. So that means 10 plus 10, you'll find 10 plus 10 is 20, and that will be the least of the compute distance. So here you have the compute distance. Let me go to the next slide. So here you can see that compute distance is 20, here it is 25, here it is 45. So that means that this is your primary path or successor. Now, as per the rule, how we are choosing the backup path or the feasible successor. So we know that formula again. So here you can see you have 10. So that means your FD should be greater than RD. Correct. So in that case, if FD is greater than RD, that will become your feasible successor. But the point here is this, and that's important point here is this, that while choosing the feasible successor, the dual algorithm, they are marking the loop-free feasible successor as well. So what does it mean? It means that you have your primary path, correct? And then you have your secondary path, correct? Now, that's the key here with the dual algorithm. So now you can see that 30. 30 is greater than the FT because FT is 10 plus 10, 20. So now what EIGRP dual algorithm will do, that they will put this particular path, they will mark this as a looped path. They will not mark this as a loop-free path. So they will put some sort of marker there, and that's the algorithm. So the algorithm may mark some loop-free path as possible loop. So it may be, and that's the key here. So it may be loop-free. This may be loop-free path, but dual algorithm this will mark this as a looped path. Okay, and maybe there may be some internal loop or something, so that's why. So it is not out of suspicion that this particular path is loop free. So you have your primary path, loop free, you have your secondary path, loop free. Primary path, we know the formula for primary path is feasible distance is the least of the compute distance, and for the secondary path, the formula is that feasible distance should be greater than reported distance. Now, if feasible distance is less than reported distance, so dual algorithm will mark that particular path as a loop path. Okay, so this is the way that dual algorithm is working. I hope you understood all the points here. In this section, we are going to discuss about EIGRP convergence process, and then we will go and check the stuck in active case. Upcoming section, we are going to follow the path. In case we have a stuck in active, what are the things that we should do? Let's discuss about the convergence process. At this point of time, we know that inside EIGRP, we have primary path, we have backup path. That means we know about the successor, we know about the feasible successor. So suppose if your compute distance, and here you can see that your compute distance, so your FT, feasible distance or your successor distance will be least of the compute distance, correct? So here you can see 10 plus 10, 20. And this 20 is the least. Now this 20 become your primary path. So this is my primary path. And we know that to become feasible successor, your reported distance. So this is the RD. RD should be less than FT. So this is my secondary path. So these things we have discussed earlier. Now what will happen if you have any problem issue with the primary path? So that means if primary path will fail, still we have the backup path inside the topology database, and the convergence will become within milliseconds. So there is no problem with the failover. If the primary will go down, this will come immediately. No problem at all. Now the convergence time will occur. It will happen when your primary and your backup or secondary path all went down. Now at this time point of time, what will happen that A will go and do the query. He will go and do the query to D, and D has to send the reply. So suppose if you have network behind E, suppose you are looking for 1110, that's the A. A is looking for 1110, and both the link you can see this is down, this is down. So he will send query to D, he will ask D, do you know this network? Do you have this particular network I'm looking for? Then D obviously will do the query to their peering devices. Once D will get that information, he will go and send the reply. And we know all these query and reply packages, they have the acknowledgement. But here you can see the problem. The problem here is this: suppose if D don't know how to reach to 110, there the stuck inactive and all those things that we are going to discuss will come into the picture. But suppose if D knows this, he will respond to A, and this process may take some time. Okay, if D knows, obviously you know that query update, he will go and install that uh, table, that route inside the table, and this will become the primary path or the successor. So it will take some time. Let us continue the previous section. Here you can see the diagram. I have router number A, and suppose he is missing one route, 10.10.10.0. Now for that route, he will send the query to B, and suppose if B has, obviously B will respond. If we do not have, then B will forward that query to C, and then if C has, then C will respond, then B will respond, and then A will go and install that route inside the topology table and the routing table. Now, by any chance, suppose if C do not know about that particular route, then what will happen? A will send the query to B, and then B will send the query to C as well, while A is waiting for B respond. And suppose if B is not responding, then after 90 seconds, A is going to send the SIA query. That means, what does it mean? It will tell that the stuck in active bit has been enabled. My route is already active and now it is stuck. See, there are two things. Route may become active. That's quite normal in a network. But if routes, they are becoming or they are getting stuck, that is the problem. Now, if a route becomes stuck, that means there may be issues in a network. And then we have to go and figure out the stuck case. Active is still okay because active means some flapping, some interface issue, something is there. But if it is in a stuck phase, that means need to be get troubleshooted. And there are so many different scenarios, use cases are there for a stuck in active. Maybe some internal bugs as well with Cisco that you have to go and reboot the routers in between the paths. So those things are also there. Okay, great. So what is happening that after 90 seconds or 1.5 minutes, router A will send the stuck in active query to router B. Suppose if B is not responding, then again this particular timer will get reset. And there are certain messages. I think router will send 6 messages until it will go and mark that that particular route is unreachable or it will delete from its active state. Okay, so there are chances that suppose if you are looking for route, if router A is looking for this particular subnet and he is not getting it, that means after a certain period of time, it will mark this as a unreachable and it will remove from its database. Okay, now how we can go and do the troubleshooting for this case. So what we can do, there is one nice command, show IP EIGRP topology active, but this command is useful when you have the issue. Suppose if issue is gone, this command is not that useful. So suppose if you have issue related to active and stuck in active states, you can go and run this command, because this command will clearly tell you that you are looking for this particular route which is active 2110, and then I am querying to my neighbor. You can see 10.11.12, and it's slow to respond. You are waiting for the response from B. Now what B will do, obviously B will go and send this query message to C. So while doing the troubleshooting, you can go and check here, you can go and check at the B, you can go and check at the C, at the D. Everywhere you can go and check show IP EIGRP topology active. correct? Now you are following the path, you'll find that at the C also you can go and check that it is active since, and slow to respond. But suppose if you go and check on the D, and in D you will not find any active route, no messages related to that, then what will happen? Correct. That means that you have issue in between C and D. There may be some other issue, maybe a processing issue, maybe some unreachability issue. There are a lot of issues. So you can go and troubleshoot to this culprit device. That's the router number C, which is not responding. If you go and check show IP EIGRP neighbor, you'll find that queue count is one. But again, this is one of the use case. There may be different issues, and let me go and show you. I have a list of issues. So maybe bad or congested link, maybe query range is too long, maybe excessive redundancy, overload, high CPU, router memory issue, software defects. Sometimes there are some software defects, some bugs are there. So these issues may be there. Okay, so I hope at this point of time you understood about stuck in active, how we can chase stuck in active states, how we can go and try to troubleshoot, figure out this issue, troubleshoot, and get the resolution. All right, so let's stop here. Now we are going to discuss the theory of load balancing, stub areas, and authentication lab will do in the upcoming section that we have already discussed. EIGRP is a protocol that can do unequal cost equal load balancing. So what does it mean? It means that if you have feasible successor, if you have successor and feasible successor, or vice versa, so in that case, one is your primary link, or one is your primary path, one is your backup, but still with help of variance, we can make both as an active link. So that means that we know that successor only get installed in routing table. But if you use the variance command, both the successor and backup successors, or the feasible successor or backup paths, those things will get installed in routing table, and you will get, although you have the unequal path. So for example, you can see these two paths, still you will see that those things will be installed in routing table. So you have the successor and you have the feasible successor, that's your backup, but still if you send 4 packets, 2 will go via this, 2 will go via this. Just an example. The devices, they are not doing packet based load balancing, but it's something called flow based load balancing. So what's the command? Variance. We'll see that how much variance we can use. We can use up to 128. We'll see that in the lab section. Maximum path, by default it will be 4. We'll see that how much maximum path load balance it can do. Maximum it will be 6, but in higher version of operating system it may be more. By default it will be 4. Next topic, we have a stub. Now we have discussed this earlier that suppose if I lose my successor and feasible successor, so at that time I will send the query packet, and query packet will get propagated until unless we get the reply. Suppose if I get the reply within 3 minutes, that's okay. Otherwise this process is known as a stuck inactive. Now to mitigate or to overcome from this, that already I know that network is not after this particular hop or router, I can make that spoke router as a stub. So that means that I am sending a query packet, but you will simply reply no. You don't have your what you are looking for from this direction or from this route or from this gateway. So that the query will get answered that this is the stub. All right, what's the command? We have the command. We should go to the EIGRP process. We can go and run this command EIGRP stub, and then we have 4 options. Receive only, that will not share the update with neighbor. We have connected, static, and summary options. Connected means advertise connected routes. Static means router will only advertise a static route. Summary means router will advertise only summary route. Okay, so these options we have with the stub. Then we have some verification command. We have seen this show IP EIGRP neighbor. Then we have seen show IP EIGRP topology. You can check who is the successor, feasible successor, FT and AD, those values we can check. Show IP EIGRP traffic, already we have seen. Show interface, and you can go and check the interface, what is the delay, what is the bandwidth, reliability, load, etc. Show IP protocols we haven't checked so far, so we'll run this in the lab. Show IP protocol will tell you detail about the protocol. It's a very useful command. It is giving the detail, structure or detailing about that particular protocol. Show IP route, we can check the routing table. Show IP route EIGRP if you want to filter it. And then finally we have some debug commands such as debug EIGRP neighbor, packet route and summary. Remember, do not run this debug command until unless you have the maintenance window. Alright, so what we can do now from this point of time, I can go and log into the lab. We can continue our lab because we have to run, or we have to verify few of the things one by one. Load balancing a stub, and then we have to do the authentication lab. Alright, so we are inside the lab section. So far we have ran that EIGRP 1/101, and let me quickly see that if we have done over 102. 102 we haven't run, so let's go and do that. What is the network we have? We have 3 and 4. So I can go here and router EIGRP 10, no auto summary, network 10.1.4.0, and then the wildcard. Then other network we have 3.0, so I can go and do that. We have 3.0, and then we have network 102, 102, 102, 102, 0000. Okay, so here also I can see that the protocol, EIGRP protocol, is not coming up. Let me quickly go and check the interface. Maybe the IPs assigned are not correct. So we have 4 and 3. That's correct. Let me quickly check where it is connected. So it is connected 0/0 and 1/2 as per the diagram. Here you can see. So it should go to 101, and seems this 0/0 may be passive interface that we have done. So I can go here and you can see the usefulness of passive interface. So I can go and check the configuration first. Router EIGRP 10, I should do no passive interface for E0/0, and let's see. So now here you can see that the protocol is running. Great. From this direction it's okay. Let's quickly check 10/1. So I can go to 105 and I can check here the EIGRP protocol. Do we are running the network command or not? So I can go here and check section EIGRP. We have 10, 1, 2 and 3. Is it correct? So we have 10, 1, 10, 2, 10, 1, 3. That's correct. Let me go and quickly check E 10/1. So run interface E 10/1, and we have wrong IP. So E 10/1 IP address should be 10.1.3.105, and then 255.255.255.0. Alright, so now we can see that it is working correct. Now if I go and check show IP route EIGRP, so here you can see that you have the loopback 1, 3, 5. So we have the loopback 105, 101, 103. All these we are getting. Finally, let's quickly go here to router 1 and check, do we have the configuration for the EIGRP. We don't have, and we have some configuration related to summary as well that I actually don't need. So I can go to 00 and I can remove this command. Let's do router EIGRP 10, no auto summary, network 10.1.1.0, and then we have one loopback. That loopback is 0000. Now if I go to any of this switch, say for example 103 also, I should get all the loopback. So let us continue and perform the lab related to authentication, and then we have the unequal cost equal load balancing, and then we'll see that what is the command for the stub as well. So let's start this. We have the topology. Here you can see I'm going to enable the authentication in between R1 and switch 105. The common interface is E0/0. So how we are going to do, first of all, you need to create the keychain. Say for example, the name is Ccnp in caps, just to refer this is the name. Then key I can give one, and then I can go and give the key string, say Ccnp and then key. Okay, great. Then we have to go to the interface E0/0, and then we have the keyword called IP authentication. I should give the mode as EIGRP 10 and MD5. So we have actually two commands. One is IP authentication, and at the moment I have executed this command, you can see this neighbor relationship is down. Then we have the keychain option, keychain EIGRP, and then the name of the key chain, that is the CCNP. Okay, that's it. So these are the commands we need to run in order to enable the authentication. Now the same copy paste I can do to this side, and you can see this neighbor is down. I can go and create the keychain first. Then I can go to the interface, and then over the interface also we can go and run this command. So let's do this. Over the interface I have these authentication command. We can go and enable this. Now we'll see that the neighbor will converge, and now I have the neighbor relationship with the router 1, that is 10.1.1.1.0. Just now it came back up 10 seconds back. Alright, so this is the way that we can do the authentication. Next we have the variance. So let's try to understand the unequal cost equal load balancing. Now here you can see that I can go and reach via this path to R1, and then I have the other path as well. So let's try to check the loopback that we have here, that is nothing but 1.1.1.1. So how many path we have to reach to 1.1.1.1 from switch 101. If I go to switch number 101, and if we go and check show IP route for 11111, and I should give the network. So 11111, here you can see that I have only one path to reach there via E1/2. And if we go and check show IP EIGRP topology, and then if we go and check 1111/32, so inside topology it is telling that you have 2.105 and 4.102. So here you can see that it can go via 102 this way, and it can go via 105 this way. Obviously the metric value that you can see here, the FT and AD values, those are different, but you have two paths. Now, is it a successor? So we know that who is the successor. Successor is this, because obviously it has lower FT. Here you can see 435200. And if you go and check this output in this manner, just to see that to reach 11111, I have only one successor. Okay, although we have two paths to reach there. So in this case, this will be direct like this via 105. Other one will be via 102 and then 105 and then R1. So what we can do now, I just wanted to add up the value for uh, two different paths. So suppose if I want to decrement this, first of all, let's try to understand, can I do some sort of traffic engineering that traffic will go via this direction rather than directly? Let's try. So that means I have a bandwidth here defined and here defined, and that means that I have to uh, increase the bandwidth at 2 points over switch 101 and then switch 102, correct? Because all the links have equal bandwidth. So if we go and check the bandwidth for 0/0, show interface is 0/0, here you can see that it has bandwidth this. Now I should increase the bandwidth. So 1, 2, 3, 4. What I'll do, I'll go to interface E0/0, bandwidth is, so for example, 5, 1, 2, 3, 4. Now let's see the show IP route for 1111, how it is going. So now you can see that still it is going via 105, that is still it is going directly. Now next what I will do, I'll go to 102 and I'll change the bandwidth of E1/2. So I am here, E1/2, bandwidth is 1, 2, 3, 4. If I go here and check, so what we are doing here, that we are trying to forcing the bandwidth so it will change its metric value, and so we can see that show IP EIGRP topology, that it is going via E1/2 rather than it is going via E0/0. And if we go and check topology for 1111/32, now if you check the composite metric here and composite metric here, still we don't have much change in the composite metric. Obviously the reason here is that you are changing the metric here and you are changing the metric value here. We should change here also, that is E0/0, and the bandwidth is, so we are just forcing the bandwidth. Now if you go and check, and still we can see that it is preferring this way. So IP route. So there is no change while we have changed the metric. For 1111, it is still going via the directly connected path. Okay, still it is going via this direction, although we try to change the calculation because still it may be less than what we are getting from tooling. So for example, 102 you can see what's the metric value here. Now 2048000, and then if you go and check the metric value from here, so if I go and check show IP route to reach to 1111, so switch number 2 to reach to router number 1, here you can see this is the metric, and if you go here, so seems the metrics are very much same. So how these guys are reaching is that they are coming to this this point, and then it is getting advertised to these directions, correct? All right, so here you can see that in this case, if you want to do traffic engineering, it's very difficult to do the traffic engineering. But one thing that we can do here is unequal cost, equal load balancing, correct? So if we have successor and if we have feasible successor, then it will be very easy to do it. Now in this case, I don't have any feasible successor. So IP EIGRP topology. So I can see here that I have only successor. I don't have any feasible successor. If I have feasible successor, then it's easy to do, but still I can go and use the router EIGRP 10 and then the command say we have variance. I'll give the worst case, that is 128. And then if you go and check show IP route, specifically I want to see for uh, one of the route, but here I can see that 105 now have two different having equal cost multipathing, although you can see the metric value is different. So if I go here to the topology, you can see that from uh, switch 101 to reach to 105, and obviously you have one loop back. I have two paths, this path and this path, these two paths. You can see their metric value is different. One is 2300, one is 409, and how we are doing the calculation actually, that's 230 and 409. You have to simply divide it, and you'll find it's almost double. So the difference is of double. So what I'm telling here is that when you are using the EIGRP value, we have given the variance of 128, that's the worst. You can give 3 also. And then if you go and check the route, you'll find that they are doing the unequal cost equal load balancing. And again, if I go and check show IP route, or maybe show IP EIGRP topology for this guy, and should do this with 32. So now here you can see that you have this path that is going via directly to the switch and then loop back, and then it is going via the other switch, and then here you can see the metric value, this and this. The difference is almost double. Okay, so now we can see this, and if I go and check show IP EIGRP topology, so here in the topology you can see that it is 105. So here you can see that you have two successor. So at this point of time it is showing two successor. Obviously if you have successor, then that will be installed in the routing table, because we have done so many changes in the bandwidth also. So that may be one of the reason the metric values get very much balanced. So let me quickly go and revert back the change. So I'll go to 102 and I'll change the bandwidth for E12 and E00. So let's do this. 00 bandwidth is 1234. E1/2 1/2. The bandwidth is, because again if you change the bandwidth you'll go and see the values will get changed. So for 105 now you can see that we have only one successor, although we have used the command called variance. So if I go ahead and check show IP route for 105 there you can see that you have only one path. Okay, so this is the use of the changing the metric value with help of bandwidth. Although we know that we can change with a delay as well, but I'm not showing here. We can change with the bandwidth, and then we can play around with the variance command. Finally, we have one use case related to stub. So suppose in this case, if I got some issue, and if something will happen with my destination network, somehow if I am not able to get my destination network, so what will happen? So in this case, suppose if 105 is the hub, so this guy here is the hub and these are the spokes. So you can go to the spoke and simply you can enable the command called stub. So suppose if this link will go down, for example, just in case of example, and because this is the stub, so the query will not processed, and simply the stub will respond to the hub that, oh, you can't go beyond me, I don't have any network that you're looking for. So in this case what we can go do that we can directly go here and we can go to router EIGRP and we can check the stub command. So if we have EIGRP and stub, now you can see that you have connected, link map, receive only, static, summary. So we can give connected and summary. Now you can see that it reran the algorithm. So now this become the stub, and the theoretical aspect of this we have already discussed. All right, so let's stop here. Let us understand some more terminology and theory for EIGRP, and likewise we are going to continue our lab as well. So the next topic we have related to passive interface, auto-summarization and authentication features. Let's see here in the slides, we'll go step by step. Now first of all, when you're doing the baseline configuration that we have already done, go and enable the EIGRP process with autonomous system, and then we have option to advertise the network. Now we can go and add the wildcard bit as well, so we can get the specific network advertisement. Once we do up to this point of time, obviously we know that the hello packets will start exchange and then they will form the neighbor relationship. First of all, we have the neighbor relationship or neighbor table, then topology table, and then finally the routing table. All these things we are going to see in the upcoming lab as well. Then suppose if you don't want to form the EIGRP neighbor relationship like we have done in OSPF earlier, So then I can go to that particular interface and I can make that interface as a passive interface. A standard format is that you deny all the interfaces like passive interface default, and then selectively you can go and add the interfaces who want to do the EIGRP hello exchange or EIGRP packet exchange. So for that we have the passive interface default, and then we can go and give no passive interface and then the interface name. Now again, we have learned this in OSPF that how we are going to do the summarization. In OSPF, we have summarization, or we can do summarization over area. So we have used that command. I have shown you that how that command work, or how we can use that command, and then we can do the summarization for ASBR as well. So we can do the summarization for ABR and ASBR. Here in EIGRP, this summarization is a bit easy. So first of all, in the previous section, in the lab section, we have used the auto summarization, because if you do not do the auto summarization, so in that case, what will happen that it can be converted to their class boundary. So for example, if you have network 10100/16, if you do not use the auto summarization, like no auto summarization feature, then it will think that his network is 10.0.0/8 because uh, 10 is belonging to class A whose subnet mask is 255.0.0.0. So like that, we need to use this keyword like no auto summary. You have to use this. And then coming to the manual summarization. Now the same thing that we have discussed in case of OSPF, you have to go to the interface and then summary address EIGRP, the autonomous system, and what you want to summarize. So you can do the summarization. I'm going to cover this in the lab section. We'll create some different type of network, and then we'll do the summarization, and then we'll send to the devices. Now when we do the manual summarization, at that time the AD value is 5. We know that the internal AD value is 90, that EIGRP AD value is 90, but for the summarization, our AD value is 5. Now we have one note here that as with auto summarization, the router performing manual summarization will add the summary route to its routing table with the next hop of null interface as 0. So we know that uh, you're doing no auto summary. See, that's the combination. Do the no auto summary. You're not doing the summary automatically, and then you are doing the manual summarization, and that's the reason we have this AD distance as 5. Obviously, that is more than the internal distance. Okay, so do not mix with auto summarization and use this practice no auto summary and then the manual summarization. Then finally in this section we have the authentication. First of all, we have to create the authentication key. So here you can see that key chain. Define the key 1, 2, 3, 4, 5, etc. Then key string, define the password. And then over the interface, we have to go and apply it like IP authentication keychain, autonomous system, and then key. If the authentication or the password will match for both the peer interfaces, then only they will start exchanging the EIGRP hellos. Okay, so these are the topics that I'm going to cover. Let me open the lab section and let me show you whatever we have discussed here and what are the things that we have in the leftover in the previous section as well. As per our lab topology, what we have done that we have enabled EIGRP over 101 and 103. So now if I go here and I can show you this, show IP EIGRP neighbor, show IP EIGRP topology, and show IP EIGRP. Better I do show IP route EIGRP. That's the routing table. So whoever is your feasible successor, that you will see in the routing table as well. So here you can see that what is the network that I am learning here, and that's why it is there. Rest all the network actually is connected. So you can see all are connected routes, and then finally I'm learning one of the loopback, so that's why it is coming inside this routing table. We should check all these things first of all. Then if you want to check the packets, so we have the show IP EIGRP, and here you can see the traffic. Here you can see that what type of packets you have: hellos, update, query, replies, acts, stuck in active. So all those packets we have. With this command we can go and check the packets as well. Okay, and then how we can go and change the metric value, so that we have discussed in the previous section. I can go to EIGRP, and then you have command metric weights, and then you can see that say for example type of service K1, then K2 for example, then K3, K4, K5. So like that we can go and put all these values. I'll not put this value, and I'm showing you that you can go and check these values. Now let me go here and let me show you show IP route EIGRP. So here you can see that you have your AD value, you have your metric value. Now if you go to the interface E0/2 and 0/2 where it is, so we are here, that is going to switch 103, and I have this option that I can go and change the bandwidth. So if I go and change the bandwidth to 5000, and if I check show run interface E0/2, show interface E0/2, here you can see this bandwidth is 5000, and here it is 5000. Now if you go and check the metric value, because we know that the metric value will get changed, so now it become this. Initially it was, so now it is 1 2 3 4 5 6 digit, because initially I think that was 10000, I think 1 and 4 times 0 the bandwidth. Now if I go up and if I can show you the bandwidth that was before change, so 1 2 3 4 5 6 409 600, that is increase, because this increment is bandwidth and metric are inversely proportional. So if this number is increasing, that means the bandwidth is decreasing. What I am telling you, that if you go to interface E0/2 and if you give the bandwidth, say for example 1 move 0, so if this will increase, this will decrease, correct? Do show IP EIGRP, or do show IP route EIGRP. So now you can see that this is decreasing. So if you increase the bandwidth, your metric will decrease, and that will become more and more preferable. All right, so these things are related to the previous section. Whatever things we have studied now, that let's cover that. So first of all, we have a study about the passive interface. If I go here and let me do one thing, I'll enable the EIGRP over these devices as well, 101 and 105. So let me quickly go to 105 and enable the EIGRP. And before that, let me check what is there inside 101, what interfaces we have. So we have 1 2 3 three interfaces, that's correct. And then we'll go here to 105 and we are going to add the interfaces. So we have 10120, 10130 and 1. So 1 2 and 3. All right, so let's do this. Say router EIGRP 10, no auto summary, network 10.1.1.0. Then we have 2 and 3, correct? And then we have one loopback as well. So 2 and then we have 3, and then we have network related to 105, 105, 105, 105, 0000255. All right, so here the network we have. Now since it is not coming up, that means something is wrong related to interface is down or something that we need to check. 10120 E11 and E10/0. So if I go and check to show run interface, say do show run interface E10/0, I can see that the interface is correctly defined. Then I'll go and check to E1/2, E1/1012, and if I go and check to show run or show run section EIGRP, should have a routing for that. So I can see 10120 12.105. Yep. Some issue seems to be related to connectivity or maybe interface that we need to figure out. So here you can see the issue. My interface should have correct IP address. So IP address is 10.1.2.105, and you can see 2.1 and 1.2, how minor mistake that was, but again we should give the correct IPs, and now it is up and running. I can go and check show IP EIGRP topology, or I can go and check show IP route EIGRP because I'm interested in that. So here you can see that it is getting the loopback 103 and it is getting the loopback 101. That's why I've given the loopback addresses. So that means I have the reachability. Now if I go to 101, because he has two neighbor at this point of time, so IPE as ERP neighbor, one of the neighbor I want to make passive interface. So for that, I can go to router EIGRP10, say passive interface default. That means everything is passive. Then we can do no passive interface E, say for example 1/2, and then I can go and do no passive interface for E0/2. So this is the use of passive interface as well. Okay. Now what we can do next, that we have the summarization option as well. So for that I can go to, let me open this diagram. I can go to 103 and I can create some loopback addresses here. So for example 7 or maybe 103, anything. So let me go and create some of the loopback. So I'll go to 103 and I will create few loopbacks, say interface loopback 101, IP address, say for example 2.2.2.1, then interface loopback 102, IP address 2.2.2.2, and then interface loopback 3, or maybe anything, IP address 2.2.2.3, 255.255.255, interface loopback 4, IP address 2.2.2.4. Like that, I can go and create some of the loopback I want to do the summarization for. Then I can go to router EIGRP10. I can do the advertisement, say network 2.2.2.2.0.0.0.7. Do show IP interface brief if you want to check your loopback. So 3, 4, 101, 102, etc. But network is 1, 2, 3, 4. Now if I can go and check these routes here, show IP routes for EIGRP, do I am getting the loopback. So here you can see that we are getting four network. Rather, I want to want one advertisement. So what I can do here, that I can go to the interface. So let me check what interface we have. Brief, we have interface inside 103. So let me show you this diagram here. So we can go to 103 interface 0/0 and we can do the summarization. Okay, so interface is 0/0 IP, and then the summary address EIGRP 10, and then we can do the summarization. So 2.2.2.0, and then we can give the mask, say 255.255.248. All right. Then if I go here to 105, you can see the AD value is 90, 90, 90. 105 is getting this single advertisement, that's okay. And if I go to, I'll cover that. So now you can see that this, once you do the summarization, the EIGRP algorithm will rerun, it resynced, and it has sent the summary. Now if I go to 102, and here if I go and check, oops, we'll wait, and let's see the final command. So what we have, show run section EIGRP, and we have done this summary. Great. So we'll go to the 102, and in 102 also I'll go and verify that what advertisement exactly I'm getting here. So we'll go here and check show IP route EIGRP. Where we are, I should go to 101 as per the diagram. We haven't done any configuration for 102. So show IP route EIGRP, and we are getting this advertisement. And if I go to 103, who is the originator, show IP route EIGRP, it is sending the summary to the null, and then it is getting advertised to all the devices, correct? In this section and upcoming few videos, we are going to learn more about EIGRP troubleshooting, and I have one lab as well. Inside that lab, we'll go and do the troubleshooting related to EIGRP. So here you can see the lab. In this lab, there are two domains, EIGRP and OSPF. You can see the IP schema. So suppose if I have router 1 and if I have router 2, so I have taken the IP subnet like 10.1.router1, router 2 is just the name of the router. So in between 1 and 2 we have 12.0 network. In between 2 and 3 we have 23.0 network. In between 3, 5, router 3 and router 5 we have a network 35.0, and everything will be a start with 10.1. So 10.1.x.x is the network I'm using. Now we will go first of all and see the baseline configuration in this particular lab. So at least the first portion where we have the EIGRP configured. So in this EIGRP with respect to router number 1, 2, 3, and 4, we'll go and verify the configuration related to EIGRP. So I have done baseline configuration related to IP addresses over the interface plus EIGRP routing configuration. Now this router here, router 6, actually it is working as a client network. He is a client, because then we'll go and examine the path, traffic path that will be optimal. So if you suppose at this point of time, if we go and do the redistribution, there are chances that to reach to certain destination, the router, so this client may take some suboptimal path, or it will not go via as per intended, or as the as per the lowest hop count. It may take longer route to reach the destination. We'll see that. There's a troubleshooting that we have to do in the upcoming section. Okay, so to start with, what are the things we want to do? While doing the troubleshooting, first of all, we should have the proper network topology diagram. We should know the network first. Then we should go and do the neighbor adjacency troubleshooting. We should check the best path selection. If it is not doing best path selection, some redistribution issue, some AD issue, we should check that. Then do we have primary backup paths? If it is there, then failover scenarios related to primary and backup, we should know that. And if some features related to EIGRP that is causing issue, we should check all these things. Good to know that we should have good understanding of that particular protocol and the topology, and then we can go and use different type of tools. So what type of tools we have? See, we have the tools, we have the troubleshooting tools, show command, we have log commands, event history, debug commands, and packet capture. These are our tool belt. Correct. So first of all, with the show command, you'll come to know. So there are always some basic show commands like show IP, EIGRP neighbors, interfaces, topology table, routing table. With show command, we should check all these information, because we should be knowing that what exact issue we have in the network. Then you should go and check the log files. We can go and check the event history if required. Now, if we go and enable the debug, that is in T-shape. So if possible, use it with caution, use it with ACLs, filters, and then apply the debug command. Because if you go and apply the debug command, there are chances it will break down the device. And then packet capture. Even packet capture and debug commands, we should use with caution while doing the debugs, while doing the packet capture. Best practice is that always try to use ACL, access control list, associated with these informations, these tools. How we can go and verify? So always use the show command. We have various show commands. We can go and check the log commands. We can go and check the event history command. So some top commands: show IP or IPv6 EIGRP neighbors, EIGRP interfaces, and detail options are there, the events, and then show logging. And then you can go and use the debug, but use it with care. Okay, we can go and check the log. Even we can collect the log somewhere and we can analyze the log. Like that, we can go and collect the logs and then we can analyze the logs. Okay, so let me quickly log into the lab device where we have R1, R2, R3, just to show you that what basic commands we have. Router 1 is actually working as a gateway for router number 6. Here you can see that if I go and check show IP into brief, if we have issue with the client and he's not able to use the specific applications, so that also you can go and check the best path. So is that client using best path to reach the destination, etc. Okay. Show IP. Let me show you the configuration first in router number 1. So I can go and do show run section EIGRP, just to see the EIGRP related commands, and you can see that we are using the default metric here. The command, you can see redistribute connected. If you want to advertise your redistributed network, you can use that. Now here, what I can do, I can show you show IP EIGRP neighbors, just to start with. Then you can go and check show IP EIGRP interfaces. Then you can go and check show IP EIGRP. Oops. Let's see what options we have. So you can go and check always the interface. You can go and check the neighbors, and one of the top command is the topology. And with the topology, and these things we have discussed earlier as well. The topology can go and give certain IP subnet as well, that exactly what topology you are looking for. And active is also one command that we have discussed earlier as well. The topology will give you complete topology table. If you have one router where you have multiple redistributions and all, so there you can get much more view related to the network. Okay, so these are the top commands that you can go and check in the first instance. You can go and check show log. You can see the log. You can go and enable the debugs as well with cautions. And let me go here. So I can go and use debug EIGRP packets. And at the moment you'll go and enable, you will see so many messages will come. Okay. And you can see that not only debug packets, but we can debug transmit as well. All right, so these are the basic command. What we'll do in next section, we'll go and check the trouble tickets related to our lab setting. Now we have trouble ticket related to EIGRP. In this particular trouble ticket, let me explain that what's the issue and what we want to sort out. So we have the topology and we have seen this earlier. In this particular topology, we have one host whose IP address is 10.1.16.100, and we'll go and verify the host IP. Now what is happening here that R4 here wants to reach to this particular IP. Let me draw the path here. So R4, router 4 wants to reach to this IP, but what is happening due to redistribution problem, due to AD issue, administrative distance issue, what is happening that R4 to reach to that destination is taking longer path. It is termed as a suboptimal path. Why? Because EIGRP having external AD value 170 for this particular route, and OSPF having AD value of 110. So what is happening when router number 4 is getting this network? He has two options. He can get this network via a router number 2, is this advertisement, or he can get the network when the EIGRP will go to OSPF, and then OSPF will redistribute and send it to router 4. Due to this AD problem, this particular router is installing the route via OSPF, and that is not the shortest path. That is actually the longest route. Okay, so now we have to go and fix this issue, so that the actual path that router number 4 will take to reach this particular IP or host via the first one, not the second one. So first of all, we'll go and verify this issue, and then we'll go and correct it. Let me quickly go to the lab devices that we have. And here we have the lab. All right. So here in this lab, if you go and check the host IP, that is actually in router number 6. And what I have done, I have made this as a host. That means so routing is disabled on this particular router. He has this particular IP whose gateway is 10.1.16.1. Now, if we go here to router number 4, and if you go and check the route related to that particular route, that is 10.1.16.0, you can see that it is learning with respect to OSPF E2, correct? Learning from the interface that is 45.4, and 45.4 is something here. So let me clean this stuff here, and I can see that 45.4 is there. So he's learning the route in this direction. He should not learn in this direction. He should learn in this direction, via this direction. Great. So let's go and correct this. And meanwhile, I will copy the running configuration and share so you can see the configuration. One important configuration that we should check here is the redistribution. So I want to show you the redistribution configuration over router number 3. because router number 3 and router number 4, they are in both the domains, correct? So you can see here in the back, router number 3 and router number 4, they are belonging to both EIGRP. So you can see EIGRP and OSPF. Although in router number 3, we are going to OSPF and we are redistributing the EIGRP routes, correct? And router number 4, router number 3, we are doing the redistribution, correct? And then it is router number 4 is learning via R5. So if I go here to router number 4 and if you go check the configuration, you'll find here I'm not doing any redistribution, but we know that we can do the mutual two-way redistribution in case we need high availability. So if one link will go down, one side will go down, still it can learn the routes from other side as well. Okay, so one solution here is this, that we can go and shut down this particular link, correct? This link is what? This is on router number 4, gig is 0/2. So if I am here in router number 4 and I can go and shut down interface gig is 0/2 is the interface actually. And let's shut down this interface. And now if you go and check the route, do show IP route. If you do, you will see that now it will start learning the route with respect to EIGRP. But you can see the AD value. The AD value now he is learning is 170. That is way more than OSPF 110. And thus that's the reason that you can see that he is learning that if you go and do shut down the interface, that is not a good solution because you are shutting down one of the interface, correct? So what we can do here, we can do the no shut. Let's revert back the network and let's check the route again. You will see now it will again start learning from OSPF. That is not the optimal path. So what we can do here, that we can go to router EIGRP1. Remember, one very important thing here is this, that administrative distance, they are locally significant. Okay, so now here we can go and we can use the distance command, and then you can give the internal AD distance, that's 90, and then external, instead of 170, I can go and give less than 110. So I can go and give anything less than 110, maybe 109 will also work fine. Enter. Now once we do this, and if you go and check show IP route, you'll see that it will again start learning with respect to EIGRP. So here you can see that EIGRP got flapped. See, reconvergence is happening, and now it formed the new neighbor relationship. And now if you go and check the routing, you can see that he is learning the route in the correct path with a lower AD, lower than 110. So you can see clearly this 99. So now the route is learning via the correct path in this direction. So this is the troubleshooting, and in a bigger network, there may be chances to troubleshoot this. You have to find out the issue, so it will take much longer time to find out the issue, and then you need some change approval to do the configuration related change. Okay, so it may take good amount of time while you are doing troubleshooting in the production network. All right, so let's stop here. In section 1.10, we have to understand about OSPF and OSPF related troubleshooting tickets. What I have done, first of all, I have covered the theory related to OSPF plus the lab. So the idea here is this, that you please complete the OSPF related theories and OSPF related labs, not only OSPF version 2, but OSPF version 3 as well. So you will find videos related to OSPF version 2, and let me mark. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 videos related to OSPF version 2. And then I have added OSPF version 3, that is IPv6 version of OSPF. So 2 videos related to that. Please complete these videos. Once you complete, then the OSPF troubleshooting videos will start. So please complete up to here, and then you will find troubleshooting related videos. Let's start with OSPF. Now OSPF, that is Open Shortest Path First Protocol, is a link state protocol like ISIS. Now what link state protocol is doing, that instead of sending the entire topology table hop by hop, they are sending the state of a link to the neighbor device. Now how this technology is working, and let me try to draw here. So generally all the link state protocol, they are forming first of all the neighbor table. So they are sending the update to all the adjacent device or the neighbor. With help of neighbor table, they are forming the topology table. Sometimes we are referring this as a entire database as well. And finally, they ran the SPF algorithm here. From the topology table, they are going to form the best path, that is the routing table. So we have three different types of table: neighbor table or database table, topology table, and then finally the routing table. Now the mechanism behind this and the theory behind this we'll see in upcoming slides. So OSPF is entirely dependent upon areas. Generally, we are telling that we have one backbone area. So here you can see that you have area 0, and logically all the areas are connected with area 0. Now these areas are 32-bit. They can be a flat number, or you can define like in dotted representation 000 like this. Areas has continuous means area. You can see that you have area 0 and then area 1, 2, 3. So maybe you can think that can't I connect area 3 with area 5 or 4? Yes, we can do that connection, but you can see that area 4 is not directly connected with area 0. So somehow I have to create tunnel, or the area 3. Uh, I have to create area 3 as a tunnel, or we have to use some sort of virtual link. So area 4 can think that is directly connected with area 0. So such type of arrangement we need to do, and then the link state advertisement will flow from one place to other place. That's the LSA, correct? Now OSPF send LSA when there is a change to one of its link, and will only send the changes in the update. LSAs are additionally refreshed by after every 30 minutes. So how we can summarize it, that OSPF is a link state protocol dependent upon area. They are sending their LSAs or their advertisement to all their neighbors, and with that they are forming the neighbor table, topology table, and finally the routing table. Apart from that, that OSPF traffic is multicast. They are using 224005 for all the routers and 224006 for the designated router. The theory behind this we can discuss in upcoming session. They are using the Dijkstra shortest path first algorithm to build the routing table from the topology table, and they are supporting the variable length subnet mask. So here you can see that first of all they form the neighbor table, then they form the database, then they do their algorithm, that's the SPF algorithm, Dijkstra's SPF algorithm. Finally, they will form the best path table, that is the routing table. OSPF supports IP routing. Their AD value is 110. Their metric is cost. They are going to form the neighbor table, topology table, and routing table. Uh, all the areas should be supposed to be connected with a backbone. That's the area 0. If we have non-backbone area connected with any other area, then you have to create tunnel or virtual link in between that. Now, suppose we have such type of topology here. You can see that I have area 0 connected with area 1 and area 2. So now what we are going to tell about these devices, these routers, router A and C, they are termed as a ABR, area border router. They are termed as a ABR, area border router, because they are in the border of different areas. Okay, and we'll see that according to that the routes are also going to get reflected. So when we are talking about the routes, you'll find that you have O routes and then OIA, that is OSPF intra area. So you have two type of route, OSPF intra area route, that is this. Then you have inter area, across the area, that is this, and we'll see that we have E1 and E2 routes as well, that is coming from the external as well. Now if you see this diagram, it's actually very simple, straightforward, but that we have two or three routers in area. But assume that if you have 50 or 100 routers in area, and suppose if I have 200 routers and all the 200 routers are inside area 0. So at that time, what will happen? The computation, means to run that SPF algorithm, becomes CPU intensive, rather than if you have a small areas and then you have 50 device, 100 device and 50 device in those areas. So in that case, all the areas, they will run their independent SPF algorithm, and then they will send the update to the backbone. So in that case, the way that we are going to run the SPF algorithm, or in other words, the process, the CPU utilization, the memory, will be optimized and will be used betterly, because now you are running the SPF algorithm across small areas, and then those areas are going to send their LSAs to the core or to the other areas. Correct? So that's the thing, and that when we are that's why we don't have only area 0, rather than we have multiple logical areas, and then we are going to divide the devices or the routers inside the area. Then here you can see that, suppose in case that if you have device and that is not connected with the area 0, so in that case you have to create the virtual link, the device which is separating the area, they are termed as a ABR. Then you have internal router, then you have backbone router. Again, these are just the terminologies. All right, now here you can see that you may have chance that you are connected with non-OSPF protocol. So you are getting the route, say for example, from the EIGRP domain. So in that case, that router is termed as a ASBR, Autonomous System Border Router. So now here you can see that C and D, they are ABR, Area Border Router, but router G is ASBR, because now the routes is coming from the other routing domain to the OSPF. Okay, so uh, here you can see that if we have any other routing domain, that will term as a separate autonomous system, and then you have to do the redistribution. Obviously the router G will do the redistribution from EIGRP to OSPF when it is coming to OSPF, and OSPF to EIGRP when you are sending your update to the EIGRP domain. Now in that case, we have E1 and E2 type of area. Now what is E1 and E2? Here you can see by default it will be OSPF external area type 2, that is the E2. So include only the external cost to the destination network. External cost is the metric, being metric is cost advertised from outside the OSPF domain. This is the default type. Then you have E1, that will also have the metric value, that is the cost, but this will be additive, means it will add the cost per hop per router. So include both the external cost and the internal cost. So that's why you have the external cost plus the internal cost to reach uh, the ASBR to determine the total metric. But E2 having only the external cost, that will be constant. So in summary, here you can see that you have internal routers, that all router interfaces belong to only one area. You have ABR, you have ASBR, you have backbone router that is inside area 0. Okay, so this is the baseline summary for the OSPF routing protocol. In the upcoming sessions, we will learn more about OSPF terminologies, and we have to perform the lab as well. So what type of LSAs we have in OSPF? OSPF has a long list of LSAs. We are going to discuss the top 5 at least, because these we are going to use more and more in the course. So we have LSA, here you can see type 1 and type 2. Now these type 1 and type 2 LSAs are reside within the area. They are very much area specific LSA. Then we have type 3 and type 4 generated by ABR, area border router. They can flow from one area to other area. We'll see in the upcoming slide. And then we have type 5 LSA that is generated by autonomous system border router, means non-OSPF protocol. They are going to generate that. Now here you can see the detailed explanation of all the LSA. Type 1 is LSA and type 2 as well. They are within the area. The use of type 1 LSA is that they have the link, obviously the status and the cost of all those links, and they are generated by all the routers in a network. So you can think that type 1 as a default LSA generated by all the routers within that area. Then we have type 2 LSA generated by DR in the OSPF network or OSPF domain. Again, this is also specific to the area. When we have the broadcast type of network, obviously at that time the DRBDR will come into the picture. Then we have the network summary LSA, that is type 3. What it is doing, that generated by ABR, and this can be used for inter-area communication. We'll see that all the places you have this inter-area link. So you have area 0 connected by different areas, and all these ABR shown in the diagram, they are going to generate type 3 LSA to do this inter area communication. Then we have ASVR summary. Now the next question here is, suppose from OSPF inter area you have to reach to non-OSPF domain. So for that reason we have autonomous system border router summary LSA, means somehow you need to reach, or somehow you have a route to reach to the non-OSPF protocol. Then we have external LSA type 5. Now this is generated by the ASBR, and this information will be flooded inside all the areas. So all the areas, if obviously you have the redistribution, all the areas should know how to reach to the autonomous system border router or the network behind the ASBR. We have type 6 as well, that is the multicast OSPF, type 7 as well, that is not so stubby area. And this type 7 is actually very important, and we'll discuss this later on. Now here in the diagram you can see that you have area 1, area 0, area 2. So belonging to area 1, area 2 and area 0, you have this router and network LSA, means type 1 and type 2 LSA will be generated in that. Then you can see that router C and D, they are ABR, so they are going to generate the type 3 and type 4, and the router G is belonging to ASBR, he is going to generate type 5 LSA. Okay, great. Then how this OSPF is going to form the OSPF neighbor relationship. So if you go and connect two OSPF or two routers in between, so suppose for sake of simplicity I have only two routers connected in a network. So in that case what will happen, suppose I have router 1 and router 2, and these two routers are connected, or they are inside area 0. So obviously these routers, because they are within the area, and suppose if it is a point-to-point network, then they will send and receive the router LSA. correct? So what will happen that they are going to send their hello packet in the point-to-point network or in the broadcast network. This hello timer is 10 second and dead timer is uh, 40 seconds, so it's 1 into 4. And in the broadcast network, actually, in the NBMA network, that will be 30 second, and then the dead timer will be 30 into 4, that is 120 second. So they will send and receive, they will exchange their hello packets, and if they are matching certain criteria while sending and receiving the hello packets, then they are going to form the neighbor relationship. So here you can see that what are the things inside the hello packet, what are the fields inside the hello packet. They contains area ID, area type, prefix, subnet mask, hello interval, dead interval, network type, and authentication. Basically it is termed as that they have 8 field inside hello packet, and you should match at least the area ID, the subnet mask, hello and dead interval, authentication, etc. So some fields are mandatory that should match in between two routers to form the neighbor relationship. Okay, so here you can see that a neighbor table is constructed from OSPF hello packet, which includes the following: the router ID, the current state, directly connected interfaces, and the IP address of the remote interface of each neighbor. We'll see that in the lab section, and we'll go and we'll run the command show IP OSPF neighbor, and then we can see the specific about the neighbors. Now the next topic here is that OSPF designated router and backup designated router. So what is happening and how they are going to form the DR BDR, or how they are doing the selection for the DR BDR. Let's discuss about that. So here you can see in the diagram, first of all, these devices, they should have their priorities. So let me show you what I try to tell here. I should have slide for that. Yeah. So here you can see that these devices, they have their unique identification. That's the router ID. All the routers in a network, they have the router ID. We can configure it manually, or suppose if device has the loopback interface or they have the physical interfaces, first of all they will check the loopback interface if you are not doing it manually. So that loopback interface will become the router ID, or the highest physical interface will become the router ID. So they should have the router ID. That will be by default if you are not doing it manually. Once they have router ID, then they are going to do the DR-BDR selection, and this selection will happen only in the broadcast network. So here you can see in the diagram that if we have router ABCD connected with a shared network or the broadcast network, so at that time they will go and select the DR and BDR. Okay. Now, what will be the selection criteria here? The DR-BDR selection are determined by the router's priority, which is configured per interface basis. The router with the highest priority becomes the DR, and the second highest will become the BDR, and the rest are DR to other, something like DR, BDR, others. Okay. Now, if there is a tie in the priority, whichever router has highest router ID, that will become the DR. Now we can go and set this priority like this also, like we can go to the interface and we can set IP OSPF priority, and then we can force to make certain device as a DR or BDR. Now by default the priority will be 1, so obviously the selection will happen with respect to router ID. So whoever having the highest router ID in the network, that will become DR, BDR, etc. like that, in that manner. Suppose if you don't want that certain routers or device will take part inside the DR, BDR selection, so you can go to the interface and you can set the priority as a 0. So if you set the priority as a 0, that device will not take part inside the DR, BDR. Okay. So what are the important things we have studied in this video? That type of LSA, then how they are going to form the OSPF neighbor relationship, what are the important fields you have inside the hello packet, all the devices they are sending the hello packets to the peer devices or the neighbor devices to form the neighbor relationship, then how they are going to form the DR/BDR selection. Again, the router ID will be important factor here, and as per the router ID, they are going to form the DR/BDR because by default we are not setting the priority. By default, the priority will be 1, and according to the router ID, they will select who is the DR, who is the BDR. Let us learn more about OSPF neighbor state, and then I'm going to perform a small lab task where we'll understand more about the OSPF process, OSPF actually neighbor process, and even the baseline commands of OSPF as well. So now when the OSPF, the first stage is that they have to form the neighbor relationship. When they are forming the neighbor relationship, at that time they are exchanging or they are going through a process or they are going through multiple steps. So what are those states we have? Here you can see that they will start with a down, init, two-way, etc. So in down state indicates that no hellos has been exchanged, but the actual process will start from the init state. Init state, the devices they will start sending their hello packets. We know that inside hello packet we have some important fields. Few of them are mandatory, like the area, like the authentication, uh, the network subnet, etc. So few of the fields are mandatory that two sides or the neighbors they should match those mandatory things. Then they will go to the two-way state. By the end of two-way state, uh, the devices, if they are in the broadcast network, they have to select the DR and the BDR. And by the end of two-way state, the devices they are forming the neighbor relationship. Okay, then we have the external start and external exchange. Now external start and exchange is a state where the devices they have to select that who is the master and who is the slave so they can exchange their databases. So obviously the devices they are sending their link state or LS information to each other to build the database. Once they have the database as per the uh, master and slave entry, as per the master and slave role, they have to exchange their LS type. Correct. So someone may sending say link state advertisement. Someone may asking link state request. So LSA, LSR. Those things are going in depth when we are talking about the exchange state. Then we have loading where all the devices they have to sync their database, and by the end of this loading state, the OSPF process they are forming the topology table. Remember, we have three important table. We have neighbor table. So by the end of two-way state, they will form the neighbor table. We have topology table. By the end of loading, the devices will form the topology table, and finally once they have the topology table, on top of that the devices will run the SPF algorithm, shortest path first algorithm, and then they have to form the routing table. We'll see that if we have the broadcast network, then they will have the rules like DR, BDR, and DR other. All right, so here you can see that suppose in broadcast network, if we have these roles, this DR other, they will go and stop at the level of two-way, because what is happening in that situation, in that case, is that we are giving the authority to DR and BDR to exchange all the LSs with all the other. Rather than all the other, DR others, they are exchanging their database packets. So that means they will stuck at the two-way state, means all the DR others, they will stuck at the two-way state. They will not have the full authority to exchange the databases. correct? All right, so we have a small lab topology. In this first lab, just to start with, what we are going to do that we will go and initiate the OSPF process. So let me show you this. Although we have this master lab topology, what we can do as per our requirement will go and use it. So what does it mean that we'll go and make these devices, say for example R1, R2 and switch 101 within area 0 at the moment. So they will be the part of area 0, and this switch that you are seeing here, switch 105, that I will make as a switch only. Later on we will make this as a L3, but at this point of time I assume that I have R1, R2 and switch 101, and the IP that I am going to use, the IP will be, say, let me write here the IPs, and according to that I am going to configure the lab. So the IPs that I want to use is, say for example 10.1.1.1 and 10.1.1.2 as per the name of the devices, and here, so for example 10.1.1.101. They are inside the same broadcast network, so you can see that they will go and form the DR and PDR. Loopback addresses I will give like 111, and then this I can give 2222 as the name of the device, and this I will give as 101, 101, 101, 101. Okay, we are going to initiate the OSPF process inside area 0, and then we'll see that how they're going to exchange all those hello packets and the important ls type. All right, so let me go and log into the lab devices. All right, I logged in, and we know that we have other interfaces and links also connected that I don't want. So this is the topology that we have. What I can do here, that I will start with 101 E1/2. So let's do that. I can go to, first of all, let's see this neighbor, and I want to shut down few of the interfaces that I don't want to use. So for example, I want to use only interface 1/2, so 0001 and 1/2. So 0001, so I can do one thing, interface range E0/2 to 3, shut down, interface E1/0, shut down, because I want to use 1/2 only. So rest of the interfaces I'm making shut down. Like that, 1 also I want to make shut down. Now if I go and check show CDP neighbor, so I have 0001 and 12 that I want to use. Now next I will go to switch number 2. So switch 2 is not required in this particular lab, so leave it. Then I'll go to switch number 5, and we should check this E1/2 configuration as well. So I will go here and check E1/2, and what is configured here, nothing is configured. If nothing is configured at this point of time, at least what we can do is we can make this interface as a switch port, correct? So here you can see this capabilities R, S and I, and that I don't want. I'll make this as a switch port. Then we'll go back to the switch number 5. Here you can see, and the interfaces we have is 0, 0, 1, 2, 3 and 10/0. So apart from that, what I want, that I want to make other interfaces as a shutdown, and we have so many interfaces here you can see. Even we can leave it as well, just to check the configuration for any of the interfaces. Say so run interface E0/0 that is connected with router number 1 and then router 2. So these are the interfaces connected. I don't want to do anything. Rather, I will do one thing, that interface range E0/0 up to, for example, 4 maybe, and 3. I'll make this as a switch port and no shutdown. And then interface E10/0 that is connected with switch number 1. That if you see here, switch number 1, what interface we have here, let me scroll up, 10/0. Yeah, so I can go here, interface E10/0. I'll make this also as a switch port, no shutdown. Alright, so we are very much good with switch number 1 and switch number 2. Here again I can go to interface E1/2. I'll make this as a switch port, no shut. Alright, so let me quickly see here that what I exactly required. So E1/2 should not be switch port. It should be a routed port. So I'll do no switch port and then I'll assign the IP address. So for example 10.1.1.101, and then I'll create one loopback, say loopback 0, IP address 101 and 101.101. So what I have done here, we can check show IP interface brief. So I have interface E1/2 and one of the loopback interface where I have assigned the IP addresses. Okay. All right. Great. So now we can go to R1 and R2 and the interfaces you can see here. So I'll go to R1 first and I can go to interface E0/0. I'll assign IP 10.1.1.1 and then I can do ping just to check that the far end switch is reachable or not. So it is reachable, then I'll go and create one loopback, say 0, and IP address I'll give 111 to that loopback. We'll go and check the show IP interface brief, so you can see that we have the IP configured here. Now let's go to R2 and inside R2 we have interface E0/0. I can go and give the IP like this and then I'll create one loopback 0 where I can give IP related to as per the diagram or as per our schema 22222, and then let me try to ping. First of all, within the same network, obviously everything is inside the same network for this example. So what I'm doing, that I'm pinging to all the devices from R2. So now we have the baseline IP at this connectivity connected. The thing here is that we are going to enable the OSPF to all these devices and we are assuming that all these devices are inside area 0, correct? So let's do this and let me go back to the lab. Yep. So before doing that, at least one of the device I want to enable the debug. So I want to enable the debug OSPF packets and events. Debug IP OSPF packets, and then I want to enable the events as well. Okay, let's do this OSPF configuration. So we can go to router OSPF and then you have to define the process ID, say 1, I am giving at this point of time. Then I should go and advertise the network. So network is, I have two network, one is 10.1.1.0. I can go and give the wildcard bit inside area 0. So this is the format that we can go and enable the OSPF. And at the moment I enable that, you can see that we have event because we have enabled the debug as well. You can see that this router using this multicast address and the router ID is get selected as 11111. We have discussed this earlier. If I go and check show IP OSPF, you can see the read router ID is 11111 and we have the other information as well. Okay, so we have the OSPF configuration and periodically he is sending the hello packet. We can go and check the configuration for that, what we have done. So we have enabled the OSPF process and then we have advertised the network, correct? So likewise, I can go here and initiate the OSPF process here as well. Then I can go and I can assign the router ID via the CLI command as well, means manually as well. But if you do not do this, automatically they will take this loopback, highest loopback address as a router ID. So then I have network 10.1.1.0.0.0.0.255 area 0, and then I have network 2222, say 0.0.0 area 0. Alright, and let me see that what configuration I have done here. Now they try to exchange this neighbor relationship. From there they will go and form the topology table, and finally they will go and form the routing table as well. Okay, so let me quickly see that what command I have given here for the network. Because we have used /32, that's why I have given 0.0.0.0.0. Now somewhere you will find that you are moving to loading to full state, and here if we can see that information in the log message. So we have enabled the debug and OSPF authentication is 0. We haven't put any authentication, so it is telling that OSPF authentication is 0. And here you can see that we have this loading to full message. If you go and check show IP OSPF neighbor, then you can see that you have DR BDR selection already happened. For router 1, he is telling that router 2 is BDR. Now if you go to router 2 and if you check show IP OSPF neighbor, you can see that he will tell who is the DR. So for router 2, this 11111 is the DR, what is the interface, what is the IP address that we have discussed earlier. Now I'll go to switch number 1, and here also I'll go and do this router OSPF say 1, and then I will put the network, for example the loopback address that we have 101.101.101.0.0.0.0 area 0, and then I'll put the network that we want to form the OSPF relationship. So we have a network and with the wildcard bit 0.0.0.0.255. Alright, and within area 0. At the moment I'll do this, I can go and check show IP OSPF neighbor. Now you can see that he is seeing that who is the DR and who is the BDR, correct? The third device. Now if you go here and check the OSPF neighbor, you can see clearly that DR other. So now this IP is DR other. We haven't assigned the router ID manually, but here you can see that they can detect it. Means the router process can go and assign what will be the router IP or router ID for these devices. We can go and check like this, show IP OSPF, and you can see the ID. Now if you want to filter and use that I try to do with this command, simply you can go and check the ID. That will tell you who is the router ID. Alright, so this is the way that they are going to form the DR and BDR. And if I have one more device in the DR other, then you could find that the process will stuck as two-way state. Okay, so what I'm telling here is that if I am here and if I have one more device connected to this guy here, and that is also working as a DR other, then these two devices, they will stuck as a two-way state. They will not exchange the entire topology and database table set, etc. All right, so let's stop here. So let's quickly understand the network type, Ospf metric, and the usefulness of passive interface. Now Ospf is supporting a wide variety of network type. Here you can see that in Ospf you have these many network type support. Now how to memorize this, because you can see it's a big number, this network type. So you can think like this, that you have point to point and you have, see here, so point to point, and then you have point to point, point to multi-point, broadcast and non-broadcast, like you can think. So you have network type broadcast, and then you have network type non-broadcast, and then again if we add with point to point and point to multi-point. So now point to point, obviously we know that point to point is just point to point network, two devices are connecting with each other, it's a point to point network. Then what about point to multi-point? So here you can see that point to multi-point non-broadcast. So you can think that you have point to multi-point broadcast and non-broadcast. Okay, so that means you have 1, then 2 and 3. Apart from that, you have network type broadcast. So you have network type broadcast and you have network type non-broadcast. That means you have total 5 different type of network support. Now again, if you go and check the nature of the broadcast and non-broadcast, so if it is a broadcast, that means the DR-BDR selection will happen and the neighbor will form automatically, means you don't have to write the manual command to form the neighbor relationship, correct? But if it is a non-broadcast, and suppose if DR-BDR is forming, you can see that the hello is unicast multicast. When you're seeing unicast, means you have to go and use the neighbor command. So you have to manually form the neighbor, correct? So once we know about the broadcast and non-broadcast, and again you can see the timer as well. For broadcast network is 10 and 40, and for non-broadcast is 30 and 120 seconds, correct? Now same concept we can use here. So here you can see that point to multi-point, you can think this is a point to multi-point broadcast, so that's why it's a multicast. Hello, they will not form the DR-BDR because again it's point to point, and you have so many points to point to multi-point, you can think like this. So whenever you have point to point network, you are not going to form the DR-BDR because just two devices, why you will form DR-BDR. Then I get point to multi-point non-broadcast. Now this is non-broadcast, so that's why you have to go and use the neighbor command to form the OSPF neighbor relationship. That's the whole summary we have for the OSPF network type. So let me go back to the theory. Now here you can see that it's a broadcast, so it will do DR-BDR selection, then it is using these multicast addresses. Because this is the broadcast, they will not form the neighborship manually, automatically they will form. Point to point, no need to define the neighbors because you have only two ends. They will form the neighbor relationship. Their timers will be 10 and 40 seconds. They are going to use the multicast address. But again, point to multi-point as well. Everything that is valid here for point to point, it will be valid for point to multi-point as well. Okay. Now, then we have non-broadcast. Whenever we are talking about non-broadcast, then you have to go and form the neighbor relationship manually. Now, OSPF will elect DR and BDR, but neighbor relationship will be manual. And that's why we have this summary. This summary, it's easy to memorize. Even no need to recall, but just will make a point that okay, you have point to point, point to multi-point, point to multi-point, non-broadcast, point to multi-point broadcast, and then you have broadcast and non-broadcast network. How we are going to do the configuration? Configuration part is actually very easy. Only one command is there to define the network. You have to go to the interface. Suppose you are over this serial interface, you go to the interface and use this command IP OSPF network. Suppose if you go and type question mark, then you'll get all the options. So is it a broadcast? Is it a non-broadcast? It's a point to point, point to a multi-point, etc. Each and all these options you will get. And if it is using unicast method, means if it is a non-broadcast, then you have to go and define the neighbor. Otherwise, rest of the configurations are standard OSPF configuration. So for example, NBMA, non-broadcast multi-access. So here we are going and defining the network type is a point to multi-point, and if it is a non-broadcast, then you have to go and define the neighbor, right? So just refer this summary and things will become easier. Now OSPF is using cost as a metric. Here you can see the speed and the cost. So for example, for fast Ethernet and EPUB, your cost will be 1, and then you can see for token ring for Ethernet, for token ring 4 Mbps, you can see the cost. Now the lower is better. So if lowest cost is there, that will be the preferred path in the route selection. How we are going to do the basic OSPF configuration, although we have done one lab, so there you have seen that you can go and initiate the OSPF process. You can define the router ID, otherwise it will take the highest loopback or highest physical interface if it is not configured. Then you can define the area, and that's it. So this is the baseline configuration. Now here interesting thing is that we are defining the wildcard bit. And now it is recommended that if you know the exact subnet, so according to that you can use the exact wildcard as well. So suppose if I am using point-to-point network, so I can use, say for example, 172.168.1.0. So here it's 17. So 172.171.0, and then I can use wildcard 0.0.0.3. So like that we can go and use the wildcard wisely. What will happen if we go and initiate the OSPF process, and once we start advertising the network, or once we put this network command, then they will send the hello packet, the neighbor relationship will start working. We know that as steps down, init, two-way, X start, exchange, loading to full. First they will form the neighbor table, then topology table, and finally they will run the SPF algorithm and we'll get the final OSPF routing table. Correct. Now the final thing here in this recording, as was the theory, the passive interface, the concept of passive interface. Now suppose if you don't want to form OSPF relationship, then you can go and make any of these interface as a passive interface. So suppose if I make this interface as a passive, then you can see that the passive means the command prevents update from being sent out or received from this interface. So if I go here in this example, it is showing this interface. So if you go and make this particular interface as a passive or any interface as a passive, they will not participate in OSPF neighbor relationship. Means they will not send or receive the updates, and that's the usefulness of passive interface. But generally how we are using this command is we will do this thing: no passive interface E0. Here you can see first of all we'll make all the interface as a passive. So the command one is passive interface default. Suppose if you have 10 interface, that means all the 10 interface you're not sending and receiving the updates, and then you will go and add the interfaces one by one where you want to send or receive the updates. Okay, we have one important note here that the passive interface command will prevent OSPF and EIGRP from forming neighbor relationship out of that interface. No routing updates are passed in either direction. So this passive interface is true not only for OSPF, but this is true for EIGRP as well. So we are going to stop here, and in next section I will show you a few of the things that we have a study here, like network type, how you can go and change the network type and you can enable the passive interface. Let us do the lab. Here you can see the topology. We have router 1, router 3 and switch 101. I'm using in between switch 105 as a L2 switch. So that means I have area 0. So this big blue circle is area 0 and the network is 10.1.1.0/24. Then I have switch 101 and 102 connected. That is inside area 2020, and the network is 10.1.102.0. So 101 is dot 1 and 102 is dot 2. I have already assigned the IP address. So what we'll do, we'll go and enable the OSPF process. Then we'll go and check the default network type, and then I will make any of the interface as passive interface inside area 0, and then again we'll verify the OSPF neighbor relationship. So let's do this. I can go to router OSPF 1, and even if we are here, we have option that we can run the script as well. So if you are doing the configuration over empty putty, you have this option for a script, say conft router OSPF 1, and then you can advertise the network as well. I can select the devices and then I can send the script. Now once OSPF is configured, then I should go and assign the, or I should advertise the network, or should I can use the network command. So what you can do here, you can go and check the IP route, your connected interface, and in the network command, actually, you can go and use it with wildcard bit, and we should check this 10.1.1.0 is part of area 0. So we know as per our topology this is correct. Then we have one loopback here that will be depend that in which area you want to put. This also I'll put inside area 0. And then I have one more network that is this guy here connected with area 20, area 20. So these are my network command. Likewise, I can go to switch number 2 and I can go and check the connected routes. I can use my network command. First of all, I'll advertise my loopback inside area 20. And then I have my network that is connected, that is inside area 20, because the bottom switch is actually Everything is inside area 20. So that's why area 20, area 20. All right. So at the moment we run this command, you'll find that both the switches, they are now interfaces are part of area 20, and they will run the Ospf, and here you can see that the Ospf loading to full means all the states are completed. So I can go and check show IP Ospf neighbor. You can see full BDR and the interface as well. Then we can go and check show IP Ospf, actually show IP route Ospf. So here you can see that you have the metric value and you have the AD value. AD is 110 and the metric is 10 plus 1. So that's why it is 11. We know that for Ethernet interface that is 10, and then 1 is for loopback. So that's why it is showing like this. Alright, here you can see the Ethernet. So for that we have 10, and then generally 1 it is using for loopback. Alright, next thing that I want to check here is that is show IP Ospf interface, and that is E0/0. Now here you can see that interface where the network type is broadcast. So what I can do that the switch is connected over E00. I can go to the interface E00 and I can make that IP Ospf network as point to point. Now here you can see that you have broadcast, non-broadcast, point to, multi-point, point to point. And if you go to point to multi-point and type question mark, you have point to multi-point. By default it will be broadcast, and then you have the non-broadcast like that. So I'm interested to make this as point to point, and both side I should do like this. So other side also I should go, and I should go here to E0/0 network point to point. Now you can see that again Ospf process is running. It is going from full to down, and the SPF algorithm is running one more time. And then we have the new tree, SPF tree, and from there we have new routing update or routing table. Show IP Ospf, and the interface is E0/0. You can see this network is now point to point. You can see this cost as well. There is other information as well related to timers, non-stop forwarding, etc. All right. So we have done this task with these two switches here. Likewise, I will go and initiate the Ospf process, and I will advertise the network for R1, R2, and only R1 and R2. We don't have any R3. All right. So let me quickly check here in switch 101 what is the complete Ospf configuration that we have done. So these three network, one network is belonging to the network that we have connected with R1 and R2, that is nothing but the area 0. And then these guys have one loopback address 111 inside area 0. And likewise, I'll go here and then I will use 222 area 0 and then this. Now if I go ahead and check show IP Ospf network, here we have 3 devices who is forming the Ospf relation. If I go and check show IP Ospf interface, I want to check the interface E0/0. So here I can see that again the network type is broadcast. Now in our topology, either I can use network type as a point to point or broadcast, but we have seen that chart that as per the topology, suppose if you are working or dealing with frame relay, then you can use NBMA and then you have the mode for NBMA, correct? I don't want to make this as a non-broadcast. If you make this non-broadcast, so suppose if I go to R1 and R2, and I should know what is my neighbor, show IP OSPF neighbor, and if I go to interface E0/0 and if I make this IP OSPF network is non-broadcast, then I need to add the neighbor command manually. So now if you check your neighbor, you can say it's a down, because in this case you have to use this neighbor command. So you have to go to router OSPF1 and use the neighbor command. Who is your neighbor? So this guy is your neighbor. Then use the neighbor command. This guy is your neighbor. So manually we are adding the neighbor now, and here also it is detached. So these are my neighbors. I'll go to interface E0/0. IP OSPF network is non-broadcast. Then router OSPF1. We'll go and add the neighbor, this, and again I'll go and add one other neighbor. Then we can go and check show IP OSPF neighbor. Still this is down. Show IP OSPF interface and then E0/0. So now it become non-broadcast, but we are seeing here that the network is down because we are using the wrong network type here. If we have the NBMA type of, or if we have a non-broadcast type of network, then we should go and use here. Again, you can see this hello and dead timer is changing. Okay, so what I'll do here that I'll go and make this interfaces again backup. Interface is 0/0 and IP OSPF network is, say for example, broadcast. So one side is broadcast and other side is non-broadcast at this point of time. And now you can see it is forming the relationship with the switch 101. So if I go and check do show IP OSPF neighbor, you can see it is forming this. Likewise, I'll go here and again interface is 0/0. IP OSPF network is broadcast, and then we can go and check show IP OSPF neighbor. Alright, so now we have to test the final piece, that is the passive interface. So suppose if I go and make one of the interface over R1 as a passive, so let's do that. I can go to router OSPF1. You can see that we have this command passive interface default, and then you can go and make no passive interface. So once you do this command, all the interfaces become passive, means your neighbor is down. So here you have to use no passive interface, and that is the E0/0. E0/0 is the interface. I want to make no passive interface. And again, if I go and check the neighbor, so here you can see this is up. So that was the lab related to whatever we have studied in the previous recording. You can refer this particular lab. Next, we have OSPF authentication and virtual link. So let's start with OSPF authentication. Now, actually, it's very easy to configure and it's different than RIP and EIGRP. what we can do, first of all, we can go to the area. So here you can see I'm over OSPF, I'm inside area, I'm putting area 0 authentication. Then I can go to the interface level, and then I can go and give the authentication key. So we have two things. We have the plain text or clear text, and then we have MD5. Now same way we can go and configure the MD5 as well. So again you have to go to area 0. Here you can see that I'm over area 0 here and the authentication message digest. Then I will go to the interface, and then I can assign the message digest key. So it's very easy and straightforward. I'm going to show you in the lab section about the message digest key, this authentication. So more we can discuss in the lab. Now next thing here is, what about virtual link? Virtual link is again one of the use case we have in OSPF, that for example, due to any reason the customer network, they are not able to directly connect with area 0. We know that all the areas should be connected with area 0. So suppose you have area 1, 2 and 3. For example, later due to some reason you are connecting area 4 with area 3, not with area 0. So in that case we can create the tunnel in between area 0 and area 4. So the router inside area 4, they will think that I am part of area 0 or I am directly connected with area 0. And that's the concept of virtual link. Again, you will see the configuration here. The configuration, you'll find it's a very much like we are creating that tunnel. So router, the area 1 is working as a transit, and then I have tunnel in between, say for example, area 0 and area other area. So let me go back here. So here you can see this is a classical example that you have area 0, area 1 and area 2, and then you are creating the virtual link in between that. Okay, now there are possibility that you may have area 0 and in between you have area 1, and that's again the possibility is less, but still you can create the virtual link in between that. Now once we create the virtual link, then over the area 0 we have put the message digest. So same key we can put over virtual link as well. Okay, so we have seen all these steps, and let's perform the same task in the lab setup. So we'll understand more about the authentication and the virtual link. Let us perform the lab related to authentication and virtual link. I have done the change in my setup. Here you can see that now we have R1, R2, and that's R2, but switch 105, then switch 101, and then switch 102. So R1 switch, and then again switch, and then the switch 102 in the bottom. Subsequent network IP addresses I have changed. So we have network 10.1.1, 10.1.2, 10.1.3.0, and then we have respective area like area 0, area 1, and area 2. Now in lab number 1, we'll go and um, create or run the OSPF in between area 0, and then we'll do the MD5 authentication. In the same lab later on, we have to create the virtual link, and we have to make area 1 as a transit. All right, so let me show you this IP addresses assignment here. You can see that we have created and assigned the IP addresses only so far as per the diagram. So these are the IP addresses assignment related to R1, R2, related to R1 and all the switch. So now let's start with area 0, that is R1 and switch 105. I'll go here and enable router OSPF 1. Then I have network, say for example 11111, and then I'll put this inside area 0. So let me do that. Then I have network 10.1.1.0, This also I'll put inside area 0. Alright, now we'll go to the switch, that is switch 105, and we can go and check the network. First of all, we'll go and initiate the Ospf process. Then we have one network that is 10110, but we have 105 network as well. So let me quickly do that. And 00000 area 0, for example. Then we have the rest of network. So now you can see I have enabled this, or I ran this command, but still I can't see that Ospf is coming up and running. So I should go and check the IP over E00, and we should have address IP reachability. So E00 here, it is correct. If I go and check the interface configuration for this switch, so let me try to check 0/0. Wow. So we have this command configured and protocol is up. So if I do the ping, so let me do the ping from here for 10.1.1.1. That's the router IP. And I can see that ping is working. If we could go and check show IP Ospf neighbor, show run section Ospf. So here you can see that I have this network inside area 0, and then I have my network, that's the loopback, but still I can see that they are not forming the neighbor relationship. So now what I'll do, I'll go here and make this network as a 10.1.1.0 area 0, and then I'll remove this network statement. You can see that the problem here we have. Then again I'll go back and delete this and add this. So let me try to do both at a time. In router number 1, okay, and let's try to check show IP Ospf neighbor. Now they are in two-way dweller state. They're stuck in dweller state. Alright, and if I go here and check in this, because we haven't removed Ospf from here, show IP Ospf neighbor. Okay, so the reason maybe now it is up. Maybe the network type that we haven't changed, but now it is showing it is up and running, so that's okay. Now we have the Ospf relationship over area 0. What I want to do now, that I want to run the authentication. So I can go to router Ospf 1 and then area 0 authentication. Here you can see that you can do plain text if you want. You can leave with this authentication, or if you want to do the MD5, that is the more secure, then you can go and use this. Now at the moment I have done this, you can see that the neighbor is up, but we are getting one problem here, that authentication key, you don't have any valid key. So now what I'll do, I'll go to 00 and then IP Ospf authentication. You can see that you have authentication and message digest option. So I can go and put the key as a Ccnp. You can see here that you can go to authentication and key, and then you can see here that you have option say unencrypted. This is not that I'm looking for, so I can go and give the message digest, but I want to put the key as well. So let's see, IP Ospf authentication, and we can give the authentication if it is a plain text an authentication key. And suppose if I'm using authentication, then I have this option for message digest. Actually, that is quite a confusing option that Cisco is giving to you. So, because obviously natural thing is that we'll go and check IPOSP of authentication, and then whatever authentication will be there. But in case of message digest, you should go and check IPOSPF, and then you have this option of message digest key if you want to put your key. So I'll put key as Ccnp, but let's see, yeah, MD5, and then so this is the long command that we need to put here. Now if we go and check show IP OSPF neighbor, we can see that neighbor is down because of mismatch of the, or we don't have the key configured to the other side. So here also we can go to router OSPF1 area 0 and then the authentication message digest, and then we'll go to interface E0/0 IP OSPF message digest key. Now we are getting this error MD5 CCNP. So now you can see that the neighbor is coming back up. So this is the way that we can go and do the authentication inside area 0. Now what I want to do here, that I should go to the I should first of all do the OSPF rest of the configuration, and then we'll create the virtual link. So let me do that. R1 is okay. In R2, let me check show IP route and what network that we have configured so far. So we have router OSPF1. We should have one more network, that is 10 dot let's see the network. That's 10.1.2.0. So 10.1.2.0 0000255, and that is inside area 1. Correct. So this network is in area 1. Now we have switch number 101. So let's do the configuration for switch number 101. And what network we have? We have network 10.1.3.0, that is in area number 2. Then we have network say 101, 101, 101, 101. So for example, I'll put this in area 1, and then finally I have 10.1.2.0, that is inside area number 1. Alright, so we are very much done with this OSPF configuration. Finally, we have switch number 102, where we have 10.13.0 network. So I'll go here as well and should enable OSPF, and then we have network. Say for example, first of all I'll advertise the loopback, and this is inside area 2. And finally we have network 10.1.3.0, that is again inside area number 2. Now here you will see that after running all these commands, If we go and check show IP OSPF neighbor, so he has neighbor that is 102 and 105. Now if you go here and check to the switch 105, you will find show IP OSPF neighbor. So he should also have two neighbor, but if you go and check show IP route for OSPF, you'll find that he is not getting 102 because it is never getting tunneled or passed through the area 1. So in this case, we should go and create the virtual link. Okay, so let's create the virtual. So I'll go and create the virtual link here inside area number 1. So first of all 105 and then 102. So already we are here and router OSPF1 area 1 and then the virtual link. What is the ID? So we know that the neighbor ID is this. You can see here that we have option for message digest key as well that I'll put later on. But that's it. Area, virtual link, and then the peer device router ID. Now I'll go to 101. I'll go here and router OSPF1 area 1 virtual link is what's the router ID you're looking for to make the tunnel. That's sorry, not this one. This is 105. Okay, so I'll go and remove this, and that's it. So once you do this, then if you go here and check the OSPF, you'll find that you will start getting the routes. Now, what is happening here in this case that since you don't have key configured, so inside area 0 we have the key configured. You should go here and give the key so it will work properly. Go here and here also we'll go and we should give the key, say Ccnp, and now you will see that they will start getting the routes. So if I go here and check show IP OSPF neighbor, now show IP route OSPF, you should get 102 102 102. That will be the final valid verification for this. So after running this command, I can't see that anything is happening. And let me go and check here as well. You can see this configuration is 100% correct. You're creating virtual link with this, and in router 1 also the configuration key, everything is correct, but it's still they are not forming this. So what we can do here that we can go to router OSPF one more time. Router OSPF1 area 1, say for example the authentication is message digest. This belongs to area 1, and here also we have area 1 as well. Let's see the final configuration. SPF. Now invalid key for 10/0 that we can verify. So what is happening actually here, that if you go and check the configuration, you'll find that once you are putting the key here over the virtual link, now this belongs to inside area 1. These are the interfaces where you have to put the authentication key. So for example, as a MD5. But when we are creating the virtual link, actually, in that case, that is going to propagate area 0 only. So it's not required to put the key there. Okay. But just for the security purpose, I'll go and put the key over 10/0 and E1/2 as well. So E say 10/0 and IP Ospf, or maybe IP, yeah, Ospf message digest key 1 MD5 Ccnp, correct? And then finally I can go here and interface E2/1/2. Wow. So this much configuration we have done. And now if you go and check show IP Ospf neighbor, first of all we should have the neighbor. And if I go to R1 and if I go and check show IP route, so here you can see that it is getting the route as a O routes, as it is directly connected with area 0, and we don't need to put actually authentication over the area 1 interfaces that I have done, but for sake of security we want to put the authentication key at all the places, so you can go and put the authentication keys at all these places. Alright, so this was the authentication. And the next important section we have Ospf summarization, different type of areas, and the default route concept. So let's start and understand the summarization. Now clearly you can see in the diagram that you have area 0 separated by area 1 and area 2. And for example, if you're getting routes, say 10, 1, 0, 0, 1, 1, 1, 2, 3 up to 7, and other side you can see that is 8, 9 up to 15. Now we are sending all these routes to the core router. Here you can see all the individual route, and hence the database or the topology table of the inside the area 0 will increase. Rather than what we can do, that we can summarize the area 2 as 10.1.8.0 and area 1 as a 10.1.10/21/21. Correct? So in that case, we are sending only one update, and our routing table will be efficiently utilized. Doing so, we can reduce the load over the router CPU. So this is one of the interesting use case we have with inter-area Ospf summarization. Now what's the command? Command is very easy and straightforward. We can go to the router, and over the router you can go to the area, and then you have to use the keyword called range, and then you can use the address and the subnet mask, and then this will be done. Now there is one important point to mention, that suppose if you have some of the routes in between that is not part of subnet. So for example, if I don't have 1.5, 1.6, is still I am using this summarization, that is 10.1.0/21. So in that case, what we can do, we can use the concept of static route null 0, and we can point out this summary route towards null 0. So that means that anything that is not matching, that will be garbaged, that will be bit bucket. Correct. Now here you can see that note that after 12.16, and now we are running the modern or advanced version of operating system, even this command is not required. It was required for the earlier version of iOS. Now the second point related to summarization we have is Suppose if the summarization is coming from the external system, it's not related to inter-area routing, but it is coming from outside. Now at this point of time, we should go to the ASBR. Suppose router B is ASBR, who is connected with non-OSPF domain or non-OSPF routing protocol. So in that case, you can do the summarization, but syntax will be little bit different. So in this case, instead of doing area, the command is summary address and then the network and the subnet mask, means whatever network we want to summarize. Correct. So now this concept is very much like we are doing the aggregation, and we have two type of border. We have ABR and we have ASBR, and like that we can easily do the summarization. Now here you can see that we have one use case in case of ASBR summarization, that if you don't want to advertise certain prefixes. So in that case, you can go specifically to that particular network and you can use the keyword called not advertise. If you use not advertise, obviously these networks will not be advertised inside the OSPF. Okay, so this is the concept related to summarization. Now next important concept we have is the OSPF area type. Now I have one summary chart as well where we can go and summarize the OSPF area type after a few slides. So here you can see that you have area type called backbone, non-backbone, stub area, totally stubby area, and not so stubby area. That is NSSA in short. So let's learn and discuss about the area type. Now starting with the basic area, that is the normal or the standard area. We know inside that area we have LSA type 1, we have LSA type 2. So here you can see that we have all the LSAs inside the standard area, the type 1, type 2, type 3 and 4 generated by ABR. Then we have type 5 as well, that is generated by the ASBR. So it is able to understand all the LSA. That's the standard area. Now the second thing here, that when you are making a stub, at the moment you will make the area as a stub, the stub will not accept type 3 and type 5. But remember, they will automatically inject the default route. Now doing so, we are not, while doing so, you can think like this, while doing so, we are cutting off the SPF calculation. And who is doing the SPF calculation? My CPU, my process. So that means that we are cutting off the intensive cycles, CPU cycles, and hence we are providing good type of optimization in terms of CPU and memory. Correct? Now, what's the command? Again, the CLI command is very easy and straightforward. You can go to the network. So here you can see a router process. First go to the router process, and then you can go to area 1 stub. At the moment you do the stub, that means it will start stopping type 4 and type 5, although it will get router, network and ABR generated LSA. That is type 1, type 2 and type 3. And other thing is that it is generating the default route. Now the third concept we have is the totally stubby area. Now what totally stubby area even will do, that will accept only type 1 and type 2. It will not accept type 3, type 4 and type 5 LSAs, although it will go and generate the default route for type 3, 4 and 5 LSAs. Again, the use case is that we are saving the bandwidth, we are saving the CPU core, process cycles, etc. Now the command here is interesting, that here we have used in a stub area, we have used area 1 stub. For totally a stub area, you have to add one more keyword, that is no summary. So the command is area 1 stub no summary. It will stop LSA 3, 4, 5 and it will generate the default route. Okay. Now the fourth one is not so stubby area. Why we need not so stubby area? Here you can see that you may have chance that area 0 is connected with external network, or you may have chance that area 1 is connected with external network. Correct. So in that case, we'll see that when you have area 1 connected with external network and you want to filter some sort of LSA, you are going to use the not so stubby area. Means it's a stubby area, but it's not fully stubby area. What it will do, here we'll see that like a standard stub area, NSSA area routers will share type 1 and type 2 LSAs. Okay, they are not blocking type 1 and type 2. NSSA area will also accept type 3 LSA. So they are going to accept type 1, type 2, type 3. But NSSA will not accept type 4 and type 5. Okay. Now we are going to introduce one new LSA, that is LSA type 7, that we haven't discussed so far, but not so stubby area is linked with LSA type 7. And what's the use of LSA type 7? Now we'll see. So if an ASBR exists within the NSSA area, this is ASBR will generate type 7 LSA. Again, NSSA areas are almost identical to a stub area. If area 1 was configured as NSSA, it would not accept any external route originating from router G as ASBR outside area 1. So here you can see that they are not accepting any type 4 and type 5 LSA. Rather than we have type 7 LSA. So here you can see that it will not accept, this is the router G, it will not accept any external network, external non-OSPF domain network. Correct? Great. However, area 1 also has an ASBR within the area router A. Those external route will be flooded into area 1 as type 7. So here you can see that you have area inside area 1, you have router 1 and who is getting the uh, external routes, and that will be flooded inside area 1. Now these external route will not be forwarded to other area as type 7 LSA. Instead they will convert it into type 5, and that's the key, and that I'm going to summarize. Type 5 LSA by area 1 ABR router C. So what is happening here when you are creating not so stubby area? In that case, you are getting type 7 LSAs, and router C, what he will do, he will convert type 7 LSA to type 5 LSA, and then it will flood it into the other area, or the other area will calculate as per the type 5 LSA update. The configuration is very simple. What you have to do, you have one keyword, go to the route process and then area 1 NSSA. Okay. All right, and final concept we have is totally not so stub area. So let me stop here, and remaining concept we'll discuss in the next recording. But here you can see the summary, and in this summary, let me try to highlight. Backbone LSA 1, 2, 3, 4, and 5. They are not getting LSA 7. Non-backbone like area 1, area 2, etc. They are also getting all the LSA. Stub area LSA 1, 2, and 3. Totally a stub area, only LSA 1 and 2. Remember, they are going to generate the default routes. The not so stubby area type 1, type 2, 3, and type 7. This type 7 will be converted to type 5, and then it will be reaching to area 0. That's the overall summary we have with this recording. So let's just stop here, and next section will continue from here. Let us continue where we have left off. Now next concept we have is not totally not so stubby area, that is TNSSA. So what is the main difference between a stub and totally a stub area? The same difference you'll find between not so stubby area and totally not so stubby area. Totally not so stubby area will allow LSA type 1 and 2, and he is going to filter type 3, 4, and 5. Here you can see the configuration is very straightforward. You can go to OSPF area and then you can give area 1 NSSA. The keyword is no summary. And here we have the summary just for your reference. Now the next topic we have is OSPF and relation with default routes. We know that when we are generating a stub area and totally a stubby area, at that time the OSPF process, they are generating the default route. But in case of ABR and ASBR inside a standard area, we don't have default route. Now suppose you are sending LSA type 3 from router C and you are expecting that you are getting say LSA type 5 from router 1. So you are getting LSA 5 from router 1 and it will go to router C and then other areas. Likewise, LSA type 3 will go to B and A and actually B and then A and then the external network. At that time, suppose for the external network, you want to create the gateway as router A, so we can go and create the default route. So here you can see that additionally force router A to generate a default route, including itself as the next hop for the external network and injects into this inside area 1. Okay. What is the command? Command is router process, go to router process and default information originate. So this will inject the default route. But in case suppose you want to force it. So for example, if a default route does not exist in its routing table, router A can still be forced to advertise a default route using always command. So in that case, if I want to force the default route, lab that what type of IPv6 addressing we are using. So here I'm using this type of lab. You can see we have router R1, R2, R3, 4 and 5. Here you can see 1, 2, 3. These are the router number 4 and 5. Now in this topology, although just for sake of simplicity, I'm using only area 0, but we are not restricted to use just the area 0 because we can go and create same type of topology and methodology that we have learned earlier and multiple areas we can create. All right. Coming back to the addressing, what type of addressing we are using. So we have something loopback either 0 or loopback 1. If it is a router 1, so I'm using 1 and then double colon 1/128 as a loopback IPv6 address. So suppose if it is a router number 4, you can see the numbering, it is router number 4 here and this is router number 5. Let me clean this and let me write one more time. So suppose if this is router number 4, so IPv6 address over loopback address, either loopback 0 or 1, you'll find 4 colon means double colon and that will be used inside IPv6 4 and then /128. That's the IPv6 address I'm using for loopback. And what about the interfaces? So suppose if this is router 1 and this is router number 4, so IPv6 address that I'm using here will find 14 colon 1/64 here and then 14 colon 2/64 here. Again, if we have router number 2 and router number 3, so I'm using 23 colon 1/64 here and then 23 colon 2/64 on this interface. So like that you'll find the address schema and that's why I haven't put all this information in this diagram. Once you see the lab you'll understand. Very easy and straightforward, correct? And the configuration and the complete configuration you will find in this particular document as well. So once we go, what we need to do, we have to first of all enable IPv6 routing, you'll see that how we are enabling this and all. So once your OSPF IPv6 means OSPF version 3 is up and running, then you can go and verify the router ID. Now router ID, although you can see that it having number very much, this is showing IPv4 type of numbering. That's right. But the point here is this, that this IPv4 type of numbering that we have related to uh, IPv6, you may think that why not we have something 1:1, something like that here as a router ID. Router IDs are not that much important in IPv6. You can see the notes here. So OSPF v3 picks read router ID, exact algorithm used by OSPF version 2. It is 32-bit dotted notation that we have in OSPF version 2, but has nothing to do with IPv4 address. You can use any format, 0001, 025510, it's a. Okay, should not use 0.0.0.0 because it is reserved. Apart from that, you can use any 32-bit dotted notation. Now, once we'll go and configure all the routers, and then we'll go and verify router LSA, network LSA, link LSA, inter-area LSA. These are the OSPF version 3 command. I will show you these commands in the lab. Now, what's the difference here? So OSPF v3, you can see, is almost similar, and all the LSA types are almost equal to OSPF version 2. We have two new LSA, link LSA and prefix LSA. Now the summary LSA is now called as a inter-area network, and summary BR is called as an inter-area router. Correct. Rest of the things you'll find is very much similar. Now, what about the configuration? You can see the configuration. We have 5 routers. So you can see IPv6 related configuration. First of all, we need to go and enable IPv6 unicast routing, and then we can go and do the configuration. So for example, in R1, you can see that loopback1 having this IP, and then loopback1. The command is, we can go to the interface. Once we are over the interface, then we can go and run this command, IPv6 OSPF1 area 0, area 2, area 3, etc. But we know that concept that you have one backbone area, and then rest of the areas are connected with that. We have checked all these things in the previous OSPF version 2 section. Correct. Then here you can see that how I have given the IPv6 address just for sake of simplicity. So 14::1/64. Then somewhere you will find 12. So that means if you are at the R1 and if you are going to R4, you'll find 14 address here. And then if you are going to R2, you'll find 12::: here. Okay, /64. So like that, we have used this strategy, and rest of the configuration are almost same, that we have what we are using inside our OSPF version 2. Although you can see the IP address is related to IPv4 as well, but it's up to us that if we are purely inside the IPv6 network, then these addresses are not required. These are the 4 configuration related to router 1 up to 5. So next, what we want to do here, I will go and show you in the lab section that everything will be up and running. I'll show you that how you can go and check the OSPF neighbor, and then few of the LSA's output in the lab. All right, so let's stop here. I will show you the rest of the output in the lab. Now we are ready to perform the lab related to OSPF version 3, and let's do it. So already I have done the configuration, and let me log into all these devices one by one. Let me show you this. So same topology that we have seen earlier in the slide in the PPT. I have all those 5 routers which is running here. They are virtual routers over viral environment, but if you want, you can use GNS3 or any other emulation that is available. Now what we can do here, we can go here and we have this script option, and we can send to all. So let's select all and use show IPv6 interface brief just to see that what IPv6 interfaces we have in configuration. So here you can see that gig 00, you have your global address, you have the link local addresses as well that is derived there over these interfaces. So gig 01, 02, and likewise you can see all the IPv6 addresses in the same way that we have discussed earlier. If it is R5 to R3, so you will see here 35 colon colon 5, like that we have the address. Now next what we want here is that we want to check the OSPF version 3 configuration. So for that actually we need to go and we can go and check these interfaces. So if you go to these interfaces, only one command is there, that is uh, IPv6 OSPF 1 area 0, and apart from that, let me show you that what other configurations we have. So you can see that I have used IPv6 unicast routing. IPv6 was there automatically, and these configurations we have used. Let me highlight these configurations we have used over the interfaces, and now the OSPF is up and running. Now here if you can go and check the OSPF version 3 neighbor, so you can see here that in broadcast network still it is following the DR BDR rule to form who is the DR BDR etc. We know that how it is forming, we have done this in the previous sections. And router 2, because router number 2 has 3 connected neighbors. One is router number 1, one is router number 5, one is router number 3. So likewise you can see here that it is showing you this information, and here you can see the router ID as well. So in this output you can see the router ID as well, and there are other outputs as well. We can go and check show IPv6 OSPF, and here you can go and check the ID. So here you can see the router ID. We have the router ID. Show IPv6 OSPF also will give you the detailed information, and then if you want you can go and do the filtering there as well. So I'll go back to router number 2, and here we can go and check different type of LSA's output. So we can go and check show IPv6 OSPF, and once you are there you can see that what filters here we can see good long list of options that we have, but we are looking for database, and after database you can see that we have options related to a router, a link, network. You will see the router as well, correct? So if you want to check the router, and then we can go and check the self-originated link status. So here you can see that we have the router LSAs. Likewise, we can go and check the network LSAs as well in IPv6. So instead of router, you can go and use the network and then self-originate. You have the network LSAs. Likewise, we can go and check the link as well, link LSAs. So here you can go and check the link LSAs, and finally you can go and check the prefixes as well. So if we have the prefixes, let's see the prefix self-originate. Great. So this is the way that we can go and check all the LSAs, most of the LSAs, but we know that there is good amount of LSAs. But this is the way that we can go and do the implementation, and then again after implementation we can verify as well what's the output we are getting here. And the implementation in all the devices, I told you that I am using only area 0 just to sake of simplicity, but to do the deployment related to version 3, OSPF version 3 is the same. So not a big thing, it's very much same like we are doing inside OSPF version 2. Alright, so let's stop here and we'll move to the next section. Now we are ready for the Ospf troubleshooting section. In this section, we are going to discuss some of the troubleshooting use cases, some of the troubleshooting tickets related to Ospf, starting with the path computation. So let me quickly walk you through the topology diagram that we have. We can see that we have big topology diagram, starting with router number 1 to router number 19. And this topology I'm going to use for different use cases. Different sections, subsections going to be used. Same topology diagram I have over Cisco viral, and different use cases again we are going to discuss with that. Now in first use case, we are going to discuss about the path in between R1 and R4. So again, before going there, I just wanted to pause here so you can mark it down that what is the IP schema I'm going to use. So suppose if it is R1 and R2 and the address in between, how I have used. So 10 dot the lowest router number, then the highest router number, and then suppose if you are in router number 1, so last octet will be that router number. So 10 1 2 1, and then /24 will be the IP for router number 1, this interface. Other interface will become 2.2, correct? So 10.1.2.2, like that. Now if it is a broadcast type of network, such as here you can see. Now for broadcast type of network, I'm going to start with 10.0, and then the router, so lower router, say router number 1, and then the router number, first router or second router, whatever router is there in that list. So for example, R1, R2, R3, so X will become 1, and then X will become 2, and X will become 3. So here the IP is 10.0.1.1. Here the IP will be 10.0.1.2, and in this interface the IP will be 10.0.1.3. Okay, so easy type of address formatting. Two different type of interfaces are there, broadcast and point to point, and IP you can understand. Then for loopback, 10.0.0.x, X will be the router. So suppose if it is router 8, so 10.0.0.8. If it is router 19, 10.0.0.19 will be the loopback addresses for the interfaces. So three different type of address schema I have used here. Now let's check use case number 1. So we have some issue in between router number 1 and router number 4. And if you go and trace the path, you'll find to reach from router number 1 to router number 4's loopback. So router number 1 loopback to router number 4 loopback, you have three different paths. Via R14, via R2, via R3, R5. The optimal path, the desired path we have is obviously via R1, R2, and R4. But due to some reason, we may able to send the traffic from R1 to R2 to R4, or the return traffic is coming via this direction or any other direction that we need to figure out. But the problem here is this, that you are facing some sort of latency, slowness in between two peers, and we have to find out that why this issue is. Do you have asymmetric routing, or your traffic is not flowing as per the lowest hop counts, etc. Okay, now obviously we will go and make some hypothesis that, okay, via this path you have some issue, via this path you have issue, via this path you have some congestion, etc. But before starting any troubleshooting ticket, we should have full topology diagram. We should have layer 3 topology diagram, IP schema, the device accessibility, etc. Now, what we can do in this case is, since we are dealing with OSPF, we can go and check the cost value. We know that the metric value is the cost value, and if you see the main topology diagram, you'll find that everything is gig interfaces. So for gig interfaces, the cost value is 1. Although here you can see I have used 1010, but it's okay. You can understand that what you need to do, that for all different paths that we have. So via this path, via this path, via this path, all three different path, we should go and build the cost value or the metric value, correct? And once we go and build this cost value, then we should understand. So we'll come to know that what is the actual path and what is the desired path. The actual path may be via R14 or via R3, R5, but our desired path is from R1 to R2 to R4. You can say R1, R2 to R4, correct? So that we are going to verify once we find out that the issue is there, we can go and resolve it and things will work. So let me go and open the lab. I'm in the lab section, and if you go here to R1, we know that we should check the destination. Destination is 10004 with the source 10000.1. Let's see the reachability. You can see it's reachable. Like that, I can go to R4, and from R4 also I can go and check the source 10004. So you can see that reachability is there, but still there are some issue. So now we can do the trace. We can go and trace the path, the destination with the source, and start this trace. And likewise, I can go to R4 and I can trace, I can go and trace the path. So do the trace route for the destination. From here, the destination is 100001 and the source is this. All right, so if I go to R1, here you can see that R1 is going to 10.0.1.3. It is going to 1.3 means is router number 3. This is 3 to 5. Then 3 to 5, then 5 to 4. So you can see it is taking extra path here, how it is going. So when I have started the trace, we check the trace and we'll finding that when we are doing the trace, it is going via this path to reach the destination from source to destination. And now if you go and check the return traffic or from 4 to 1, you can see that it is going via R2. This is the desired path. So from one direction, we are getting the desired path. Other direction, we are not getting the desired path. We can go and do the debug. Let's see. Debug IP, IP packets. And we can use ACL here. 1310. I'll do 1310. Okay, I'll create that ACL. You can see so many packets. This multicast packet exchange is happening, and that's the problem we have with the debug. Let me do undebug all and undebug. Let's create the ACL. So access list, and I want to create extended access list 1310. We can give the permit host 10.0.0.1 is the source, and the destination. I just wanted to create extended access list. I don't want to create the standard one. So here I can see, let's see in the debug IP packets. And you can see that we can go and use in between 1 to 199. correct? So 101 will be perfectly fine for us, correct? Access list 101, permit the host, okay, permit the IP, host 10.0.0.1, and then the host 10.0.0.0.4, okay, enter, and then we can end, and then we can go to the debug IP packets, and then we can give 101. Then if we do the ping or trace route, so let's do the ping. I want to do the ping from the source to the destination, and I want to repeat it 2 times. So let's see. So here sending, you can see source to destination, I can see source to destination, we can see here, and I want to do one more time this debug detail, and then ping. Great. So now you can see that source to destination, but you're not seeing anything that is coming from 10.0.0.4 to 10.0.0.1, correct? Now, this is one of the way that you can debug with access list, and you can check the result. If you do not use the access list, you have seen earlier that so many packets, so many packet related to hello and others will come into the picture. Great. Now we are going to focus on the classical way, that we want to create the graph theory, OSPF graph path, and then we want to check it. So if I go here and check the route related to OSPF, and we are very much focused on the path that we want to reach here. So you can see that 4, okay, great. And now if you go to R4, show IP route OSPF, you can see here 3. Now the desired troubleshooting is this, that we can go to hop by hop and we should check. So if router 4 has to come here or it will go here, so you can go and check the comparative cost, correct? Then here to here you can check the comparative cost, and suppose this is the destination, in terms we are coming as a return traffic. So to reach to here, what will be the cost? So cost here, cost here, cost here, and to reach in this direction, what will be the cost? So if the cost in this path will be lesser, obviously that it will go via the longest path, correct? So that we want to correct here, and you can see here R4, likewise we can go and check this to R2, we can go and check this to R3 and R5 as well. So what is the intermediate devices? See R5, R3. Okay, so let me quickly go ahead to R5, at least one hop we can go and check. Okay, so here let me reconnect my host, and once it will come, we can go and check show IP route related to OSPF, and you can see here to reach, it has one path that is going via 3 because it is assuming lower metric. Okay, so you can see somewhere you will find the highest metric. So if you go via the router 14, you can see via router 14 it has 25, correct? And if you check R4, let's see the 14, 24. So that's why it is not taking the path. So now we have actually 2 paths only. So this path because of high cost values not desired. So we have two paths. We have to troubleshoot this path and this path. Because while doing the troubleshooting related to trace route, we found that the 1 to 4 traffic is going via this path, but return we have some issue. So that means some cost values related to OSPF, those are coming into the picture. And if it is related to cost value, we should check this guy here and we should check this guy here, the cost value to R2 and R5. Better, we can make the cost value common to all the devices, correct? So if I go here and check to R4, let's just start with R4. Show run section OSPF. Do we have any cost configured here? No. Now we can go to the peering devices, correct? So I should go and verify two devices. One is R5, one is R2. So let's go to R5, which is already open. And here you can go and check. Okay, do we have any cost value? No, you don't have. Show run section cost. Oops. If cost is configured, so it will tell you. So if cost is not there, that means that you should go and check R2 first. Show run section cost. Inside R2, I can see so many costs are configured. Let's see how many interfaces we have here. So we have 4 physical interfaces, and if you go and check all the interfaces one by one, so cost 1 place, cost 22, that is going towards router number 14, that I don't want to do any change. Let's see 3, and let's see 4 as well. Cost, so that is going to router number 4. So that means if I go here to interface kick 0/4 and I can do no IP OSPF cost, remove this cost value. Okay, and now once we remove this cost value, then let's see when we have done the trace route. Again, we can go and check the metric values and we can do the trace as well. So let me try the trace. And from R4 as well, I just wanted to do the trace one more time because we have corrected the cost value here. So one change we have done in a network, and after that change, because anyways capturing the trace result as well. Wow. Anyways, let the debug going on. It's no problem with that. Undebug all. Let's do undebug all and let's run the trace one more time. Meanwhile, let's see router number 4. So router number 4 path is good now. And what about router number 1? Let's wait and watch. It's coming up. So it's going to router number 2. Then it's going to router number 4. That's 100% correct. So now you can see router number 4 and router number 1 is behaving properly. Great. So you can see that we have done the OSPF path manipulation and we are now able to find the optimal path from router number 1 to router number 4 and 4 to 1. In this lab, we are going to see that if we have issue related to OSPF adjacency, that means that OSPF, they are not forming the adjacency. What are the common issues? What are the common problems we have? We have to gather the problems and then we have to fix it. In our lab diagram, we have two routers, router number 2 and router number 10. So in between these two devices in between these two routers, they are not forming the adjacency, and there may be any issue, means there may be n number of issues that we have to go and fix it. Maybe the link is down, maybe it's passive, maybe authentication misconfiguration, maybe router ID misconfiguration, wrong IP, any type of security configuration, stub configuration, etc. Okay, so what we need to do here, we have to go check the configuration, we have to go do the troubleshooting, and we need to fix the issue. Okay, so I will go log into router number 2, router number 10. We'll try to identify the issue and then we'll try to fix it. Okay, what we can do here, you can see that we have a debugging option. We can go and check the debug condition over the interface. We can go and check the debug IP OSPF packets as well. Okay, so let's start this. Let's check the configuration, what configuration we have and how we can solve it. Now, if we go to router number 10, and if we go and check the debug condition, and we need the interface, what interface we have, this particular neighbor. This particular neighbor is forming over gig 0/2. And here you can see that condition 1 is set. Then we can go and check the debug IP OSPF. And then you can see that we have multiple options. The popular ones are adjacency and then packet. So I can go and enable the packet option here. Okay, so we have on the debugging, and at the moment I on the debugging, you can see that we are getting some sort of authentication failure. So clearly it is showing that we have some sort of authentication mismatch. Now, if we go and check this particular interface, let's see that what authentication configuration we have here. I can see plain text in Cisco 123. And if we go here and if we verify inside router number 2, what authentication we have on the router number 2, and let's see, this interface is gigi 0/3. Show run interface gigi 0/3. Here you can see the authentication is a small Cisco 123. So that means either any of the place you have to go and you have to correct the authentication parameter. So I can go to router number 2 and then I can give Cisco with capital C 123, and we have fixed this authentication. So let's see the debug message. It should not come now. It's telling that area 0 had some authentication in and out. It should be corrected now. Still, I can see that authentication is coming, mismatch is coming. Again, we'll verify this interface. So authentication key, Cisco 123. And here, authentication key, Cisco 123. So I can see that authentication is working fine. And again, interface gig 0/3. Let me redo this configuration. So what is the message? The version 2, type 1 length, read area, checksum, auth1. Okay. All right. So we have fixed that authentication, but still we are getting the authentication related message. So what we will do next, I can see that one extra configuration we have here is called TTL security. I should not have TTL security here. So I will go and negate that. No IP OSPF TTL security, remove that configuration from here. And let's see. At the moment, I'm still getting the authentication issue. So over this interface, what I will do, let's remove the authentication. first of all. Later on, we'll go and put that. At the moment, we just wanted to fix the issue. And once the issue will get fixed, then we'll go and revert back the configuration. So one place I have removed that, other place also I should go and remove that authentication. Oops. And here also I can go and remove the authentication key, that is Cisco 123. Okay, so both the interfaces I have removed that authentication 0/2. Clearly you can see that there is no authentication configured. And oops, here also I could go and verify 0/3 on this interface. So authentication is gone. Let's see if I can ping to the destination. The destination IP is 10 to 1010, 10 to 1010. And still I can see that there are some issues going on, checksum and auth 0. Same type of message we are still getting. So what we can do here next, that we should go and verify that the IP subnet should be 100% correct. So one side I can see that IP subnet is 192, and other side you can see this IP subnet is /24. So that means that over gigi 0/3 should have the correct IP subnet, and that I will go and correct from one side 255.255.255.0. Okay, and then we can go and do the ping. So let me do the ping from here to 10 to 1010, and let me do the ping here 10 to 10 to. Okay, so you can see that we have corrected the authentication, we have corrected the TTL security, we have corrected the IP subnet, whatever wrong subnet was there. Still, we can see that something related to area, which is not allowing this to form the neighbor relationship. So now we should go and check the Ospf configuration. And 10 to 10.0 is inside area 1. Okay. And from this side also, we can go and check the router Ospf configuration. And 10 to 10.0, 10 to 10.0 is in area 1. But I can see some stub is configured. So router Ospf 1, no area 1 is stub. I don't want the stub configuration. And we have removed that stub. Now I can see these messages, they are coming fastly. But although these messages are coming, maybe this is belonging to some other subnet or something, but show IP Ospf neighbor. Do I have 10.10.02 neighbor configured? Some checksum, some bad auth, and debug. Let me remove this debugging. Undebug all. And here also we can go and check show IP Ospf neighbor. I can see that I have my peer 32 seconds dead timer. Now what we can do here, we can go and check show IP route Ospf. And we know that the network that we have associated to this particular subnet, and if you go and see behind the network what subnets are there, so R2, R10. So R2 should get the network related to 10.9 or this router ID 10.0.0.0.9. So let's go here to the R2 and you should see 10.0.0.9. So first of all, let's check here in the R10. So IP route OSPF 10.0.0.0.9 is there, and he should advertise this route to its neighbor as well. So 10.0.0.9 is missing, but apart from that, do we have any other network to verify? Quickly, we'll go and verify other as well. So do we have 11? Do we have this network? Let's see. So inside R2, do we have 10? I can't see other network. So you can see that we have 10, we don't have 9, we don't have 11. So that means that neighbor is there, but they are not advertising their agencies. But anyways, that's okay because you can see that this is area 1 and again this is area 0. So other way around, that means I have to go inside R9 and check that these routes are coming to R9 or not. But this particular issue got resolved because we just wanted to form the neighbor relationship in between R2 and R10. And yes, we are able to form the neighbor relationship in between R2 and R10. There are different type of issues, maybe configuration, maybe a stub configured, maybe authentication, maybe OSPF security configuration, etc. But one by one, we have corrected all those problems, and now we have the adjacency form in between router 2 and in between router. In 1.11, we have to understand about BGP troubleshooting. So what I have done, that I have created one playlist related to BGP where we will go and understand each and everything related to BGP. First of all, the basics of BGP, how BGP forming, IBGP relationship, EBGP relationship, how BGP go and use the synchronization. So I have covered the theory, not only the theory, but you'll find that lab as well. So lab related to synchronization, lab related to IBGP, EBGP, lab related to route reflector configuration, peer group, lab related to best path selections as well. So that means if you go and complete all these videos, so you can see number of videos 1, 2, 3, 4, 5, and 5 plus 5, 10 videos. So that means you will be very much good knowing BGP technology, and you will be very much good doing the troubleshooting as well, because in the lab section you'll find that I have done the path manipulation. So you want the traffic coming from this direction versus this direction. You're preferring ISP1 versus ISP2. What type of changes we can do, what type of attributes we can tune. So once we know the tunability, the changes, once we know that how BGP basic configuration happening, peer groups happening, etc., it's actually parallel that we can understand BGP design, we can understand BGP troubleshooting as well. So please complete these 10 videos, and these are going to cover our BGP section. So let's start. What is border gateway protocol? The first question arises is that already there are protocols, routing protocols. There is still why I need one extra protocol. Now the answer for this is that this is the exterior gateway protocol. Means this will override, or this will run on top of any of the underlying protocol, any of the underlying IGP protocol, and it will work such as the application protocol. And that's true. If you see the port number that BGP is using, this is using TCP port number 179. Generally, applications, they are using TCP port numbers, or they are using TCP or UDP. So BGP is a type of application protocol generally built to run over the over any of the protocol and cross the one or one autonomous system. Again, the autonomous system is one region, so cross one region, and then it can go to multiple regions. Or if you want to control multiple region routing, or the network advertisement, or the routing control you want across the multiple region, then that's the protocol. Or in other words, we are telling that it's a protocol for internet. It's a highly robust protocol, and it has so many tuning options, it has so many attributes, so we can tune it. And that's the thing. So it says advanced vector protocol with high level of tunability that can go across the regions. It is a type of application protocol. And the final point about this is that it can interact, or it can hold, actually it can hold a big amount of a routing database or routing table. Okay. Defined by the AS path, we know that autonomous system to autonomous system, it has its reachability. It is a distance vector protocol. It has the autonomous system number defined here. You can see from 1 to 65K. Few of the numbers are private and reserved. Nowadays, we have dotted notations as well for the BGP. Now, here you can see that why you want to use BGP. So when you have multiple connection exist to external autonomous system, means you have multiple exit, or you have multiple ISP connected with you. Either those multiple connections with the same carrier or provider but connect via routing policy. The existing routing equipment can handle the additional demands. So it is highly tunable. So if you want to do some sort of preference, path preference, some sort of load balancing, etc., etc., so those things are achievable with help of BGP tuning capabilities. Okay. Now, one very important point here is that BGP true benefit is to controlling how traffic enters the local AS, local autonomous system, rather than how traffic exit from it. So the true benefit is that how you are controlling the traffic when it is coming to you, when it is coming to local AS. Now we can have two type of neighbor. We can have iBGP, or we can have eBGP, exterior and interior BGP. iBGP means within the autonomous system. So in this diagram, router B, C, and D, they are iBGP peer, or they can be iBGP peer. And then different autonomous systems like AS 100, 200, 300, they can be eBGP, exterior BGP peers. Now we have options that what type of IBGP relationship I want. Do we have full mesh, or what other tuning options we have? We'll go and check later on that we have multiple options when we are talking about the internal neighbor relationship or interior neighbor relationship. Generally, when we are creating the IBGP relationship, we should create fully meshed. Otherwise, there are some other options to uh, do the advertisement for the network that one IBGP peer is getting and advertising to other devices. Now, one device can have only can be part of one autonomous system, and if you want to make part of multiple, it will throw an error. We have the AD value fixed for eBGP. For eBGP, the AD value, the administrative distance is 20, and for iBGP, it is 200. Okay, so that means the eBGP routes are preferred than iBGP routes. So 20 versus 200, lower is better. That thing we know. Now the BGP peer messages, we have BGP peer messages. What type of messages we have? So we have open message, we have keep alive, we have update and notification. Now open means that I want to form the relationship with my neighbor, and here you can see that an open message is sent between peer to initiate the session. The open message has several parameters like version, local AS, BGP router ID. Then you have the keep alive. Keep alive is something like you are sending the keep alive message to your neighbor that you are alive or not. In BGP by default, it is sending that keep alive message after every 60 second. A 60 second into 3, that is 180 second, is the hold down timer. So after 3 keep alive message, if you are not getting response, that means your BGP neighbor is dead. You will mark this as a dead with help of notification message. So now this notification message is sent when there is a fatal error condition. If a notification message is sent, the BGP peer session is toned down or reset. Anyways, if your peer is down, that means you will send the notification peer is down. Then we have the update message that are used to exchange the route between the peers. Now here in BGP state machine, that is the finite state machine, we have some other messages as well. So what exactly this is, that when a BGP peer session is forming, at that time, if you go, suppose if I have two routers and I want to form the BGP neighbor relationship in between that, so you will find that they will exchange some sort of messages. Those are idle, connect, active, open send, open confirm, established. Correct? So idle means that it is initiating the BGP state. Then connect, that you are waiting for the remote peer. Active, that you are actively initiating the connection. Obviously this connection is TCP. Then open sent. Open sent means you have sent the open message. Once you send the open message, then BGP listen for a reply keep alive. So you have sent the message, you got the acknowledgement, that is open confirm, and then the finite state machine will establish the connection. Correct? So it's very easy. Idle, connect, active, open send, open confirm, and they establish. Now if peer is stuck in active state, the potential problem may be that maybe you have password mismatch, maybe ACL is blocking port number 179, maybe you have incorrect AX, maybe you have incorrect neighbor statement, and so on. So if it is stuck in the active state, that means it is not good. Correct? Then you have to troubleshoot and make this as a working. Now how we are going to configure it? We know that one router can be part of one BGP autonomous system. Go to the router BGP, and then the autonomous system. If it is a eBGP peer, remember, if it is a eBGP peer, they have the TTL value of 1. So they are always thinking that their next hop is, or their peer is one hop away. So in that case, you don't need to modify the TTL value. You don't need to modify anything, any other thing. Means router B of AS100 and router C of AS900, they have to give simple command router BGP neighbor and remote AS. That's it. Now if it is a IBGP pair, then you can go and you want to update the source. So for example, generally we are using a loopback as a router ID. So in case of IBGP neighbor relationship, you need this update source loopback command. Correct? And I'll come to that eBGP multi-hop option as well. Suppose if you have eBGP relationship and it is multiple hop away, then you can go and use the eBGP multi-hop. So for example, 200. So in this example, it is showing simply that suppose if you are using the loopback address instead of this physical address, if you are going to use the loopback address, that is again one hop away, then how you will form the relationship? So in that case, say for example, the router C is using the neighbor 1111, and we can see that who is 1111. Obviously this router B loopback address is 11111. So in that case, that will be hop away. For that we should go and use neighbor 111 EBGP multi-hop 2. So you should count how many hops away your peer is, and then you can use this multi EBGP multi-hop command. Finally, we can go and use the password with the neighbor command. So for that, we have the neighbor password, and so for example, Cisco. We have other option as well, that if we want to change the keep alive timer, we have discussed this about that the default keep alive is 60 seconds and 180 seconds is the hold down timer. But suppose if we want to use some aggressive timer, we can go and use timers BGP 30 and 90. And in that case, we can go and set the BGP timers. All right, so let's stop here, and in the next section, we'll perform the lab, whatever we have covered in this section. Now we have to perform the lab related to BGP. Here you can see in the diagram that I have router 1 in AS100. So AS100 and AS200 router and switch 105, they're going to form eBGP relationship, exterior BGP. And in between AS200, say for example switch 101 and 105, they are going to form IBGP relationship. Okay, so let's start the configuration for R1. If I go to R1, I can go and I can initiate the router BGP process. So for example, AS is 100. Then what is your neighbor? Now for neighbor, I can go and check the directly connected neighbor. So that is directly connected neighbor is this 10.1.1.1, 10.1.1.1.0.5. So he has the neighbor 10.1.1.1.1.0.5. And then what is the remote ACE? So we should go and give the remote ACE. Say for example 200 I'm going to configure. Then here if I go and check show IP BGP summary, you can see that state is idle, correct? So it has initiated, and if I go and do some debug IP BGP, what type of packets I want to debug. So for example, I don't want all, but if I can get events and monitor. So I can go here. Yeah, I can see some of the messages. So already we are monitoring over the screen. It's showing some of the events. If we debug IP BGP, just wanted to see the TCP number. So all address families and import in IPv4, keep alive, don't want that, out in, etc. Okay, if I do all, then it will be big output. Okay, now one other command we have. So here you can see that at least I am getting this message, active went to active to idle. It's tried to move from idle to active, but it is not. And then here you can see that you have the TCB. So if we go and check show TCP, TCB, and then enter, show TCP, and if you want to see the brief, you just wanted to see the open ports if you have, and if you have any other option related to that. So you have the TCP TCB. Actually that's the command. TCP TCB is the command, and if you know the TCB address, that will work. Anyways, so let's move on and go to the other side. Here I want to initiate the router BGP process 200, and then the neighbor is say 10.1.1.1, whose remote AS is 100. That's it. So now if I go here and if we see the packet here, you can see, let's stop the screen. So here you can see that you have the open, capability is open, and then a route phrase, then open, again active, went to open send to open confirm. These exchange we have actually checked in our session, and then you can see the neighbor is up. And now if you go and check the TCP TCB, so now you're getting this established session, and you have the address as well. And let me do let me undebug, and now you can see the output for this. You can see the port number is this, so local port is this, the foreign port is this. Great. So most of the information we are getting from here. All right, so now the eBGP relationship is up and running. Now what I want, that as per our diagram, I want to create iBGP relationship as well. So for that, I know that neighbor is say 101, 101, 101, 101, and whose remote AS is the same that I have. But since I am using the neighbor command, which is the loopback address, so I want to do the update source loopback 0, and I should check sure and interface loopback 0. So yeah, that's correct. Now I'll go to 101. So let's go there and let's do the configuration for this. First of all, let's enable the BGP 100 whose neighbor is 105, whose remote AS is the same that I have, and then the neighbor, this update source loopback 0. Now if you go to 103, we go to 105, you will get one message, show IP BGP summary, that you have two neighbor, both are up and running. So one is up and running, that you can see here, you have 0 prefixes, Srtt is up and running. Now if everything is okay and correct, in between 105 and 101, so 101 and 105, then they should form the BGP, but it is not. So let's quickly check the BGP configurations, show run section BGP. So here you can see that I am part of 200, and this is also part of 200. So here you can see that directly you can see that problem, that we should have correct configuration. This is part of 200, and now you can see that we are getting some sort of notification messages. We have seen that this is something when you have some error notification messages, we are getting some malform construct. And if you go here and you check the summary neighbor idle, like that it is coming. Let's go back and let's change the AS, and we'll come back to 10. All right, so let's complete the basic lab. Now here, if you go to 101, we can see that the BGP AS is wrong. So I will go and do the changes. We'll go and change this to 200, and then rest of the configurations are correct. All right, now once we done that, we can go and check the summary. You can see this is up and running. Likewise, if you go and check show IP BGP summary, that is up and running. All right, so now once we have this, what we can do, we can check other basic stuffs as well. Now, for example, that we are going to continue the lab, plus I'm going to add few topics more in the lab section. We'll go and check the BGP neighbors once we enable run the BGP. Then we'll go and check the BGP neighbor. Plus we have one concept related to BGP synchronization. What does it mean by BGP synchronization? Although our lab setup is different, but I'm going to take same type of structure that I have one device for eBGP and few devices for iBGP, and then already we have checked the iBGP and eBGP, how we are going to form these BGP tables. Now what is happening that once we have the neighbor table, then it will build the BGP table, and then we have the routing table. Correct, but one of the important table we have is the neighbor table. We have this command show IP BGP neighbor, where we can go and check the BGP neighbor details. If you want to check the specific detail to a specific neighbor, then you can go and use this command show IP BGP neighbor and the neighbor address. Next we have the BGP synchronization rule. Now this is important. What is happening that the general rule for BGP, or the golden rule for BGP, is that if your BGP is there inside the autonomous system or within the autonomous system, so you should enable iBGP rule, or you should do iBGP full mesh capability inside the autonomous system. Suppose if you do not do like this, so what will happen? Say for example, in this diagram, this AS wants to reach to this network. Now suppose if I have iBGP relationship here, so here I have obviously the eBGP, and here obviously we have the eBGP relationship. So the traffic or the update will come to B, and then B it can go to D, because remember in BGP the iBGP neighbor relationship, it is not mandatory that they should have physical connectivity. So these BGP relationship can form over non-connected interfaces as well. Okay, so that means that I can have the iBGP relationship in between B and D. Now then it will go and reach to E. Now at this point of time, the router C, he don't know about this network 10505 etc. 10500. Next time if the return traffic will go and hit to D, and again suppose if it will go to C, since C is not having the update related to 10500, or he don't know how to reach to 10500, he will be working as a black hole. He will start black holing the traffic. So what is the rule then? Then the rule here is that you should have eBGP relationship, should have iBGP relationship in between all the devices. Correct? And that's the rule you have. You should have this type of mesh rule or the topology, and that's the reason we are using uh, some sort of other technology like configuration or route reflection. Because say if you have so many devices within autonomous system, and if you go and turn on BGP, and if you do this full mesh iBGP relationship, then obviously the CPU, the core utilization, memory utilization will increase. So this is not the optimal design solution. This is not that all the routers could achieve this target, because obviously they have to think more, because they have more number of control packets to process. The same explanation here. What we can do for BGP synchronization, uh, the local AS is not a transit. So in which case you don't need, if your AS is transit, or all routers in the transit AS run IBGP and are fully meshed. Okay, so the question here is that when you don't need the synchronization rule, answer is when your AS is not working as a transit. Second, when you all the devices in the transit, they are running the IBGP rule. How you can disable the synchronization? The command is no synchronization, and you can see that 12.28T synchronization is disabled by default. So in latest code, the synchronization rule is disabled. All right. So let's stop here and we'll go back to our lab section, and whatever small and basic verification commands are there, first of all, we'll check that before moving further. Now we are going to perform the lab task. You can see in the diagram that we have AS100, we have AS200. Inside AS200, we have devices that are going to form the IBGP relationship, and in between AS100 and 200, we have the EBGP relationship. So let me quickly log into the devices. We are going to perform some of the tasks that we have covered already in the theoretical section. So let me quickly show you that what configuration I have over these devices, and obviously let's see the IP addresses as well over these devices. So if I send this script, you can see over switch 101 we have this IP. Let me show you this diagram as well. So here you can see the diagram and the IP schema. Router 1, that is inside AS100, having loopback 1111. All the switches, they have loopback as their name. So for example, here you can see the loopback IP, then the interface IP, then the interface IP. All right, so you can refer the diagram that we have, and as per our diagram, we have assigned the IP addresses to the interfaces. All right, now next thing that we should go and check the BGP neighbor. So I can go and check show IP BGP summary to all the devices. Now here I can see that as per our diagram, we have EBGP relationship and the IBGP relationship. Now, if we have this type of topology, still what you want that switch 103 and 105, although they are not directly connected, they are indirectly connected, they should form the neighbor relationship. In that case only they have the full mesh, correct? So suppose even I have the back-to-back connection here, although I don't have, but still I can go and form the neighbor relationship in between the 103 and 105, because underlay we have EIGRP up and running. So before doing that, you can see here that all the devices, they have their EBGP and IBGP relationship running on. EBGP in between R1 and 105. So 105, one interface having EBGP relationship, other one is having IBGP. Now suppose if you want to know detail about that particular neighbor, so what we can do, we can go and check show IP BGP neighbor. And first of all, let's see that in this neighbor command, let me see that what outputs you have. So you can go and simply check show IP BGP neighbor. Obviously it will show you all the neighbors. So here the neighbor ID is this, belonging to 100 as a autonomous system, the router ID, the establishment, what time the neighbor got established, what type of messages they have exchanged. Here you can see open, notification, update, keep alive, and route phrase. So like that we can get the details. Now, if I am very much specific to a certain neighbor, then I can go and run the neighbor command related to that particular neighbor. So I have one neighbor 10.1.1.1, and I can run and I can verify that. Okay. So what I will do first of all, that I want to show you that we can form the IBGP relationship in between 105 and 103. So let's do that. I'm already inside 105. I can go here and router BGP 200. I have my neighbor, for example, 103, and whose remote is the same. Then for this neighbor, I can go and use update source loopback 0. Now again, I will go to the 103 and we can run the same command. Then we have the neighbor, say 105, 105, 105, 105, and the remote is the same, and then the neighbor update source is loopback 0. Alright, so we can see here now show IP BGP summary that we have one new neighbor added. So not only my directly connected neighbor, but my indirectly connected neighbor is also there. That's the true power we have with the BGP, because this is working as a overlay type of protocol. Alright, so once we have all this information, then what I want, so I want to have a, so for example in router 1 and 105, if you go to router 105 and you want to put the password, suppose if I go to neighbor, say neighbor 10111, and you can give the password the Cisco. So if you put password from one side, other side also you should go and check the password, router BGP 100, and just to show you that it will take some time because we know that keep alive is sending after every 60 seconds and the hold down timer is 180 seconds. So it will take some time to tear down the neighbor relationship. Still your neighbor is up and running, because BGP is meant to be slow protocol due to various reasons. So if you wait, it will take some time, because one side your neighbor having the password, other side we don't have the password. So I'll wait till the timer will expire, and then I can come back here and I can set the password. Meanwhile, we'll go and check the other option. So we have timer option as well. So for example, I can go here to the router process and then I can check the timers for BGP. Oops, timers, BGP, and then keep alive. I can give 30 and then hold down. Suppose if I 10 and 30, keep alive 10 and hold down if I give 30. That means for all the neighbors it is true. Now suppose if you are specific and you want to change the timer for a specific neighbor, so for example 105, 105, 105, 105, then also you can do that. So where we can go and check the timers here, you can see so many options we have. So for example 20 and 60. So it is telling that you should go and specify the keep alive, say for example 20, and the hold down is 60. as a peer group, so then it will take that command. We can check later on about the peer group as well, so we can leave it, but yeah, we have option that we can go and specify over the uh, per neighbor as well. Okay, so let's quickly see this BGP configuration. So here I have the neighbor with some timer, and then if I go here and check, and we can go and check show IP BGP neighbor 10.1.1.1. So here you can see that we have the neighbor established time. It is showing that what is the hold timer and the keep alive. Although if you go here and check show IP BGP neighbor 105, and what is my neighbor, that is 10.1.1.105, and here you can see that still is this because maybe the command that we have run is okay. So here you can see the timers and the neighbor command. When we are running this neighbor command earlier, so let me show you that we are getting some error because that was not my neighbor. So that's the reason it was throwing an error, correct? Because my actual neighbor is 10 11110 not 105.105.105. So what I'll do now, I can go here and I can do this neighbor, and then 10.11.105 timers I can specify set 10 and 30, and that's it. All right, we'll go here as well, and I can go here router BGP 200, neighbor is 10.111, timers are 10, 30, and then we can go and check show IP BGP summary clear IP BGP say star. I'm clearing the BGP table, and now if we go and check the neighbor table, so let's go and check the summary. Now you can see that after clearing that, we have the authentication issue because we haven't put the password for one side, and here you can see the password issue is there. So I should go and show this neighbor and with the password. So I can go here and give the password as Cisco. Once I do that, you'll see that it will get converged and the neighbor will come back up. Now it is up. So we know that in BGP, first of all, it will form the neighbor table, then it will go and form the BGP table, then it will go and form the routing table, or those things will go and get added inside the routing table. Okay, so let's stop here, and next section we'll discuss more about all these behaviors. Next topic we have BGP route reflectors configuration and the peer group. Now what is happening in case of IBGP relationship is that whenever IBGP peers, they are getting the update from outside. So what they are doing, they are assuming that all the neighbors, either it is physically directly connected or it's not physically connected, they assume to be in full mesh. Now, if they are in the full mesh, then all the IBGP neighbors will send the update to everyone. Otherwise, there are chances that, say for example, router D will get the update, he will send to A, but A will not send to the other router because he will think that update will come from some other way that is again connected in full mesh. Now, while we are doing the approach of IBGP full mesh behavior or approach, so in that case, what we are doing that we are using some more bandwidth. We are consuming actually more bandwidth, more processing and cycles. So why? Because we have more number of BGP neighbors, correct? So if you have more number of neighbors, more number of control packets will send and receive to maintain that BGP state or BGP neighbor tables, correct? So that's one of the thing that what we can do, that we can use route reflector. So the idea behind this is that any of the router which is there who is working as a symmetrical device. Now what does it mean by symmetrical device? Symmetrical device means he is approachable or reachable to most of the other routers. So that particular device, we are making this as a route reflector. So when he get the update, now his responsibility is to give the update to all the other devices. And this approach actually has been taken inside software defined networking as well. How? So if you go and check software defined networking, you will find that we have clause architecture. We have leaf spine and leaf. And again, suppose if you have more spines, spine 1 and spine 2. So all the leaves are assumed to be connected with the spines. So what does it mean? It means that behind the scene, all these spines, they are working as a route reflector. So at the moment they are getting the update, now their responsibility to send the update to all the leaves. And that's the fundamental here in route reflector. At the moment he will get the update, so suppose if I make him as a route reflector, now his responsibility is to give the update to all the other IBGP neighbors. Rather than we have the full mesh topology, route reflector will reduce the number of code, reduce the number of IBGP pairs, will drastically increase the CPU and the memory performance. Correct? Now, not only the route reflector is the technique, we have other technique as well. We will see in the next slide. So how you can do this? Here you can see I can go to router 1 and I can tell router 1 that your router B and D are the route reflector client. So the configuration is very easy. Just use neighbor, the route neighbor ID, remote AS, neighbor ID, route reflector client. That's it. Now we have other approach as well. We can use BGP confederation to come to the same place or to achieve same target. Although the configuration look like little bit tricky, but the concept behind this is to reduce the number of IBGP pair, and inside IBGP you can use EBGP type of behavior. So what is happening in this case, you can see in the diagram that you have main autonomous system. These main autonomous system, they will form the EBGP relationship. Inside this main autonomous system, I have sub autonomous system who is responsible, and you can think that who is child of the main autonomous system. So he is the child. But now since you have two different autonomous system, so 777 and 888, they will form EBGP type of relationship. So they will send and receive the updates because there is no problem with the EBGP relationship. We have this issue only with IBGP relationship. So inside the autonomous system, although it is showing only one device, but you may have multiple devices inside one AS. So they can exchange their neighbor tables, or they can exchange their updates within the across the autonomous system, correct? So that's one concept, that you can see that you have different autonomous system inside same autonomous system. But what about AS500? When AS500 will see, he can see only AS300. He will not see the inside autonomous system, and that's the key here. Now the configuration is again straightforward, but it's like a little bit tricky. So first of all, this 888 is part of 300, 777 is part of again 300. Uh, so here you can see that router BGP configuration identifier this, then router configuration peer is this, then neighbor this, neighbor this. So you can see this configuration. If you go and check, you'll find that inside the configuration you have to think that these are the eBGP peers, and inside that these devices can peer, but they are part of the main group, that is 300. So your 888 and 777, they are part of the identifier 300. Again, you can see that BGP configuration peer is 77. So for him, he is the peer. This is the configuration for router B. Likewise, if you go and do the configuration for router A, you have to follow the same step. So you can see that step number 1, step number 2, step number 3, and then this is the same one that we used to use, correct? And then finally, the remote AS that he has is the having the AS 500. Okay, so these are the steps that we should follow, and you can go and check all these steps. You can refer the diagram, and then you can have all these steps as well. So let me quickly go back and let me quickly show you that if you are here you can see router B is a part of eBGP. It's part of configuration group as well. So that's why you have this last line. Apart from that, you have these 4 lines. So it's tricky because see that he is part of main AS. He is doing the BGP with this AS, and he is doing the eBGP relationship. Now all these commands have been configured here, and you can understand all these steps. Now for outside device, the configuration will be straightforward, and what we have discussed earlier, neighbor and the remote AS, that's it. All right, so final topic for this session is the peer group. Why you want to use the peer group? Again, to increase the performance of BGP, to reduce the number of line, to reduce or to optimize the processor and the memory usage, you can use peer group. So suppose I have 10 different neighbors, and all those neighbors has 6 command that is common. So what commands will be common? So for example, remote AS, update source, route reflector client. These things are common. And I have 10, for example, I have 10 devices. So 10 into 3, that means 30 configurational lines you can put inside the peer group. So next, what you have to do, you don't have to write all these codes. Rather than you can go and use a neighbor 1111, for example, peer group, my group. Neighbor 2222, peer group, my group. That's it. Neighbor 333, that's it. So you are saving a good amount of code, and apart from that, it is effectively to optimize the process and the CPU cycles. Okay, all right. So what I'm going to do in the next lab, that I will perform the task related to route reflector, and again we can go ahead and we can add the peer group as well. There are very less number of people that we know that they are using configuration. So, and even in this syllabus, it is not required that you do the lab or do the CLI configuration for configuration, but just for understanding purpose, I have given this notes and you can refer this. Okay, even in our CCNP course, it is not required to do the CLI configuration, at least for this section 3.2 for route reflector. But for future perspective, to understand more about BGP and their coding and stuffs, we should understand the at least the route reflection and the peer group. Now we have the lab related to route reflector client and the peer group. Here you can see the topology diagram. We have R1 router and then switch 105, 101, 103. They are inside one AS. Already we have done the setup, like we have IGP as EIGRP running in AS200, and then we have eBGP relationship between AS200 and 100. So what I'll do here, that we have one loop back, you know that we have loop back here in AS100, and that loop back I will go and advertise. So for example, I can go to my BGP 100 and we have various methodology to advertise a network. One of the method is to use the network command and then give the exact mask. Now once we advertise this, I can go and verify this inside the peer router. So I can go and check show IP BGP, and here you can see that I am receiving this route. The next hop is 10.11111. The AS path is 100. Now let's see if you check the diagram. So 111 loop back is coming to this device, this switch actually 105. Then let's see that how it is reaching to 101 and 103. So the same command show IP BGP, that's the BGP table. I can go and check to 101. 101 again, it is coming via this next hop. It will show like this only because eBGP next hop are not getting changed automatically. We have to run a command, so they will change the next hop. Now finally 103. Again, you can see that next hop is this. Now one thing I want to highlight here is that when you go and check the output in 105, you can see that you have the asterisk and the greater than sign. This asterisk means that it's a valid, and this greater than sign is best. So it's a valid best route that it is coming to 105. But if we go and check 101, so it is not telling that this is the best. Even if again further down the line, if you go to 103, it is telling that it's not the best route. That's the one thing. Second thing, that since we have created full mesh IBGP relationship, so if I go here and check show IP BGP summary, so we have the relationship with switch 105 as well. So what does it mean? If I go and check the BGP configuration, and if I go and remove this configuration, that is, I don't want the neighbor relationship form with this switch 105, and then obviously I should go and remove these subsequent lines. Now if we go and check the BGP, here it is. Now what I can do here, I can go and clear the BGP. Since this is a lab, so I can use IP BGP star, but be very careful if you're running this command. There are chances that thousands of route will get refreshed. So that's the reason we are using keyword like soft. So this is soft reconfig inbound and outbound, and inbound or outbound, like that we are using those keywords. All right. So now if I go and check show IP BGP summary, and we can see now that we have only one neighbor. And if we go and check the show IP BGP, that's the BGP table. So let me go and run that command show IP BGP. I want to check the BGP table. Now you can see this BGP table is gone. Why? Because that's the nature that the BGP has. So the routes coming to this, because they are directly eBGP peers, and then he will advertise to this. But 101 will not advertise those routes to the other devices. Okay, and that's a loop prevention mechanism we have inside BGP until unless they have in full mesh or route reflection or sub AS or this configuration. So now what we'll do, that will go ahead and make 101 as a route reflector. So let's go and do the configuration for 101. All right, so we'll go here to 101. We are inside 101. I can go to router BGP 100. Then what neighbor we have? The AS is 200 for 101. So we have neighbor. Let's check the neighbor. We have this command. We can go and check. So I have 103 and 105 as my neighbors. So I can go to the neighbor, and then we can go and use as a route reflection client. So both for 103 and 105, I want to make this as a route reflection client. So 103 I have made it. Now if I go to 103 and if I go and check show IP BGP, still you can see that they are not learning the route that is coming from 105. So what I can do, that again I will go and make this neighbor as a route reflection client. And now if you go here to 103, that's the bottom one, you will start getting the update from router number 1. So it will be like it is coming from here, and then it will go here. Since he is the route reflector client, he will reflect the route to 103. And same is true. If the routes are coming in this direction, he is getting the routes, then he will go and reflect the routes to 105. So both ways you will find that it is valid. All right, so let's see this, because BGP updates, they are taking some time to get update. It's taking some time. Let me quickly see this. Do I have the relationship with 101? It's there. I'll go and do clear IP BGP star. Now it is showing idle because now it is up. So I have my table that is up. Now I told you one important thing, that whenever we are getting the routes, what is happening in case of IBGP? So you got the route, you know who is the next hop. He got the route, and his next hop should be this device, correct? From where I am getting the route. But if you see it, you will find that the next hop is still 10.1.1.1.1. That's the problem we have with the uh, IBGP relationship. So what we can do here, we can go to 101 and we can make, say, neighbor. So who is his neighbor? Say 103. So neighbor, before doing that, let me quickly show you this, if all the BGP configuration is correct. It's correct. So I can go to neighbor. Hey, this is the neighbor, and you know your next hop is me. Okay, and likewise this router, I can tell router BGP 200 neighbor 101, your next hop is me. So this guy, your next hop is me. Now if you do this thing, if you go to 101 and if you check show IP BGP, you will see that first of all I need the best route here. Okay, so here you can see that 105, he is telling 101 that next hop is me. Hey neighbor, this is my neighbor, your next hop is me. So that means if you go here and check, this should change. See, it's got changed. It took some time, but it got changed. Now if you go 103, you are getting the updates. Even we don't need this command here to 101. If I go to 101 and if I remove this command 200, that is no neighbor 103, I'm your next hop self. Before pressing enter, if you go here to 103, who is the next hop it is showing? It is showing that its next hop is 105. That's okay for this point of time. So I can go to 101 and I can delete this. We can clear the routes as well, but ultimately we can see here that the target is achieved. So without having IBGP relationship, with help of route reflector client, 103 is able to get the routes from the EBGP from other AS whose actual AS is 100. Great. Now the second thing that we have to do is to do the configuration related to BGP peer group. So if you go again and check the configuration, although I have one command, I have two commands, very less lines of configuration I have here. But if I go to 103 and sorry, if I go to 101 and 105, so if I go here show run section BGP, I have more number of configurations, so that I can reduce. So how we can do? We can create the peer group. I can go to 200. I can make neighbor, and then you can see the name of the peer group. Say BGP peer group BPG. That's just the name. Then what I can do here, that I can go and give the peer group. That's it. Now next, what we can do, say neighbor BPG, and what's the remote? Say remote AS 200. Actually, I'm making this just for the IBGP relationship, so that's why I'm using this. Then again, I can go to neighbor BPG, update source loopback 0. Then again, I can go and check the other commands. So let me quickly go and check show run section BGP. So I have taken this command. I have taken update source loopback command. Then I have one more command, that is route reflector client. So for that also I can use it. So neighbor m say BPG and then route reflector client. All right. So once we have these commands, obviously I'll go ahead and I will remove these configuration. This is not required now. So once I have these, then I can do neighbor, say this, and peer group is BPG, then neighbor, say 105, and the peer group is BPG, correct? And if we go and check the, oops, so for that, if we go and check the configuration, where we are, I think I lose this. Run section BGP. All right. So here you can see that now I have the peer group, and then neighbors are mapped with the peer group. Correct? Even I don't need this command. Say I should remove this, is not required, taken care by peer group, and this is not required, taken care by peer group. Now think that suppose if you have more number of IBGP table or relationship, still what will increase? Only this line, correct? So now you have template where at least your 3 configuration lines are constant. That will be recalled by all these peer groups, correct? So now what I can do, I can go ahead and check show run section BGP, and I have an IBGP command. So what I can do here that I can copy and paste. So for example, these 4 lines here, and then my neighbor is this 103. Actually I don't want because we have removed that, and this peer group is a PPG. But suppose if you have more number of uh, peers or the neighbors, then you can go and do these commands, correct? Then obviously I can go and do no for this, and finally no for, oops, the neighbor command that we have with 101. We can go and check show run section BGP. We can go and check show IP BGP summary. Seems one is gone. Show run section BGP. So here you can see that I should have that neighbor command that is not showing here. So finally what I can do, I can go to neighbor, say 101, 101, 101, 101, and then the peer group is say BPG, and we can check to show run section BPG, that is BGP. Alright, so here you can see that you have the template, and then you're calling that template with this command, and our BGP is up and running. So this is the way that we can do the peer group. This is the way that we can go and do the configuration for the route reflector as well. We have very important topic, BGP best path selection. We know that BGP has a long list of attribute, and with help of these attributes, BGP used to uh, provide best path. So what are those? Let's understand those first, and then next we have series of lab, and we'll test all these attributes, at least the important path selection attributes in the lab section. So how BGP providing the best path selection criteria? BGP contains multiple routes to the same destination. It compares the routes in pair, starting with the newest entry and working towards the oldest. Now, if you see that how it is going to determine, so suppose if I have uh, multiple paths to reach a certain destination, and then I'm going to check, means BGP is going to check criteria A, B, C, D, etc. in order to provide, okay, if this criteria, so I have to go via this path. If this criteria, I have to use this. If this criteria, I have to use this, like that. So this is in the order. First of all, it will go and check the highest weight. Then it will go and check the highest local preference. Now the weight and local preference we'll see in the lab section as well. We have following lab with that. You'll find that weight and local preference, at least local preference, is one of the attributes that is mostly used. Now both the weight and local preference, they are dictating the best outbound path. So what we are doing, we are applying the weight and local preference, um, say attribute values or these values in the inward direction. So we are going to apply to the inward direction. That's the key actually. So where you're going to apply these and to whom he is going to affect. So we are going to apply in the inward direction, inbound, and then they are going to dictate the outbound path. So that's the important thing that I want to cover. Now here you can see the order. So let me go back. Weight, local preference, locally originated route. We know that if it's local originated route, their next hop will be 0000. That means it's the self-originated route. Then the AS path. Now AS path and MED, the metric value, both are again important. So remember, weight plus local preference, both are very much similar. Then AS path and MED. These are the attributes that is used more and more in the production network. So AS path, we know that BGP is dealing with, or BGP is a distance vector protocol, and as per the AS, so you think that one autonomous system has a router for a moment, and then if you have to cross more number of AS or more number of hops or router, that means it is not preferred. So if I am reaching to certain destination with 3 AS versus 1 AS, that means that 1 AS means via the path I am reaching with 1 AS, that will be the preferred. So shorter AS will be preferred. Then the origin code in the number, so IGP over EGP over unknown. Then MED, again I told you that this AS path and lowest MED, both are very much similar, and even we have lab as well for these. Then BGP route type, eBGP over IBGP, eBGP will win. Then the age of the route, who is the oldest is preferred. Then the router ID, who has the lowest BGP router ID. Then the peer address, which router originate from the router with the lowest IP. So everywhere you will see that except weight and local preference where the criteria is high. Apart from that, AS, MED, then age, everything is lowest or the oldest. Correct? All right. So here you can see that weight and local preference are applied inbound, dictating the outbound. That's the key actually. So these 3-4 lines are the key. Inbound dictating outbound path, and AS and mid are applied outbound dictating inbound. So what does it mean? So at least in case of MED, and let me draw here. So suppose you have ISP1, ISP2, and then you have your local AS. Now in case of MED and AS path, if you want to prefer ISP1 versus ISP2, so then you will go and apply the either MED or the AS path, AS prepend. That's the key. Because you have to choose, because you are choosing the outbound, so you have one subnet XXXX and you want to prefer either ISP1 or 2, you can use this method. Now when we are going to use the local path, so in that case, say when you are going to dictate the outbound path, so suppose if you have two exit and you want to choose one exit via versus second exit, so that in that case you are going to apply the either wait or local preference. Obviously I'll go and clarify these terms in the upcoming lab, and we are going to check the scenarios as well. So here you can see that we have one situation, one scenario, that you have one route, say for example 192.1.1.0, that router D is also getting, router B is also getting. Now what I want, that I want that route should come or should preferred via router B. So in that case what we can do, that we can go to router A, say router A, and then we can give neighbor and then the wait command. That's the one way. The other way, nice way, is that we can go and use the route map. So then what we can do, we can create one ACL or prefix list or access list, and then we can create the route map. We can match the prefix list, and then we can set the weight, and then we can go and apply to the neighbor. So here you can see the direction. Direction is in for the outbound traffic, correct? So to reach this network, I have applied weight to my neighbor, and that neighbor, so that means router A will prefer B to get these routes, correct? Again, you have the local preference. In local preference, the same thing, only the way that we are going to do the coding will change. And here you can see that um, we are going to apply now. Local preference has little bit difference with weight. What is that difference? So unlike weight attribute, local preference is passed on to IBGP peers and sending updates. Local preference inform IBGP router how to exit the ACE if multiple path exist. So now what we can do, that local preference even I can go and apply to these guys. So suppose local preference here, if I put 200, and if I put local preference 100 here, obviously this path will be preferred, correct? So that's the use of local preference. And here you can see that we have the example, but here we'll check the route map way of applying the local preference. Again, you can see here the direction is inbound, so here we are at router D, or maybe at router B also, there's no problem. So what we are doing for router B and D, here you can see that B and D, lower is better. So here if B is 200 and D is 300, obviously the traffic will come via this B, because his local preference is 200. Likewise, you can see here in the policy, we can create the policy for B and D as well in the upcoming lab section. So I have this route, same way we have created the route map and we have applied it. I'm matching this, and then I'm setting the local preference as so for example 300, okay, and then I'm applying in so here you can see that is 1.2, that's my neighbor. Then I'm applying in, likewise I will apply with local preference of 200 to router B. So obviously router B will prefer. Okay, so here you can see there's difference between wait and local preference. The local preference is passed on IBGP peers when sending the update. So that's actually the main reason you will not find use of wait more and more, because anyway the wait is Cisco proprietary as well. So mostly you will find the use case with local preference. The same thing we can do with wait with local preference, so better use local preference. And in the lab section, so we have the lab section. In the upcoming session, I will go and perform this task of wait and then local preference, and we'll see that how we are applying the in rule to affect the outbound traffic. Correct? All right, so let's stop here. We'll start the lab now. Let us perform the lab task. In the lab, what we are going to do, first of all, I'm going to show you the entire setup that we have. Here you can see that we have 4 different autonomous systems, say AS50, then AS100, AS900, and AS200. Now from AS200, you can see the iOS, the router is router 7, for example. There I have one loopback, and that loopback is loopback 7777. 7.7.7.7, and that particular network I am advertising with BGP network command. So they will go and reach to AS 900, and then it will go and reach to AS 100. Inside AS 100, it will go and reach to router number 2. So before showing a complete path and how it is reaching, let me quickly go and show you the uh, configuration that we have. So if I go here and check the configuration, show run section BGP, here you can see the configuration, and these IPs that you're seeing over the interface, these IP addresses you can refer the topology diagram as well. So router 1, here you can see the router 1 has very minimum configuration. It has one interface, and then we are advertising one of the network. Then router number 2, you can see the BGP configuration, where we are running EIGRP inside the AS, and then we have 2 neighbor peer command, router 3 and router 4, and obviously we have one eBGP with router 1. Likewise, the configuration, BGP configuration for router 3. So let me do this. So here you can see the configuration for router 3. Router 3 in the diagram, you can see that it has eBGP relationship as well. So on the top you can see eBGP relationship with AS900. Likewise, we have router 4 configuration for BGP. Then we have BGP configuration for router 5, and then you can see router 6 and 7 as well. This is router 6 configuration, and finally router 7. Now what we have done, you can see that inside router 7, we are advertising one of the loopback with the BGP network command, and then we are going and seeing that how it is reaching to router number 2. So if I go and check show IP BGP, first of all I'll show the BGP table. So clearly you can see this AS is getting prepended. So the originator for that is AS200. So here you can see this 777. So the originator, then next is 900, and then it is reaching to AS100. Now here you can see that you have valid and best path, and who is the valid and best path? So it is telling 172.1.7. Now if you go here and check 172.1.7, so this is the best path. Via this it is going and reaching here, although you have the alternate path as well, that is 172.16. So 172.16, that's only the star we have, and the star means valid. So that means if I go and check show IP route for this particular network, and let's see. So here you can see that it is coming via 172.171.2, and they have learned this is the router tag and how many hops, etc. Correct? So it is learning via this. So what I want at this point of time, that it should go and learn via this particular neighbor, not via this neighbor. Other thing that we can see here, that is this changing the next hop? So if I go here and check the diagram, so obviously whenever it will go and move to the eBGP, then it will change the next hop, correct? So from here, either from router 3 or router 4, it will go and reach to router number 2. But suppose behind router 2, you have one other router in the same AS. So at that point of time, you can see some differences. So you have to do some next hop self command, correct? So suppose if I go to router number 1, and if I check show IP BGP, now since this is the eBGP relationship, so for this route, who is the next hop? So he is saying that his next hop is changing, that's okay. But if router 1 will be also inside AS100, then it will be the problem. Anyway, so what is our target here? We want to have, or we want to learn this particular route from this next hop, or from this peer. So let's use the wait attribute. Before that, I want to create IP prefix list. So IP prefix list, say loopback 777 is the name of my network. Even I can go and give the a sequence number, and then I can use this if I want. So sequence 10, and then permit 7777/32. Alright, then I'll go and create one route map. Say my wait permit 10. What I want here, I want to match. So let's see, match the, let's see what is the option we have. So match the IP address, and that is the prefix list. What is the prefix list we have created? This loop 777. All right. Now what I want to do with this, I want to set the wait, say for example 8989. Then I will give one default statement for route map where I will not match anything, say for example 100. We can go and check the route map configuration. Say route map. So what we have done, that we created one IP prefix list. We have matched with the route map. Then we have set the width for that. Now we should go and apply this to the neighbor. And which neighbor you want to apply? So you want to apply this with 172.161. Sorry, we want to apply with this neighbor, that is 10.1.1.2. So I'll go and apply with say 10.1.1.2. And what's the route map we have? The route map name is my TT. Because this is wait, so I want to apply in the in direction. So here you can see that it is telling that Okay, so this is not the configuration that we have done. If you go and check, we have created the neighbor with the loopback, correct? So we should apply the loopback statement. So here you can see, so I should go neighbor, and the neighbor is router number 4, that is 444, and then the route map, and that will be in the my width in the in direction. All right, now if you go and check show IP BGP, now clearly you can see that uh, the next hop is not get changed. So for example, that's a problem actually with IBGP, and that's just to prevent from the loop. So that's a loop prevention mechanism. So what does it mean? That here you can see when the routes are coming, say 77777, and when it is entering to this AS, they are putting their uh, IP as a next hop. When it reaches here, it should put these IPs as a next hop first of all, correct? So we should go and do a small changes in the configuration. So let me go and do the small change in the configuration. So let's do this. I can go to router number 3, say router BGP 100. I can tell neighbor 222222222 next hop self, and likewise we can go to router number 4 as well, and then we can tell router BGP 100 neighbor is next hop self. Now if you go here and check show IP BGP, you will see that next hop will get changed, otherwise I'll force this BGP to converge. Here you can see at least next hop is not get changed, but the priority, I can see that wait update has been done and it is going via the uh, bottom router. So here you can see that wait has done his effect, but it should change the next hop as well, and now you can see that they have changed the next hop. That's the correct actually. Wait has been changed, next hop has been changed. So this is the way, this is the use case with the wait. Now what we want here, that instead of wait, the same thing I want to do with the local preference. So first of all, I'll go to router BGP 100 and I'll remove this command. I don't want this wait, for example. So we don't need this wait, and next what we want, that we want to use the local preference. So for local preference, let's go and check the route map as well. Route map, because now for local preference I want to create one route map as well. Now this time I don't want to apply this policy to R2. Rather than I want to apply this policy to R3 and R4. So how the local preference is working, that they are much more intuitive than wait, and their attributes can flow inside the AS. That's the key we have. So what we can do here, first of all we'll see that how the 777 is getting reached to router number 2. Then here over router 3 I will set the local preference as 300, and router number 4 I'll set the local preference as 150, because I want that it should go and prefer this direction. Suppose what we can do that I'll go and create one more network here. So for example, 88888 as well. Already we have 7777. I'll create one more 8888. So 77777, for example, should go in this direction, and 888888 should go in this direction. So how we can do that? Okay, so let's think that and let's try to perform that task. All right, so the target here is that 7 should go via router 3 and 8888 should go via router 4. So primary, secondary, secondary, primary, like that. So what I try to explain here, let me go and show you here. First of all, I go to router number 7 and I'll create one more loopback and I'll advertise that as well. So I can go here and create say loopback 8, IP address 88888, and then let's go to router BGP 200, and then we have the network 888 with the mask of 255. Now if I go here and check this same BGP route here, so now you can see that 8 is also coming and getting here. Now it is coming 3 and 3. So both the update, they are coming via router 3 that we don't want. For 7, so for example, I want that it should come via router 3, backup will be router 4, but 8 should come via 4 and 3. Okay, so primary, secondary, and secondary, primary, like that we want to use. What we can do here, that we can go to now to router number 3 and we can create the prefix list first. So I'll go and create IP prefix list, say loop 7777, sequence say 10, permit 777732, and then I want to create one more loopback because the deterministic criteria, I want to put some condition inside the route map. So I can go and create the network statements like this. Okay, so I have two different IP prefix list, and even I can copy and paste the same configuration to 4 as well, just to save our bandwidth. Alright, so once we are here, then we should go and create the route map. Say local pref, what I want to this route map. Say permit 10, match IP address, and that is the prefix list 777. For this, I want to set the local preference. So for example, 8888. Okay. Then I'll go to the other statement, that is, say for example 20, and then I'll go and match the address, that is this guy here, and then I want to set the local preference a little less. So for example 88. Okay, and then I have another default route map like this. All right, so here you can see the strategy for 777. We have the higher local preference. Likewise, I'll go and I'll create one more route map here to router number 4, where I want to match the 888. So statement number 1, I'll go and match the IP address, that is 888, and then I'll set the local preference, say for example 9999, that is very high, and then I can go to the other statement where I want to match the address, that is this guy, and then I can set the local preference 99. So the idea behind this is that for one of the prefix lists, say for example for 888, what is the local preference? Very high. And here for 888, what is the local preference? Very low. So just the condition. For 7 we have high, for 777 we have high local preference, for 8888 we have low local preference, here the reverse, correct? Now we should go and apply this to the neighbor. So let me see that who is the neighbor. It's the neighbor IP, router BGP 100. My neighbor is this guy here, and then the route map is local preference in direction, correct? Now here also I can go and check router BGP 100. My neighbor is this guy, and the route map that we are going to use is the local pref is the name and then the inward direction. All right, now if I go here, so for 888 the 4444 should be the best path. So here you can see, now we can see clearly that they are losing the backup. So here you can see that now the routes are converging and they are getting set with the correct local preference. But still, if you want to clear the IP BGP star, you can go and do that, and then you can go and check show IP BGP. So it will take some time, but it will build the route, and clearly whatever our target was, we are able to achieve that target, correct? So this is the way that we can go and apply the local preference. We have completed section 1, that was 35% related to layer 3 technologies. In section 2, we have to understand VPN technologies, and that weightage you can see is 20% highlighted here. Now inside VPN technologies, we have to understand two major technology. One is MPLS, other one is DMVPN. So what I will do, first of all, we'll go and learn MPLS technologies, and then we will go and learn about DMVPN technology. So let's start MPLS technology first. So what is MPLS? MPLS is multi-protocol label switching. So what does it mean? Is it mean that while routers, they are forwarding packets, they are using switching technology? Or do we have a separate routing table, and do we have different or separate forwarding table? So we are going to understand about MPLS, label switching. Okay. Now, interesting thing here is this, that MPLS is industry propriety, and later on in this section, I will show you that there is one terminology called Cisco Express Forwarding, that is the CIF. So the idea behind either it is MPLS or Cisco Express Forwarding. So this was Cisco proprietary, and MPLS is industry standard. Obviously, the MPLS taken from Cisco SIF technology, means Cisco was using earlier, and then you can think as enhanced version we are using or modified version we are using inside MPLS. So think like this, suppose if you have multiple routers, so many routers that ISPs have, and while you are running any type of protocol, any type of interior or exterior protocol, the problem here when these routers, they are taking the router decision or routing decision, they have to scan, they have to check their routing database, whatever entries they have in their routing database. So maybe they have 5,000 entries, they have to go and scan 5,000 entries, and then they have to take the best out of it. So doing this, what will happen that not only the routing process, so obviously the routers, they will use their routing process. That means the software cycles will use. Apart from that, they have to run that or rerun that algorithms all the time related to routing. So that cycle will also get used. So that means in turn that time is there, means time lagging will be there because you are taking the decision based on the routing, or all the time you are taking the decision. Suppose if you are building or rerouting the traffic from one location to other location. Okay. Now, this term has been eliminated from this routing decision, and the solution we have in terms of MPLS. So what MPLS is doing is that instead of building the table, instead of building the decision table, instead instead of taking the decision based of routing entries, they are taking the decision based on labels. So suppose if you have 20-bit label, so all the routing entries that we have, and again, that is belonging to MPLS. So where you are using the MPLS network. So what does it mean? It means that suppose I have big routing infrastructure. In this big routing infrastructure, I'll go and enable label switching. So inside that, I have so many routers who understand, who are building their label tables, and according to that label, the routers, they are taking decision. But outside this, or maybe coming inside this, you do not have MPLS. Here you don't have MPLS, here you don't have MPLS. So that means at location 1 and at location 2, you are taking decision based on IP routing. So these may be customer network, these may be transit path, where the decision purely based on IP tables. But once you go and enable the MPLS for organization, suppose if you're ISP, so inside that organization, inside that specification, inside that private zone, you can think that the decision as being used with respect to labels. Correct. And again, labels can be imposed. And again, we'll see in upcoming sections, there are various parameters, things that we will learn in upcoming sections. So you can impose a label based on destination IP, source IP, QoS parameter, VPN destination, outgoing interfaces, layer 2 circuits. Okay. So this is the MPLS technology. Means first point is this, that it is taking a decision based on the labels. So that's why the software cycle or CPU process utilization will be less. Now, the other very important thing that is derived from Cisco Express Forwarding is this, that suppose if you have router, obviously you have a routing process, RP inside that. So first time the router is taking the decision, and then they are telling this information to the software process. Correct? So all the time, whenever the entry will come, it will not take the decision, although next time routing will not happen, next time switching will happen. Okay, so first time we have done the routing, next time we have done the switching. That's the core idea behind the MPLS. Okay, so what we are going to do in the next section, I will go and enable the MPLS inside few of the routers, and I will show you that how these labels look like, how the basic decision formation happening, and then we'll go and learn more and more about the MPLS labels and other technical stuffs. In this section, we are going to perform a small lab task, and we are going to understand about MPLS labels as well. As we know that MPLS is purely based on label switching. So in this section, in upcoming videos, we are going to dig deeper inside how the label switching working. Let's understand that what type of labels we have, means what are the fields we have inside the MPLS label. So here you can see that first of all, the label is of 20 bits, and I'm going to show you in the lab that these numerical means the labels are numerical, and how they look like, what's the range, etc. Then we have 3 bits experimental bits, and basically Cisco is using as a IP precedence for the cost markings. We have bottom of a stack as well. That means if you have multiple labels and this bottom of a stack bit set to 1, that means this is the last label in that marking. We have 8 bits of TTL, time to live, as well in this particular MPLS label field. Apart from that, you can see that for unicast packets, we have the hexadecimal number 8847 in the label, and for multicast packet, we have 8848 just to identify the packets. All right. So let me quickly go and show you the blog side where we have the basic lab. First of all, we'll do the basic lab, and then in the upcoming sections, I will go and cover more and more theories. So you can see that in my blog side, I have created chapters. Actually, total chapters you'll find 1 to 11. So let me go to the bottom. Let me show you how many are there. I'm going to cover each and everything, and I will show you the references as well. So while you are doing your study, you can go and find these important references. So starting with the basics, you will find the lab is also there, and the same lab as well I'm going to cover in the upcoming section. So let's just start with the first chapter. What is the agenda for MPLS chapter 1 in this section is just to understand 2 things. Question number 1 in form of question. So what are the command to enable MPLS to the routers? Then how to verify that the local label a router has chosen for a given network. Means you have to go and enable the MPLS, and how you can go and check the MPLS levels over that router. What are the CLI commands? So here you can see one of the lab topology. I'm going to use the same one in our lab as well. Let me use the pen here. So you can see here that you have router 1, router 2, router 3. Same, I'm going to take router 1, router 2, router 3, same type of network subnets and loopback as well. And I will also go and enable the OSPF inside this small network, and then we'll go and verify. So first of all, you have to go and enable MPLS IP. If you go and enable over the global, that means for all the interfaces, you are enabling the MPLS, but we can go over the certain interface and we can give this command MPLS IP. That means that these particular interfaces, so suppose R2, this fast Ethernet 00001, we want to enable this. So we can go to those interfaces, give the command MPLS IP, and this will be enabled. Once it is enabled, then we can go and verify certain CLI commands. Again, about LDP and labeling protocols, we are going to discuss in the upcoming section. More and more we'll understand about this. So let me quickly show you the basic commands, how to enable MPLS over the routers in the lab. Let's see the interfaces. So I can go here to router interface gig 0/1, and I can go and give MPLS IP, correct? Likewise, you can see in the diagram that router number 2, both the interfaces are part of MPLS. So I can simply go to the global mode and I can enable MPLS IP. Then I can go to router number 3. Router number 3, one of the interface having MPLS facing interface. You can see here the diagram in the blog. I can see router 1, router 2, and router 3. So once we have that enabled, then we can go to the router number 2 and run some verification commands. So I can type enter here. I can go and check show MPLS, and you can type question mark. You can see various options are there. LDP, and with it LDP, Let's see that what options we have. So you have the neighbor. You can go and check the neighbor. You can go and check the bindings as well. And basically we want to check the binding. So show MPLS LDP binding. And that binding we want to check for which loopback. So suppose I'm in router number 2, I want to check router number 1 and router number 3 loopbacks binding. So we can go here and we can see here binding say 111132. It's telling that lib not enable. Okay, so that means here you can see that I should go and run this lib. So this is the command that you can go and run MPLS IP and it should work, correct? But it is telling that lib is not enabled. Now, one very important thing here is that while you are enabling MPLS, you should have your routing, unicast routing protocol enable. So let's see that we should have, you can see I'm getting 111, I'm getting 333. That means my unicast routing is working. So I should have my MPLS working here. We can go and check gig 0/1 in router number 2 and gig 0/2. I have run this over the global interface, but I am not seeing enable over the physical interface. So you can see I am now doing MPLS IP over the physical interfaces, and now I can see the messages. So you can also see that MPLS now it is showing here. I can go press up arrow just to check the bindings, local bindings, and here you can see that we have the local binding. So here you can see the label starting with 16 and then the remote binding. So yes, router number 2 has 2 bindings. Now why this is null, why this is 16, we'll go and understand later on. Okay, likewise if I go here and if I check with respect to 3.3.3.3 32. So here you can see local binding is 17, and then you can see the labels for the remote binding, correct? Now we can go parallelly and check the MPLS forwarding table. That's a very nice command that we have. How we are reaching to 1.1.1, and then how we are reaching to 3.3.3.3. So I am router 2, how I'm reaching to 1.1.1, and while reaching there, how we are popping, we'll understand that uh, what is label imposing, what is label uh, swapping. All those terms we are going to understand. So in upcoming section you'll come to know that when the labels are get attached, when it is detached, when we are doing swapping, when we are doing popping, all these things we are going to understand in upcoming section. But obviously suppose if you are the last hop, so the last hop router means, suppose if you are the destination, the last hop router will remove the label and then it will send to the destination. Now, if we are the incoming packet, okay, means you are going to go inside the MPLS domain. So what will happen that the router will impose the label, correct? And then it will send. So what will happen, suppose if we have enable MPLS here, if traffic will come, so this router will put some label here and then it will send here. Then this router, suppose it is checking label 17, it can swap the label with 18 and then it will send to the next hop. Then it will see, oh, 18, and this is my final hop, so it will remove the label. So label will get attached here, then label will get swapped here, and label will get removed here, correct? So this process will continue along the path. Okay, so this is the way that you can go and enable the MPLS label. You can go and do the baseline verification as well. And final thing, you should check that what about the safe entry. So again, you can go and check the safe entry related to 111 if you want. And you can go and check the self entry related to 333 as well. So simply it is telling the next hop, what is your adjacency? What is the physical path along which you are sending the packet? Let us continue and understand more terminologies related to MPLS. So as we know that in our day-to-day activities in our infrastructure, we know that our routers that to whom we are managing our routing table, to whom we are running our routing services, they are nothing but the customer edge. And when these customer edge, they are connected with ISP, so suppose ISP1 and ISP2, then if we go inside the ISP, suppose I am inside ISP1, so this CE is actually connecting with PE, provider edge. So your CE, your customer edge routers, they are connecting with provider edge, and this provider edge basically they are connecting with the core routers. They are termed as a provider routers. So CE going to P going to P, or the provider. The same nomenclature you have in MPLS like LSR, they are working as a core, means they are the core routers responsible for these MPLS packet forwarding or the label forwarding, you can say, but they are working as a core. So they are forwarding the MPLS labels. Then we have the edge. So edge routers, they are PE, they are termed as a edge LSR, and basically they are adding or removing the labels. So when the customer traffic will come, they can mark the label and then they can forward to the provider. Or if the traffic is coming or the return traffic is coming, again they will go and remove the label and then send to the customer. So marking the label or removing the label, that's the responsibility of the P router or edge LSR. Then we have the non-label routers, that's the customer edge or CE devices. Okay, again, we have the control plane build up, we have the data plane build up. More I will show you in the upcoming section in the block side as well. But yeah, control plane will go responsible for routing and label tables. So routing tables will be there and different type of tables are going to form. We will understand more and more in the upcoming section. And then we have the data plane who is going to forward the data based on the label information. So next hop label, what is the next level I have to reach, because this data plane information or data plane decision is happening hop by hop or label by label. Okay, so that means in turn that we have the routing table. So any routing protocol or domain, they will form it. But again, you have routing in your CE, then you have routing in between CE to PE, and then you have routing from PE to P. So different routings, and where MPLS, where BGP, where IGP, these are fitting, you will see in the upcoming sections. When we have one big lab where you will find CE, PE, and P, you will understand that how everything will fit into the picture. Okay, then we have label table as well. So that means that we have two different type of tables. One table is related to routing, and once you have the routing table up and running, once you have end-to-end reachability, then label table will come into the picture. Then again we'll see that with respect to label table, what type of protocols are into the picture. So we have two protocol, one is LDP, one is TDP. LDP is label distribution protocol, that is industrial standard. Then you have TDP, that is tag distribution protocol, that is Cisco proprietary. LDP, now default Cisco devices, they are using TCP port 646. In the lab, we'll explore more on that. And Cisco proprietary TDP, they are using TCP port number 711. And mostly we are going to use LDP. So if you go to the routers, if you enable MPLS IP, and suppose if your underlying unicast routing is up and running, so they will go and form the LDB table. Okay, and we can go and verify as well. I will show you that how you can go and check the LDP neighbor table, LDP tables, etc. Okay, so MPLS is going to form different type of tables, and where and exactly what point they are forming what table, I'm going to show you in the diagram as well. But we have at least two table But again, we have other table as well. Say we have RIB table, routing information base. Then we have FIB table, that is the safe forwarding information base. And then we have the actual dynamic table, that's the label forwarding information base. So whenever the packet will move, they will see what is the next level, what is the next level, what is the next level, and the packet will move. Okay, so I hope you understood this basic terminology. What I will do, quickly we'll go to the blog side, and inside the blog side I will show you one of the lab, and we are going to cover few of the questions, few of the answers related to the chapter MPLS chapter number 2. So you can go to this blog site, you'll find MPLS chapter 2, where we have to go and answer these 4 questions. Question number 1, what protocols port are used for LDP hello session? As we have discussed, the protocol TCP port number 646. So what is happening? Let me answer you one by one. So what is happening that first of all, they will go and discover their neighbors. So assuming that you have underlying routing protocol up and running, then these devices where you have enabled MPLS IP over the interfaces, they will go and send the multicast packet with 646 with this multicast address. Once they discover the neighbor, then they will go and create the TCP relationship with this particular port number. Okay, so question number 1, answer completed, that they are going to use the LDP is using the port number 646, and they are using TCP for reliability. Then question number 2 here, how does R3 know what R2's labels for the specific network? Now, how R3 is knowing that R2 is using such label or not? Okay. Again, what is happening that MPLS itself, they are forming the label relationship. That means that they have the label table. So all the devices, they will form the label. So they have the local tagging, they have the remote tagging as well, correct? And as per the tagging information, they have to forward the packet. Okay. So that means that R3 is only knowing how to reach to R2. Once it will reach to R2, then R2 will come to know that how to reach to R1. Like that, the label swapping and label imposition, label removal or detachment will happen. So the answer for this is that because you have the routing table, on top of that you have label table. With help of label table, with help of LDP label table, that label database tables that we have, they will come to know about the each other's label, so local level and the remote level. Now what is the next question? When MPLS is enabled, what would prevent LDP neighboring? Now LDP neighboring, who will prevent and how it will broken? That means if you have unreachability, suppose if routing is not working underlay, suppose in between your filtering port number 646, some firewall, some access list rules are there who is blocking this neighbor to be discovered, this port to be blocked. There may be congestion in a network, so there may be loop in a network. So network related issues plus physical issue plus access issues can prevent to form the LDP neighbor relationship. And then final question here is that why would we are using ACL when using MPLS debug? Remember, this is common thing. We have discussed this earlier, that whenever you are using debug, please use with care. Please use with certain restriction. Please use with exact sources, exact destination. Because if you use debug, this is intrusive, and there are chances that your device may reboot or crash. So whenever we are using debug command, we should use with certain ACL, and that's why it is recommended here. You can see that we can go and form one ACL, either it is a prefix list or access list. You can form one ACL and then you can apply to the debug command. Okay. So like that, we can go and proceed. Let me quickly log into the device. Let me show you these configurations one by one. So first of all, what we can do here, we can go and check few of the things. So I want to verify the MPLS LDP neighbor. And then let's see. So here you can see R2 is knowing about R1, R2 is knowing about R3. Likewise, if you go to the R3 and if you go and run the command show mpls ldp neighbor, you can clearly see the port numbers. So see R3 is knowing that LDP ident local, he know about himself, he know about the TCP connection, he know about the remote and the local connections, okay, with help of LDP, correct. Again, if you are in R3 and if you are looking for LDP table, LDP binding table, so you can go and check the bindings and you can check the all as well, and you can go and check local binding as well. Okay, so these are some of the basic commands we can go and verify, and we can check baseline configuration with them. Let us continue our lab, and in this section I'm going to cover few more important interesting topics. We have some questions to answer. So for example, how does the IGP next hop affect the LSP? We have the switch path and how it is going to be affected. So one point we know at this point of time that in my domain, where I am running my MPLS, once I have my up and running loop-free unicast network, on top of that, we can go and enable MPLS IP. That means we can enable MPLS, and then they will go and start building the LDP sessions. So that means that once I have the rib table, then the lib table, label information base, will come into the picture. So that means that if I have break inside the rib table, that means the break will be inside the lib table as well. Correct. And that's the reason you'll find that it is a prerequisite that you should have your rib up and running. Question number 2. Why does LDP advertise all local IPv4 addresses to a neighbor? We'll see that when we have the LDP, we'll go and run few verification command. We'll see about their label exchange. We are going to use some CLI commands for that. Okay, and then by default does LSP path. So we have the label switch path match the IPv4 path. That's quite interesting. And in upcoming session, I'm going to cover even little bit more about this, that how different type of tables means where exactly they are forming. Okay, so wait for the next video where we'll go a little bit deep inside that. But here also I'll cover that what exactly happening in between the rib table and the lib table. Okay, what's the relation in between them? And finally, what is the liberal label retention? Let me go quickly open the blog side, and in the blog side where you will find these questions. So here you can see that you have question number 8, 9, 10, and I'm going to cover one by one all these things. But here also, if you go and read the blog, you'll find that some explanation was there. Only one thing I just wanted to highlight here. So suppose if you want to change the path. So here question number 10, by default does LSP match the IPv4 path? Now LSPs, they are driven by the IGPs, Interior Gateway Protocol. And if you want to manipulate, then we can go and use some sort of MPLS traffic engineering. Since there are certain protocols we can use and we can change the path, we can do some sort of traffic engineering. Okay, so that's the one thing. Rest of the questions also you will find here the important notes highlighted in little bit bolder. So here you can see this is very important point. IPv4 control plane build. So IPv4 control plane, that is the RIB database, that will be used to form the MPLS control plane. So IPv4 control plane is building MPLS control plane, and that's not exactly the case when we have the actual data plane with respect to MPLS. Okay, that may change, and if you want to do the changes again, there are ways that we can use traffic engineering, some other ways that we can force change these paths. Okay, so what I'm going to do here, let's go back in the lab that we have. And first of all, I will show you that changing the next hop path, how it will affect. And we have to do some sort of debug ACLs in the previous section that also I am going to cover here. Okay. Then finally, you will find the label, liberal label retention. So there is one or two liner explanation about that. Okay. So here you can see the explanation. For a given router, the upstream and downstream labeling is liberal label retention. So here you can see the downstream. Some labels will be there, upstream and downstream. That's just the term. Okay. All right. So let's go to our lab. And mainly we are focused on router number 2, where I want to create one access list. So let me create one access list 1, and I can do permit host 3333. Great. Now what I want to do here, I want to change the next hop. So to change the next hop, I can go and create one IP route. And before doing that, I just wanted to enable the debug as well. So I just want to enable debug MPLS LDP, and then you can see the bindings. You can see that you have prefix ACL, and the name of ACL is 1. Okay, now what I will do, I will go and create IP route, and this IP route is for the next hop, means the reachability for this prefix, that is a loopback network /32. And then the next hop, we know that to reach here you have 10.1.23 network, correct? But I'll go here and I'll make the next hop like this. That was wrong information I'm giving. And you can see here that we are getting lots of debug messages. So what it is telling, a prefix recurs, walk start, get path, labels, update, etc. Means some problem is there. Now if you go and check the let's see here, yeah, show MPLS, and if you check the forwarding table with respect to 3.3.3.3, let's see. And see here the byte count. So you can see that you have some problem here, and that's why the labels, you can see bytes label switched. So MPLS switch path, LSP is having problem, and that's why they are getting counters here. If you get counters here, that means you have some problem. So clearly you can see that if you have a wrong wrong IPv4 path, then LSP path is also not correct. Okay, so that's the one important aspect here that we are checking. Okay, apart from that, I'm going to show you a few more verification command. So let me quickly go to router number 3, and few important CLI commands we are going to see. You can go and check the show MPLS LDP neighbor. You can see the LDP neighbor. Then you can go and check the LDP bindings. These are actually very, very important commands. And I want to check this with respect to my peer, that is 22232. And then I want to check the MPLS forwarding table, and 22222. Okay, so here you can see that we are checking first of all the LDP information. Who is my neighbor, correct? Now once we know that who are my neighbor, you can see clearly the neighbor entry is here. Once I know my neighbor, then I can go and check the LDP binding. Okay, so this prefix that we are checking, you can see the local binding, you can see that implicit null is there. If it is destination, obviously you want to remove the tag and you want to reach there. And then finally you can see the forwarding table. Now what is the relation between lib, fib, rib, and all those interconnections? We are going to check in the upcoming section. Okay, in the upcoming video I'm going to show that. Meanwhile, I just wanted to remove that command, so I will restore my MPLS, I just wanted to go here to conft and negate that command. Okay, so let's wait last DNS will get resolved, and then I'll go and revert back that. Okay, so conft and we'll go here. This is the command do no, and you'll see soon that they are forming the LDP relationship. When you can take a screenshot of this, and you'll find most of the important message related to debug we have here in this slide. All right, so let's stop here. This is quite important section where we are going to discuss very important topics related to control and data plane and different type of tables that RIB, that the routing and the MPLS they are going to form. Okay, so let's understand these topics because they are the core, they are the fundamentals understanding the MPLS technology. Okay, and even you can bookmark this particular video session and you can refer. So in future, if you want to refer, you can come and refer this theoretical section. So whatever we have studied so far, we have discussed different type of thing. Like we have discussed that we have something called label. We know that if we have a routing table built, we know that if we have loop free routing protocol, this routing protocol is going on and you have loop free network. Then on top of that, this LDP, the label distribution protocol, they will exchange their label and they will form their label information base, correct? So the order of operation is such that we have or we should have a routing in a first place. So you have your RIB table, and then you will find that you have your label. I'll write here RIB and LFIB, label based, or in Cisco we are referring as a tag based forwarding information base, or TFIB, correct? But remember earlier I told you that there are two different type of plane. One is termed as a control plane and other is termed as a data plane. And with respect to control plane and with respect to data plane, where exactly what type of information base, what type of databases are creating, that we are going to discuss in this section. Okay, so here you can see that different questions are there. First of all, suppose if you are getting the packet with unknown label, then what router will do, what it will do next? If you are getting one packet without any label, so we'll discuss about that what is PHP, penultimate hop, what does it mean? We will go and discuss about penultimate hop popping as well in few minutes. Then what is RIB, FIB, LIB, LFIB, CEF, etc. You will understand each and everything related to these topics, and there should not be any doubt, any confusion. Then which is the preferred CEF, MPLS, or IPv4 forwarding? So that also we will discuss in this particular section, and what are different type of labels we have in MPLS. So we are going to discuss each and everything in this particular section. Let me clean all these drawing. Yeah. So we have one table, and let me highlight that table here. And let me scroll a little bit down. And let me highlight the table first. So here you can see that suppose if you are a router and then you are getting packets, then what will be your forwarding decision? And that's question number 1, 12A, that if you are getting a packet without label, what you will do? Now, suppose if it is related to IPv4, you can take the decision with respect to IPv4 engine. Okay, so the FIB will come into the picture. Again, we are going to discuss about the FIB, the lib, LFIB, etc. Whatever you are seeing here written, we are going to discuss about that in couple of minutes. So IPv4 packets, if you have, means obviously unlabeled packet, if you have, you can send to unlabeled packet. Again, if you are getting something as a CE and then if it is going to PE, that means that IPv4 packet going to MPLS. So you can go and use, you can go and mark it as a tag or label. So IPv4 can go to MPLS. Then if it is a MPLS packet, obviously it can go to a next hop MPLS label, correct? And finally, it may be MPLS packet, but you are going to the IPv4 domain. So MPLS packet can go to the IPv4 domain, correct? So all these possible options we have, right? Great. So we understood now question number 12A. What about question number 12B? What is PHP? Now, as the definition says about PHP, PHP is nothing but penultimate hop popping. And what does it mean? So it means clearly is that this will be last, normally last hop must, means what is happening, and maybe you have seen this in the previous lab. We have seen one type of label called implicit null. So what does it mean? Now if this router knows that my last destination is IPv4 and my last packet is going to the IPv4 network, so he will not impose any label in this, because he know that the last hop is something that I don't have to push the label and send it, or put the label, send it. So that's why this PHP will come into the picture. So what PHP is doing, this is simply mean normally last hop must, look up MPLS label, pop MPLS label, look up IPv4 destination. PHP avoid extra lookup on the last hop. Okay. Anyways, you know that this is my last hop, so why I will put the labels and then remove it. So better do not put any label or put the label as an implicit null. And that's the meaning of PHP, penultimate hop. Great. Now coming to the main question that we have today. And the main question is about all different type of control and data plane, different type of uh, engines or different type of information basis that we have. Okay, so let's try to understand that. I'm going to pause it here. If you want to take snapshot, let me clean the stuff. You can take a snapshot and let me continue from here now. So here you can see, first of all, with respect to routing protocol, you are forming something called a RIB, routing information base, correct? Now RIB is inside the control plane, and what will be the data plane equivalency? IP to next hop, IP to adjacency, correct? And that is nothing but the fib. So you can see that you have a RIB to fib connection. Now, when MPLS is coming into the picture, so inside the control plane, you can see inside the control plane, they are doing something MPLS IP routing. We know that LDP will come into the picture, label distribution protocol, or TDP, tag distribution protocol. And here you are forming the label related database. That is nothing but lib. You can see lib or tib. In Cisco, it is tag information base. In industry and standard, it is a lib, label information base. So what we are building inside the control plane, in the control plane, we are simply building the rib and we are building the lib, correct? Now, what about data plane, where the actual packet will forward? So in data plane, you can see that the rib is building the fib, but lib is building the, and you can see lib is building the tfib or lfib, correct? Lfib is nothing but label based forwarding decision, or tag fib nothing but tag based forwarding decision. And that's the core of MPLS. That's why if you get the terms like this is happening in control plane, this is not happening in the data plane, so this is the reason behind that. Now, how we can go over the lab devices or over the routers and we can see different type of tables. So yes, you can go and verify it. Suppose if you are looking for a RIB, routing information base, you can go and run the command show IP, and let me highlight here. So you can run the command here. You can see that show IP OSPF1 RIB. It will give you the RIB table. If you are looking for lib table, label information base, you can go and run the command show mpls ldp binding, correct? Let me clean this. And finally, if you are looking for lfib, that's a dynamic, that's actually the table inside the data plane. So lfib you can check with show mpls forwarding table. This is the command. Okay, so 3 different table. The rib table you can see with show IP ospf1 and rib. Then lib table you can see with show mpls ldb binding. And finally, the lfib table, that's the dynamic table that you can go and verify with the show mpls forwarding table. Now there are, so last question here is this, that in mpls you have different type of labels used. What different type of labels you have? You have pop, means you are popping out the label. You have swap, you can make 10 to 20 swapping of the label. Push means you are pushing the table inside the frame inside the packet. Untagged means the stack is removed and the packet is forwarded unlabeled. No label or untagged means the packet is forwarded unlabeled. And then finally aggregate. Aggregate is the label stack is removed and an IP lookup is done on the IP packet. Okay, so again here also you can have a look and you can make your notes that different type of labels we have inside MPLS. We have pop, swap, push, untagged, and aggregate. All right, so I hope that this particular video lecture is quite interesting for you, and let me stop here. In 2.2, we have to understand about MPLS layer 3 VPN. And these sections also, this section and upcoming video also, you'll find that we are going to understand these with respect to questions. So we have few questions like 2 to 3 questions per section. And according to that, we are going to understand that. Apart from that, what I have done that for this particular section, we have lab as well. So upcoming videos, you'll find that we have full-fledged lab understanding that how CE to PE communication is happening and how PE to P, that's the provider. So provider age, customer age, how these routings are happening and how different type of technology fit into the picture, such as what is a VRF, use of VRF in this particular lab section. Then you will understand use of VPN v4, use of MP, BGP, where all those things will fit into the picture. So we are going to understand each and everything. But before going to the lab section, let's understand a few of the terminologies. Those are very useful for our lab section. So let's check the question number 20, 21, and 22. First of all, what is layer 3 VPN? And what does it mean by sharing the routes between customer and the provider? Okay, then why does we are using VRF, virtual routing forwarding instance, and what's the use of it? And then finally, what is the protocol being used in between different PEs? Okay, so let's understand one by one. First of all, what is layer 3 VPN? And you will understand this with respect to this particular diagram. This is our lab diagram as well. And you'll find that you have CE routers. Now, suppose this is the service provider in the green, and this service provider may have to deal with multiple customer. So suppose he has customer 1 and he has customer 2. Okay. Now what is happening here at the PE level, we'll go and enable some sort of VRF, virtual routing forwarding instance. Now what this VRF will do, that different customers, although those customers, they are using same address space, but still because we are using VRF, they will be separated. So that's one of the very important aspect we have with layer 3 VPN, because they are using the VRF. And with help of VRF, the PE is able to segregate same address space in between different customer, customer 1, customer 2. Okay, so that's one of the very interesting aspect of layer 3 VPN. Second, very important thing here, is that exchange the customer routing information. Now, how they are doing the exchange, we'll come to know that we are going to use MP BGP, and then we are going to use VPN v4. So in between to customer and P to other P, you'll find that you are going to enable BGP, and then they are going to form some sort of, you can think there's some sort of private network for each customer and with respect to BGP. All right, what is VRF? Again, I told you that VRF is nothing, but you can go and segregate different routings. You can create instance of routing. Is something like routing virtualization, correct? So you may have one global table, but inside that you can create multiple VRF or multiple segregated routes for that particular customer. Now, suppose if you are not using label switching, and if you go and enable VRF without MPLS, you can see that if you go and enable the VRF and you're not using the label switching or tag switching, then that terminology is termed as a VRF Lite. But anyways, for routing optimization, we are going to use MPLS. But again, if you go and check only the enterprise network, so few of the customer, they are still enabling a VRF just to segregate their address space, just to segregate their routing space. Okay, great. So this is the overall topology lab diagram that we are going to discuss in the upcoming section. Step by step, I'll go and configure all the devices. We'll see each and everything. We'll see the level, we'll see the transport level, VPN level, etc. So everything we are going to discuss in the upcoming section. Before starting the lab sections, we have a few more questions. Let us discuss these questions, and in the next section, we'll go and start building our lab. So question number 22 here, you can see that which protocol is used between P's. We know that we have P, provider edge, and these provider edge, obviously we are going to run MPBGP inside these provider edge, because these PEs, they are going to connect with the CE. So different customer edge, they are going to terminate it at PE, and PE has to enable the address family that is known as a VPN v4. So we have to go inside BGP and we have to enable address family VPN v4 in between the P's. And in the lab section, you'll find that these P's in our lab, they are part of same autonomous system. That means they are running iBGP. And then there are some other terms that we are going to use, that how we are going to exchange the route from CE to PE or vice versa. Okay, so one domain we have where we are not enabling the MPLS, and one domain we have where we have the MPLS, where we have the labels or where we have the tagged routing table. Means you have the routing entries with the labels, correct? So the answer for question number 22 is that the address family is VPN v4 that we want to enable. Now question number 23 is connected with 22, that what are the commands? So I'm going to show you the command, and let me quickly show you the diagram first. So here you can see this is our lab diagram where you have the PE provider edge, where you have the provider edge, and in between these provider edge, we are going to run the BGP. The address family should be VPN v4, and how we are going to enable. So here you can see, first of all, we are enabling the BGP in between these PE. So first of all, we have normal BGP relationship as iBGP relationship. So these commands we are very much familiar. We have done in our previous sections in the BGP section. But when we are talking about the address family VPN v4, here you can see that we are enabling VPN v4 address family, and for R1 this loopback is my neighbor. For R3 or PE3, as per our diagram, this loopback address is the neighbor. So neighbor 111 activate, and then we are doing the send community extend. Now why we are using this community extend? So let's see. Question number 24. What is the use of extended community? Why would you activate VPN v4 capabilities with IBGP pair? And what are to command, or what are the commands to activate VPN v4 feature? So very much we have addressed question number 26 because you have seen the configuration. We have to go there and activate it. Once you are activating, you should understand about the configuration related to community extension. Now, in upcoming few slides, we are going to discuss one very important concept related to tagging the routes to make it unique. So we are going to discuss about two terms. One is route distinguisher, other one is route target. So suppose if we have any IPv4 route, and if you want to make this unique, and again this route distinguisher is locally significant, so you can go here and do some sort of tagging. So you can go and use the tagging with the route, and this route will become that's why this marking is something known as route distinguisher. So you can see that VPN v4 route, how it look like. They have the RD plus the prefix. Okay, so your VPN v4 routes having two component, first of all the prefix and then the RD. Now this is part one, that you're marking the route. But what about you want to import or export? Means you want to send to the C or you are taking from the C. What about that? That I will show you in the next slide. Okay, so RD is something that we are making the routes unique, and obviously the labels will be there. MPLS VPN labels will be there. Actually, there are two different type of label, and you should understand at this point of time. Let me clean the stuff here. So we know that whenever you are sending the routes, you are putting some sort of tag or label, and we know that the PE devices, they are imposing the tags and sending to the next hop, next hop, next hop, next hop. Correct. Now, important thing here is this, that when we have two tag, that means when you are talking about VPN v4, I should write VPN v4. You can understand this is VPN version 4. So when we are talking about VPN v4 and MPLS together, how these tags are looking. So here you can see the transport. So you may have payload. Up to here we have the payload. But after that, you can see that you have VPN v4 label, that's your RD. And then you have the transport label. Okay, so which C, which customer? VPN will tell, VPN level will tell that which customer, and the transport level will tell which PE, correct? Because PE has to send the route to the C, and that's the relation. It's actually very, very important. You should mark it, these labels. Transport label is for PE, VPN level is for C. Now, second very important thing here, so that's the tagging here. You can see that you can use ASN colon NN or IP address colon NN, and I'm going to show you this in the lab section, so you will understand more and more how we can create it, how we can mark it. But second very important point we have here is the route target, RT. Okay, route target is something which has the significance when you are importing and exporting the routes. Okay. So this is 8-byte field. You can check RFC 4360 for more information. This is part of BGP extended community, and how this route target is working. So we'll see that this route target is working when we are importing and exporting the routes. So when you are at the PE level and you want to exchange the route with the CEs, so here you can see that when you are using the keyword called export, that means you are sending the route from VRF to BGP. When we are using the keyword called import, that means from BGP to VRF. Okay, and what exactly BGP to VRF, VRF to BGP? Again, you will understand this in the upcoming section. Okay, so what we have done here, that we have answered few very, very important questions here, that how to enable VPN v4. What does it mean by RD, route distinguisher? What does it mean by RT, RT is there to import export the route. RD, route distinguisher, is there to label, to put the marking over the route. And this payload information, it's very, very important. Okay, so how we can signify the CE, how we can signify the P, each and everything we have discussed in this particular section. All right, so let's stop here. In next section onwards, we'll start building our lab. Let us start the lab configuration. What we are going to do, that we are going to build our lab configuration step by step. So first of all, I will go to the backbone. So we have the backbone here, and we'll do the configuration related to the PE1, PE2, that's PE3 here in our nomenclature naming convention. And then we have provider router as well. So you have PE, so different PEs, and then we have one assigned as a P. Now what we are doing here is that for the PE router, so for the MPLS backbone, we are going to run OSPF as IGP. And in between these PE devices, we are going to form the BGP relationship, and we want to enable VPN v4 address family. Okay. So let's do that first thing first. And again, you will see in the upcoming section, we have to do the routing in between PE to CE. Somewhere you'll find that I enable OSPF, somewhere we are going to run EIGRP, somewhere you will find BGP, somewhere you will find RIP. Okay, but we are going to do the configuration slowly, step by step. So first of all, let's focus on the lab topology devices. Those are R1, R2, and R3. We'll go and do the configuration on R1, R2, R3, and slowly we are going to move our configuration, and we'll go to other devices as well. All right, so let me go and start R1. In R1, so this is the R1, and safely I can go here and enable the OSPF over all the interfaces, or at least the interfaces that is facing towards the core MPLS network. All right, for sake of simplicity, I can go to router OSPF1, and then I can use 000, means I am advertising everything inside area 0. So for example, so this is my configuration on one of the router, that is the PE. Then we'll go to provider router. Oops. And I should configure OSPF and then the network configuration. And then I'll go to R3, that is other PE. And here also we can do the configuration related to OSPF. So OSPF 1 and the network this. Now once we have this IGP running, and you should go and verify that you have your OSPF neighbors, that should come up. Still they are in some excess state, loading to full that we wanted. All right, and then you can go and check show IP route related to OSPF. You should get the routes that is coming from router number 3 actually. That'll do back 3.3.3.3. So I can see here that in between R1 and R2, there is no problem. And R3, let's see, should have correct IP configuration and everything. So I can see one of the interfaces down here. We'll go here and make this no shutdown. I'll come back here. I should see loopback 3333 as well in a while. Now, once we have our IGP running, then I'll go and enable the BGP. So we'll do the BGP configuration in between the Ps, correct? Because our provider router, that is router number 2, is BGP free core. Okay. And meanwhile, should come also. I can't see that it is coming up. That means that we have some network issue. I can see now that OSPF is loading to full. And if it's so, after convergence, this router should receive 33. Okay, so that's okay. Now let's do the BGP related configuration. So I can go here to router BGP. The AS number we are going to use here is 100. And once we are inside the BGP, then what BGP related configuration we want to do. So we can go here and we should form the IBGP neighbor relationship in between here. So for that IBGP relationship, what we can do, neighbor 3333 remote AS, and there also I'm going to put this neighbor as a inside AS 100, correct? And again neighbor 33333 update source loopback. You know, everywhere we have created loopback 1, correct? Now we can go here, route to BGP the 100. Its neighbor is 1111 and the remote AS is 100 because we're going to form IBGP relationship in between. Update source loopback 1, and you should go and check show IPBGP summary. I can see here that you can see here that we have this neighbor relationship up and running. Now this is one part. The other part that we want to enable the address family with respect to VPN v4. So here you can see that we have VPN v4 address family. And once we have address family VPN v4, then for this, we want to activate the neighbor, that is 333 activate. Let's see that what options we have. So neighbor, you can see that we have activate option. We can go and activate this. And then we want to send the extended community. Now here you can see that the topology for this has been changed to IPv4. Great. Now next what we want to do here, that my neighbor, and we are going to configure RD, route distinguisher, and route target. So those extended community also we can use here. Send community extended. Great. So R1 to R3 configuration is done. Here also I can go and use address family VPN v4, and when we have this, then we can go and give the neighbor 1111 activate, and then neighbor 1111 send the community extended. So this is the configuration we have related to R1 and R3. There are so many things that we are going to do still. So this is the baseline configuration that we have in between R1 and R2. Now next what we want to do, that we'll go and follow our topology. According to that, we can do the routing related to one of the customer edge. Okay, so let's stop here, and in upcoming session, I'll go and do the configuration related to customer edge and the P's. Okay. All right, so let's stop here. We are going to do the configuration related to P to C for one side. One side means for one of the customer 1. In this area, we are going to use OSPF. So the customer, they are running OSPF, and we'll see that how we are going to redistribute OSPF inside BGP and BGP inside Ospf will see that how the routing is going to happen in between P to C, C to P. Likewise, here for customer one only, the other side of the customer, they may run any other protocol. We are going to take example with respect to RIP. So suppose this side customer one, they are running RIP protocol. So how we can go and do the redistribution related to RIP that we are going to see. Now here, we are going to use the RD and RT. So we want to segregate the routes as well. So we are going to create the VRF, and then we are going to use the route tagging, route import and export everything. Okay, so let's see that how we can perform these tasks one by one. First of all, I will go and do the configuration for this section, and then we'll go and continue on this section. So let's focus on the configuration for router number 4 and router number 1 in this topology. Let me go and open the lab device. So here we have router number 1 and we have router number 4. Since router number 4 configuration is easy, straightforward, I can go and do the configuration. Let's see that what interfaces we have in router number 4. And here you can see, let me see the reachability to the router number 1, that's the PE1 10.1.14.1. It's reachable. Now before doing any configuration here, I just wanted to go on router number 1, that's my PE, and we want to do the configuration. So we should have configuration related to VRF. So here I will go and create the VRF, IP VRF, say customer 1 or customer underscore 1, whatever suitable. Once we are here, I can go and give the RD. You can go and assign like this. I can go and give the IP address RD, correct? Now, once we have the RD, and let's see that you can see the format here for RD, and you should use that format. So IP address and NN. So let me go and use that .1, and then I can go and use any number we can use, correct? So I'll go and use here 101. Great, and let's continue and do the rest of the configuration. So let's continue and do this route target configuration. Route target. I want to export my routes. So here we can go and do this export related to 1111 is my loopback 101, and then route target import the other side loopback address I'm taking here as an example. Okay, so we have the VRF configured here. Now, once we have the VRF, what I can do here is that we can go to the interface where we have the connection to the CE. So you can see the configuration here. This interface is connecting to the CE. So over this interface, we can go and use IP VRF forwarding customer 1. And then you have to rewrite these IP addresses because now they're part of VRF. So again, we should go here and have the reachability. See, from the customer point of view, we are not doing anything. Customer as it is, they can run their own local protocol. They are doing whatever they have. There's no problem. But once this traffic will reach to P, we are doing the manipulation at the level of P. Now here I can go to router OSPF and I can do the router OSPF configuration. 114.0.0.0.0.255 area 0. Then I have one loopback 4444. 0 area 0 like that. And that's very much done with the configuration related to CE. Now let's go and focus on PE. Okay, so we have our configuration related to RD and RT. You can go and give the MPLS level range as well if you want to specify our own range. So we can go and give. Great. So what we have done, basic configuration, we have created RD, RT. Then we have assigned the interface inside the VRF. Now next thing we have to do is the redistribution. Okay, so let's do it. So here I can go to router OSPF. We have to enable OSPF process related to our VRF. So we have our VRF. We know that VRF is customer 1. And then once I am inside OSPF, I can redistribute BGP. We know that BGP is BGP 100 here and metric. So we are going to OSPF calling BGP so that BGP metric should be like OSPF. And we have discussed this in our redistribution section earlier. Great. Then what we can do that we have the network related to OSPF. That is nothing but 10.1.14.0 255 area 0. Now what we have done here is that we have redistributed BGP inside OSPF. Now if you go here and check show IP route, let's check the show IP route. Right, and if you go and check show IP OSPF neighbor, so it has his neighbor 14.1, and from 14.1 he should receive certain routes, should have the reachability, correct? All right, I'll come back to this because the idea here is this, that one point of CE should communicate to other point of CE, correct? And we are going to discuss this. So I'll come back to this point. Now let's continue with PE configuration. What we have done, OSPF, we are calling a BGP like that. We should go inside BGP. And once we are inside the BGP, we should go to the address family that, let's see address family, what address family we have. We have IPv4 address family. And inside that, we can go to the VRF. What's the name of the VRF? Customer 1. Now inside BGP, we can go and we have to go and redistribute OSPF. And we know that the VRF that we have is the customer 1. Let's quickly check the VRF. Customer 1. That's correct. Okay. So now what we have done the two-way redistribution, and you can see the configuration. Let me show you that. So what we have done that inside OSPF, we have called BGP, and inside BGP, inside address family IPv4, we are calling OSPF. Okay, so we are doing good configuration here, and there are some command that we should use it while doing this VPN v4 configuration related to our configuration. So here you can see show BGP, VPN v4, unicast, VRF, customer 1. Let's see. So clearly you can see that the provider edge, they are getting the loopback 444, they are getting the IP over that is over the interface 10.1.14.0 subnet. Okay, and now let me go here and let's see that how much he's seeing. So still it is good. It's still the customer 1 network. So we'll go to other side. So what we have done the configuration for one side. So that means that this side is good. Now we'll do the configuration to this side, and once we do the configuration to this side, you will see that they will start exchanging the routes, because here also I have to go create VRFs and everything. Okay, so let's do it. Now I can go to router number 3 and let's working creating on VRFs. So here we are. What I want to do here also I want to create IPVRF, and that for customer 1, because customer 1 and customer 2 here also you have. For this RD I want to give 111, say 333, and here also I can give 101, because 101 for example is for customer 1. Then route target, I want to export my, so 101, and then route target import, I want to import 111 101. Then again I can go to gig interface 0/2, where we can go and do IPVRF forwarding related to customer 1, and then let's see, I think it has been removed. So then we have the IP here, IP address. That's IP, we know that what's the IP. This is 326. So 10.1.36.3, I should ping this. So if I go here to R6, and in R6, the routing protocol we want to use is a RIP routing protocol. So simply I can go here, router RIP version 2, no auto summary, and we have 10.1.36.0, and then we have one loopback as well, 6666. Great. So you can see that customer 1, other side, that's the router number 6, is configuration also done. Okay, let's go back to router number 3 where we are doing the configuration. So now what we want, inside RIP we want to call BGP, inside BGP we want to call RIP, means we want to do the redistribution. So I can go to router RIP, and here you will see that how we can do the configuration. I can go to the address family IPv4 VRF, that is customer 1, redistribute BGP, and for BGP what we can do, we can use the metric, correct? First of all, give the AS number and the metric. I'll give metric as 4. Done. And then I should go to router BGP, but before going there, should advertise the network as well. 10 dot, anyways, the RIP is going to do the summarization. So I'll use 10.0.0, or maybe you can go and use 10.1.36.0. Now we can go to router BGP. This is very important configuration, because this time we want to go inside the address family IPv4 VRF customer 1 redistribute RIP. Done. Now let's check. Show BGP VPN v4 unicast. That's the VRF is customer 1. Let's see. So now you can see that we are getting 444. Remember, 444 is coming from the customer 1 from other side, and he's doing 666 as well, 10.1.14 as well. So that means that if you go to router number 6, and if you go here and do show IP route, should C444. C444 is coming from far end. And if you go to router number 1, sorry, if you go to router number 4, correct? Show IP route. See, nothing was coming earlier. Now you can see that he's knowing 6 network. He's knowing 36 network. And you can see that metric that we have used. So clearly we can see that end-to-end communication is happening between these two routers. That means that our configuration, import, export, everything is working perfectly fine. All right, so this way we can do, so you can see here, this is actually MPLS end-to-end configuration. All right, so let's just stop here. In this section, we are going to do the configuration for customer number 2. Now for customer number 2, we are going to use different routing protocols. So here we are going to use EIGRP. So within the AS, you'll find that we have within the autonomous system, because EIGRP using autonomous system. So within the autonomous system, you'll find that we are going to run EIGRP with AS15. And here in this portion, we want to use BGP. So here I will go and enable AS, that's a BGP 200, and in between AS 200 and AS 100, we'll go and form the relationship. All right, so let's do this thing, this configuration step by step. First of all, I will do the configuration to R1, this is router number 1 or PE1, and then R5, that's the customer 2 router number or one of the router. Okay, let me go back to the lab. So we are here in R1. And for R1, first of all, we need to do the VRF creation. So here I can go and create, say, customer number 2. Then we'll go and give the RD. So last time we have given 11111 This time I'll go give 1111 and then 102. Then route target export. I want to export 111. Then the label route 102. And then I want to import 333:102. Once we have that, we know that our gig 0/3 is going to connect with customer 2. So let's see the configuration here. Once you're over this interface, you can go and use IPVRF forwarding, correct? For customer 1. It's not customer 1 actually, this is for customer 2. And then IP address should be this. We can check this configuration. Interface gig 0/3 should be customer 2. That's right. Now we can go and do the verification related to this. I can go to router number 5 and we can ping. Let's see. The gateway is reachable. Yes. Great. And here what we want to do, here we want to enable router EIGRP15, no auto summary. Let's check the IP addresses here. So the IP address network is 10.1.15.0. Other network I can use 5.5.5.5. Okay, great. So this is configuration related to R5. Let's go back to router number 1 or PE1 and let's continue our configuration. So next thing what we want to do here is the redistribution. I can go to router EIGRP1. Here we are enabling EIGRP. And once we are inside router EIGRP1, we can go to the address family, IPv4 VRF customer 1, and then we can do the redistribution. Do the redistribution related to BGP, but the metric value should be EIGRP. And we know that we have the bandwidth, so I can go and give bandwidth. Delay should be less. Reliability should be 100%. Load should be less. MTU, it's up to us that what MTU we are giving. All right. So this is the redistribution. Once we have the redistribution, again, I can go and advertise the network. We have the network between this router and router number 5. It's the network we have. You can see 10.1.15. So I can go and give the network 10.1.15.0 and space and enter. Auto summary. Great. So we have done the configuration. That is again one part of configuration. Next, we should go. You can see that it is telling that you should give the autonomous system. So one line is missing here, that once we are here, so let me go back to this system one more time. You should give the autonomous system for the EIGRP. And we know that EIGRP autonomous system that we are advertising here is 15. Correct. So let's go back one step more here. Oops, we are here and we should give the autonomous system. So let's see that what options we have. All right, so we have done the redistribution here. So once we are here, and okay. Yeah, let's see. So router EIGRP1, then we can go to the address family IP v4 VRF customer. Actually, this should be customer 2 autonomous system. Here you can see 15. Like that, you can give, or you can give the autonomous system. So once I am inside here, I should give me option for autonomous system. Okay, so you can see it's not giving it. Like that, we can give the autonomous system, and then we can do rest of the configuration. But before doing that configuration, let's quickly see section EIGRP. And here you can see, okay, so entirely wrong configuration that I have done, because this is not customer 1, this should be customer number 2. But yeah, anyways, we know this. No router EIGRP1. Let's remove everything. EIGRP, let's see. Nothing is there. Now we can go to router EIGRP1. We can go to this address family. Then we can do the redistribution related to BGP. Correct. Great. And then I can give the network as well. And I can see here that the EIGRP is working and it's exchanging some of the route. What configuration CLI command to do the verification? So this time we can go and check the VPN v4 unicast, and the VRF is customer number 2. Let's see. Great. show IP VRF. That's okay. I'll come back to this configuration. Let's continue our configuration to other side. To other side means let's do the configuration to PE number 2 and the router number 7. So router number 7, what configuration we have? BGP configuration, correct? Show IP interface brief router BGP 200, and then what is his neighbor? So neighbor is, let's see the IP here. Start 3. So his neighbor is this, whose remote is going to be 100. I just want to redistribute my connected routes, and that's it. Okay, and redistribute connected means I'm not using network command, although we can go and use the network command to advertise my loopback and the interfaces, connected interfaces. Okay, so that's it. We have the configuration related to R7. Let's go and focus the configuration here inside this PE. So first of all, we want to create the RDs. Okay, and let's check section VRF. So here you can see that I can go and create VRF for customer 2, then RD. I can go and give the RD, say 3333, very much same, but only 102. Then route target, export. I want to export 3333:102, and then I want to import 1111:. So you can see the configuration is very much similar, only few things are changing now. Okay, we can go and check the interface key 0/3. I can see the IP here, so you can go back and assign this IP once it will get removed. So interface key 0/3, IP VRF forward the customer number 2, and then you can give this IP. Make sure that once you assign this IP, should be reachable from the customer. So we can go to the customer now and we'll ping this. You can see this is reachable. Great. So our RD and route target configuration done, VRFs done. Now what we need to do here that we have to go and do the redistribution related to BGP. Now since we are using BGP here as a MPLS core and a redistribution point for P and C, so we can go to BGP 100, and inside address family we have to play around. Okay, so before doing that, we should have the configuration related to P to C with respect to BGP. Okay, so let's do that. Address family IPv4, and what is that? VRF customer 2, correct? So first of all, we'll go inside the customer number 2, and then who is my neighbor? My neighbor is 10.1.37.7, whose remote AS is 200. And this neighbor, I just want to activate. So now we can see that neighbor is up. We can go and verify BGP summary. I can see the neighbor is up. Show IP route. Now before doing any further enhancement here, what we can do here is that we can go and check show BGP, VP and V4, unicast for VRF customer number 2. Let's see what we have. So he is getting 77737. At the moment, I can see that he is not getting 555. And let's go back here and check. Same configuration, big configuration, CLI verification commands. I can copy and paste here. Let's see customer 2. So good thing here is this, that I can see that one-way communication. That means that if we go to router number 5, and if we go and check show IP route, you can see that he is learning 777 means customer from other side, but he is actually not advertising his own network. So he should get 555 here. That is not. So one-way communication is happening actually in one direction, and we need to continue go and fix this. So what is happening here actually, that from here to here you have the route, but from here to here we don't have the routes advertised to customer to that end. All right, so what we are going to do here, I will go and continue this troubleshooting. Let's break here, and in the next section we'll go and check if we have any missing things, if we have any issues. Apart from that, what we'll do in the next section, that we'll go and do some verification as well, some CLI commands for verification. I will show you that. Okay, so let's stop here. In this section, we are going to discuss about the troubleshooting steps that we have. Apart from that, we have seen that in the previous section, we try to bring up, or we try to reach to one of the subnet, and you see that one-way communication was there, but 5555 was not going advertising inside customer number 2. So we are going to troubleshoot that as well. Now, while doing the MPLS related troubleshooting, we should go and verify the VRF configuration. The VRF is assigned to correct interfaces or not, enabling the VRF related routing, the VP and V4 related configuration, the redistribution, finally the redistribution related to VP and V4. Redistribution means, so what does it mean? It means that when you have the CE routers, although CE routers, they are running their own IGP, and then when they are going to do the exchange, routing exchange with P routers, you should have the redistribution configured at P. So suppose if you do the redistribution one way, so we will see only one way traffic is coming, the return traffic will not go and reach, correct? So we have to go and check the redistribution. Basically, since we are running BGP here, and remember BGP peer, so we have two different PE, PE1 and PE2. Both are IBGP neighbors. Now, since you have two protocol here, one is related to CE, one is related to BGP. Make sure that inside CE, we are redistributing BGP. Make sure that inside BGP, we are redistributing CE routes. And we have taken example related to almost all the routes. Like we have taken example related to OSPF, RIP, EIGRP, and BGP. Okay. Now there are some additional steps that we can go and verify the VRF. So VRF configuration, so IPVRF, show IPVRF detail. We want to go and check the route import export. You can go and use show IP route related to that particular customer VRF. Then we are using this command. This is actually very important command. Show BGP, VP, and V4 unicast VRF with related to customer 1 or customer 2. Correct. Again, we have a debug commands. We can go and check more on BGP, VP, and V4 unicast related commands. We can go and check the MPLS are enabled over the interfaces or not. If you want to do the label related troubleshooting, so you can go and check show IP BGP VPN v4, the RD name and the labels related to that. Again, we can go and check the show IP BGP VPN v4 unicast VRF, customer labels and their detail. Great. So this is the way, these are the very important verification commands that we have handy. Let's go back and let's check the router number 2, that do we have the configuration related to redistribution. Actually, we should go to PER1 and let's check this. This is one of the very important verification commands. Show BGP VPN v4, BGP VPN v4, unicast VRF customer one. If we go and press enter, obviously it will show you all the VRF. So if you go and type, okay, unicast all, you want to see all the VRF information, you can use this all command. So here you can see that related to customer number 2, we are focusing on customer number 2. You can see that customer number 2 can see 777 and different RDs are there. Let's focus on customer number 2. We are not seeing that. Okay, let's go and check the redistribution. First of all, we'll go and check inside EIGRP, are we calling RIP? Inside EIGRP, are we calling BGP? So router EIGRP, we are redistributing BGP. That's 100% correct. Likewise, we can go and check the BGP. Inside BGP, are we calling EIGRP? So we are inside BGP, you can see BGP 100, we are calling customer 1, Ospf, but seems we are not redistributing here the EIGRP route. So we can go to router BGP 100, should go to address family IPv4, VRF, customer number 2, redistribute the EIGRP, whose autonomous system is 15. And again, you can go and assign the metric. Leave the default metric at this point of time. And now if you go and check show BGP VPN v4, unicast VRF is customer number 2. Sweet. So now you can see that 555 is coming into the picture. And now if you go here and check show IP route, you can see now that 555 is appearing in the routing table. Okay, and since we haven't given any specific metric, so it is taking the default metric, but we can go and assign some metric. All right, so we have completed our MPLS related lab. Let's just stop here. In section 2.3, we have to understand about DMVPN, and inside the DMVPN, we have different type of terminologies, technologies to understand. So what we are going to do here is this, that first we'll go and understand DMVPN, and then in the lab section, I will show you that DMVPN, how we can do the configuration related to Cisco IWAN, because Cisco IWAN is one of the technology before SD-WAN who was using DMVPN heavily. But DMVPN, the multi-site IPsec connectivity or tunnel, we can use anywhere. It's a high scalable IPsec VPN solution. And why it is this, we are going to discuss more and more in this particular section. So let's begin understanding Cisco DMVPN. Build our knowledge about DMVPN. DMVPN is nothing but dynamic multi-point VPN. And what about the evolution of DMVPN? So you'll find that DMVPN evolution, so what is happening initially, Cisco uses Cisco IPsec. Still we can go and use 0.2, point IPsec or site-to-site IPsec VPN, correct? Now the problem with site-to-site or point-to-point IPsec VPN is this, that it can't scale because always you have to go and create the tunnel in between two peers. You have to go and do the manual configuration, etc. But suppose if you want to scale, so what you want that you have one hub location and you may have n number of spokes, and you want to create the dynamic tunnel in between hub and spoke, or maybe from hub to hub you want to create those tunnels, that can be easily achievable with respect to DEM VPN. As name suggests, this is dynamic multi-point VPN. That means that tunnel will form dynamically. Either hub to a spoke or a spoke to a spoke communication will happen. Again, the line of configuration as well, you'll find that less line of configuration required. Okay, so since DMVPN is providing such type of solution, which is a scalable, which is dependent only upon the source and the destination IP address, that means that irrespective of transport, so either you are using MPLS or you are using internet, doesn't matter as long as your IP addresses. So as long as your gateway IP addresses are reachable, they are identifiable, DMVPN will go and form the IPsec tunnel. There are some underlying technology we should know about multi-point GRE. And whenever we are talking about any type of tunnel technology with respect to Cisco, GRE will be there by default. So MGRE is one method, means one technology we should understand. The other technology inside DMVPN is NHRP, next hop redundancy or resolution protocol, not redundancy. It's a resolution protocol because you want to know the entries inside DNA or cache entry. So all the spokes should know the entry what you have inside the hub, and hub should know that whatever entries they have inside the spoke, means it's just like cache entry, and those cache entry how different devices are learning, we are going to discuss in upcoming section. All right, then. So GRE is one method, that's the tunnel method. The caching technology you can think as a next hop resolution protocol, very much similar like DNS, how name to IP resolution is happening. Then IPsec crypto profile, obviously you want to secure the tunnel. Either it's a private or public, the traffic should be encrypted and all CIA parameters should be matched. Confidentiality, integrity, and availability, and then obviously the routing. So underlay routing, we have actually the tunnels that we are going to create, they should be reachable. Why we are using DEM VPN? First of all, this is independent of transport. If you have any restriction with MPLS L3 VPN, DEM VPN, they don't have any such type of restriction. Then they are highly scalable. So if we go and design in a way, suppose you can go and design in a way that you have hub 1 and hub 2, a few of the spokes, they can think that their primary is hub 1 and the fallback is hub 2. Then few of their spokes, they can think that their primary is hub 2 and the fallback is hub 1. Okay? So like that, we can go and design it in a high availability sense. Okay, so the DMVPN configuration is first of all that you should have GRE going in between that, and we know that GRE, their protocol is 46. This is actually the default method, default tunnel method inside Cisco iOS. And what about the GRE configuration? It's very easy and straightforward. So here you can see that we have hub, and here you have a spoke, and you want to create DMVPN. In this example, only you have one hub and a spoke, but later on we'll go and add more devices here. So either it's one or two devices or n number of devices, you'll see that configuration will be constant. So first of all, let's see that in this, how we can go and add the MGRE configuration. So while you are creating the tunnel, you can see that these devices, they have tunnel IP address configured. Configuration is easy, straightforward. We can go to tunnel, assign the IP to the tunnel 3.1/24. Tunnel source is loopback because loopback will be available always. Tunnel destination is other side loopback. Likewise, the flip of the configuration. So tunnel IP is 3.2, tunnel source is loopback, and tunnel destination is this side of tunnel. Now, if you want to add the tunnel mode GRE multi-point, you can go and add only one line there. Actually, you can go and add the tunnel key as well along with that tunnel key 123 or whatever. After that, you can go and add one extra line that is related to tunnel mode GRE multi-point. All right, so now we understood that DMVPN, their use case, usability, etc. They are highly scalable, but they have underlying technology as well, such as GRE, NHRP, IPsec profile, routing profiles, etc., routing, etc. One by one, we are going to learn everything, and by the end of this series, you'll find a lab section as well. In this section, we are going to understand about how DMVPN is working behind the scene. At the moment, we know that the usability of NHRP. NHRP is a resolution protocol. It can map the tunnel IP with the peer public IP address. And in the previous section, I told you that the analogy may be referring, you can refer to DNS resolution IP to URL mapping or IP to name mapping, or you can think this as a ARP cache as well, IP to MAC to IP type of binding. But anyways, this is something that that having the map in between the tunnel IP to the public IP address, and I'm going to show you as well in the diagram. So why NHRP is important? Because NHRP knows that private tunnel IP address of my peer and the public IP address of my peer. So suppose this is the spoke and this is the hub. So NHRP will come to know that what is the tunnel IP and what's the physical IP as well. We'll see. So here you can see that DMVPN, how it is working, and NHRP, where it is fit into the picture. At the moment, only one hub and a spoke, but you will see later on we have more hubs as well, but the logic will be the same. So we know that importance of GRE. Once we go and create the tunnel, here you can see that we have tunnel 0 created to all the hub and to all the spokes. So once you have the tunnel created with help of MGRE, then the next phase here is that we can go and check the NHRP registration and request and registration. So clearly you can see that all the spoke, correct? So you can see that the hub location, they have the tunnel IP 3.2, and that's the reason you can see here that the NHRP NHS, that's the next hop server, is 10132. And here you can see the CAS, the mapping is, so your tunnel is mapped with the loopback. We know that the use of loopback, irrespective of interfaces, loopback, they are always on. So what is happening that first of all, the NHRP registration request will go. So the spoke is requesting to the hub about that NHRP registration request, and you can see that packet is encapsulated inside GRE, the spoke. So 3.1 is the spoke and 3.2 is the server. Correct? So you can see 3.2 and 3.1. And then the request is going to the server. Obviously, in the later phases of the configuration, you'll come to know that over the interface, you have to go and apply the IPsec profile. That's okay. In the lab section, you'll find the configuration in much more detail. But here you can see the step number 4, that NHRP registration request is going to the hub. Once hub is getting that request, then he's telling that your registration is successful. You can cache my entry. Okay, so hub is responding with the response, and now you can see that these spokes, so here you can see that more spokes have been added. So spokes have the NHRP cache static binding here. So 3.2 glued. So you can see that NHRP is telling that the tunnel IP and the loopback IP or physical public IP, tunnel IP or the physical public IP, they are glued together. And the spoke and the hub, actually, this portion you have the hub, and hub knows that your spoke 1 learning the dynamic entry, spoke 2 learning the dynamic entry, the same thing, tunnel to the physical IP address. Correct. So now your MGRE done, now your NHRP registration done, and then the routing exchange will happen. So now you can see that with help of GRE, the spokes, they are exchanging their routing database with the hub. So here you can see here and here, if they will go and do the IGP exchange routes over the tunnel. So this will also do the IGP exchange route over the tunnel, and same thing the hub will also do. So hub also, you can see that they are exchanging the routes with all the spokes. So far, the DMVPN that we are discussing is with respect to DMVPN phase 2. Okay, again, we will see the differences are there in phase 1, phase 2, and phase 3. There are total 3 different type of DMVPN differences are there. We are going to discuss in the upcoming section. But here you can see that clearly with help of GRE encapsulation, you can see the routes being exchanged. So the hub having the route 5.0 and this spoke having the route, so let's see, that's 2.0, and he has route 4.0. So what he want 2.0 and then he want 5.0. So you will see here that this is getting 2.0 and 5.0. See, likewise what he want, he want 5.0 and he want 4.0. So here you can see that he is getting 4.0, 5.0. So he is also getting 245, he also getting 245. And the previous section you can see that since he has 5.0, he is getting 2.0 from one of the spoke and 4.0 from other spoke. So now the MGRE completed, NHRP completed, routing completed, and now you can see the routing database as well. All right, so this is the way that behind the scene, the DMVPN is working. In this section, we are going to do the summarization that whatever we have studied so far. And after that, we have 2 more videos where we will see the configuration and few of the verification commands. Great. So we have 3 phases of DMVPN phase 1 that is strictly hub and spoke. Then we have phase 2 where there is some restriction in phase 2. In phase 2, all the spokes must know the routing of all the other spokes. So a spoke to a spoke, they have to know their routing databases. Although in phase 3, and that's quite useful and usable nowadays, that in phase 3, the spoke and a spoke can create dynamic tunnels. That means that they can talk to each other. That's the first thing. And second very important aspect we have in phase 3 is this, that hub allow to summarize all the routes from a spoke. That means the hub can send the summary routes to all these spokes. That's one thing. And set the next hop of summarized routes to itself. So not only that hub is sending the summary to the all the spokes, but the next hop for those summaries, hub marking to itself. Okay. Now, earlier we have discussed about NHRP registration and resolution, and we have seen that slide as well, that how the request from a spoke to hub is going, and then response, so that is the resolution request from hub to a spoke, it is coming. And there is third item in this, that is NHRP redirect, that is mentioned at the rate of DMVPN phase 3. So inside DMVPN phase 3, you will find in the upcoming lab section that over the spoke, we are going to use one keyword called NHRP redirect. So what does it mean? It means that the first time, so what is happening, that these spoke will do the request to the hub for first time to reach to the other spoke, means the spoke to spoke communication will happen. So here you can see that it is sending the request to the hub. Hub is providing the response. And once he has the response, so once the spoke knows that how to reach to the other spoke, so next time they will do the communication to each other. And that's something like if you go and use the redirect keyword, that means at that time, spoke to spoke communication will happen. Okay. Now, in the same line, in the upcoming two videos, you will find the configuration example and the configuration verification as well, where I will show you that configuration as well. Okay, and this is with respect to Cisco IWAN. Nowadays, Cisco IWAN, their clients they are using, but they are moving from IWAN to SD-WAN. So please go complete these videos, and we are very much completing DMVPN. Let us discuss about DMVPN configuration related to hub and spoke. Now here you can see that the configuration snippet with respect to hub in the hub router and how it is configured. So obviously we have to go and create the VRF. And suppose if you have two ISPs, then you can go and create two VRF. One maybe for MPLS, one maybe for the internet. So let me highlight here. You can see that we have one transport for WAN transport one. Maybe this is for MPLS, and one we can go and create for internet as well if we have dual connection. So simply you can go and create the VRF. You can go to the interface. You can assign the VRF forwarding and the IP address. And this is something related to front door VRF, which is equivalent to VPN 0 inside SD-WAN, Cisco SD-WAN Viptela. Great. Once we have this configuration, the next thing we are doing here is to doing the tunnel related configuration, correct? And this tunnel, again, we have to go and associate with the physical interface. So we have physical interface configuration. Next, we are doing the tunnel specific configuration, attaching the that particular tunnel interface with the tunnel source as a physical interface. You can see that protocol we are using the GRE multipoint because this is DMVPN, dynamic multipoint VPN. And then we have the front door VRF information over the tunnel. And then we have the IPsec profile. Actually, we can go and create IK based profile as well. I will show you in the lab section that how exactly this look like. Correct. So what we are doing in tunnel itself, we can see that we have IP address schema for the tunnel. Then we are using NHRP because this is the hub. So it is pointing himself as NHRP, because if you go and check the spoke related configuration, you'll find in this section we are pointing those spoke to communicate to the hub. So it can go and do some sort of DNS resolution. And then we have this tunnel specific configuration, and finally we are giving a static route. In this case, we have the VRF based static route pointing towards the gateway as per the diagram. Correct. So once we understand the MPLS transport related configuration, same we have with respect to internet transport related configuration as well. And here you can see that we have transport 2, that's for internet, IP address, and the tunnel specific configuration, NHRP related configuration, and then the tunnel key and the profile and the front door VRF configuration. Correct. So fairly straightforward here. Now, in case if we have, so you can see that since it is a internet transport, so obviously in between we'll put some sort of firewall, because this is data center edge device or data center WAN edge device. So if you have the firewall in between them, then you can see here that we have the static NAT configured, and you can see that 192.168 configured here, which again it is going to NATed, and then again it because since it's a static NAT, so the return traffic will also get NATed. Correct. Now here you can see the specifics about this configuration, that definition of front door VRF, then transport, then the DMVPN tunnel, then the uh, setting up of DMVPN phase 3 with the command, its key command, important command IPNHRP redirect, and then rest of the configuration. Now once you do the configuration with respect to the hub, then we have to go and put the configuration with respect to spoke, correct? Now inside this spoke, and one thing I just wanted to highlight, so there should be key exchange as well, and in the actual level I'll show you that the how the configuration look like. Even I will post those configuration as well with the session recording. So let's go here. Let's at least understand the high level points, and then in the lab section, we'll check a little bit more about this. So again, you can see the spoke configuration, and in this spoke configuration, go and give the IP over the physical interface. Then we are defining the tunnel. Now once we are defining the tunnel, then we are giving the IP NHRP NHS, that's your hub location, and then you are giving the primary and secondary hub IP address in case if you have two hubs. Like that, you can go and change the priority as well. So for few spokes, you have primary AB, uh, primary and secondary, and for few spokes, you may have BA as a primary and secondary. So like that, we can go and do the load balancing. You can see that we have IP NHRP shortcut. In the hub, it was redirect or direct, and here you have the shortcut just to do the communication related to spoke to spoke. So here you have the redirect, and here you can see that you have the shortcut, and then rest of the configuration is very much same that we have inside the hub. So only difference here you can see that we are using the NHRP shortcut, and we are giving the NHS, the hub location as well in this configuration. Correct. And then we have the static route pointing towards the gateway. Obviously, this tunnel protection IPsec profile is also very important, and that we will discuss in the lab when we'll go and verify the lab configuration and the output. Now, finally, the DMVPN spoke related to internet transport, and here you can see that IP DHCP, if you are getting the IP from DHCP, and again it depends. So if you are getting the IP from the DHCP, then you are vulnerable for certain attacks as well. In that case, you can go and create these ACLs related to non-50 500 Ccnp and boot PC and eco reply, etc. With certain ACLs we can go and apply like that. You can see here over the interface, because since it is a spoke router and maybe you don't have firewall, like we can leverage firewall inside the hub. So hub can go to the any type of appliance firewall, and then it can go to the transport or internet. But in since it's a small branch, and you can't afford firewall or security appliances here, so in that case you can use this device itself as a firewall, or this device itself as a small gateway, firewall type of gateway, and then you can restrict certain things there, correct? So the rest of the commands you can see, it's almost the same. Only thing here is that we are giving hubs public IP address instead of the private. So if you go here, you can see the public IP is 172.168.140.1. Like that, we are giving .1 and .2. It's a public IP, because again it will go to the firewall where it will do the static NAT, then it will go to the hub. Correct. And here also you can see that static route not required when using DHCP, it will automatically done for us. So this is the configuration, and let me quickly show you the lab topology as well. So we have the lab. In this lab, you have one data center, say DC1, and then we have two branch 3 and branch 5. Again, if you go and expand this, so let's go and check the first of all the data center. So inside DC data center, you can see that we have the obviously the core routers. They are connected with the master controller. That's one of the term used inside IWAN. We have the branch 1 and branch 2. These are the IWAN branch 1 and branch 2. You can see it is connected with core router. It is connected with different type of transport. Since you want to do the migration, so you can see the SD-WAN devices as well at this point of time. But let's do not focus on these SD-WAN devices at this time let's focus only on these two routers and their connection. So over the high level, we have one connection going to the core. So you can see it is going to the core. Then I have inter IWAN connectivity. So IWAN to IWAN direct link, or maybe in between you have some switch or something and it can be connected, or maybe it can indirectly connected means it depends upon design. So in this design you have one connection going to the core switch or core router, one connection we have direct connectivity with other IWAN, and then I have two transport, but although in this lab only one transport is active. So this branch 1 is connected with the MPLS transport and branch 2 is connected with the internet transport, like that we'll see in the next slide. So let me go to the next slide and let me show you the IPs as well. So here you can see that with respect to first device, so you can see the description as well. So here you have the description, and you can see that gig 1 is going to the core router, then gig 3 is going to the MPLS transport, and for that we have this particular tunnel 100 showing here. Then we have gig 4, that is direct connectivity, and then you can see the IP schema as well. Likewise, if you go and check the IWAN 2, inside IWAN 2 you can see that internet is gig 2. So gig 2 connection we have for internet, and you can see the IP, and then you have gig 4 as the IWAN to IWAN connectivity, and then you have gig 1 going towards the core router 2. So fairly simple, straightforward connectivity. You have two routers. They are going to connect it with, say, for example, this is going to MPLS. Let me clean this and let me quickly give you one reminder type of diagram topology here. So let me go and clean here. So you have two routers, IWAN 1, IWAN 2. One is going to the core switch. Here you can see this is going to core 1, and this is going to core 2, and then this is going to MPLS, and this is going to internet. So you can see the internet firewall is going to core, and then you have back-to-back connectivity, IWAN to IWAN connectivity, and then the IP schema that you can see here. So once you are familiar with the data center topology, data center diagram, or the same diagram topology you can create in GNS or any type of emulator as well. Then we have branch number 3. In branch number 3, you can see that branch 3, this is the master controller plus border router. Okay, you can see the master controller here. Again, these are the IWAN specific terminologies which will help you to do the performance routing, etc. So here you can see that we have the master controller, and then we have two ISP connection. One is going to MPLS, one is going to internet, and like that you can see here that you have gig 1 going to internet. So actually this side here, it is going to the internet. So this is, oops. So one side, let me highlight here with the highlighter. So this is going towards the internet, this is going towards the MPLS, and you can see the internet, some public IP address is there, and then for MPLS some private address is there, and then one interface is going to the LAN. So everywhere inside the LAN we have 10.x.100.0 type of subnet, and then since we have two transports, so we have tunnel 100 and tunnel 200. Those configuration we'll see later on. And finally we have other branch as well, as branch 5. Here again you can see that we have branch 5 master controller and the border router. So same device is working as a controller plus the border because you have only one. And then you can see the connected interfaces. So one is going to the maybe core inside that particular branch, then other going to the other edge device which is connected with internet. And here you can see that one is for auto tunnel, that's the gig 1, then one is going to the MPLS. So this gig 2 is going towards the MPLS. Then you have one of the core link, that's the gig 3, is going to the core. And then you have the gig 1 as well, that's to form the tunnel with respect to this direction. Great. So this is the topology diagram. This is the topology, and these are the IP schemas that we are using. What we are going to do that in the next section, we'll log into the devices and we'll see the configuration. First of all, we'll go and verify the baseline configuration related to DMVPN, VRFs, IP routing, etc. And then we have to go and perform certain tasks related to testing as well. In this section, we'll go and do the DMVPN related verification. So first of all, we'll go and log into the hub devices, where we'll go and check the VRF setting, the configuration, and then the output. And then in the spoke as well, we'll go and verify the same. And then finally, we'll go and do the baseline testing. So from one of the branch, we'll go and trace route to the other branch, and we'll see the path that they are using, correct? So let's go to the lab section where we have the devices. So you can see that we have DC, IWAN, BR1. BR is the border actually. So inside DC, we have seen this in the topology that we have the MC, that's the master controller, and then we have the border. So one master controller and two border 1 and border 2. So let's verify from the border router 1 inside the data center. You can see here the transport is true. And if you go and check the interface description, here we have the MPLS connection. Now, if we go and check the gig3 configuration, so you can see that our transport is this, and we have the VRF forwarding, means this particular interface is working as a front door VRF, and here you can see the IP address over this interface, correct? So this is the configuration over the physical interface. What about the tunnel? So now if you go and check the tunnel configuration, you can see that we have the tunnel, we are giving the bandwidth and then some net flow related configuration, but over the tunnel I have IP address, correct? And then a rest of the configuration related to IPMTU and non-broadcast multi-access, etc. But then we have the NHRP configuration that we have discussed earlier. We are working in phase 3, so we have a redirect keyword. We have some policy groups as well related to, again, we can do performance routing, we can do per tunnel QoS, and all those stuffs are there. So those configurations are here. Finally, we have the tunnel specific configuration. We have the IPsec profile. We'll go and check about this profile as well. So if I go and check sure and this particular profile, you can see that we have the IPsec profile. We are using Eigrp v2, and the best option we have here, we can simply go and check the IKE. And if you go and check like this, you will see that we are using Eigrp AES 256, GCM 256. We are using PRF SHA 512. Group is 15. That's the MD5 Diffie-Hellman group, DH group. Again, the rest of the configuration, like we have the Eigrp policy, and then we have the keyring. In the keyring, we are using any to any address. Any to any address. So that means that any spoke can come, and if they have this particular IP, they can go and do the Eigrp based negotiation or crypto Eigrp version 2 based negotiation. Then we have the profile here. You can see that inside the profile, we are giving the remote address as 00, that's the any, then your address, then the authentication pre-shared. Now in terms of scalability in IWAN, um, different deployment, you'll see that either you can use a pre-shared key or you can use some sort of central authority or central CA server based authentication as well, correct? So this is the configuration related to the profile, and we have seen that profile inside tunnel number 100 that you have DMVP and IPsec. So you can see the rest of the configuration is straightforward. It's not difficult. And then next we can go and check the route. If we have static routes here, you can see for transport number 2, we have a static route pointing towards the next hop. That's the gateway next hop, correct? All right, so same type of check we can go and do with this particular data center as well. That's DC, and the other router, that's the border 2. We can go and check the VRF, and then we can go and check the interface. So interface is gig 2, physical interface configuration. You can see the front door VRF is configured, and then you can go and check the tunnel configuration. So first of all, see that which tunnel is there. This tunnel is 200, so we can go and check tunnel 200 configuration, and almost the same set of configuration you can see here. Only thing here is the path ID. So we are defining the iDomain and the path ID. So internet is having path ID 2, MPLS having path ID 1. The rest of the proposals and other things are almost same. Now go back to the other device and let's check the VRF, because this branch having two transport, MPLS and internet, and inside this you can check the gig 1 and gig 1 having internet, and you can see that we have the June configuration as well. Since it's the internet interface, we have the NAT configured. These things we have discussed earlier, and then we can go and check the gig 2 interface, that's the MPLS. So straightforward configuration is there. Then we can go and check the IP route configuration, and you can see the two gateways related to front door VRF. Configured here, if you are using public IP in case of you are NATing towards the firewall, then in the gateway you have to give the public IP. Correct? Great. Likewise, we can go and check the last one. So here we can go and check the VRF, and then we can go and check the physical interface, and then we can go and check the tunnel interface as well. Sure, run interface tunnel 100. Great. Now the tunnel configuration that we are seeing here. So let me go back to the tunnel here. So tunnel here as well. Sure, run interface tunnel 100 and 200. So those tunnel interfaces that we are seeing here, you can see the tunnel configuration is less because mostly things are configured at the level of the data center or at the level of hub. Here you have NHRP configuration, and then you are telling that who is your hub. So we have this NHS configured as a hub. The rest of the things, so now you can see that we have the NHRP group, RS group 30 Mbps, and then it will go and match if we have the 30 Mbps anywhere. So you can see this RS group 30 Mbps, like that it is matching, correct? So one policy there, another policy there is matching, then the tunnel interface is glued with the physical interface, is using multi-port ZRE, transport is 1, and then the profile. Great. So now you can see the configuration related to DEM VPN. Now what we can do, we can go and check the DEM VPN. And we can see here that it is telling that it has two peer, one is 1030, one is 1050. And if we go and check here, show DEM VPN, first of all, we can go and check show IP int brief. So 1030 you can see here, and you can go here and check show IP int brief. You can see 1050 and show run int gig 2 is your MPLS, and show run int gig 2 is your MPLS, because this particular device having MPLS as a transport, so it is telling you MPLS, and then you can see the attribute D and D as a dynamic, so it is forming the dynamic tunnel. If you want to see the detail about this, you can go and check the detail about how it is forming, where it is forming, what is the QoS group policy, good amount of detail. It is telling you the transport, and then the IPsec related information and the flow related informations as well, correct? Same thing we can go and verify from here as well. So we can go and check the DEM VPN, and you can see that should have the primary secondary peers like this. So again, we can go to the tunnel. If we have tunnel 100, we can see that it has two tunnel 100 and tunnel 200. You can see the next hop NHS IP here, 10634.1. So one is 34, that's related to MPLS, and 36 is related to internet, and that's the reason why we are doing this show DMVPN. You can see the tunnel 100 and tunnel 200, and you can see their next hops. Great. So this way we can verify the DMVPN. Now if I want to check the route, correct, so I want to check the route related to obviously the VRFs that we have, and we have the VRF. Let me go and do like this, show IP VRF or show VRF, and then we can go check show IP route with VRF, and this is the VRF that we have. We can go and check. So static route showing here. That's okay that if we have routing protocols configured, so it will show you that what type of route we have. At the moment it's having the static route, and you can see they are pointing here, and we can go and check. Great, if it is not present it will tell you it's not there. So this is the way that you can go and verify the particular VRF specific route that is coming there. Now what I want here, that I want to check the routing table in general. It's a global routing table because things are coming from the global routing table as well. And here, this is branch number 5. I'm just looking for 10.3 subnet if it is coming from somewhere. So if I go and check show IP route related to 10.3.100.0, you can see that it is coming from this specific subnet. It may be learning from the default route that we have. So we have one summary route, it's a BGP, and you can see this is the place that it is learning, and you can check the detail, or the longer prefixes will cut down everything. So here you can see that we are looking for one of the specific route. It is learning from this particular subnet because this is quite a specific summarized subnet, and this is the next hop, or this from this particular gateway it is learning, correct? So what we want here is that we want to check the dynamicity of the DMVPN. So from this location, if I go and do the trace route, and let's go to the branch number 3, and let's check show IP int brief their LAN interface. So that LAN interface should be gig 3, and you can see this is the LAN interface, this is the IP. So if I go here and do the trace route, and let's check the trace route, so you will find that it should go first of all to the hub, correct, and from hub it will go to the destination, because we are doing this first time. But once the NHRP will get resolve the hub location, so that we have done the configuration related to NHRP redirect, correct, and we have the shortcut as well. So that means that if you go and run this next time, you will see that it will go to the next hop directly, because those DNS entry will be cached next time to the edge devices, to the IBAN branch devices, and next time you can see that it is directly going to 10.6.34.41, and you can see that show IP int brief 10.6.34.45 is mine, and show IP int brief, you can see 10.6.36.41. So let's see. So 34.41 and 34.40. You can see that it is going via this route. So that's the power we have with the DMVPN first time, because first time it is going via the hub, but hub has the information that how these devices, these channels can communicate directly, and the next time it is going spoke to spoke. Okay, these things has been taken care inside SD-WAN as well. In SD-WAN also now we have the on-demand routing, and there are so many things that we can do from the VS Smart policies as well. All right, so this was the demonstration related to DMVPN configuration and how we can go and verify our DMVPN related tunnels. In section number 3, we have to learn about infrastructure security. And the weightage, you can see the weightage we have 20%. So let me show you the topics here. The topics here inside 3.1 up to 3.4 related to security. 3.1, we have iOS-based AAA. Then troubleshooting security features such as IPv4 ACL, IPv6 traffic filter, reverse path forwarding, COP policies related to different protocols, and then IPv6 first hop security. So all these topics I'm going to cover one by one in the upcoming section. Let's just start with section 3.1, that is iOS-based AAA security features. What I have done, I have created one playlist here. You can see in this playlist, you have 6 different videos related to AAA. First of all, understand the concept related to AAA, and then how we can implement this AAA inside the switch, router, and ASA. So please complete these 6 videos after this video, and then we are completing section number 3.1. You can see AAA stands for. Now, obviously, you want to do the authentication, and then you're authorized to do certain tasks, and you are accountable for. That's the use of AAA. Now, one of the popular AAA server we have is the Cisco Identity Services, and over that you will see and learn lab related to that in the upcoming session. So let's try to understand the basic things, the baseline, and then on top of that we'll go and perform the lab task. So AAA can be used for multiple purposes like network device administration, network access like wired, wireless, VPN. Not only the network devices, but these identity services you can integrate with external AD servers, and then you have the user credentials, so you can give the authority to the users that what users can do at what particular time. Apart from that, there are multiple features related to, say for example, bring your own device user, or the corporate user, or the guest user, or the Wi-Fi user. So all these profiling that we can do. Again, there are a lot many things that we can do with the ICE server, with the AAA servers at this point of time. All right, so the basic ones are authentication, authorization, and accounting, and then we have policy and rule set related to all of these. What authentication will do, that it will authenticate the validated user, so it can go and do the authentication with respect to username, password, and certificate. It will tell that okay, you are the valid user. Then it will give you authorization. So how much access you want. You are privilege level 15 user, or 1 user, or 2 user. What commands you want to run. Again, which particular portion of network you belongs to, which ACL you belongs to, what is your SGT, security group tagging, what's your encryption. Each and everything we can give the authority. So for example, if we have the MAC based authentication like MAB, or user based authentication like 802.1x, or maybe authentication for IP phone, maybe authentication for wireless devices, maybe authentication for any user. Correct. So once you do the authentication, so first phase is done, then in the authorization phase you will get the access So for example, to certain device or maybe certain IoT devices, how much authority you have to that device, that will be decided by the authorization phase. And finally, we have the accounting. Again, this is for auditing purpose or reporting purpose, that the device that get authenticated and the authorization, then how much he has done the work. So here you can see that it will provide you the evidence of what you have done, like auditing. For network administration, a different type of commands for forensic analysis. For network access, session stats, session identification like MAC, IP, username, session state as well. Okay, so as name suggests, accounting, and starting with authentication. So authentication, authorization, and accounting, these are the key fundamental we have with the TPLS server. And in the upcoming session, we are going to learn more, and we are going to do the lab, and then we have nice arrangement and setup to understand more concept when we are going to learn this with respect to ICE server. Let us learn about access and AAA. Now, I'm going to do authentications with respect to users or MAC address or web authentication. In all these cases, once my devices will get authorized, authenticated, then the ICE will change the authorization. Now, what is the rule? What is the principle that ICE is following to do the authorization? We'll see that in the upcoming slides. But here you can see that, say, wired, wireless, VPN, all these endpoints, they are using, say, 80x, and VPN is using SSL IPsec VPN. So these 80x, say, wired or wireless client, they are using EIGRP, Extended Authentication Protocol over LAN, to communicate to ICE. And we'll see that we have different protocol. So let me highlight here, let me draw here so you can understand that we have three terms. One is supplicant. So your end device is supplicant, and between supplicant to the switch, suppose this is my switch where I am doing the authentication. So this switch is known as authenticator. So in between the supplicant and the authenticator, the protocol that is used is, say, for example, EIGRP over local area network, LAN, and in between radius server, or in between ICE server and the authenticator. So this is my authentication server or authenticator server. In between that, I have protocol called radius. Okay, so we have two protocols here. Here you can see that Cisco supports third-party solution via standard radius 80x, EIGRP, VPN protocol, etc. So in between endpoint and the authenticator, I have EIGRP over LAN, and here we have the radius protocol working. Now we'll see more on these things in the upcoming recording and section. It's just an overview that how things are there inside our network. Now again, you can see all those terms that I have my supplicant here, then I have my authenticator, and then I have my radius server or ICE server. In between, I am using the protocol, say, radius or Tachicus Plus. So here I have authenticator server. These are the terms used, or I'm going to use in the upcoming sections. Let's see that what network access components we have. So in this animation, you'll come to know that, okay, we have endpoints, we have network devices, authentication server, identity store. So you may have identity store such as, or for example, where you are storing the RSA tokens or some other card or some flash cards, etc. Something where you are storing the identities. So that's why you have the identity store. Now, the endpoint user either using 80x or SSL L2, L3, maybe over Ethernet, LAN, WLAN, Internet. they are coming and authenticating. So these are my supplicants. This is my authenticator. This is my server, correct? So how this process will follow? So endpoint, they try to communicate with the authenticator. Authenticator example, say Ethernet switch, wireless access point, VPN gateway, etc. Now in between that, you can see that I'm using layer 3 protocol radius/SNMP. I have my ICE server here, and the ICE server is storing its identity here in the form of, say, token server, Active Directory, Open LDAP, etc. So here one thing I can mark or highlight that for ICE they are using internal database, either SAM database, or they can use external database, say for example Active Directory, or you have some identity store server. Okay, so you may have these two databases. Either ICE can use internal or they can use external as a AD or other servers. Okay, so for up to this point, I hope that you understand that how this phase of authentication happens. In between this, you have EAP over LAN. Okay, EPOL. Here you have layer 3 protocol called Radius. And then you may have internal database inside ICE, or you may have external databases. Okay, so next what I'm going to do, I'm going to log into the ICE and I'm going to show you some of the tabs. Okay, these things like what are the components we have for ICE while we are doing the deployment. So you'll come to know that we have policy service node that is making the policy decision radius attack servers. We have policy administration node, single pane of glass or plane of glass for ICE admin, replication hub for all database config changes. We have MNT, monitoring and troubleshooting nodes just for reporting purposes. We have Pixie grid to connect to some third party devices where you can facilitate or where you can send the context aware data. Okay, so we'll see all these things in the upcoming section where we'll learn and understand about deployment of ICE and what are the key components inside that. I'm going to cover these things. Now what I'm going to do here that I'm going to log to the ICE and I'm going to show you some of the tabs on the top. Here you can see that you have what type of tabs available. Say you can go to home and then you can see the endpoints, guest, etc. Then you have context summary, operation, policy, administration, work center, etc. So one by one I'll show you few of the tabs that you can go and check over the dashboard. Okay, so let me go and log to my ICE and then I'll show you all these things in the ICE dashboard. So here I have my ICE. Let me log into my server and it will start logging. Once I will log in, then I'll show you few of the tabs on the top. So if you are logging first time, it will start loading. Now it depends upon your server capability. If you have good server hardware resources, then it will log immediately. Now here it is showing login message is successful. I am able to log in successfully. On the top you can see all the tabs are small, but you can see that we have the home, then we have endpoints. At the moment everything is blank, nothing is connected here. We have guest, vulnerability, threat. Then here you can see that context, visibility, endpoint, user, network, device, applications. Then operation, we have radius. We can check the live logs, live session, TACACS live logs. So all these logs related things we have inside operation. Then policy, we can create policy, say for authentication, authorization profile, etc. So you can go inside policy and you can go to authorization and then you can create authorization profile. You have downloadable ACLs, all these things. You may have some of the profile postures created by default, but you can go and create your own as well. Then inside administration, you can see we have very important tabs. So we have system, deployment, license, certificate, login, maintenance, upgrade, etc. Identity management is also very important. You are creating user accounts, group account like Active Directory or some third-party groups. Means you are creating groups to connect to some third-party databases as well. So that option you have identity store sequence, network resources. You can add switches, firewall, routers inside the ICE for the authentication authorization purposes. Then you have network device group, external radio server, etc. You have device portal management where you can do blacklist, BUOID, certificate provisioning, client provisioning, all those things. We have Pixie Grid that we can send the contextual information to the other third-party softwares. Then I'm going to click to the last tab, that is the work center. If I click there, you'll see that how many options we have, you see. So here you can see inside work center, I have network access, guest access, trust sec, one of the very important feature of ICE, that from where you can use SXP as well. You can use tag-based policies as well. Complete bring your own device policy set, profiler, postures, device administration, passive IDs. So all these things you can see how many options we have, and inside option also you'll find some options to add or to delete or to enforce policy. So all these things we have inside the ICE. Let us create authentication and authorization result rules. This authorization result rule I am later going to use inside the authorization policies. Okay, so as per our topology, you can see that I have IP phone, I have say PC for MAB, PC for .1x, means one is doing MAC address authentication, one will do user-based authentication. I have access point. So if I create my authentication rule, how many things we have? I have first of all say MAB PC, then I have say .1x PC, then I have IP phone, say then I have access point, say then I have two other things. We have router, which is going to do SSH, and then again I have one Cisco any client user as well over the ASA firewall. So I need to create one rule for any connect as well. Now you'll see that IP phone will be there, means as a profile. So we have profile for IP phone, and for any connect also we'll see that we can do permit access. So that means if I create authentication rule, say for MAB, this rule, so this will take care of IP phone as well, because this is also doing some MAC based authentication. This will also take AP as well, because this will also do the MAC based authentication. So one rule will take care of all these three. Next, I'll create a rule for .1x, that will be authentication rule number 2. And then I will create a rule collectively for say SSH and any connect. So that means I'm going to create 3 rule. One is MAB rule that will take care all MAC based authentication. One is .1x rule that will take care of users, and one is say router SSH plus any connect. Okay, so these authentication rules I'm going to create 3 rules. Then when it is coming to authorization result, so at that time we have say for IP phone already we have profile, so I'll leave that. For any connect, because we are using say permit access, so that also we can leave it, but I need to create authorization result rules for say MAB, for .1x, for R1SSH, and for access point. Okay, and remember my MAB and .1x, they are inside say VLAN 10, My IP phone will leave that IP phone. IP phone has voice VLAN of say 30. My access point, this is in VLAN say 2020. For R1 SSH, we have some other conditions. Okay, we'll see that. So let me go and create first of all authentication rule, and then I'll show you how we can create the authorization rules. Let us create authentication rule. So we can go inside policy, and inside policy we have authentication. Few rules are already there. Let me delete and create new rules so you can see those rules. Delete both the old ones. Save it. And then let's create new rule. So first of all, say I'll create a rule MAB. Now what is the condition for this? The existing condition and the new condition. I know that I have existing condition here, and that will be compound condition. That will be wired map. So I can use wired map. Then the allow protocol. For allow protocol, I have say default network access. Then because this is the MAC based authentication, so instead of internal user, we should select internal endpoints. Select internal endpoints and done. So we are very much done with the authentication rule, authentication policy, that is MAB. Then next I'll go below. I'll create .1x. So .1x. Now this time the condition is say wired .1x. So I'm going to select compound condition and then wired .1x. Now what will be the network? Network again I am going to use the default network access, and this is correct. The use is internal user, that's correct. So now my two authentication policy done. Our final policy is SSH and any connect. So I'll go and create one new policy, say router SSH and any connect. Now for this I don't have condition, so what I will do, I'll create new condition. This time the condition is virtual port type 61. Why? So let me show you that why we need that. Actually I need port number or attribute number 61. So for that I can go and search say for example virtual, or I can select say search say name for example. So here you can see that I'm not able to search port number 61, that is the attribute. So what I can do in this case, suppose if you're not sure, simply go and type nash, and in the nash you will get the attribute numbers. So here the attribute is 61, nash port type is 61, and then again I'll go and search this time virtual. So if I search virtual, you should have give the correct spelling. Okay, so virtual, we have virtual port type 61 as well. We are very much done up to this point, and in the allowed protocol I'll select the same default network access. We are very much done with three authentication policies. Say MAB, it will do authentication for all the MAC based devices, .1x for user, and R1 or router 1 SSH any connect we have. So let's save this. Once we are done with the authentication policy, I'll go and I'll show you that how you can create the authorization policy. So for that you can again go to policies, authorization, and then you have results. You can simply go to the authorization and the authorization profile. Inside authorization profile, I want to create profile, say for first of all .1x, so for .1x, and then the DACL permit all. VLAN we have for this is VLAN 10 as per our diagram. Scroll down. Advanced attribute setting, we don't have anything. I can click here submit. Likewise, again I'll go and I'll create one more for MAB. Same set of things I am going to give. This time for MAB, and the VLAN is also 10. I can give VLAN 10, no problem. So our two authorization profile is done. Likewise, I can go and create two more. One is for SSH. So we have router 1 and we want to do SSH for that. For this particular SSH, what is the condition? Now my condition is that it will get full access, full privilege level 15 access. So I'll go and select web authentication, local web auth, and in the bottom you can see that I have full privilege access. Okay, so this you can give if you have some time. So here also you can go and select some idle time as well. So say idle time limit is, for example, 2880000. Whatever idle time you have, you can select that. Submit. We are done with these policies profiles, and let me go and create the final one, that is for access point, that is for AP. And for AP, what is our VLAN? That VLAN is 20 as per our diagram. That is also done. Alright, so now we can check for, and if you want to filter out, you can go and filter your policy. But anyways, for AP.1x, MAB and SSH, these four we have created. And when we are talking about the policies, so three policies we have created. Policies, say I haven't saved those policies, so that's why they are gone. So you should go and save those policies as well. So let me redo that. MAB, this is existing condition, yes. This is compound one. That will be wired MAB, correct. Then allow protocols, that is correct. Internal endpoints, let me go and choose internal endpoints. We are done. Now one more, that is my .1x condition, same, this time wired .1x. So we'll see where is our wired .1x, and then the protocol is this, and this is also done. So now I can finally save this. Okay, saving it. So this is the way that we can create our authorization profile and authentication policy. Our next task is to create the authorization policy. So you can go inside policy and then authorization. Here we have to create all those policy. Say whatever by default, let me delete that. The old policies I'm going to delete, because now I'm going to go and create the new policy that we are required or we needed here. So what are the policies? Let me list all those things that I'm going to create here. So I'm going to create authorization policy, say for .1x mab. We have one access point, we have IP phone, we have R1 SSH, we have ASA AnyConnect. So these 6 authorization policies I am going to create one by one. So let's do it. Alright, so we'll go here and create new rule above. I can give say mab. So what's the condition for mab? It will be endpoint workstation. So I'll go here and then I will select say endpoint identity group is there. So let me go and select that. Inside endpoint identity group, inside say profile, let me scroll down so I'll get to workstation. That is the first thing. Second thing, that yes, it is existing condition that will be wired map that will come under compound condition. So let me go to the compound condition. Once I'm inside compound condition, I can scroll down, I can select wired map. Now what is the next thing we have? Next attribute we have is the NAS IP. So we have switch in between. And what's the IP for that switch? We'll give that. So my NAS IP address is say 198.119.10.28. Okay. And what will be the final condition? So that's enough. Now we have one permission. So what's the permission we have now? We have permission inside a standard that is for map that we have created in the last recording. Done. So you can see now map workstation wired map. This is the switch IP and this is the permission. Likewise, I can create other policies. So let me go below and let me create policy for .1x. .1x, simply I'll go inside condition. Condition is compound condition, that will be wired .1x. I'll go here, I will select wired .1x, this is here. Then I'll add the attribute value. What's the attribute value we have? We have NAS IP. That will be the IP of the switch. That is the radius NAS IP 4. Let's give the IP say 198.119.10.28. And then here we have one user as well. Okay, so we'll add attribute value one more time because we need to add one user. Username is say, first of all, let's select with that user. This is 1. For example, user is CCI. Alright, then we'll go and add the permission. We have one permission for .1x. Done. Okay, so here you can see I can add map.1x. Let me save this. Next I will create policy for say IP phone. So let's do that as well. And our IP phone is also connected with the same switch. So again I can create one rule below. And here I can go and IP phone. This will be the part of endpoint identity group, obviously. So if I go inside the profile, you will get that IP phone option. Let me click profile. It is opening up. Let me scroll down. Cisco IP phone. What's the conditions? I don't have any pre-existing conditions. Only thing I can do here is that I can add the NAS IP. So that NAS IP will be the same 198.110.28, that is the switch IP. Then finally I'll add the permission. Permission, we have default Cisco IP phone permission there. Done. So now we have 3 rules. Likewise, let's create other rule as well. So one rule we have, say, any connect. Let me go and add any connect as well. Any connect. Now for any connect, do we have anything that we can select from here? No, we don't have. Then I'll go here. And do we have any existing condition? No, we don't have. Now for any connect also we have user. So let me give the user. User is, say, for example, Cisco. And then here it is connected with, say, ASA firewall. So for that I can give the IP address of the ASA firewall. That will be 198.110.29. For this we have permission. What permission we needed? This is like, let me show you this permit access. Yep. So we are very much done with 4 authorization policies. Now we have to add 2 more. One is for SSH. So let me go below. I'm going to add one more for SSH. For SSH, we have any group? Yeah, we have one group. And that group is under, say, user identity. So I haven't created any group. What I can do here, let me reset this. Okay, so I have this 4 authorization policy already. What I'll do, I'll create one group for my SSH. So for that, what I can do here, I can go to administration, groups. Inside that, user identity group. Inside user identity group, I can create any group, say for example, lab access or lab group. Submit. Now I can go back to my policies and my authorization policy. Alright, so now I can create one rule below SSH. This time I can go to my user identity groups. I have lab access user. Then we don't have any condition, so we can create a new condition. And new condition, I can add the IP address of the router, so I can search with NAS. The IP address of the router as per our topology is 198.110.30. Then we have permission you have created in the last section. What is that? That is for R1 SSH. Okay, so we have created 5 policies. Now we have to create one more, that will be the last one, and that will be access point. So for AP I can create. The problem here that by default you won't find AP is profiled here. So suppose if I go here inside the profile, and inside the profile if I search, the access point is there. So by default you will not find that access point. So that means what you have to do, that you have to go to your policy and profile and you have to add that. So I am here inside policy. I can go inside profiling. You can see profiling policies we have. I can expand that. So I can expand that. I can go to Cisco, starting with C, that Cisco devices, Cisco access point, Cisco Air AP, and then I can tell, okay, yes, create the matching group. So once you create this, save this, and then you have to come back to policy and authorization. So come back here, then again we'll create new, and this time you will find that the access point will be there. So access point, and in the group, that will be the endpoint group. If you go and expand that endpoint group inside profile, this time you'll find that your access point, Cisco Air AP is here. We don't have any pre-existing condition. I have one thing, that this AP is also connected with the switch. So I can give the NAS IP. I can go here and I can give, say, NAS IP 28, and then I have permission for that. That is for AP that we have created. For AP. Done. So this is the way that you can create your authorization policies. In this section, I will show you that how you can configure this switch for your AAA and what are the configuration required over the interfaces. So you can see here I have interface gig01 that is connected with two domain. One is the voice domain, one is the data domain. Voice VLAN is 10, data VLAN is 30. The other interface gig0/2 is connected with access point. So we'll do the configuration for the switch in this particular section, and in the next recording I'm going to do the configuration with respect to, say, R1 SSH method and then the ASA firewall for AAA. Okay, so let me go log to switch number 2 and then I will walk you all the steps. So here I am inside the switch. First of all, I will enable the AAA new model. Then I can go here to authentication, login, say no authentication for line console 0. So for line console 0, logging authentication is no auth. Then I am going to give a name for the radius server. So the radius server name is, for example, CCI. What is the address for our radius server? That is 198.1.10.27, and here you can see what is the auth port. So auth port is 1645 and accounting port is 1646. Key is Cisco, so everywhere we are using radius key as a Cisco. Now once I have this radius server defined, what's the IP address and the radius key, then I'll create AAA group, and this AAA group, say for server, radius name is ICE, where my server name is, the server name is, say, CCI. Okay. Now once I have this basic configuration, then I will do configuration for AAA, that is authentication, authorization and accounting. So authentication .1x, default group is say ICE, then AAA authorization. So authorization I need to give network, default group is ICE, then AAA accounting .1x, and then they start. So I can type question mark here. Okay. So default start stop is group ICE. We can check here what are the configuration we have done with respect to AAA, and these many configuration we have done so far. Okay, now next is to give the configuration related to radius attributes. So I can go to radius server, say attribute 6 on for login auth, then 8 and 25. So for 8 I will give include access, and then for 25, so let me go back, scroll up, yep. So 25, attribute 68. So what attribute I have used, let me click up arrow, and yeah, that's correct. Then we have attribute say 25, that will be for access request include. Now we have some vendor specific attribute, so that also I'll give radius server vendor specific attribute send authentication. Authentication and authorization will happen in the single packet, so we don't have command related to authorization. So authentication and accounting. So we are very much done with the say global configuration related to AAA over the switch. I will give IP device tracking. If you have several VLANs, then you can do IP routing as well. Finally, I will give .1x system auth control as well. So we are done with the device configuration. Now what I can do here, I can go to gig 0/1. So we can give the interface related command. First of all, I'll do switch port mode access. Then the second thing we have, that is the switch port vs VLAN is 30. Okay. Then I have to give authentication command. So authentication host mode is say multi auth, because we have two domain. Authentication order say mab and .1x. Authentication priority .1x map. Authentication port control auto. Okay, so these are the commands related to authentication. Now because here we are using the MAC address authentication as well, so I can give map, then .1x PIE authenticator, and we are very much done. Finally, we have spanning tree port fast. And then we can do shut, no shut. Alright. Now we can check the interface related command gig 0/1, and here you have all the commands. Now next we have interface 0/2. So we'll go to interface 0/2. Here also switch port mode access. Then authentication. Now this time the host mode is multi-host, because here I don't have two domain. Here only I am doing Mac based authentication. Because I have only Mac based authentication, so order I can give MAB authentication. Port control is auto. MAB .1x PAE is, so PAE is authenticator, and we are very much done. Finally we have spanning tree port fast, so port fast, and then we can do shut, no shut. We can check the configuration. We can type show run interface gig 0/2 as well. So this is the configuration where I have connected my access point. So this is the way that I can configure my switch. Next we have to do the configuration for router R1 and the ASA. So let's enable AAA here. Then the authentication login, same thing that we have done in the switch. Say no auth none. Then I can go to line console 0 and login authentication is no auth. Okay. Then I can go and create, say, radius server. That radius server name is a CCIE, and what is the address? IPv4 at 198.190.10.27. Auth port I can give as 1645, and account port I can give, say, 1646. The key is Cisco. Exit. Then again I can create AAA group, and that is radius ICE. The server name is CCI that we have created. Then we have AAA commands like AAA authentication and authorization. So let's do that. The login is SSH, but our group is ICE. Likewise, AAA authorization is exec mode SSH, and the group is ICE. I can go to line VTY 02, say for example 98. I can give, say, login authentication SSH, authorization exec is SSH, and then if you have requirement for session timeout, you can give that. If you have exec timeout, that also you can mention. That's it. Let's do the firewall configuration. Firewall side, it's very simple. You can go to AAA server, say ICE protocol is radius, then say AAA server ICE, say ICE, and some management. Obviously you can give the host address, say 198.190.10.27, and you can give key as a Cisco, and that's it. So this is the configuration related to SSH, and this is configuration related to ASA communicating with ICE server. Now we reach to section 3.2, where we have to learn about router security features. First of all, I'll go and cover ACLs related to a standard and extended ACL with the lab. Then I will cover time-based ACL. After that, we have to learn about IPv6 traffic filter and unicast reverse path forwarding. So let's start section 3.2 with the basics of ACLs and the lab. We have two forms of ACL. One is a standard ACL, one is extended ACL. Now, as name suggests that when we are using a standard ACL, then we have limited capability. That means that we can create rules or table entries related to source IP, for example. But when you have extended ACL, so at that time you have option that you can match source address, destination address, UDP port numbers, protocol, etc. TCP UDP port numbers, protocol, etc. Okay, so let's try to understand one by one that how ACL works. Now here you can see the normal flow of ACL traffic. ACL, you can think this just a table, and if certain packet will go and hit that table, this processing is from top to bottom. First of all, it will check the first entry, second entry, like that, and then it will go to bottom. Now again, when it will match the entry, it will check that do it has permission. So is it permit or deny? If it is deny, obviously it will block it. If it is applied on certain interfaces, either ingress or egress, depending upon how we are applied this policy. But yeah, if the deny statement is there, that means the ACL wants to block this. If permit statement is there, ACL will allow it. So here you can see that incoming packet, you have the table. Do you have match? Yes. This table is permitted. Yes, packet will get processed. Now no. Access list configured? No. Again, if you don't have ACL configured, that means the packet will get processed. If you have ACL configured and apply to certain interface, then according to that table entry, it will match and process. So for example, here you can see that ACL is configured. Yes. Is packet permitted? No. That's the deny. So this is the deny statement, and this is the permit statement, and this is without ACL. So that means we have three conditions. With ACL, permit deny. Without ACL, obviously the packet will go and get processed. Now, when we are talking about the standard ACL and extended ACL, so at that time, again we have option. We can go and create named based ACL. Now, when we are talking about named based ACL, so that means that instead of numbers, here you can see on your screen that 1 to 99 and 1300 to 1999, this is the range, numeric range for standard ACL, and for extended you have range 100 to 199 and 2000 onwards, 2000 to 2699. Okay, now we have option that we can use these numbers for a standard or extended, or we can use named based ACL as well. Now, what is the syntax for the standard ACL? I told you it's very easy and straightforward. You can go and give, say for example, access list number. So access list, for example, 8. Then you have these statements: permit, deny, and remark. So suppose if you want to put some sort of remark or comment, you can go and use this remark keyword. Otherwise, we can go and give the permit, deny, and then you can see you have to go and give the source address and the wildcard. Now this wildcard is interesting, and it is mostly covered in the CCNA world. So suppose if your subnet mask is 255.255.255.255, then your wildcard will become 0000. So wildcard is just the reverse of the subnet mask. So suppose if the subnet mask is 255.255.255.0, the wildcard will become 000.0. 255. Okay, it's just the wildcard, means which particular network you want to allow, you want to deny, and if you want to use the range, so then you can go and use the wildcard bits. Again, the syntax here you can see, and the description. So access with number, the permission, the source address, and then the wildcard. That's for the standard ACL. Now, if we go and see this standard ACL, this is not going to solve the purpose, because still there are so many things that we want to use uh, inside the ACL entry or inside the permit deny entry. So when we are creating the table, so table creation is one thing, and again where you want to apply this uh, table, either going outside or coming inside, and which interface, here or here. So all these things are very important. Now when we are talking about applying the policy or applying the access list, uh, applying ACL is same, either it's a standard or it's extended. Okay, so application, how you're applying this ACL is the same, is the common in both the case, but the fields are different. So now if we want some more options, we should go and use the extended ACL. So let me show you that how this extended ACL look like. Again, all these examples that we are seeing here, and you can make this or put this as your personal document or notes as well. I have given all these notes here. So you can create the ACL. Here you can see, still we are talking about the standard ACL. You can create it, you can create it, and then you can apply it. We'll see these things in the lab section. Okay, now let's quickly go and learn about the extended ACL. Okay, and then I'll come back, and we have one use case that I just skipped, so I'll come back and I'll show you this use case as well. So when we are talking about the extended ACL, you can see the numeric range is 100 to 199, 2000 to 2699. But the good thing about this, that you have long entries, long list of things that you can match. So you can match, for example, ICMP. I can go and create access list related to ICMP, and then here you can see that ICMP, let me highlight it. So ICMP source, the wildcard destination, the wildcard, because here you have source address, destination address, then ICMP type, the echo type, message type, precedence, toss, log. Even we can use the log keyword as well. Likewise, we can go and create the ACL policy or access list policy related to IGMP as well. So ICMP and IGMP, both we can go and create inside the extended ACL. Then we can go and create the ACL based on TCP, ACL based on UDP, and we'll see that we can go and match different type of protocols as well. So here you can see that we have the list of services that we can match related to TCP, UDP. Not only that, but we can go and we can uh, specify, or we can match certain fields related to EIGRP, GRE, ICMP, IGMP, IGRP, IP, Ospf, TCP, UDP, etc. Correct? So this is the power we have with the access control list, and it's actually quite powerful uh, in terms of defining or creating the ACL. So extended ACL is quite powerful. Here you can see the example that you have one statement ACL 100, you want to permit TCP any source, any destination equal to SMTP. So if you have any mail transfer protocol, you can go and match. Like that, you can go and match the DNS query for any to any equal to DNS, any to any related to ICMP echo reply, OSPF TC any service BGP, because BGP is using TCP port number 179. Okay, so these are the formats. In the lab section, we'll check both the ACL, and that's the standard ACL, and then we'll go and check the format for the extended ACL as well. Now in between, we have one nice example that will help you to understand more about the wildcard bit. So suppose you have this type of segmented network, say 141.108.1.0. Again, you have 1.0, 1.2, 1.3, etc. But it is divided into two segments, odd network and even network. And suppose you want to block the odd network, and if this list will grow, that means you have to put uh, so many lines for ACL, and that's not a good thing because all the ACL entries will get processed with respect to CPU. The CPU utilization will be more. This is important point here is that whenever we are using ACL, ACL is something that is going to consume not only the CPU cycles, but it is going to consume the MAC as well. So all the platform, they have their allocation related to ACL MAC entries as well. So it's very important for us that either it's a router, switch, or firewall, we should group the ACL. If we are not able to group the ACL in the object, so we should use the wildcard carefully. So we should have the summarization or summary type of network ACL permission or deny. Okay, so now the use case here is that you create one ACL. Instead of 20 lines, you use only one line where you want to permit all the even network, but you want to block all the odd network. Now, how this can be achieved? This can be achieved with single network statement, and that single network statement here is access list 1 permit 141.108.2.0, and then the wildcard that we are using 00254.255. Now, how we can do that and how we can understand this? So you will understand this when you are talking about odd network. So 1 3 5 7, if you go and convert this into decimal, so here you can see the odd numbers, say for example 1 3 5 7, all these they are ending with 1. All the even numbers, they are ending with 0, and that's the thing we have. So in wildcard bit terminology, 1 is don't care, 0 is must match. Okay, now if you create this particular, so let me show you the mathematics. So if I go here and if I have 8 digits, say 1 2 3 4 5 6 7 8, we know 1 2 4 8 16 32 64 and 1 to 8. Okay, so that means when you have 255, if you have all the 8 bits are 1, it will give you 255. But when you have 254, that means you have 4 5 6 7 and then 0. So if you have a 0 in the last bit, that means you are going to allow the even network. So this ACL will go and block the odd network. Okay, again you can pause the recording and you can read this busy slide that we have. But this is the overall concept, that how we can efficiently go and utilize the wildcard bit, and this is true for both the standard and the extended ACL. Even if we have the extended ACL, we should use the wildcard bit carefully. Alright, so these are the terms and theory we have related to a standard and extended ACL. Let's stop here, and in next section we'll go and create few of the ACL and we'll play around with that. Let us perform the lab tasks with the ACL. What we want to do here is that we have this lab setup first of all, and you can see the IP addresses like that. We have done the configuration over these interfaces. These IP addresses are there. All the devices, including the loopback addresses, they are running EIGRP, and all the networks are advertised. So now if I go to R3 and if I check these loopbacks are reachable or not, it should be reachable. Then what is the task? First of all, we'll block all the loopback. So block all the loopback. It should be loopback, say all the loopback, whatever loopback we have. starting from 1 to 4, from R1 to reach to R3 with the ACL, and then we'll go and play around with the odd and even methodology. Means even will allow and all the odd will block with a single ACL statement. Alright, so let me quickly show you. If I go to R3 and if I do show IP route for EIGRP, here you can see that I have the network that I'm getting from R1, and if I go and do the ping, so here you can see that I'm able to ping 2.1 and then 3.1 and then 4.1 as well. So all the loopback addresses are reachable. Okay, great. So now what I want to do, that I want to create access list, and again we have option. We can create numbered ACL, we can go and create named ACL as well. So here what I will do, first of all I want to deny one of the loopback just to show you. So deny 1.0, and then we should give the wildcard bit, and then I'll go and permit rest. So we'll go and do the permit for 10.10 2.0 0.0.0.255. We'll go and permit 3. We'll go and permit 4, like that. And now this should be applied to the interface. Now if I go and apply this to interface, what will happen? So here you can see the problem. IP access group 10, and in the inward direction, that in the receiving end I'm applying. You'll see that with this the EIGRP will also go down. Why? Because you're applying this policy coming inside here, and then you are blocking the EIGRP advertisements as well. So let's go back and see. Here you can see EIGRP is down. I don't have the EIGRP neighbor. So what we can do here, that first of all, let me show you the access list. We have these statement. So I can go and create one more access list, say 10, and I'll do permit any. At the moment I'll do permit any, and next time we'll go and see this thing, that how we can play around this with the extended ACL, because in extended ACL we can go and give the permission, and that's highly tunable. So now you can see that I am getting the EIGRP neighbor back, and we are getting this 10.1.1 as well. But if we go and ping, okay, basically we are looking for these loopback network. So 1.1, you can see there's 10.10.1.1 that is coming from R1 is not reachable, but if I go and check 10.10.2, 3 and 4, those are reachable. So let me quickly do the ping for 2.1 and 3.1. These are reachable. Now what we have to do here, first of all, let me quickly show you the ACL. So this is the ACL, and if you want to convert this in the named base ACL, you should go and use IP access list standard, and then you can give the name, say loopback router 1. Then you can go and give the same thing like permit or deny, whatever. So I can go and give deny this, then permit rest of the network. Okay, so this is one of the way that you can use it, although I'm not applying this, but yeah, you can see that you can go and use the named based ACL as well. Not only that, but here you can see that we have a remark option as well. So this is R1 loopback. So what will happen with this, that in future if we go and check this, you'll find that okay, you have the remark as well. So let me show you this, how you can check the remark. and they should become inside the ACL, actual ACL. So here you can see that you can go and check the remarks as well. Now let us learn about the extended ACL. So what I'll do, I'll go and create few loopbacks here, say 2021.0 slash 24 2022.0 slash 24, and we'll create the rule that 10 10.10 and 10.10.20 will communicate only with 2021.0. Likewise, 3 and 4 will go and communicate only with 2022.0. That's the rule. That means 1.0 will not communicate 3.4, 2.0 will not communicate with 1.2. Like that, we can go and create the extended ACL. Although we are going to give only the permission related to source IP, destination IP, but we can go and use, or we can go and give TCP, UDP, or certain application permissions as well. Okay. So let's go to the R3, and meanwhile I'll go and create few of the loopbacks at 2020 1.1 255 255 255.0, and then loop back to 2020 2.1 255 255 255.0. And now if I go ahead and check in R1 show IP route, we should get this 20 network. So if I ping say 2021.1 with a source of 10.10.1.1, it should work. And if I ping with 2.1, it should work, but after the policy 3.1 and 4.1 should not work. Okay, so this is the policy we want to apply. Now when we are talking with respect to R1, I can go and apply this policy here in the inward direction where I'm learning those network over the fast Ethernet 0/0. So let's do it, and we can go and use the named based extended ACL as well. So I can go here and I can use IP access list extended, say loopback to loopback. Okay. Now what I want to permit the IP and who is the source, who is the destination. So for example, the traffic with the source say 20.21.1, this is the source, and the destination is say 10.10.1.1. This is permitted. Then 2.1 is permitted. Okay, then permit IP host, and we have option, we can use host or I can go and use wildcard as well, say 2.1.0.0.0.0. This 0.0.0.0 is nothing but the host, and again I can go and use say 10.10, say 3.1.0.0.0.0. Likewise I can go and use 4.1.0.0.0.0. So what this access list is telling, that you have permission from this host to this. So 21.1.1 can access with these two IP, and 2.1 can access with these IP. We know that we have implicit deny to all. So that means apart from that, if we have any other traffic which is coming related to these IPs, they are going to be blocked. Correct? Alright, so what I will do, I'll go and apply this policy to F00 inward direction. So let's go here and fast Ethernet F00 IP access group, say loopback to loopback in inward direction. Alright, so once we apply this, and let's see, because apart from these statements, all other statements are denied or implicit denied. So we can go and check show IP EIGRP neighbor. So here you can see that neighbor is down. Why? Because we are not giving EIGRP related statement here. So what I can do here, that I should go to this statement, and again you can check the access list. Now at this point of time you can learn how to edit as well. So if I go to this particular access list, say IP access list extended loopback to loopback, and instead of adding all the lines one by one again, I can go to line number 50 and I can permit, say, EIGRP. Again, if you know what exact IP, you can give that exact IP, but I will do permit EIGRP any. I can see this EIGRP is back. Alright, so that means that policy is done, and if I go and ping, this should be working, and this should be working, but as per our rule, this should not work, and 4.1 should also not work, but this should be reachable with 2022.1. So if I go and change the destination, say ping is 2022.1 and the source is 10.10.3.1, this will work, and even 4.1 will also work. Now when we are talking about extended ACL, so here you can see that what are the other things you can match. So you can match EIGRP, ESP, GRE, ICMP, IGMP, IP in IP, NOS, object group. Even we can create object group as well, OSPF. So we have these many options, and we know that TCP and UDP is huge. At least the TCP is huge because most of the applications they are using TCP. So if I go to TCP and then if I give, say for example, any, it will ask you that TCP which port, is it equal to, greater than, less than, equal to, not equal to. All these options we have. Now suppose if I go and do equal to, then it will give me the option to 65,000 port numbers, and that's the power and capability we have with the extended ACL. Right, so this was the lab related to a standard, and then we have done the extended ACL lab. The next ACL we have in this series is time-based ACL. How we can do it? Again, the creation and the use case is very easy. Means we can create and use it inside the ACL. So first of all, we have to go and create the time range. We can go and create the time range, and we can give any name. That name we can refer later on in the actual ACL. And we have option. We can create the absolute time range, or we can create the periodic time range. So absolute means that with one name, we can create only one absolute time range. But periodic means that with one time, we can create multiple periodic statements. Correct. So the first line, you can see that absolute start at 8 a.m. 23 of May, ending at 8 p.m. 26 May. So it's a strict 8 to 8, 23 to 26 May. Correct. Next, you can see the periodic, that we can give the weekdays from 6 to 11 p.m. Correct. And this is applicable for weekdays for that duration. But again, here you can see that note we have that only one absolute time statement is allowed per time range, but multiple periodic time statements are allowed. So if we are using periodic time statement, we can use multiple. If we are using absolute, we can use only one. Now, once we have the time range defined, then we can go inside our ACL. So here you can see that we have the ACL, and inside the ACL, say we have one statement, and by the end of this statement, we can go and use. So what will happen with this ACL? That deny any equal to port number 80 or HTTP with this particular time. What is that time? 8 to 8, 8 a.m. to 8 p.m. 23 to 26 of May, and then we have seen that 6 p.m. to 11 p.m. in the weekdays. And then rest of the things are permit, IP, any. Means that this ACL is applicable only with this duration of time or time duration. Okay, so this is the use case. Actually, this is nice use case with when we are adding with ACL. So time range become important if we are putting some site tight security with respect to time inside the ACL. In this section, I'm going to show you the lab that how we can go and perform the task related to IPv6 access list. And in IPv6, the access list, we are known as a traffic filter. So I'm going to show you that how the traffic filter works inside IPv6. We have a small lab topology here. You can see that in the lab, we have R1 and R2. These two routers, we are going to assign IPv6 addresses over the physical interface. So gig E0/1 and gig E0/1 we have on both the interfaces. Although these IP addresses, IPv6 addresses are already assigned. And then I have created one loopback 1. For loopback 1 also, I will show you that I have assigned the IPv6 address. And over this R1 and R2, I am running IPv6 OSPF version 3. Okay, so IPv6 based protocol is running here. And then what we need to do here, we have to go and we have to do the configuration related to traffic filter or access list inside IPv6. Okay, now what is happening that when you go and create this, it will ask you. So when you go and create the ACL, it will ask you, okay, IPv6 ACL name, and then you can go and do the configuration very much same that we are doing in the extended ACL with respect to IPv4. But when you go and apply this ACL, so at that time it will ask you over the interface that IPv6 traffic filter and then the access list name. So idea here is this, that we want to apply, first of all, we have this up and running lab, and we want that router 1 loop back will not go and telnet. So port number 23, we want to block for router number 2 loopback address, but rest of the things like ping and all the services will be as it is. So we are going to deny port number 23 access from router number 1 loopback to router number 2 loopback with respect to this particular access list. So I'll go and do the configuration. Let me quickly show you that what is configured over router 1 and router 2, how they are looking like. So we know that to check the IPs related to IPv6, you need to use one extra keyword. Instead of IP, you can go and use show IPv6 interface brief. And here you can see that we have 10:1 and loopback we have 1:1. Like that, I can go to router number 2 that we have here. And here also we can go and examine the IP addresses. Apart from that, if you want, we can go and check show IP v6 route. And here you can see that we are learning this particular route with respect to OSPF version 3. So if I want to ping this particular IP, that's 2:2 with the source of loopback 1, you can see we are able to reach. And if I want to do the telnet to this particular IP with my source interface loopback 1, seems that ACL is already created earlier. So let me quickly go and check gig interface 0/1. I can see that one ACL is already applied. So I'll go and remove this because we want to create our own. So use the no keyword and remove this ACL. And after that, let's see if we can telnet. And we should have line VTY configured as well, correct? So I'll go here and use line VTY 024 login local login local, and then username Cisco privilege 15, password Cisco. Great, let's try one more time. Still it is showing connection refused. Okay, let's see here. Show run interface click 0/1. So here you can see that we have ACL that we have applied to the interface. Now this is removed, and ping, there is no problem. Ping is working. Let me try to do ping one more time. While doing the telnet, source interface loopback 1 showing connection refuse. So let me do clear line, and let's see if these lines are busy or something. Confirm and show users. All right, and now let's see. Still I can see this is not working. Okay, no problem. Let's check the line configuration. So here I can see that line VTY 024 and line VTY 024 transport input telnet was not configured there. Great. Cisco and Cisco. So now you can see that we are able to do the telnet. Now what I will do that we can go and create the IPv6 related access list, correct? So name I'll give block the telnet, and then you can go and give the sequence number. So sequence number 100. What I want to deny the TCP traffic for the host. The source is, and we, okay, that's right. Deny the TCP host, and we should know the host. We know that host is 1:1 to the destination. Oops, to the destination of 2:2, and the port equal to 23, correct? Then I'll go and give one sequence, a big sequence, say sequence 3000, permit IP v6 any, like we are using in access control list or ACLs. Great. Now what we can do here, we can go to the interface gig is 0/1, and here we can go and apply the IPv6 traffic filter, and the name of ACL is block T telnet in the inward direction. Now it is applied, and if we do the telnet now, it should block. But if you go and do the ping, it should do the ping, correct? And now if you go and verify, so IPv6 access list with related to block T, you can see matches. And if you do the telnet one more time, you should see the hit count related to telnet should increase. So block count should increase. Even the IPv6 permit ICMP is also increasing. Correct. So this is the way that you can go and apply it. Again, if you want to remove it, so you can go and do no IPv6 access list. Oops. Traffic class, and the access list is block in. So we have removed. Let's confirm. Show run int 0/1. So nothing is applied over the interface. And now if you go and do the telnet, we should get that. Great. So this is the way that we can create and apply the IPv6 related access list or use of the traffic filter. Next topic we have unicast reverse path forwarding. Now with help of unicast reverse path forwarding, what we can do that we can track back the source address, and if that source address is not legitimate, if the source address is spoofed or not valid, then the packet will get dropped. That's the whole idea behind configuring the unicast reverse path forwarding. So here you can see that the configuration itself is telling that we want to verify. You can see the IP verify unicast source reachable via RX, or we'll see that other option as well. But you can see the CLI command itself is telling that we want to verify the source, and if source is not valid, that means this is a spoof need to be dropped. Okay, now how we are doing this, what are the modes we have that we are going to discuss here. Okay, so here you can see that with help of unicast reverse path forwarding, we are verifying the source address. Now, while doing the configuration related to verifying the backtrack path, we have two options. We can go and configure it in a strict mode. We can go and do the configuration in the loose mode. Now, configuring strict mode, that means that the originating interface should get the return packet. So what will happen? Suppose in this case, suppose if you are configuring the URPF in a strict mode, and suppose if we have asymmetric routing, that means it will not work. Okay, so in terms of a scale, suppose if you want to provide the security, but you are checking the scaling option as well. So the loose mode is a scalable option, because in that case we have multiple ways. Suppose if you have asymmetric route, means you are sending the packet in one direction, but you are receiving the packets in the other direction, that is the asymmetric routing. So if you go and do the configuration in a strict mode, this is failed, and obviously you will not scale. So that's why the loose mode is a scalable option. Okay, and it will track the asymmetric routing paths as well. Great. So what is unicast reverse path forwarding? With unicast reverse path forwarding, we are checking the validity of source. Source is itself legitimate or not. We have two options. We have a strict mode. That means originating interface should get the traffic back. I am sending, I am receiving the return packet. If not the case, means suppose if it is in loose mode, then it will support the asymmetric route as well. How we can go and configure it? First of all, you should enable IPsec. Nowadays, all the devices, they have IPsec enabled. Then if we want to do the configuration in terms of a strict mode, so for a strict mode configuration is this: IP verify unicast source reachable via RX. See, this is for the strict mode. And for loose mode, you can go and use the any keyword. To enable loose mode, administrator can use any option. Okay, so if you use the any option, that means either path A or path B, we have the return traffic, but there are other options as well. So here you can see, you can go to interface, you can go and use RX for strict mode, you can go and use any as a loose mode, but we have allow default as well. Allow default means suppose if you have any sort of summary route, correct, and the summary route generated via the source itself, so we can go and use allow default. Okay, and I can show you here. If you go and read the document, you will find that I have mentioned the allow default option as well. So we know that what will happen in the loose mode. So when administrator use the URPF in loose mode, the source address must appear in the routing table. That one of the requirement, correct, in the mode as well. But if you want to change the behavior, you can go and use the allow default. That means use the default route in a routing table in place of source being inside the routing table. So now it's not mandatory that your source address is in the routing table, your default route is in the routing table, that will work. So you can think this is in loose, again, you have some flexibility. Okay, so strict is strict, but inside loose, you can go and use allow default. We have other options as well, like allow self ping, which is not advisable because you don't want to get attacked via denial of service attack conditions. So do not use it. And then we can go and mark down the list of addresses as well in the list option. Now either it is a loose mode or a strict mode. In any case, suppose if you have default route pointing towards the null zero, suppose if you have such type of condition, basically it is with loose mode, because we know that with loose mode we are using allow default. A strict mode is anyways strict enough in terms of security, but restriction is in terms of scalability. So point being here is this, that although you are using the allow default, but if your route they are pointing towards null zero, that means the packet will get discarded. Okay, how we can go and verify? So verification is easy. You can go to the CLI mode and you can run show Ceph interface and the interface name. You'll find that IP unicast RPF check is enabled or not. So if you have done the configuration, the verification is like this. You can go and check via show Ceph interface and whatever interface name, and you will get the detail. All right, so this is all about the unicast. In 3.3, we have COP policy to understand. COP is nothing but control plane policing. We can go and limit down the control plane traffic, various type of control plane traffic, such as management traffic, protocol traffic, etc. What I have done, I have created a playlist of 2 videos. So after that, you'll find one video related to details about control plane policy. And next section means next video, you will find the control plane policy related lab. So please go complete these 2 videos after this video, and we are covering section 3.3. Over the Cisco devices, we know that we have 3 different type of plane. We have the control plane, management plane, and the data plane. Now, how we are going to protect the control plane, that's all about information about COP. So we are going to create a policy over the control plane, and then we can apply that policy to protect the control plane related traffic. Means that we can limit the traffic, because the end goal is that we should not break the control plane. So control plane, we should limit that how much traffic is coming and hitting to the control plane. Now you'll find that you have one default policy already there in the controller. The name of that default control plane policy is policy default autocop. Now this particular policy, if you go and check, you'll find that you have multiple class map and those are called inside policy map. So what type of class map you have, you can see here. Let me highlight few of them. So I have class map match any, and this is just the name. So class cop ICMP redirect unreachable. So what I want to limit the redirect IP redirect packets or ICMP redirect packets that is reaching towards control plane, because these traffics are processed, are queried to the control plane, and control plane should not be busy enough just to process or just to uh, answer these packets. Apart from that, you can see that you have the glean, receives, option, broadcast, multicast, ACL, SLB, MTU fail, TTL fail, ARP snooping. All these traffic that you are seeing here, that is termed inside the class map, and again these are just the name, they are going to hit the control plane. And if they go and hit the control plane, so that means the process, the CPU cycle will increase, and there are chances that the router will got crashed. Now again you can see slide 1, slide 2, slide 3, these are just the class map, but I have to call this class map inside the policy map, and then I have to put the policy. So here you can see that I have one policy, and again these are the default setting. So I have one policy called policy default autocop. Inside that I am calling class map with this, and what I am doing. So I am telling that okay, police rate 10 pps, burst for one packet, confirm action drop, exceed action drop. So what is happening, say in terms of QS, in terms of quality of service, we know these terms that you have certain threshold. So you have B sub C, that is, and again you have B sub E, excessive burst and confirm burst. Now here you can see that you have confirm burst, and again you have the excessive action. So here you have option that you can transmit, and again you have option that you can drop as well. And if you transmit, then you can go and drop at the level of exceed action. So it's up to us that at what level we want to process and we want to drop. If we want to give certain buffer in between B sub E, B sub C and B sub E, we can go and give. So here you can see that for different uh, class map that we have. So for example, COP multicast version 6, the policy rate and the packets. Now it's not necessary that although you have the class map and the policy map or the policy, your router having these traffic, it's not required. These classes are there. If those traffics are there, then they will get polished in the control plane. So my control plane will be protected. Okay. So maybe I'm not running IPv6, but still I have IPv6 related class map. If in case in future I will go and use IPv6, then my control plane will be protected. So I have highlighted few of the class map, and then you can see the burst action and the confirm action. Like that, you have all the different classes that we have checked in earlier 3 slides, and their confirm excessive burst and the uh, confirm burst, and what actions we have. This is here. So for example, let me go back if I can have the ICMP unreachable. Yeah. So here you can see that ICMP redirect unreachable. For that, transmit, and then in exceed action I'm dropping. So I'm giving 100 pps, burst is 10 packet, and then it is transmitted, but at the level of excessive it will go and get dropped. Now how we can go and configure, I will show you in the lab that this is the default configuration, but if you know the system, if you know all these protocols, and if you know all these class, obviously in my system I know I can do the classification of traffic, then I can go and do the configuration of COP, how it can be. You can create the ACL. If you want to put those ACL inside the class map, you can do it. Now we already know that how we can go and create the ACL. So ACL stubs we know from the previous section. Then I can go and create the class map, and then I can match. Now in the match option, here you can see that I can go and match the IP precedence. I can go and match the access group that I have created on the top. So these things you can match, but again you can create the class map, and then you can match the DSCP. It's up to us that how we are going to create and apply the policy. And the last thing is that you create the policy map, and then you call the class, and then you can go and apply the policers. So here you can see the policers and what is the exceed rate, what is the confirm action, the police rate, etc. So once we create this policy, then we should go to the control plane. So from global config, I can go to the control plane, and then inside control plane, I can go and use service policy input, the service policy name that we have created. Now, while we are doing this, own customization while we are creating the own control plane policy. So we should understand what important protocols that we are running. So for example, BGP, then I can go and create BGP related control policies. IGP, here you can see the EIGRP, Ospf, RIP, etc. Management protocols, reporting protocols, monitoring, options related to ICMP traceroute, critical application related control plane policies also we can create, layer 2 protocols also we can go and add, some undesirable traffic that we are getting or getting complaint from somewhere, that also we can put, and then finally we have the default also. So we can go and put the default control plane rate limit as well. Now once we create the policy, then we have option that we can go and check the show policy map control plane, and then we can go and although this output is cut, but you can go and verify whatever class map you have. You can go and check the counters as well, because we have done the setting for the policies, committed burst and excessive burst. Okay, so we can go and do that. All right, and then again, if you want to see the drop, so we have the show platform QSIP. We can go and check the ACL related to control plane ACLs as well. All right, so this is the way that we can go and configure the COP policy. Let me stop here, and in next section, I will go log into the device and I'll show you how you can build your own policy. I'm going to show you that how we can go and do the configuration for the COP. Let me log into one of the router. All right, so what we can do at this point of time is that let me show you the configuration for this. So I can go here and we can go and create the class map, say type, or what we can do that we can go and do class map match any ICMP COP. All right, then we can go and if we have any ACL, we can go and create that ACL. So what basically I'm telling here is that once you are inside the class map, you can go and match. So for example, I can go and match. What are the things I can match? I can match the ACL. I can do nesting of class map as well, but I can go and match the DHCP flow, etc. Even we have this option to match the protocol as well. So what we can do here that I have created the class map. Let me go and create one more class map. Say for example, IP redirect. Okay. Now since I have these class map, what I can do now is that I can go to the policy map and say for example COP policy. Then I can go and call the class. So what class map we have? Let me go and show you the class maps. So here I can go and take this ICMP COP and then I can give the policing. So what you want? The policy rate is okay 20 PPS and burst is for example 1 packet. Then what is the conform action? Say for example transmit, and then the exceed action is drop. Okay. Likewise, I will go to other class as well. So what is the other class we have? Here you can see, let me scroll up. So we have created this policy with respect to ICMP, and then I have other class called, so let me call the other class as well. Let me go one step up, class IP redirect. Once I am inside this, I can go and create the policy. Say for example 100 and 100 PPS, and then the burst is drop. What you want to do with the burst? So let me give, say for example, 2 packets, and then the packet confirm action is drop and exceed is also drop. Alright, so what policy we have created? Let me show you that. Policy map. Here you can see the policy. Just to showcase, I have created only two policy, two class map, and then called inside the policy like this. But yeah, we can create as per our requirement. So once we have this policy, what we can do now that we can go to the global configuration mode and we can go to the control plane, and then you can go and apply this service policy whose name is cop policy. So you should give some string here. Let me show you that what options we have here. So we can go and use service policy input and then policy, and that's it. All right, now how we can go and verify? So now you can see that control policy feature, control plane policing feature enable on control plane aggregate path. We can go and verify this. So for example, show control plane, and then we have the Ceph counters, features, host, etc. But what policy that we have created, that we can go and verify like this. So policy map and the control plane. This is the policy that we have created. Okay, and you can see the packet hits and all. But yeah, you have the control plane option as well, where you want to check the aggregate path and the counters, that you can go and check. Okay, and you have the features as well that you can go and verify. But the main important thing here is to check the control plane, and then we can go and check the platform and the QoS as well. So if you go to the monitoring section here, you can see that you have this control policy map control plane, and then you can go and check the control plane QoS IP as well. So let me show you this. Show platform. Now all these hardware, they don't have this supported output. So here for example, I don't have this output support. I can go and check the hardware, but it's not equivalent to show platform QoS IP. Okay, but yeah, we have option that we can further go and check the control plane and the option. So you have aggregate, that is the control plane aggregate path. You have the Ceph exception path, you have the counters, you have the features, you have the control plane host path, you have control plane transit path. So these things we can go and check. Now this is the way that we can create the policy, apply the policy, and after that we can go and verify it. Now we reach to section 3.4, where we have to learn various features. You can see that I have created one small playlist with 4 videos. First of all, apart from IPv6, you can understand about IPv4 first off feature as well. So that is the first video I have given, and then 3 videos are there that will give you information about section or subsection 3.4, and these are the high topic inside the section subsection 3.4. So please go complete these 4 videos. As name suggests, that if you want to secure the switch port, so this is the switch port where you can go and connect the end machine, and you want to limit, because we know that switches, they are learning the MAC addresses at the moment they are connected via the interfaces, so they are learning it dynamically. Now, suppose if I want to limit the number of MAC addresses over the interface, or if I want to stick some sort of MAC address, only this MAC address will get learned over this particular interface. So those type of security features we can provide. Again, in the upcoming slide, I will show you that if the violation will happen, if someone will go and violate the switch port security, then what actions it may take. Okay, so let's see here how we can go and enable it. It's very easy and straightforward. Suppose this is interface gigi 1/10. We can go inside the gigi 1/10 and we can give a command switch port security. It's like power button that's on. So port security mode is on. Then we can go and limit that what will be the maximum number of MAC addresses it will learn. So in this example, suppose if maximum MAC addresses it can learn 2, that means if more than 2 MAC addresses will come, it will start dropping the traffic. We'll see that what is the default mode. But again, we can go and hard code the MAC address, or we can go and use the sticky address command as well. Okay, so this is the feature. Is very straightforward. You can go and enable the port security. You can limit the MAC addresses. Now, if someone will go and violate the rule, then what action it can take? So you can go and give switch port security violate, and then what action you have? You have 3 different actions. You can take shutdown. Shutdown means that the port will move to the error disable state. Okay, and this is the default mode. So suppose if we are creating the policy, creating the port security configuration over the switch port interface, and we are not giving any violation rule, so at that time it will be shut down. Then we have 2 more. Restrict means it will drop the unauthorized traffic and it will log, means it is going to generate the log, correct? But in the protect mode, it will not. So here you can see the legitimate traffic will be forwarded and unauthorized traffic will be dropped. Means it will drop the unauthorized traffic, but log will not get generated. So that's the only difference. Easy and straightforward, correct? You have 4 lines of command. Go to the interface, create the port security, limit the MAC addresses. If you have any static binding for MAC addresses, you can give that, and then finally you can go and give the violation rule. By default, it will be shut down. Great. Let's move to next topic that we have, and here you can see that we have the violation configuration as well. So switch port security violation, shutdown, restrict, and protect. Great. Let's move to the next topic. We have DHCP snooping. Now, DHCP snooping, we should understand first of all how DHCP, dynamic host configuration protocol, works. So you have the client and you have the server. So client, actually DORA is the process, DORA. So client is sending the discover packet, then server is responding with the offer, then client is sending the request packet, and finally the server respond with the ACK. Means I want some information like IP address and the gateways and all those information, and I'm sending that discover packet to the server. Server is responding with those information. Now I am sending the response back to the server with a DHCP request that, yeah, these are the information, I'm good with this. And then server is finally sending the acknowledgement, okay, have it. So this is the DHCP process. But what is happening when uh, what can be happen? So someone will create the rogue type of DHCP server. So suppose I'm in a network, there I have one legitimate DHCP server. So when I send my request discover packet, it should go to the legitimate DHCP server. But think like this: suppose if it will go to the rogue DHCP server in the same network. So I'm sending my discover packet, and then the rogue DHCP server, because we haven't put any trust or untrust type of relationship inside that network, inside that port. So it can take those offer from the rogue DHCP server, and that's why we are enabling the DHCP snooping. This is something like man in middle attack. like someone is intercepting your communication in between. So what we can do, we can go and enable this feature globally over the switch, hybrid DHCP snooping. So that means the DHCP snooping is globally on. That means you are not trusting any of the port. Okay. Next, you can go and enable over the VLAN as well. Because globally also you can enable over the VLAN as well. So DHCP snooping must be enabled on one or more VLAN. First, you have to enable over the global interface, and then you should enable to the VLAN. Now, once we do that, that means all the interfaces over that particular VLAN, because we are putting the interfaces inside the VLAN, they will become untrusted. Correct. So now we have to go to the interfaces by interfaces, and we have to make those interfaces as a trust. So what will happen? That suppose if gig 1/20 is now trusted port, that means that you are sending, receiving the DHCP request, offer, etc. only over this interface. Correct. And that's the key we have with the DHCP snooping. Next topic, we have dynamic ARP inspection. Now, this is sometimes referred as ARP poisoning as well. In this case, what is happening? There are chances that a malicious host can masquerade as another host, correct, by intercepting ARP request and responding with its own MAC address. So someone can go and so if I am a user, I am sending my ARP request. So someone can go and send their own crafted ARP reply, because anyways, I'm trusting everyone. Correct. So again, to mitigate from this, what we can do, that we have the DHCP snooping database, correct? And then we can go and have the ARP inspection. So with respect to database that I already have, that's nothing but the DHCP snooping table, we can go and configure the IP ARP inspection for certain VLANs. So in that case, it will go and inspect the IP to MAC database. Okay, so in that case, what we can do, that we will trust only legitimate IP to MAC binding. So someone can't spoof, correct? So if I am sending the ARP request, I should get the response from the legitimate or from the trusted interfaces. There are two ways that we can go and do the configuration. First of all, you can go and enable the ARP inspection for the VLAN. At the moment you go and enable it, what will happen? Everything will become untrusted. So then we can go and put the trust over the interfaces. That's the one way. The other way that we can go and create the manual MAC to IP database is this, that we can go and create the ARP access list, and there we can go and map the IP to MAC, IP to MAC. So simply, whatever hard work we are doing here is simply that we are hard coding the IP and the MAC binding. So I will not get spoofed from unknown IP addresses that I think that is the legitimate. Okay, so that's the reason that we can go and cross verify the DHCP snooping database in this. So enabling this is again straightforward. You can go and do the configuration IP ARP inspection. If you want, you can go and create your own ARP access list, apply to the VLAN. That's one manual way. Or we can go and first of all, we untrust that associated interface over the VLAN, and then we can go and trust the interface with the command IP ARP inspection trust. All right, we have completed this section. Let's stop here. In 3.4, we have to understand about IPv6 first hop security features. Before going to IPv6 security features, you can refer this video. You can see video number 88. That is IPv4 related first hop security feature. And then you can come back and you can start the series related to IPv6 first hop security feature. What are the security, where we are going to apply those feature security? You can see the listed features are here. First of all, we'll go and learn about IPv6 router advertisement guard, then DHCP version 6 guard, the security binding table, snooping, and IPv6 source guard. Okay, so let's start with IPv6 RA guard feature. What IPv6 RA guard feature will do, once we go and configure this and apply over the interface, means that policy, we need to configure and then apply over the interface over any of the VLAN. That's the optional. Then once the feature is enabled, it will go and check the IPv6 source address of the packet. Means it will validate the source address is correct or not. Then various flags options we have inside the RA. So it will go and check the flags related to RA. Then prefix advertised by the router. So how many prefixes it is advertising, because we can go and give those prefixes. We can go and give the limit for the hop count as well while doing the configuration related to RA guard. And then finally, the default router preference advertised. Okay, so basically the source, basically number of hop counts, what prefixes we are advertising, and the flags inside the RA guard. Okay, now how we can go and do the configuration? You can see that we can go to the conft, we can enable the policy, we can go inside the policy mode, and then we can device role, we can give this as a host or router. Then the hop count limit we can set, the flag we can set, we can match the IPv6 access list, we can match the RA prefix list, because we have discussed earlier in previous slide. Then if the other flags are on or off, then the router add preferences maximum. So you can see this default router prefixes preference advertises. Okay, and then trusted port. So once we'll go and configure how we can do the configuration over the router, you can see that you can go to the conft, you can go and give the policy name for RA guards, the device role, the hop count limit, then the manage config on, the ACL, the RA prefix list, the other config flags on or off, then the router preference maximum, high, low, mid, it's like that's high, low, medium, and then finally the trusted port. Now, once we do the configuration, we can go and apply this configuration over the interface. So you can go to the selected interface. You have to go and give the policy name. In our case, suppose this is ABC, and then you can add the VLAN add accept none. We know that while doing the trunk configuration, we are using such type of configuration. Okay, so this is applied. Then if you want to verify it, we can go and use show IPv6 ND RA guard policy. And if you want to debug, we have the debugging option as well. All right, so this is the way that we can go and enable the RA guard feature over the device. In this section, we are going to discuss about DHCP version 6 guard and IPv6 source guard. Now, why DHCP version 6 guard or DHCP guard related to IPv6 address family is important? Because when we go and enable this feature, it will not entertain the spoofed messages that is coming either from DHCP server or maybe it is relayed. Means in a path, those messages, they want some sort of transit via the devices, via the routers and switches. How this feature is working? Let me explain you that. DHCP version 6 guard block, DHCP replies or advertisement not originated from DHCP server or relay. Same thing. Either not it is relaying those information, means in a transit also you can apply these features, or it is not a valid DHCP server. Okay, now how it is working? So it decides where to switch or block the DHCP replies based on the device role configuration. So your device, either it's a server or it's a client, according to that, they have the authority or validity which type of messages it will pass or receive. Okay. Now, what DHCP version 6 is doing is that it classify the information to three DHCP messages type: client message, server message, and relay message. And what is important here is this, that client messages are switched regardless of device role. So we have switched message and we have processed message. Processed message means the CPU will use to verify those messages. On the other hand, the DHCP server messages are only processed. So only the server messages, they are CPU intense, means the system will check those messages via the CPU processing, but the rest of the messages are just the processed. It will come and it will get forwarded. Okay, so you can understand from here that depending on upon the device role, depending upon the message classes, the DHCP version 6 card will check, means it will go and check the DHCP replies and the advertisement that it is from the valid source or not. Okay, how we can do the configuration? Configuration is straightforward. Here you can see that we can go and create the ACL, that's the host ACL, and then we can go and create the prefix list. So these are the ACL and prefix lists that we are going to use inside the actual DHCP version 6 configuration. So here you can see that we can go and create the policy, IPv6 DHCP card policy, then give the device role. In this case, it's a server, then match the ACL, match the prefix list, set the preferences, and then make this as a trusted. Okay, once it is configured, then we can go and verify the IPv6 policy guard and then the policy name. Here also you can see that the steps, these are the summary of steps. So first of all, create the ACL, create the prefix list, then you have to go and create the policy. You have to select the device role as either client or server. Then inside the policy, correct? So inside the policy, so here from this point onwards, we are inside the policy. Inside the policy, we can go and call the ACL, call the prefix list. We can set the preferences, trusted port, and that's it. Okay, great. So this is the way that we can go and enable the DHCP version 6 card. The next very important feature we have is related to IPv6 source card. And I told you earlier that you may have gone through the IPv4 security feature or first hop security feature as well. There also you will find that there are similarities between IPv6 guard and IPv4 guard. What's the key point here while discussing about IPv6 source card is, that's the only key point here that we should understand, that when you are creating the snooping entries, so you should have, so there is prerequisite, and this is the important point. So before even doing the configuration related to IPv6 source card, you must have the configuration of IPv6 snooping is prerequisite for SG source card. So you should have snooping enabled, because once you do the snooping configuration related to IPv6, then you'll get the snooping table, snooping database. And according to that snooping table or snooping database, the source card will take action. Okay. Now, this is the topmost point related to source card. The second very important point you have is this. The source card, the SG, is an ingress feature and filter incoming packets. Okay, so incoming packet means, suppose if you have router or switch, when the packet is coming in, then it will check the snooping. So you have your snooping database, and according to that, it will block or allow the packets. Okay, now you have the snooping database, and then you have the source card, and then there are rules, then there are configurations. That let's understand this. So source card is a security feature that filter IPv6 traffic on layer 2 ports that are not trusted. Obviously, you have to do the configuration. We'll go and verify this statement with respect to configuration as well. Now, source card drops those data packets whose source address are unavailable. And how you can learn those source addresses? There are different ways we can learn those addresses. So IPv6 binding is learned through DHCP. The IPv6 address or prefix is learned via NDP, and you can do some sort of a static configuration. Okay, so source card and IPv6 DHCP snooping database. Okay, they have to correlate. And for the incoming traffic that is ingressing from the L2 ports, where they should go and examine those are valid addresses or not. Now, while we are doing the configuration, it should match means it has the option to match the IPv6 address, MAC address, VLAN ID or port, because these are the items, the source card they are learning. And you can understand the algorithm here. The source card, first of all, they were installing deny all access control list. Okay, so you have deny on the top, and then you have a small holes to do the permission with respect to IPv6 address, MAC address, VLAN ID and port. How we can do the configuration? Configuration is fairly straightforward. Do the enable conf key and then your policy, IPv6 source card policy, name of the policy, permit the link local, deny the global autoconf and trusted. Then you can go and verify, show IPv6 source card policy. Here you can see the detail about the configuration. Go to the config T, go to the global configuration mode, give IPv6 source card policy and the policy name, then permit the link local, then deny the global auto config, trusted, and then you can verify it. Okay, how you can use this over the interface? So over the interface, you can go to the selected interface and then you can apply IPv6 source card, attach the policy and the policy name. That's it. Again, the verification is show IPv6 source card and the policy name. All right, so we have discussed two very important features. Let's stop here. Now we are going to discuss about IPv6 first hop security binding table and ND, neighbor discovery inspection and snooping. So let's learn these one by one. Now, IPv6 first hop security binding table is something that with help of neighbor discovery protocol, the devices they are building. It is referred as a database or the binding table. Now, this secure database or binding table that can be used for various IPv6 guard features. Few of the features we have discussed in our previous sections as well. Now, what is happening that suppose if the device will get a report, then we have something called IPv6 first hop security binding table recovery mechanism that will try to secure the binding table. Okay, so point being here is that it is going to use NDP, neighbor discovery protocol, to build the binding or the database table, and then it is securing this binding table as well in case of device reboot. How we can do the configuration? Configuration is easy, straightforward. Few lines of configuration we have. We can go to the global configuration mode. We can type IPv6 neighbor binding for VLAN. For the interface, reachable lifetime, we can give the counter. Then IPv6 neighbor binding, max entry is 100. You can see here the limit, some of the options as well. So IPv6 neighbor binding max entries, VLAN limit, interface limit, or MAC limit. So we can give those limits here. Okay, max tries, here you can see the max tries, and then you can use the entry with some of the options, correct? Then we can go and use the logging command, IPv6 neighbor binding logging. How you can verify this? The verification command is show IPv6 neighbor binding. Okay, there are some IPv4 features as well that we have discussed earlier, and we are using show IP DHCP binding, snooping, etc., etc. Like that, you can go and check show IPv6 neighbor binding. Okay. Next topic, we have IPv6 snooping. Now again, these features that we are discussing, they can be used at one place or other place. So for example, IPv6 snooping tables, again, they are the layer 2, layer 3 security feature, or in between layer 2, layer 3 security feature that is providing the security with respect to IPv6 address clean, IPv6 device tracking, correct? Now, again, you know that when we have a study about the source card, so we know that prerequisite is that you should have snooping enabled for source card, correct? Likewise, we can use one of the table, one of the secure table for other features. Now, why it is important? Because there are some inherent vulnerabilities for neighbor discovery mechanism, such as attack on DAD, duplicate address detections, address resolution, device discovery, and the neighbor cache. That means, again, this process being used for other process to make the other process secure as well. Okay, now once you have the secure trusted binding table, so that means you are securing the neighbor discovery binding tables as well. Means one place you have input, then you have the output. So with help of such input, we are securing the output, or maybe some other features are glued. For example, the IPv6 snooping learns and securing bindings for a stateless auto configuration address in layer 2 neighbor table and analyze ND message in order to build the trusted binding table, correct? So they are analyzing the auto configuration feature that we have in the IPv6, and then they are analyzing the neighbor discovery messages to securely build the table. Now, what happened if IPv6 ND message that do not have valid binding? So if you don't have valid binding, IPv6 to IPv6 to MAC bindings or valid binding, they will get dropped. So they are securing, they are making secure that our IPv6 to MAC bindings mappings are verified. How we can do the configuration? Configuration, you can see this is again a straightforward. You can do the configuration, apply to the interface. So go and write it like this: IPv6 ND inspection for policy. For example, name of the policy is policy 1. Drop the unsecure, give the security label minimum 2. Here you can see that option that we have with the security label. Then device role monitor, then tracking disable stale lifetime infinite. You can see the options are there. So tracking enable reachable lifetime infinite, disable stale lifetime infinite, etc. Then trusted port. Then we can go to the interface and we can apply this policy that we have configured as a policy 1. Okay, so this is the way that we can go and apply this particular policy. In 4.0, we have infrastructure services. Let me show you the content. We have to understand the basics related to console, VTY, telnet, HTTP, HTTPS, etc. Then you can see the topic related to Ccnp and other services and features. What I have planned, I'm going to cover all these sections one by one, subsection wise. So the first section is 4.1 console and line VTY. I have created 2 videos here to understand this topic, to understand the theory plus lab as well. So please go complete these 2 videos, and we are very much covering 4.1a. Once we complete this 4.1a, in next section I will go and start 4.1.b. Okay, so please complete video number 93 and 94 to complete 4.1.a. Right. So when we are talking about the basic security on Cisco routers, when any user, any remote user try to log into the device, so how we are going to provide the line security. So line VTY, what is the transport for that line VTY? If we are using telnet, then what type of security we can do? What type of even privilege also we can assign to the client? What type of access they have to the devices, each and everything we can go and configure. So suppose if we have line console, line aux, you can go and give the password. Again, if you go and check show run, you will find that these passwords are visible. So we can do the encryption of the plain text password that we are giving to the device. So if someone can see the show run, they can't see the password. So that's the reason we have the option for the enable password. We have option for the enable secret. These are the password when we are logging into the device. So say you have done your telnet or SSH and then you want to gain the or you want the access for the privilege. So at that time you can go and run the plain text password, or you may have the secret password. Recommended is that we should use the enable secret that will do some MD5 hash. Here you can see in the show run the MD5 password, that's enable secret CCI. I'll show you this MD5 hash. This very difficult to crack. Again, if you give normal password, then it's not recommended. And suppose if you have two password, enable password and secret password, so the enable secret will take precedence with the plain text password. If you want to encrypt each and everything over the device, means all the plain text password over the device, then we can go and run this service password encryption. It will go and encrypt all the configuration. Here you can see that initially this enable password was Cisco, and now it is showing some MD7 hash or MD7 format. Okay, although this MD7 is very easy to crack, there are so many online URLs you can go and put this and it will give you the password. So at the moment you'll go and put, you'll find the password as a Cisco. So that's the reason. One recommendation is that your password should be mix of the alphanumerical or different type of characters. So even if someone try to hack that, if someone has the MD7 try to resolve that, it will be difficult for them to figure out that password. All right, so in next section we are going to perform the lab for this. Let us perform the lab task. We have the topology here. You can see R1 and R2, and over R1 we'll go and enable the telnet, SSH and all sort of password encryption. So let's go to R1 and I can go to line VTY says 0 to, say for example 1, and here we can go and give say password Cisco. Then from R2, and we have point-to-point IP configuration. Let me ping to R1 first and then I'll try to telnet. And here you can see that the telnet port is open. Password is Cisco, so I can go and use Cisco. Because I haven't set the enable password, so I'm not able to log in. Here it is telling that authentication to privilege 15 is failed, because by default we have the privilege level 15, but we have option that we can go and set different type of privileges. Alright, so what we can do here, that we can go and do the enable password again, say Cisco. And now if you go and choose this enable and if you type Cisco, you can see that we are inside R1. We can go and check the users. So here you can see this is the user who has logged in. Now once we are logged into R1 and if you go and check show run, you will find that we are using the plain text password. So for VTY 0 to 1, the password is Cisco and we are using login. Again, if we go and check show run section enable, so here you can see that the password that we have is the Cisco and it is in plain text, correct? Now if you want to check both the password, you can see here. Now to encrypt all type of password that is in plain text, we can go and do service and then encryption. Let me check if we have service. Let's see that what option we have, but we can go here and do this password encryption, and then if we go and check the output, you'll find that all the password that initially was there in the plain text, they are going to be encrypted, although to break this encryption is very easy. We can easily go and break this encryption. So what we want here, that we should not use the enable plaintext password, rather than we can go and use the secret password, say for example 123, and now if you go and do the telnet, and then if you give the telnet password is okay Cisco, but the enable password is Cisco 123. Okay, now if you go and check the enable password, you'll find that it is hashed, MD5 hashed. So that's the one thing that we can do. Now what other things that we can go and do with line VTY, say for example 0 to 1 or 4, that we can do here no login. That means login is not required. This is not a recommended way to do this, but what we can do, that we can do login local, or you can see that you have option that login, and then you can go and use say login local. So these options we have. Login local means that now you can define the username, say for example admin1, and then you can give the privilege, say for example 7, and password. Again you have option that you want to use the unencrypted or the hidden password, correct? So for example I'll go and give Cisco as a password. Again I'll go and change the privilege as 10, password Cisco. So now I should change the admin1 and admin2. So now I have two admin and they have different level of privilege, correct? So if I go out from here and try to telnet with username admin1 and password Cisco, I can go and check the privilege level. And now if you try to get the output, even you don't have show run option, and if you try to go to conft, you don't have those options. Again, if you go and do the telnet with admin2 and password Cisco, and you can go and check the privilege, you have privilege 10, and if you go and to show run conft, those things are disabled, correct? So again, that's one level of security that we are discussing at this point of time. Now, not only this line VTY, but we can go and give the password to line console as well. We can go and give the password for line aux as well. Okay, so like that we can go and give. Now these are the password related to telnet, related to enable password, and then the we have learned about privilege as well. Now what about SSH? Because when we go to line VTY 0 to 4, and if you go and check transport input, you have this option all, or you can go and use SSH, and that is the standard. So we should not use telnet, rather than we should use SSH to all the devices. So if you want to enable the SSH, you should go and define the domain name, and then you should create the crypto key. So crypto key generate RSA modulus 1024. Now once you have the domain name, once you have created the crypto key, if you want, you can give the SSH version as well. In this example, I'll give version 2. And then you should go to line VTY 0 to 4, and already we have done that configuration. So let me show you that configuration, what we have done related to SSH. So now this configuration that you have, the input and output, everything is related to SSH. Now I can do the SSH with the local user, say admin1. Okay, and what's the IP? Okay, so I should use SSL admin1 10.1.1.1, and then the password is Cisco. Now you can see that directly we are logging to the device, but if you go and check the privilege is still less. So now you can see that we are giving tighter security. We have started with line VTY plain text password, then we have given the service encryption or password encryption, then we have configured the line VTY with normal username, then we have given the privileged username, then we move to the SSH, and inside SSH we have given the privilege level. So we should use or we should follow this practice that is much more secure. Now what is happening in industries is that we are doing all this authentication, authorization and accounting for all the users from the ICE server or from the ACS server. At the moment, the standard is ICE, Identity Services Engine. So in upcoming section, you will learn and understand more about the use cases or use how we are going to use the ICE for the all these operations. In 4.1b, we have topics related to Telnet, SSH, HTTP, HTTPS, and SCP. I'm going to cover Telnet and SSH in this recording. We know that if we want to do the remote access to the devices, we have Telnet and we have SSH, both the methods. We are preferring SSH because we know that Telnet is not a secure way. In Telnet, you are not securing your password while you are remotely accessing the device. All the devices, they have line VTY option. Some devices have 0 to 15, some have more than 15 or 16. Means 0 to 15 means 16 user can be accessing the device at a time if the telnet is open, if the SSH is open, etc. Okay, but there are some prerequisites. Means while we are doing the configuration, we have to set the enable password, we have to set the login password, or maybe those login password are authenticated via AAA. So options are there to secure your remote access. You can see that you can create your local username password as well. Username, give the name, then the privilege and the privilege password, etc. Okay, or these databases that can be authenticated via IC as well, ICE or AAA as well. How we can do the configuration? Straightforward. If we are creating the local DB, username Cisco, password Cisco, means Cisco is not a good password. So while you're giving the password, you should use long string mix of different type of characters. Line video 0 to 4 and then transport input telnet. Okay, that's it. Since this is not a secure method, so we are always looking for securely remotely accessing the device. So we have SSH version 1 and SSH version 2. SSH version 1 having some issues, vulnerabilities, some exploits. SSH version 2 is quite secure. Now, while doing the SSH version 2 configuration, again, there are some prerequisites. You can see that you should have the host name, you should have the IP domain name configured, you should generate the crypto key. Okay. After this session, I have one small 5-minute video related to how you can do this basic configuration, and then from automation tool or any tool, you can go and remotely access the device if you have the IP reachability. Okay, once you do the configuration, some verification commands are there, show IP SSH, show SSH, etc. that we can go and check. So how we can configure it? Give the router name, give the IP domain name, give the username and password, and then generate the crypto key, go to the line VTY, and then make sure that transport input while the dialing inside is SSH enable. Okay. Great. If you want to do a little bit of SSH modification in the configuration related to SSH, you can go to IP SSH, give version 1 or 2. Then you can go and set the IP SSH timeout, authentication retries. Okay. And then over the line VTY, we can go and use the transport input as a SSH or as a all, etc. So options are there. Next video, do the SSH configuration, you please go and watch the next video for the lab example, so you will understand how we can do the SSH. So we have the switch here. Let me go and start this. Switch number 1 and switch number 2. So what will happen that first of all, we should log in to the switch via the SSH, because if we do not log in, then obviously we can't send the uh, script. Now when we are talking about logging to the switch via SSH, so in that case we need to go and do SSH related configuration. So first of all, we should go to line VTUI 024, and we know that we have the login local here, and transport input, your SSH should be there. But anyways, we are giving all, that means we are covering SSH telnet, means all type of remote login. So that's first step. Then we should go and define the domain name, say IP domain name. For example, I'll give cisco.com for the time being, and we should create the crypto key. So crypto key generate RSA modulus 1024, because in case of SSH, this crypto key that we are generating, this public key, should be authenticated or should be accepted from where we are going to do the SSH. Okay, so what we have done, that we have given the IP domain name, we have given the crypto key. Now if I go here and do the same, so in the meanwhile, let me go and create the template for the SSH. So when we are doing the SSH, we should have IP domain name. For example, here I am taking cisco.com, and then crypto key generate RSA, and here you can see I can even copy this command and I can paste here. And then we should have a line VTY configuration that is already there. So here you can see the line VTY configuration, and then we should have a username configured as well. So let's wait when it will come back, then I'll copy and paste. Now once we have all these configuration, then what next I want to do is that I'll try that this device is reachable from the automation tool or not. And we know the IP is 192.168.122.2. So let's go to the automation engine and let me copy as well. Let's go here and try to SSH. We know that the username is Cisco. This is the password. We are accepting the key, and then password is Cisco. And now you can see we are in the switch. Okay, so same thing, I will go and enable. I think we need only these two lines because the rest of the configuration is there in switch number 2. So I'll go here to switch number 2, and we can go to the conf key. We can generate that key, and then I can go back here, and from here this time we'll go and do the SSH 2.3. Accept these keys and the Cisco, and we are inside switch number 2. In this section, I will quickly walk you through the other features that we have, other services that we have: HTTP, HTTPS, SCP, and FTP. Now, HTTP and HTTPS there is fundamental difference in between that. So in HTTPS, you can see the keyword is S, and that's stand for secure HTTP. And when we are dealing with the organizations, we should focus on security as well. So that's one of the main reason you'll find that unless we have some specific use cases, most of the time we are preferring HTTPS. Some places where HTTPS is not supported and you want to use HTTP as a service, because these are the application protocols, then at that place you'll find that in configurations in industry people are using HTTP. But HTTPS is the recommended one because it is providing you secure sessions related to HTTP. HTTP, they are using port number HTTP, port number 80, you can see here. But HTTPS is using TCP port number 443. That's the secure port number that we have. Now I'm going to focus only on the configuration here because we know about how the HTTP and HTTPS is working. For HTTP configuration, it's very easy. Go to configuration mode, IP HTTP server. In the same mode, you can go and integrate with AAA IP HTTP authentication AAA. Now, when we are dealing about the secure HTTP, where the certificate will come into the picture. Suppose if you have 3 routers, or if you have big infrastructure where you have good amount of router, one of the router can become a CA as well. We have that feature in Cisco router that you can make routers, they can work as a root certificate authority, root server, root CA authority server as well. Okay. And you can see the configuration related to that. So IP HTTP secure server, crypto CA trust point, suppose he's the CA, then enrollment URL. So any other device they want to enroll with that CA, because before doing any type of IPsec type of configuration or creating VPN type of tunnel, they will get the certificate from the CA server and then they will form the IPsec in between the devices. Even here also, even here also. Yep. Then crypto CA authenticate CA trust local, crypto CA enrollment CA trust local, and IP HTTP secure trust point CA trust local. These are the standard configuration when you want to make your router work as a HTTPS server. That's the CA server. Then next topic is SCP. If you want to securely transfer the file, we can use the secure copy protocol, and we should integrate this with AAA. You can see the configuration: AAA new model, AAA authentication login default local, AAA authorization exact default local, and then the username Cisco privilege 15 and password 0 Cisco. Is these configuration that we already know from our AAA knowledge. Okay, this is not new. In AAA, we know that how we can configure the devices respective for switches, routers, ASA firewall. There you have to put the AAA configuration like that you can do. But there are so many other AAA configuration. This is just the standard 3-4 lines. Then for SCP, IP, SCP, server enable. So the point being here is that our routers, they are working supporting as HTTP, or our router working supporting HTTPS, or our router working supporting SCP, Secure Copy Protocol. Likewise, our router can work as a TFTP or FTP server as well, file transfer protocol. So you can store the files inside the routers. That's not the recommendation, because you should use some third-party servers, and because they're third-party servers, you have good amount of storage. When we are storing the files inside the routers or switch, boot flash or inside switch, that is not a good practice, but sometimes we are doing this. Okay, so in that case, we can go and enable it. Now you can see that FTP is using port number 28 and TFTP is using UDP port number 69. Okay, with FTP, they have different type of port numbers. So you can see that FTP uses TCP port 21 for authentication and TCP port 20 for data transfer. Two ports are there, one for authentication, one for data transfer. Then the configuration, we can go to the router. TFTP related configuration, TFTP server flash file name, copy TFTP flash. For FTP configuration, IPFTP, we can give the username and password. So if anyone is coming logging there, they should give the username, password, and then they can use the FTP resources. Okay, so these are the important services. Let's just stop here. In part or two, we have to understand about SNMP. I have created playlist related to SNMP. You will understand the SNMP, what is SNMP, the MIB version, the SNMP configuration, SNMP lab, SNMP lab result, and quick revision. So please go complete this 1, 2, 3, 4, 5, 6 videos, and you're very much completing subsection 4.2 related to SNMP. We have the management protocol for the network. That's the simple network management protocol, SNMP. Let's first of all understand the terminologies used in SNMP. Basically, we have three main or major component. We have SNMP manager. You can think this as a collector where it is getting the information from the SNMP agents. So you have agents, that's the network devices, and you have manager where all those information are getting collected with help of MIB. So third very important component, we have the SNMP management information base. Now what is happening? Now these MIBs are nothing but the information that is stored inside the agents, and managers, they are using get, that means to retrieve the information, and suppose if they want to change certain parameters, they can use set. So managers, they are using get and set methodology to get the information, or if they want to change anything, they can change. Now again, the communication channel we have, we'll see that we have versions of SNMP. So for example, community based version, SNMP version 1, SNMP version 2C, and then we have something like authentication or user based SNMP methodology as well, that is the SNMP version 3. But yeah, we have different version as per different RFC standard, and these SNMP or the SNMP protocol in general, they are used to collect the information for the management purposes. So for example, what type of information? Say interface monitoring type of information or protocol monitoring type of information. Now one of the popular tool for SNMP at this point of time we have, so for example, third party SolarWinds tool, where we are going to do the testing as well in the upcoming lab session. Uh, Most of the production network, they are using SolarWinds, or there are various tools as well. Just they are using SNMP methodology, same methodology that you have manager, you have agent, and then MIB, and then they are collecting information at a common place again for the analysis purpose. Now here you can see that the SNMP get method, we have three type of get method, means we are getting the method, we are getting the information, we are getting the next variable information, or we are getting the information in the bulk as well. So three get methods inside get method we have. And finally we have SNMP notification as well. Now what is SNMP notification? This is again a type of information, and it is referred as a unsolicited asynchronous notification that can be generated as a trap or information. So in the configuration, I will show you that we can use the methods, the agents can use these methods to tell the manager about the various type of information. So in trap or maybe in inform, you have various type of information that you want to tell to the manager, and in the configuration I'll show you that what exactly trap look like. Now we have trap and we have inform. Most popular in these two is trap. That is less reliable as well. So what is happening actually, what's the core difference or basic difference between trap and inform is that trap is a message that the manager is getting that don't have any acknowledgement. On other hand, the inform, they have the acknowledgement as well. So that's the reason the trap is faster trap methodology is faster than the inform method, but yeah, inform method is reliable because it has its acknowledgement as well. So we know the basics terminology used in SNMP. Let's stop here, and next section we are going to study about SNMP MIB and versions of SNMP. Let us understand Cisco MIB and versions of SNMP. Now this MIB is nothing but a database, and this MIB is in form of tree structure. Again, if you want to learn more about MIB, you can go and refer these RFC 1213, and for traps we have 1215. And even with respect to Cisco, if you want to again see the tree structure and the hierarchy, you can go and check Cisco MIB, and you'll get long list of MIB related to most of the things. So for example, the informations related to protocols, the information related to traps, the information related to flaps, information related to CPU, interface, monitoring, etc. etc. And again, major vendors, say for example, who is working on SNMP, SolarWind and others, they are using this MIB, and they have the SNMP manager where they can go and collect all this information that I'll show you in the uh, upcoming session, that how you can retrieve these informations, how you can query. So suppose if I have SNMP manager, I can send the query. That's nothing but the get method. I can send that get method, and once I do this get method, the responder, that is nothing but the agent, they will give me all the information that I query inside this string. Okay, now we have three versions. We have version 1, 2C, and version 3. 1 and 2, SNMP version 1 and 2C, they are very much community based. So obviously they are doing the community based authentication. The method of authentication is the community string. Again, in the lab section, we'll see that we have the community string. Even we can put some sort of ACL ACL as well for that, if you want to filter out the uh, number of volume or number of requests we can put inside the ACL. That we'll see in the lab section. Then we have version 3, that's the secure model. We have version 3 is supporting, say for example, message integrity, authentication, and encryption. Now there is a huge improvement with respect to version 1 versus 2C, and you see that still most of the organizations, they are using community based version 2C. Why? Because they can do bulk retrieval of data. That's obviously the tables and large quantity of information. Again, these are uh, belonging to the tables. Whenever we are talking about tables, they are belonging to the database system. So maybe MySQL or any type of databases that these managers, they are using behind the scene. So maybe they can use MySQL or any type of database, and depending upon those company and their partnership with the database companies. All right, so version 2 can get a large volume of data with less amount of expense. Expense here means the memory, the round trip delay, etc. That's the power we have with respect to 2C versus SNMP version 1. And when we are talking about version 3, this is based on the security model for users or users belonging to group. Now, what is the difference? I have this slide for that. Here you can see that we have model, we have label, authentication, encryption, and what is going to happen. Now, version 1 and 2C, we know that they are community based, so that's why we have the community string for obviously authentication, but they are no auth, no pref, no auth, no pref, no authentication, no pref. Again, I told you that community is itself a type of a string, or you can think a password, just to do the authentication, but it's not exact authentication like you have MD5 SHA that we used to learn inside various other protocol like IPsec and others. Okay, but still you can think that community is a password, or it's a authentication way of protection to do the authentication between the agent and the manager. So for inside V3 again, V3 just not only supporting the authentication and the encryption, but they have uh, no auth, no priv method as well. So you can do username. So user the username match for the authentication. Then you have auth, no priv. Auth means authentication, no privacy. At that time you have the MD5, maybe SHA. At that time they will go and do the authentication. And finally it has auth and priv, where you are using both the MD5 and DIS56 as a data encryption. Okay, so these are the versions we have related to SNMP.